No Human Left Behind, AI, Machine Learning, written by Valentin Vishniakov, published by Infinia Publishing. Introduction. Welcome to Machine Learning. Welcome to the Machine Learning. You are about to embark on an extraordinary journey into the heart of one of the most transformative and rapidly evolving fields of our time, machine learning. This course, Machine Learning, is the third in a comprehensive series, No Human Left Behind, AI, designed to equip you with a deep and practical understanding of artificial intelligence from its fundamental principles to its cutting-edge applications. We stand at the dawn of a new era, an age where machines are no longer just tools for executing pre-programmed instructions but are increasingly capable of learning from data, adapting to new situations, and making intelligent decisions. This remarkable capability is driven by the advancements in machine learning, a subfield of artificial intelligence, AI, that empowers computers to learn without being explicitly programmed. It's the driving force behind many technologies that are reshaping our world, often in ways we don't even realize. Throughout this course, we will explore the core concepts, algorithms, and techniques that form the foundation of machine learning. We will demystify the inner workings of these intelligent systems, providing you with both theoretical knowledge and practical skills. You will learn how to build, train, evaluate, and deploy your own machine learning models, and you will gain a deeper understanding of the strengths, limitations, and ethical considerations of this powerful technology. Why is machine learning so important? Machine learning is no longer a niche area of research confined to academic labs. It has become a driving force behind innovation across virtually every industry. Here's why it's so important: data-driven insights. We live in a world awash in data. Machine learning provides the tools to extract valuable insights from this data deluge, uncovering hidden patterns, relationships, and trends that would be impossible for humans to discern on their own. Automation and efficiency. Machine learning can automate complex tasks that previously required human intelligence and labor, leading to increased efficiency, productivity, and cost savings. From self-driving cars to automated medical diagnosis, the potential for automation is vast. Personalized experiences. Machine learning powers personalized recommendations, targeted advertising, and customized services that cater to individual preferences and needs. This is transforming how we shop, consume entertainment, and interact with technology. Scientific discovery. Machine learning is accelerating scientific discovery by enabling researchers to analyze massive datasets, identify complex patterns, and generate new hypotheses in fields ranging from genomics and astronomy to materials science and climate research. Improved decision-making. By providing data-driven insights and predictions, machine learning empowers businesses, governments, and individuals to make more informed and effective decisions. What will you learn in this course? This course is designed to provide you with a comprehensive introduction to the field of machine learning. We will cover a wide range of topics, including supervised learning, learning from labeled data to make predictions, such as classifying images, predicting house prices, or detecting spam emails. Unsupervised learning, discovering hidden patterns and structures in unlabeled data, such as grouping similar customers, reducing the dimensionality of data, or identifying anomalies. Reinforcement learning, training agents to make sequential decisions in an environment to maximize cumulative rewards, such as playing games, controlling robots, or optimizing resource allocation. Deep learning, exploring the power of neural networks with multiple layers to learn complex representations from data, with applications in image recognition, natural language processing, and more. Model evaluation and selection, learning how to rigorously evaluate the performance of machine learning models, tune hyperparameters, and select the best model for a given task. Feature engineering and data preprocessing, mastering the art of transforming raw data into features that improve model performance. Ensemble methods, combining multiple models to achieve higher accuracy and robustness. Ethical considerations in machine learning, understanding the societal implications of machine learning, including issues of bias, fairness, transparency, and accountability. Practical applications, exploring real-world case studies and examples of machine learning across various domains, including healthcare, finance, e-commerce, and more. Deployment and scalability, how to make models available for use in the real world through cloud platforms. The journey ahead. This course is just the beginning of your machine learning journey. It will provide you with a strong foundation upon which you can build more advanced knowledge and skills. Machine learning is a dynamic and rapidly evolving field, so continuous learning and exploration are essential. We encourage you to actively engage with the material, experiment with the techniques you learn, and apply your knowledge to real-world problems. The future of machine learning is bright, and by mastering its foundations, you are positioning yourself to be a part of this exciting revolution. You are not just learning about algorithms and models, you are acquiring the tools to shape the future. Let's embark on this journey together, and unlock the incredible potential of intelligent machines. Lesson 1: Embarking on the machine learning journey. The allure of machine learning. Welcome, aspiring machine learning enthusiasts. You are about to embark on a captivating journey into the realm of machine intelligence, a field that is rapidly reshaping our world. This introductory lesson will serve as your gateway, providing a comprehensive overview of machine learning, its significance, and its transformative potential. We'll start by defining machine learning and exploring its core concepts. Firstly, at its very core, machine learning empowers computers to learn from data without the need for explicit programming. This means that instead of relying on rigid, predefined rules, machine learning algorithms are designed to analyze datasets, identify patterns, and extract meaningful insights. These insights are then used to make predictions or decisions about new, unseen data. This ability to learn and adapt is what distinguishes machine learning from traditional programming and unlocks a vast array of possibilities. Secondly, the importance of machine learning in today's technology-driven world is undeniable. Its influence spans across industries and domains, driving innovation and transforming the way we live and work. From the recommendation systems that curate our online experiences to the medical diagnostic tools that assist doctors, machine learning is at the heart of many technologies we interact with daily. As the volume of data generated globally continues to grow exponentially, the importance of machine learning will only continue to increase. Thirdly, the rise of machine learning represents a fundamental shift away from the traditional paradigm of programming. In the past, programmers had to anticipate every possible scenario and write explicit instructions for each. This approach, while effective for simple tasks, proved inadequate for tackling the complexities and dynamism of real-world problems. Machine learning, on the other hand, frees us from this constraint by enabling computers to learn directly from data and adapt to changing conditions. Fourthly, the fundamental mechanism behind machine learning involves algorithms that are trained on datasets. These algorithms are designed to automatically identify patterns and relationships within the data. The training process involves adjusting the internal parameters of the algorithm to minimize the error between its predictions and the actual values in the dataset. The more data an algorithm is exposed to, the better it becomes at discerning these patterns and making accurate predictions. Finally, one of the most powerful aspects of machine learning is its ability to generalize. Once an algorithm has been trained on a dataset, it can apply its learned knowledge to new, previously unseen data points. This generalization capability is essential for creating robust and reliable machine learning models. It means that the model is not simply memorizing the training data but has learned the underlying principles that govern the data, allowing it to make accurate predictions in real-world scenarios. Tracing the evolution of machine learning. The field of machine learning has a rich and fascinating history, punctuated by periods of rapid advancement, significant challenges, and renewed enthusiasm. Understanding this historical context is crucial for appreciating the current state and future potential of machine learning. In this section, we will delve into the key milestones and influential figures that have shaped the evolution of this dynamic field. The earliest conceptual seeds of machine learning can be traced back to the mid-20th century, a period marked by a growing fascination with the potential of computers. Visionaries like Alan Turing, a renowned mathematician and computer scientist, explored the possibility of creating machines that could not only perform calculations but also exhibit intelligent behavior. Turing's groundbreaking work, including his famous Turing test, laid the theoretical foundation for the field of artificial intelligence, within which machine learning plays a pivotal role. A major milestone in the development of machine learning was the invention of the perceptron algorithm in the late 1950s by Frank Rosenblatt. The perceptron was a rudimentary form of an artificial neural network that could learn to classify linearly separable data. While its capabilities were limited compared to today's advanced algorithms, the perceptron provided a tangible demonstration that algorithms could indeed learn from data, sparking considerable excitement and laying the groundwork for future research. Despite the initial optimism, the field of machine learning subsequently entered a period often referred to as the AI winter. Progress slowed as researchers encountered formidable challenges in developing algorithms that could effectively address more complex, real-world problems. Funding for research dwindled, and a sense of disillusionment pervaded the field. However, a small but dedicated group of researchers persevered, continuing to explore new ideas and techniques. The resurgence of machine learning in the late 1990s and early 2000s was fueled by several key factors. The exponential growth of computing power, as described by Moore's law, made it possible to train more sophisticated and computationally intensive models. Simultaneously, the advent of the Internet and the digitization of information led to an explosion in the availability of data, providing the essential fuel for machine learning algorithms to learn and thrive. This confluence of factors created a fertile ground for the rapid advancement of the field. Machine learning, a paradigm shift from traditional programming. Comprehending the transformative power of machine learning necessitates a clear understanding of its fundamental divergence from traditional programming approaches. While both approaches leverage the capabilities of computers to solve problems, their underlying philosophies and methodologies differ drastically. This segment will illuminate the key distinctions between these two paradigms. Traditional programming relies heavily on the explicit articulation of rules. Programmers must meticulously anticipate every possible scenario that a program might encounter and provide the computer with precise, step-by-step instructions on how to handle each situation. This approach is akin to providing an extremely detailed recipe, where every ingredient and action is explicitly defined. While effective for simple, well-defined tasks, this method quickly becomes unwieldy and impractical when dealing with complex, real-world problems. Machine learning, in stark contrast, empowers computers to learn from data without requiring explicit programming. Machine learning algorithms are specifically designed to be trained on datasets, enabling them to autonomously identify intricate patterns, extract meaningful insights, and improve their performance over time. This process mirrors how humans learn, through observation, experience, and feedback, rather than through rigid instruction. The inherent rigidity of traditional programming renders it ill-suited for addressing the complexities and dynamism of many real-world scenarios. Consider the challenge of developing a program to accurately identify spam emails. Spammers are constantly adapting their tactics, employing new techniques to circumvent filters. In a traditional programming approach, programmers would be engaged in a perpetual battle, constantly updating their rule sets to keep pace with the evolving landscape of spam. This is simply not scalable. Machine learning algorithms, on the other hand, excel in such dynamic environments due to their adaptability. A machine learning-based spam filter, for example, can be trained on a vast dataset of emails, comprising both spam and legitimate messages. Through this training process, the algorithm learns to discern the subtle patterns and characteristics that differentiate spam from legitimate emails. As new spam techniques emerge, the algorithm can continue to learn and adapt, maintaining its effectiveness without requiring constant manual intervention. This adaptability is a hallmark of machine learning. Furthermore, machine learning algorithms possess an unparalleled capacity for processing and analyzing vast quantities of data, far exceeding human capabilities. They can uncover hidden relationships and insights within data that would be virtually impossible for humans to detect. This ability has profound implications across a multitude of fields, from medical diagnosis and financial modeling to scientific research and personalized recommendations, enabling breakthroughs and innovations that were previously out of reach. Supervised learning. Learning with a teacher-supervised learning is a fundamental category within machine learning, characterized by the use of labeled datasets to train algorithms. In essence, the algorithm learns from data where the correct output or answer is already known. This section will explore the mechanics of supervised learning, highlighting its key features and applications. The defining characteristic of supervised learning is the presence of a labeled dataset. This means that each data point in the training set is paired with a corresponding target variable or label, which represents the desired output for that specific input. The algorithm's task is to learn a mapping function that can accurately predict the output for a given input, based on the examples provided in the training data. This process can be likened to a student learning from a teacher. The labeled dataset acts as the teacher, providing the student, the algorithm, with a set of questions, inputs, and their corresponding answers, outputs. The student's goal is to learn the underlying principles and relationships that connect the questions to the answers, so that they can answer new, unseen questions correctly. Supervised learning has found widespread applications in various domains, with image recognition being a prominent example. Consider the task of training a model to classify images of cats and dogs. In a supervised learning setting, the algorithm would be trained on a dataset of images, each labeled as either cat or dog. The algorithm learns to identify visual features that are characteristic of each animal, enabling it to classify new images with a high degree of accuracy. Beyond image recognition, supervised learning plays a vital role in finance, healthcare, and marketing. In finance, it can be used for credit scoring, fraud detection, and algorithmic trading. In healthcare, it aids in diagnosing diseases, predicting patient outcomes, and personalizing treatment plans. In marketing, it powers targeted advertising, customer segmentation, and churn prediction. The versatility of supervised learning stems from its ability to model complex relationships between inputs and outputs. Several prominent algorithms fall under the umbrella of supervised learning, including linear regression, logistic regression, support vector machines, SVMs, decision trees, and random forests. Each algorithm has its own strengths and weaknesses, making them suitable for different types of data and tasks. The choice of algorithm depends on factors such as the nature of the data, the complexity of the problem, and the desired level of accuracy. Unsupervised learning. Discovering hidden structures. Unsupervised learning represents a distinct category of machine learning where algorithms are tasked with uncovering hidden patterns, structures, and relationships within data without the guidance of labeled outputs. Unlike supervised learning, where the algorithm learns from data with known answers, unsupervised learning algorithms explore data to identify inherent structures and groupings on their own. In unsupervised learning, algorithms are presented with unlabeled data, meaning that the data points are not associated with any predefined output or target variable. The algorithm's objective is to autonomously discern patterns, anomalies, or groupings within the data. This process can be metaphorically compared to an explorer venturing into uncharted territory, seeking to map the landscape and understand its underlying features without the aid of a pre-existing map or guide. Clustering is a quintessential example of an unsupervised learning technique. Clustering algorithms aim to partition data points into distinct groups or clusters based on their similarities. A practical application of this is in customer segmentation. For instance, a clustering algorithm might analyze customer purchase histories to identify groups of customers with similar buying behaviors. These identified clusters can then inform targeted marketing campaigns or the development of personalized product recommendations. Dimensionality reduction is another significant application of unsupervised learning. This technique seeks to reduce the number of variables or features in a dataset while preserving its essential structure and minimizing information loss. This can be particularly useful for visualizing complex, high-dimensional data, improving the computational efficiency of other machine learning algorithms, and mitigating the effects of noise in the data. Principal component analysis, PCA, is a widely used dimensionality reduction technique. Anomaly detection, also known as outlier detection, is a further area where unsupervised learning proves invaluable. Anomaly detection algorithms are designed to identify data points that deviate significantly from the norm or expected patterns within a dataset. These anomalies can represent errors, fraudulent activities, or other unusual events that warrant further investigation. Applications range from fraud detection in financial transactions to identifying defective products in manufacturing. Anomaly detection plays a crucial role in maintaining data integrity and security. Reinforcement learning, learning through interaction. Reinforcement learning represents a unique and powerful approach within the field of machine learning. Unlike supervised or unsupervised learning, which primarily focus on analyzing existing data, reinforcement learning is concerned with training an agent to make sequential decisions within an environment to maximize a cumulative reward. This paradigm is inspired by behavioral psychology, where learning occurs through trial and error and feedback from the environment. The core principle of reinforcement learning involves an agent interacting with an environment. The agent takes actions within the environment, and in response, the environment provides feedback in the form of rewards or penalties. The agent's goal is to learn an optimal policy, which is a strategy or set of rules that dictates which actions to take in different situations to maximize the total reward it receives over time. A classic example of reinforcement learning is training an agent to play a game like chess or Go. The agent starts with no prior knowledge of the game's rules and learns purely by playing against itself or other opponents. Through repeated trials, the agent receives rewards for winning games and penalties for losing. Over time, and through countless interactions, it gradually learns to identify effective strategies and make decisions that increase its chances of winning. Reinforcement learning has found applications beyond game playing. In robotics, it can be used to train robots to perform complex tasks, such as grasping objects, navigating through environments, or even learning to walk. In control systems, reinforcement learning can be applied to optimize the performance of industrial processes, manage traffic flow, or control the temperature in a building. These applications demonstrate its versatility. Several key components are essential to understanding reinforcement learning. These include the agent, the environment, the state, representing the current situation, the action, taken by the agent, and the reward, feedback from the environment. Furthermore, the exploration-exploitation dilemma is a fundamental challenge. The agent must balance between exploring new actions and strategies to potentially discover better rewards and exploiting the knowledge it has already gained to maximize its current reward. The broad impact of machine learning across industries. The transformative influence of machine learning extends far beyond the confines of academic research and technology companies. It has permeated nearly every sector of the economy, revolutionizing processes, creating new opportunities, and fundamentally altering the way we live and work. This section will explore the diverse applications of machine learning across various industries. In healthcare, machine learning is proving to be an invaluable tool for improving diagnosis, treatment, and patient care. Machine learning algorithms can analyze medical images, such as X-rays, CT scans, and MRIs, with remarkable accuracy, aiding in the detection of diseases like cancer, often at earlier stages. Moreover, machine learning models can analyze patient data, including medical history, lab results, and genetic information, to predict the likelihood of developing certain conditions, enabling proactive interventions and personalized treatment plans. The financial industry has embraced machine learning for a wide range of applications, including fraud detection, algorithmic trading, risk assessment, and customer service. Machine learning algorithms can analyze vast quantities of financial transactions in real time, identifying patterns indicative of fraudulent activities and enabling swift action to prevent losses. In algorithmic trading, machine learning models can predict market movements and execute trades at optimal times, maximizing returns. In transportation, machine learning is at the forefront of the development of self-driving vehicles. Autonomous vehicles rely on sophisticated machine learning algorithms to process data from an array of sensors, including cameras, LiDAR, and radar. This enables them to perceive their surroundings, make driving decisions, and navigate complex environments without human intervention. The technology promises to revolutionize transportation, making it safer, more efficient, and more accessible. E-commerce giants like Amazon and Netflix have harnessed the power of machine learning to personalize the user experience and drive sales. Recommendation systems, powered by machine learning algorithms, analyze user behavior, purchase history, and browsing patterns to suggest products or movies that are likely to appeal to individual users. This personalization not only enhances customer satisfaction but also increases engagement and revenue. Machine learning is also making significant contributions to scientific research. In fields such as genomics, astronomy, and materials science, machine learning algorithms are being used to analyze massive datasets, identify patterns, and generate hypotheses that would be impossible for humans to discern. This is accelerating the pace of scientific discovery and enabling researchers to tackle complex problems that were previously considered intractable, leading to new insights and breakthroughs. Ethical considerations in machine learning. As machine learning becomes increasingly integrated into our daily lives, it is imperative to address the ethical considerations that arise from its widespread use. The decisions made by machine learning algorithms can have profound impacts on individuals and society, raising concerns about fairness, accountability, transparency, and privacy. This section will explore some of the key ethical challenges associated with machine learning. One of the most pressing concerns is the potential for bias in machine learning models. Machine learning algorithms are trained on data, and if this data reflects existing societal biases, the algorithm may inadvertently perpetuate and even amplify these biases in its predictions or decisions. For example, a facial recognition system trained predominantly on images of white faces may exhibit lower accuracy when identifying individuals with darker skin tones. This can lead to discriminatory outcomes in areas such as law enforcement and hiring. Fairness in algorithmic decision-making is closely related to the issue of bias. Machine learning models should be designed and evaluated to ensure that they treat all individuals and groups equitably, regardless of their race, gender, or other protected characteristics. Achieving fairness in practice is a complex challenge, as it requires careful consideration of the data, the algorithm, and the context in which the model will be deployed. Different definitions of fairness may also conflict with one another. Transparency and interpretability are also crucial ethical considerations. Many machine learning models, particularly deep neural networks, are often described as black boxes because it can be difficult to understand how they arrive at a particular decision. This lack of transparency can make it challenging to identify and correct errors or biases. It also raises questions about trust and accountability. Efforts are underway to develop more interpretable machine learning models and to provide explanations for their decisions. Accountability is another critical aspect of the ethical use of machine learning. When a machine learning system makes a mistake or causes harm, it is important to determine who is responsible. Is it the developer of the algorithm, the provider of the data, or the user of the system? Establishing clear lines of accountability is essential for ensuring that machine learning systems are used responsibly and that appropriate remedies are available when things go wrong. There are currently no clear guidelines for this. Finally, the increasing use of machine learning raises concerns about its potential impact on employment and the workforce. As machine learning-powered automation becomes more sophisticated, there are concerns about job displacement in certain sectors. While machine learning can also create new job opportunities, it is important to address the societal implications of automation and to develop strategies for supporting workers whose jobs may be affected. This is a growing concern in the modern age. The future of machine learning, trends and challenges. The field of machine learning is in a state of constant evolution, driven by ongoing research, technological advancements, and the ever-increasing availability of data. As we look to the future, several key trends and challenges are poised to shape the trajectory of machine learning and its impact on our world. One major trend is the increasing integration of machine learning with other emerging technologies. The Internet of Things, IoT, for example, generates massive amounts of data from connected devices. Machine learning algorithms can analyze this data to create smarter homes, cities, and industrial systems. Similarly, edge computing, which involves processing data closer to its source, is becoming increasingly important for real-time machine learning applications. This allows for faster processing and reduced latency. Advancements in deep learning continue to push the boundaries of what's possible with machine learning. Researchers are developing new and more sophisticated neural network architectures, such as transformers, which have revolutionized natural language processing and are finding applications in other domains. We can expect further breakthroughs in areas like computer vision, natural language understanding, and generative models. These breakthroughs will lead to even more powerful AI systems. The democratization of machine learning is another significant trend. Cloud-based machine learning platforms and open-source libraries are making machine learning tools and techniques more accessible to a wider range of developers, researchers, and businesses. This is fostering innovation and enabling smaller players to leverage the power of machine learning, even without extensive in-house expertise. This trend will likely continue as tools become more user-friendly. Explainable AI, XAI, is a rapidly growing field that seeks to address the black box problem of many machine learning models. XAI aims to develop techniques for making machine learning models more transparent and interpretable, allowing humans to understand the reasoning behind their decisions. This is crucial for building trust in machine learning systems and ensuring their responsible use, particularly in high-stakes applications such as healthcare and finance. Federated learning is an emerging trend that addresses concerns about data privacy. In federated learning, machine learning models are trained across multiple decentralized devices or servers holding local data samples, without exchanging them. This approach allows organizations to collaboratively train models without sharing sensitive data, preserving privacy, and reducing the risk of data breaches. This will become increasingly important as data privacy concerns grow. Despite the exciting progress and potential of machine learning, several challenges remain. Ensuring the robustness and reliability of machine learning models is a critical concern. Models can be vulnerable to adversarial attacks, where malicious actors intentionally manipulate inputs to cause the model to make incorrect predictions. Developing models that are resilient to such attacks and that perform reliably in real-world settings is an ongoing area of research. The need for large, high-quality datasets continues to be a major challenge. Many machine learning algorithms, especially deep learning models, require vast amounts of data to train effectively. Acquiring and labeling such datasets can be expensive and time-consuming. Furthermore, ensuring the quality and representativeness of the data is crucial for building fair and unbiased models. Addressing the ethical considerations surrounding machine learning will become increasingly important as the technology becomes more pervasive. Issues such as bias, fairness, transparency, accountability, and privacy need to be carefully considered and addressed to ensure that machine learning is used responsibly and for the benefit of all. This will require ongoing dialogue and collaboration among researchers, policymakers, and the public. The computational resources required to train and deploy complex machine learning models, particularly deep learning models, can be substantial. This can limit the accessibility of these models to organizations with significant resources. Research into more efficient algorithms and hardware, as well as the use of cloud computing, will be important for addressing this challenge. This is currently a barrier to entry for smaller companies and individuals. Finally, the shortage of skilled machine learning practitioners remains a bottleneck for the wider adoption of machine learning. There is a growing demand for individuals with expertise in machine learning, but the supply of qualified professionals has not kept pace. Addressing this skills gap through education and training programs will be crucial for realizing the full potential of machine learning. This will require significant investment in education and training. We have explored its fundamental concepts, traced its historical evolution, and examined its transformative impact across various industries. We have also delved into the different types of machine learning, including supervised, unsupervised, and reinforcement learning, and discussed the ethical considerations that accompany this rapidly advancing technology. The key takeaway from this lesson is that machine learning represents a fundamental shift in how we approach problem solving. By enabling computers to learn from data, we are unlocking new possibilities for innovation and creating intelligent systems that can augment human capabilities. As you continue your journey through this course, you will gain a deeper understanding of the principles and techniques that underpin machine learning. This will open exciting possibilities. In subsequent lessons, we will delve into the specifics of various machine learning algorithms, explore techniques for building and evaluating models, and examine real-world applications in greater detail. Each lesson will build upon the foundation laid here, progressively expanding your knowledge and skills. You will learn to apply various techniques and improve your skills. It is important to remember that mastering machine learning requires not only theoretical understanding but also hands-on experience. I encourage you to actively engage with the material, experiment with different algorithms and datasets, and work on practical projects. This hands-on experience will solidify your understanding and help you develop the skills needed to become a proficient machine learning practitioner. Finally, the field of machine learning is constantly evolving, with new research and advancements emerging at a rapid pace. To stay at the forefront of this dynamic field, it is essential to cultivate a habit of continuous learning. Seek out new resources, follow the latest research, and engage with the broader machine learning community. The journey ahead is filled with challenges and rewards. Embrace it, and enjoy the process of becoming a true machine learning expert. Lesson 2, Delving Deeper into Supervised Learning. Introduction to Supervised Learning Principles. Welcome back, machine learning enthusiasts. Building upon the foundation laid in Lesson 1, this lesson delves deeper into the realm of supervised learning, one of the most fundamental and widely used paradigms in machine learning. We will explore the core principles that govern supervised learning, examine its key components, and discuss the different types of supervised learning tasks, laying the groundwork for a more in-depth understanding of this powerful approach. Recall that supervised learning, at its core, is about learning a mapping function from input variables, features, to an output variable, target. This mapping function is inferred from a training dataset that consists of input-output pairs, where the correct output, or label, is known for each input. The goal is to learn a function that can accurately predict the output for new, unseen inputs. This process can be likened to a student learning from a teacher, where the training data serves as a textbook with examples and answers, and the algorithm is the student striving to learn the underlying concepts. A key characteristic of supervised learning is the presence of a labeled dataset. Each data point in the training set is tagged with a label that represents the desired output for that particular input. These labels serve as the supervision that guides the learning process. The algorithm learns by comparing its predictions to the true labels and adjusting its internal parameters to minimize the discrepancy or error. This iterative process of prediction and adjustment allows the algorithm to gradually improve its accuracy. The process of supervised learning typically involves several key steps. First, data relevant to the problem is collected and meticulously preprocessed. This may involve cleaning the data, handling missing values, transforming variables, and engineering new features. Next, the data is split into a training set and a testing set. The training set is used to train the algorithm, while the testing set is used to evaluate its performance on unseen data, providing an estimate of its generalization ability. Once the algorithm is trained, it can be used to make predictions on new, previously unseen data. The learned mapping function is applied to the input features of a new data point, and the algorithm outputs a prediction for the target variable. The accuracy of these predictions depends on several factors, including the quality of the training data, the choice of algorithm, the complexity of the underlying relationship between the input and output variables, and the proper tuning of the algorithm's hyperparameters. Key components of supervised learning models. Supervised learning models are composed of several essential components that work together to enable learning and prediction. Understanding these components is crucial for building, evaluating, and deploying effective machine learning systems. In this section, we will examine the key elements of supervised learning models, including the dataset, features, labels, the model itself, the loss function, and the optimization algorithm. The dataset is the cornerstone of any supervised learning model. It comprises a collection of data points, each of which is typically represented as a vector of features. Features are the individual, measurable properties or characteristics of the data that are used as inputs to the model. For example, in a dataset of houses, features might include the size of the house in square feet, the number of bedrooms and bathrooms, the location, the age of the property, and the presence of amenities like a garage or a swimming pool. Labels, also known as target variables or ground truth, are the known outputs associated with each data point in the training set. In supervised learning, the goal is to learn a mapping from the features to the labels. The labels provide the supervision that guides the learning process, enabling the algorithm to learn the relationship between the input features and the desired output. For example, in a dataset of houses, the label might be the sale price of each house, or in a classification setting, it might be a category like sold or not sold. The model is the mathematical function that the algorithm learns from the data. It represents the learned relationship between the features and the labels. The model can take many different forms, depending on the specific algorithm being used. For example, in linear regression, the model is a linear equation that relates the features to the target variable through a set of coefficients. In a decision tree, the model is a tree-like structure where each internal node represents a decision based on a feature, and each leaf node represents an output label or value. The loss function, also referred to as the cost function or objective function, is a crucial component that quantifies how well the model's predictions match the true labels. It measures the discrepancy or error between the predicted output and the actual output for each data point in the training set. The goal of the learning process is to find the model parameters that minimize the loss function across the entire training dataset. Different loss functions are appropriate for different types of supervised learning tasks. For example, in regression tasks, the mean squared error, MSE, is often used as a loss function, while in classification tasks, cross-entropy loss is commonly employed. The optimization algorithm is the procedure used to adjust the parameters of the model iteratively in order to minimize the loss function. It determines how the model learns from the data and converges towards an optimal solution. The most widely used optimization algorithm in supervised learning is gradient descent and its variants. Gradient descent works by iteratively updating the model's parameters in the direction that most steeply reduces the loss function. The learning rate is a hyperparameter that controls the size of the steps taken during each iteration, influencing the speed and stability of the learning process. Types of supervised learning tasks. Classification is a fundamental type of supervised learning task where the goal is to assign data points to predefined categories or classes. In this section, we will explore the characteristics of classification problems, discuss various classification algorithms, and examine real-world applications of classification. Classification problems are characterized by having a categorical target variable. This means that the output variable can take on a finite number of discrete values, each representing a distinct class or category. For example, in an email spam filter, the target variable might be spam or not spam. In medical diagnosis, the target variable could be the presence or absence of a particular disease. In image recognition, the target variable might be the type of object present in the image, such as cat, dog, or car. Binary classification is a special case of classification where there are only two possible classes. This is a common scenario in many real-world applications. For example, predicting whether a loan applicant will default or not, whether a patient has a particular disease or not, or whether an email is spam or not are all binary classification problems. Multi-class classification, on the other hand, involves more than two classes. For example, classifying handwritten digits into the numbers 0 through 9, identifying the species of a flower based on its characteristics, or categorizing news articles into different topics are all multi-class classification problems. Multi-class classification problems often require more sophisticated algorithms than binary classification problems. Several algorithms are commonly used for classification tasks. Logistic regression, despite its name, is a widely used algorithm for binary classification. It models the probability of an input belonging to a particular class using a logistic function, which outputs a value between 0 and 1. Decision trees are another popular choice for classification. They partition the input space into regions based on the feature values and assign a class label to each region. Decision trees are intuitive, interpretable, and can handle both categorical and numerical features. Support vector machines, SVMs, are powerful classification algorithms that aim to find the hyperplane that best separates the different classes in the input space. SVMs can handle both linearly separable and nonlinearly separable data by using a technique called the kernel trick, which implicitly maps the data into a higher dimensional space where it becomes linearly separable. Random forests are an ensemble learning method that combines multiple decision trees to improve classification accuracy and robustness. Each tree in the forest is trained on a random subset of the data and features, and the final prediction is made by aggregating the predictions of all the trees. Classification has numerous real-world applications across various domains. In medical diagnosis, classification algorithms can be used to classify patients as having a particular disease or not, based on their symptoms, medical history, and test results. In finance, classification can be used for credit scoring, where applicants are classified as high-risk or low-risk based on their financial history and other factors. In image recognition, classification algorithms can be used to identify objects in images, such as faces, cars, or different types of products. In natural language processing, classification is used for tasks such as sentiment analysis, topic categorization, and spam filtering. Types of supervised learning tasks. Regression is another fundamental type of supervised learning task where the goal is to predict a continuous output variable, as opposed to a categorical one. In this section, we will explore the characteristics of regression problems, discuss various regression algorithms, and examine real-world applications of regression. Regression problems are characterized by having a continuous target variable. This means that the output variable can take on any value within a given range, rather than being restricted to a set of discrete categories. For example, predicting the price of a house based on its features, e.g., size, location, number of bedrooms, is a regression problem because the price can be any positive real number within a certain range. Similarly, predicting the temperature for tomorrow, the stock price of a company, or the sales of a product are all regression problems. Linear regression is one of the simplest and most widely used regression algorithms. It models the relationship between the input features and the target variable as a linear equation. In simple linear regression, there is only one input feature, and the model takes the form of a straight line. In multiple linear regression, there are multiple input features, and the model represents a hyperplane in a higher dimensional space. The algorithm learns the coefficients of the linear equation that best fit the training data by minimizing the sum of squared errors between the predicted and actual values. Polynomial regression is an extension of linear regression that can model nonlinear relationships between the input features and the target variable. It does this by introducing polynomial terms of the input features into the linear equation. For example, a quadratic regression model would include squared terms of the input features, allowing it to capture curvature in the data. Higher-degree polynomial regression models can capture even more complex nonlinear relationships but are also more prone to overfitting. Decision trees can also be used for regression tasks. In this case, the tree partitions the input space into regions, and each region is associated with a constant value, which is the predicted output for any input that falls within that region. Regression trees are often used when the relationship between the input features and the target variable is nonlinear and complex, and they can capture interactions between features. However, they can be prone to overfitting if not properly pruned or regularized. Support vector regression, SVR, is another powerful regression algorithm that is based on the principles of support vector machines, SVMs. SVR aims to find a function that approximates the relationship between the input features and the target variable while minimizing the error and, at the same time, staying within a certain margin of tolerance. SVR can handle nonlinear relationships by using a kernel trick, similar to SVMs, to map the data into a higher dimensional space where it becomes linearly separable. Regression has numerous real-world applications across a wide range of domains. In finance, regression can be used to predict stock prices, forecast economic indicators, and model the relationship between various financial variables. In real estate, it can be used to estimate property values based on features such as location, size, and condition. In healthcare, regression can be used to predict patient outcomes, such as hospital readmission rates or length of stay, based on patient characteristics and medical history. In meteorology, regression is used to forecast weather variables such as temperature, precipitation, and wind speed. Evaluating the performance of supervised learning models. After training a supervised learning model, it is crucial to evaluate its performance to determine how well it generalizes to unseen data and to compare different models or hyperparameter settings. This evaluation is typically done using a held-out test set that was not used during training. In this section, we will discuss various metrics used to evaluate the performance of supervised learning models, both for classification and regression tasks. For classification tasks, one of the most common evaluation metrics is accuracy. Accuracy measures the percentage of correctly classified instances out of the total number of instances in the test set. While accuracy is a useful and intuitive metric, it can be misleading when the classes are imbalanced, meaning that one class has significantly more instances than the others. In such cases, a high accuracy can be achieved by simply predicting the majority class, without actually learning a meaningful model. Precision, recall, and F1 score are other important metrics for evaluating classification models, particularly when dealing with imbalanced datasets. Precision measures the proportion of true positive predictions out of all positive predictions made by the model, i.e., the number of correctly classified positive instances divided by the total number of instances classified as positive. Recall, also known as sensitivity or true positive rate, measures the proportion of true positive predictions out of all actual positive instances, i.e., the number of correctly classified positive instances divided by the total number of actual positive instances. The F1 score is the harmonic mean of precision and recall, providing a balanced measure of a model's performance that takes both metrics into account. The confusion matrix is a valuable tool for visualizing the performance of a classification model. It is a table that summarizes the number of true positives, true negatives, false positives, and false negatives for each class. The confusion matrix provides a more detailed breakdown of the model's performance than accuracy alone and can help identify the types of errors the model is making. For example, it can reveal whether the model is confusing certain classes or has a bias towards one class. Receiver operating characteristic (ROC) curves and the area under the ROC curve (AUC) are commonly used to evaluate the performance of binary classification models. The ROC curve plots the true positive rate, recall, against the false positive rate, 1, specificity, for different classification thresholds. The AUC provides a single scalar value that summarizes the overall performance of the model across all possible thresholds. An AUC of 1. 0 represents a perfect classifier, while an AUC of 0. 5 represents a random classifier. For regression tasks, common evaluation metrics include mean absolute error, MAE, mean squared error, MSE, and root mean squared error, RMSE. MAE measures the average absolute difference between the predicted and actual values. MSE measures the average squared difference between the predicted and actual values, while RMSE is the square root of MSE. MSE and RMSE are more sensitive to large errors than MAE due to the squaring operation. R squared, also known as the coefficient of determination, is another commonly used metric that measures the proportion of the variance in the target variable that is explained by the model. R squared ranges from 0 to 1, with higher values indicating a better fit. Data preprocessing and feature engineering for supervised learning. The quality of the data used to train a supervised learning model has a significant impact on the model's performance. Data preprocessing and feature engineering are crucial steps in the machine learning pipeline that can improve the quality of the data and enhance the model's ability to learn. In this section, we will discuss common data preprocessing techniques and the importance of feature engineering. Data preprocessing involves cleaning, transforming, and preparing the raw data into a format that is suitable for training a machine learning model. This may include handling missing values, which can be imputed using various techniques such as mean imputation, median imputation, or regression imputation. Outliers, which are data points that deviate significantly from the rest of the data, can be removed or transformed to reduce their impact on the model. Normalization and standardization are techniques used to scale the features to a similar range, which can improve the performance of some algorithms that are sensitive to the scale of the input features. Feature engineering is the process of creating new features from the existing features to improve the model's performance. This can involve transforming variables, creating interaction terms, or extracting relevant information from the raw data. For example, one might create a new feature that represents the ratio of two existing features or extract the day of the week from a date feature. Feature engineering often requires domain knowledge and can be a time-consuming but crucial step in building effective machine learning models. It is often considered more of an art than a science. Feature selection is another important aspect of data preprocessing. It involves selecting a subset of the most relevant features for training the model. This can improve the model's performance by reducing noise and overfitting, and it can also make the model more interpretable. Feature selection techniques include filter methods, which assess the relevance of features based on statistical measures, wrapper methods, which evaluate different subsets of features by training and testing a model, and embedded methods, which incorporate feature selection as part of the model training process. Data augmentation is a technique used to artificially increase the size of the training dataset by creating modified versions of the existing data points. For example, in image classification, data augmentation might involve rotating, flipping, cropping, or adding noise to the images. In natural language processing, it might involve replacing words with synonyms or paraphrasing sentences. Data augmentation can help to improve the model's generalization ability and reduce overfitting, particularly when the original dataset is small or lacks diversity. Overfitting and underfitting in supervised learning. Overfitting and underfitting are two common challenges in supervised learning that can significantly affect a model's ability to generalize to new, unseen data. Understanding these concepts and knowing how to address them is crucial for building effective machine learning models. In this segment, we will define overfitting and underfitting, discuss their causes, and explore techniques for mitigating these issues. Overfitting occurs when a model learns the training data too well, including the noise and outliers, and consequently fails to generalize well to new, unseen data. An overfitted model has high variance and low bias. It performs exceptionally well on the training data but poorly on the test data because it has essentially memorized the training examples rather than learning the true underlying patterns. Overfitting is often caused by having a model that is too complex relative to the amount and diversity of the training data. Underfitting, on the other hand, occurs when a model is too simple to capture the underlying structure of the data. An underfitted model has high bias and low variance. It performs poorly on both the training data and the test data because it fails to learn the relevant patterns and relationships in the data. Underfitting is often caused by having a model that is too simple or by not having enough features to adequately represent the complexity of the data. One technique for mitigating overfitting is to use a larger and more diverse training dataset. More data can help the model learn the true underlying patterns in the data, rather than memorizing the noise and outliers. Another technique for mitigating overfitting is to use a simpler model with fewer parameters. This can help to reduce the model's capacity to overfit the training data. For example, using a linear model instead of a high-degree polynomial model or using a decision tree with fewer branches can help prevent overfitting. Regularization is a common and effective technique for preventing overfitting in many types of models. It involves adding a penalty term to the loss function that discourages the model from learning overly complex relationships or assigning too much weight to any single feature. L1 regularization, lasso, adds a penalty proportional to the absolute value of the model's parameters, which can lead to sparse models where some parameters are set to 0. L2 regularization, ridge, adds a penalty proportional to the square of the model's parameters, which encourages smaller parameter values and smoother models. Cross-validation is a powerful technique used to assess how well a model will generalize to new data and to detect overfitting. K-fold cross-validation involves partitioning the data into K-subsets or folds. The model is trained on K1 folds and evaluated on the remaining fold. This process is repeated K times, with each fold serving as the test set once. The average performance across the K folds provides a more robust estimate of the model's generalization performance than a single train test split. Hyperparameter tuning and model selection. Machine learning models often have hyperparameters that need to be tuned to achieve optimal performance. Hyperparameters are parameters that are not learned from the data during training but are set prior to the learning process. In this segment, we will discuss the importance of hyperparameter tuning, explore techniques for tuning hyperparameters, and discuss strategies for model selection. Hyperparameters control the behavior and complexity of the learning algorithm and can have a significant impact on the performance of the resulting model. For example, in a decision tree, the maximum depth of the tree is a hyperparameter. In a support vector machine, the kernel type and the regularization parameter C are hyperparameters. In neural networks, the number of layers, the number of neurons in each layer, and the learning rate are all hyperparameters. The choice of hyperparameters can affect the model's ability to generalize, its computational complexity, and its training time. One common approach to hyperparameter tuning is grid search. Grid search involves defining a set of possible values for each hyperparameter and then training and evaluating a model for each possible combination of hyperparameter values. The combination that yields the best performance on a validation set, or through cross-validation, is selected as the optimal set of hyperparameters. Grid search can be computationally expensive, especially when dealing with a large number of hyperparameters and possible values. Randomized search is another approach to hyperparameter tuning that can be more efficient than grid search, especially when dealing with many hyperparameters. Instead of evaluating all possible combinations of hyperparameter values, randomized search samples a fixed number of combinations from a specified distribution for each hyperparameter. This allows for a broader exploration of the hyperparameter space with a limited computational budget. Bayesian optimization is a more sophisticated approach to hyperparameter tuning that uses a probabilistic model to guide the search for the optimal hyperparameters. It builds a surrogate model of the objective function, e.g., the model's performance as a function of the hyperparameters, and uses it to select the next set of hyperparameters to evaluate. Bayesian optimization can be more efficient than grid search or randomized search, particularly when the objective function is expensive to evaluate. Model selection involves choosing the best model among a set of candidate models. This often involves comparing models trained with different algorithms, different feature sets, or different hyperparameter settings. Cross-validation is commonly used for model selection, providing an estimate of each model's generalization performance. The model with the best cross-validation performance is typically selected as the best model. It is important to note that the test set should not be used for hyperparameter tuning or model selection. The test set should be held out until the very end of the process and used only once to evaluate the final selected model. This ensures an unbiased estimate of the model's performance on truly unseen data. Using the test set for tuning or selection can lead to overly optimistic estimates of performance and poor generalization. Ensemble methods in supervised learning. Ensemble methods are powerful techniques in supervised learning that combine the predictions of multiple models to improve overall performance. The idea behind ensemble methods is that by aggregating the predictions of diverse models, the ensemble can achieve better accuracy and robustness than any individual model. In this section, we will explore different types of ensemble methods and discuss their advantages. Bagging, which stands for bootstrap aggregating, is an ensemble method that involves training multiple models on different subsets of the training data. Each model is trained independently, and their predictions are combined, often by averaging, for regression, or voting, for classification. Random forests are a popular example of a bagging method that uses decision trees as the base models. Bagging can help to reduce variance and improve the stability of the model by averaging out the errors of individual models. Boosting is another type of ensemble method that involves training multiple models sequentially, where each model tries to correct the errors made by the previous models. Eta boost, adaptive boosting, and gradient boosting are popular boosting algorithms. In Eta Boost, each model is trained on a weighted version of the training data, where the weights are adjusted based on the performance of the previous models. Misclassified instances are given higher weights, forcing subsequent models to focus on them. Gradient boosting, on the other hand, trains each model to fit the residual errors of the previous models, gradually improving the overall prediction. Stacking, stack generalization, is a more advanced ensemble method that involves training a metamodel to combine the predictions of multiple base models. The base models are trained on the original training data, and their predictions are used as input features for the metamodel. The metamodel then learns how to best combine the predictions of the base models to make the final prediction. Stacking can often achieve higher accuracy than bagging or boosting, but it is also more complex and computationally expensive. Ensemble methods offer several advantages over single models. They can improve the accuracy and robustness of predictions by reducing variance and bias. They can also handle complex, nonlinear relationships in the data more effectively. Ensembles are often less prone to overfitting than individual models, as the errors made by different models tend to cancel each other out, leading to better generalization. Real-world applications and case studies in supervised learning. Supervised learning has a vast array of real-world applications across numerous industries. In this section, we will explore some specific examples and case studies that demonstrate the power and versatility of supervised learning in solving real-world problems. These examples will showcase how supervised learning is used to make predictions, automate decisions, and generate valuable insights. One prominent application of supervised learning is in medical diagnosis. For instance, supervised learning models can be trained to classify medical images, such as X-rays or MRI scans, to detect the presence of diseases like cancer or pneumonia. These models learn from large datasets of labeled images, where each image is tagged with the correct diagnosis. The trained model can then be used to automatically analyze new images and assist doctors in making accurate and timely diagnoses. In the financial industry, supervised learning is used for credit scoring and fraud detection. Credit scoring models are trained on historical data of loan applicants, including their financial history and whether they defaulted on their loans. The model learns to predict the creditworthiness of new applicants, helping banks and lenders make informed decisions about loan approvals. Similarly, fraud detection models are trained on data of past transactions, labeled as either fraudulent or legitimate, to identify patterns indicative of fraud. E-commerce companies leverage supervised learning for personalized recommendations and targeted advertising. By analyzing user data, such as browsing history, purchase history, and ratings, supervised learning models can predict which products or services a user is likely to be interested in. These predictions are used to generate personalized recommendations, improving the user experience and increasing sales. Targeted advertising uses similar techniques to identify the users who are most likely to respond to a particular advertisement. In the field of natural language processing, supervised learning is used for tasks such as sentiment analysis and text classification. Sentiment analysis involves determining the emotional tone or opinion expressed in a piece of text, such as a product review or a social media post. Text classification involves assigning text documents to predefined categories. For example, a supervised learning model can be trained to classify news articles into topics like sports, politics, or entertainment. Another interesting application of supervised learning is in image and video recognition. Supervised learning models can be trained to identify objects, faces, and actions in images and videos. This technology is used in self-driving cars to detect pedestrians, other vehicles, and traffic signals. It is also used in security systems for facial recognition and in social media for automatic image tagging. These are just a few examples of the many real-world applications of supervised learning. The versatility and power of supervised learning make it an essential tool in numerous domains, driving innovation and improving decision-making across industries. As data continues to grow and algorithms continue to improve, we can expect even more transformative applications of supervised learning in the years to come. This concludes our in-depth exploration of supervised learning in Lesson 2. We have covered the fundamental principles, key components, and different types of supervised learning tasks, including classification and regression. We have also discussed important concepts such as model evaluation, data preprocessing, overfitting, underfitting, hyperparameter tuning, and ensemble methods. Finally, we examined real-world applications and case studies to illustrate the practical impact of supervised learning across various domains. You should now have a solid understanding of supervised learning and be well prepared to tackle more advanced topics in subsequent lessons. This knowledge will serve as a cornerstone for your continued learning journey in the exciting field of machine learning. Keep practicing and experimenting with these concepts, as hands-on experience is invaluable in mastering this domain. Remember that machine learning is constantly evolving. Continue to learn. Lesson 3, Unsupervised Learning, Discovering Hidden Patterns. Welcome back to our exploration of the fascinating world of machine learning. In this lesson, we shift our focus to unsupervised learning, a paradigm that deals with unlabeled data and seeks to uncover hidden structures, patterns, and relationships within it. Unlike supervised learning, where the algorithm learns from labeled examples, unsupervised learning algorithms must explore the data and find meaningful insights on their own. Unsupervised learning stands in contrast to supervised learning. In supervised learning, the algorithm is provided with a labeled dataset, where each data point is associated with a known output or target variable. The algorithm's goal is to learn a mapping function that can accurately predict the output for new, unseen inputs. In unsupervised learning, however, the algorithm is presented with an unlabeled dataset, meaning that the data points are not associated with any predefined output or target variable. The algorithm's task is to discover the underlying structure of the data without any explicit guidance. The primary goals of unsupervised learning are to discover hidden patterns, structures, and relationships in data, to group similar data points together, to reduce the dimensionality of the data while preserving its essential structure, and to identify anomalies or outliers. Unsupervised learning is often used for exploratory data analysis, where the goal is to gain a deeper understanding of the data and to generate hypotheses. It can also be used as a pre-processing step for supervised learning, for example, by reducing the dimensionality of the data or by creating new features. Working with unlabeled data presents unique challenges. Without labeled examples to guide the learning process, unsupervised learning algorithms must rely on the inherent properties of the data to identify meaningful patterns. This often involves making assumptions about the structure of the data, such as the assumption that data points close to each other in the feature space are similar. Evaluating the performance of unsupervised learning algorithms can also be more challenging than in supervised learning, as there is no ground truth to compare against. Despite these challenges, unsupervised learning has numerous applications across various domains. Common applications include clustering, grouping similar data points together, dimensionality reduction, compressing data while preserving its essential structure, anomaly detection, identifying unusual data points, and association rule learning, discovering relationships between variables. Unsupervised learning is a powerful tool for exploratory data analysis, enabling us to gain insights into the structure of data and to discover hidden patterns that might not be apparent through other methods. Clustering, grouping similar data points. Clustering is a fundamental task in unsupervised learning that involves partitioning a dataset into groups, or clusters, such that data points within the same cluster are more similar to each other than to those in other clusters. This section will delve into the principles of clustering, explore popular clustering algorithms, and discuss how to evaluate clustering performance. The underlying principle of clustering is to group data points based on their similarity or proximity in the feature space. A good clustering algorithm will produce clusters where the intracluster similarity is high, data points within a cluster are similar to each other, and the intercluster similarity is low, data points in different clusters are dissimilar. The notion of similarity or distance between data points is crucial in clustering and is typically defined using a distance metric, such as Euclidean distance or cosine similarity. K-means clustering is one of the most widely used clustering algorithms. It aims to partition the data into K clusters, where K is a predefined parameter. The algorithm works iteratively by first randomly initializing K cluster centroids and then assigning each data point to the nearest centroid. The centroids are then updated to be the mean of the data points assigned to each cluster. This process is repeated until the cluster assignments no longer change or a maximum number of iterations is reached. Hierarchical clustering is another popular clustering approach that builds a hierarchy of clusters. It can be either agglomerative, bottom-up, or divisive, top-down. Agglomerative clustering starts with each data point as a separate cluster and then iteratively merges the closest pairs of clusters until all data points belong to a single cluster. Divisive clustering starts with all data points in one cluster and recursively splits clusters until each data point forms its own cluster. The result of hierarchical clustering is often visualized as a dendrogram. DISCAN, density-based spatial clustering of applications with noise, is a density-based clustering algorithm that groups together data points that are closely packed together, marking as outliers data points that lie alone in low-density regions. DISCAN does not require specifying the number of clusters beforehand and can discover clusters of arbitrary shapes. It has two main parameters, epsilon, the radius within which to search for neighboring points, and min-PTS, the minimum number of points required to form a dense cluster. Evaluating the performance of clustering algorithms can be challenging, as there are no ground truth labels to compare against. Internal evaluation metrics, such as the silhouette score, measure the compactness and separation of the clusters based on the distances between data points. External evaluation metrics, such as purity or the adjusted RAND index, can be used if some external information about the true cluster labels is available. Visual inspection of the clusters can also provide valuable insights. Dimensionality reduction, compressing data while preserving structure. Dimensionality reduction is a crucial technique in unsupervised learning that aims to reduce the number of variables or features in a dataset while preserving its essential structure and minimizing information loss. This section will explore the motivations for dimensionality reduction, discuss popular techniques like principal component analysis, PCA, and T-distributed stochastic neighbor embedding, TSNE, and highlight their applications. The need for dimensionality reduction often arises when dealing with high-dimensional data, where the number of features is very large. High-dimensional data can suffer from the curse of dimensionality, which refers to various phenomena that arise when analyzing and organizing data in high-dimensional spaces, such as increased computational complexity, sparsity of data, and overfitting. Dimensionality reduction techniques aim to mitigate these issues by transforming the data into a lower-dimensional space while retaining the most important information. Principal component analysis, PCA, is a widely used linear dimensionality reduction technique that aims to find the principal components of the data. Principal components are new, orthogonal variables that are linear combinations of the original features. They are ordered by the amount of variance they explain in the data, with the first principal component explaining the most variance, the second principal component explaining the second most, and so on. By selecting a subset of the principal components, we can reduce the dimensionality of the data while retaining most of the variance. T-distributed stochastic neighbor embedding, TSNE, is a nonlinear dimensionality reduction technique that is particularly well suited for visualizing high-dimensional data in 2 or 3 dimensions. TSNE models the probability distribution of pairwise similarities between data points in the high-dimensional space and aims to find a low-dimensional representation that preserves these similarities as much as possible. It is often used to reveal clusters and patterns in complex datasets. Linear discriminant analysis, LDA, while often used in supervised learning for classification, can also be employed for dimensionality reduction. LDA seeks to find linear combinations of features that best separate the different classes in the data. Although it requires labeled data, it can be a powerful technique for reducing dimensionality while preserving class separability. Dimensionality reduction has numerous applications, including data visualization, noise reduction, and improving the computational efficiency of other machine learning algorithms. By reducing the number of features, dimensionality reduction can make it easier to visualize and interpret complex datasets, filter out irrelevant or redundant features, and speed up the training of machine learning models. It is often used as a pre-processing step before applying other machine learning techniques, such as clustering or classification. Anomaly detection, identifying outliers. Anomaly detection, also known as outlier detection, is a crucial task in unsupervised learning that involves identifying data points that deviate significantly from the norm or expected patterns within a dataset. In this section, we will define different types of anomalies, discuss various approaches to anomaly detection, and explore its applications in diverse domains. Anomalies, or outliers, are data points that are significantly different from other data points in a dataset. They can be caused by various factors, such as measurement errors, data entry errors, or genuinely unusual events or phenomena. Anomalies can be broadly classified into 3 categories: point anomalies, individual data points that are anomalous with respect to the rest of the data; contextual anomalies, data points that are anomalous in a specific context; and collective anomalies, a collection of data points that is anomalous as a group. Statistical approaches to anomaly detection often involve modeling the distribution of the data and identifying data points that have a low probability of being generated by that distribution. For example, one might assume that the data follows a Gaussian distribution and flag data points that are more than a certain number of standard deviations away from the mean as anomalies. These methods are relatively simple and computationally efficient but may not be effective for complex, high-dimensional data. One-class support vector machines, SVMs, are a popular machine learning approach to anomaly detection. They learn a boundary around the normal data points in the training set and classify any data point outside this boundary as an anomaly. One-class SVMs are particularly effective when the normal data can be well separated from the rest of the feature space but do not assume any specific distribution for the data. The isolation forest algorithm is another powerful technique for anomaly detection. It works by isolating anomalies instead of profiling normal points. The algorithm recursively partitions the data space using randomly selected features and split points until each data point is isolated. Anomalies are expected to require fewer splits to be isolated than normal points. Isolation forest is efficient and effective for high-dimensional data. Anomaly detection has numerous applications across various domains. In fraud detection, anomaly detection algorithms can be used to identify unusual patterns in financial transactions that might indicate fraudulent activity. In intrusion detection, anomaly detection can help identify unusual network traffic patterns that might signal a cyber attack. In manufacturing, anomaly detection can be used to identify defective products or equipment malfunctions. In healthcare, it can be used to detect abnormal patient conditions or errors in medical data. Association rule learning, discovering relationships between variables. Association rule learning is a rule-based machine learning technique used to discover interesting relationships, frequent patterns, associations, or causal structures among variables in large datasets. This section will introduce the concept of association rule learning, discuss popular algorithms like a priori and FP growth, and explore its applications. Association rule learning is often used in market basket analysis, where the goal is to identify items that are frequently purchased together in a transaction database. For example, an association rule might be diapers, beer, chips, indicating that customers who buy diapers and beer together also tend to buy chips. Association rules are typically expressed in the form of if antecedent then consequent, along with metrics that quantify the strength and reliability of the rule. The a priori algorithm is a classic algorithm for association rule learning. It works by iteratively identifying frequent item sets of items that appear together in a minimum number of transactions, and then generating association rules from these item sets. The algorithm uses the a priori property, which states that any subset of a frequent item set must also be frequent, to efficiently prune the search space. The FP growth algorithm is another popular algorithm for association rule learning that uses a more efficient data structure called an FP tree, frequent pattern tree, to represent the transaction database. FP growth avoids the candidate generation step of a priori, making it faster for large datasets. It constructs the FP tree in a single pass over the data and then recursively mines the tree to extract frequent item sets. Several metrics are used to evaluate the interestingness of association rules. Support measures the frequency of an item set in the transaction database. Confidence measures the reliability of a rule, calculated as the support of the item set containing both the antecedent and the consequent divided by the support of the antecedent. Lift measures the strength of a rule, comparing the observed support of the rule to the expected support if the antecedent and consequent were independent. Association rule learning has numerous applications beyond market basket analysis. In recommendation systems, it can be used to identify items that are frequently purchased or viewed together and recommend them to users. In web usage mining, it can be used to discover patterns in user navigation behavior. In bioinformatics, it can be used to identify relationships between genes or proteins. It's a powerful tool for discovering hidden relationships. Generative models. Creating new data. Generative models represent a fascinating and rapidly advancing area of unsupervised learning. Unlike discriminative models, which learn to distinguish between different classes or predict outputs based on inputs, generative models learn the underlying distribution of the data itself. This enables them to generate new data instances that are similar to the training data. This section will introduce the concept of generative modeling and discuss popular techniques like generative adversarial networks, GANs, and variational autoencoders, VAEs. Generative modeling aims to learn a model of the probability distribution P, X, of the data, where X represents a data instance, e.g., an image, a sentence, or a sound waveform. Once the model has learned this distribution, it can generate new samples by sampling from this distribution. This capability opens up exciting possibilities for creating new content, augmenting datasets, and understanding the underlying structure of data. It's a cutting-edge area of research. Generative adversarial networks, GANs, are a powerful class of generative models that have achieved remarkable success in generating realistic images, videos, and other types of data. GANs consist of two neural networks, a generator and a discriminator, that are trained simultaneously in an adversarial game. The generator tries to create realistic data samples, while the discriminator tries to distinguish between real samples from the training data and fake samples generated by the generator. Through this adversarial process, both networks improve over time, leading to increasingly realistic generated samples. Variational autoencoders, VAEs, are another popular type of generative model that uses a different approach. VAEs are based on the idea of encoding the input data into a lower-dimensional latent space and then decoding it back into the original data space. The latent space is regularized to follow a specific distribution, typically a Gaussian distribution, which allows for generating new samples by sampling from this distribution and then decoding them. VAEs are often used for tasks such as image generation, anomaly detection, and data denoising. Restricted Boltzmann machines, RBMs, are an older type of generative model that are based on energy-based models. RBMs are undirected graphical models with a layer of visible units and a layer of hidden units, with connections only between the two layers. They learn to model the probability distribution of the data by adjusting the weights of the connections between the units. RBMs have been used for tasks such as dimensionality reduction, feature learning, and collaborative filtering. Generative models have a wide range of applications. In image generation, GANs and VAEs can create realistic images of faces, objects, and scenes. In data augmentation, generative models can be used to create new training examples, improving the performance of supervised learning models. In drug discovery, generative models can be used to design new molecules with desired properties. They are also used in art, music, and text generation. Evaluating unsupervised learning models. Evaluating the performance of unsupervised learning models presents unique challenges compared to supervised learning. Since unsupervised learning deals with unlabeled data, there is no ground truth or correct answer to compare the model's output against. This section will discuss the difficulties in evaluating unsupervised learning, introduce various evaluation metrics, and explore techniques for interpreting the results. One of the main challenges in evaluating unsupervised learning is the lack of a clear objective metric. In supervised learning, we can measure the accuracy, precision, recall, or other metrics that compare the model's predictions to the true labels. In unsupervised learning, however, the goal is often to discover hidden patterns or structures in the data, and the correctness of these patterns is subjective and depends on the specific application. Internal evaluation metrics for clustering, such as the silhouette score, the Kolinsky-Harabas index, and the Davies-Bolden index, assess the quality of the clusters based on the distances between data points within and between clusters. These metrics can provide a quantitative measure of how well the clusters are separated and how compact they are. However, they do not necessarily reflect the usefulness or meaningfulness of the clusters for a particular task. External evaluation metrics can be used when some external information about the true labels or categories of the data is available, even if it was not used during training. For example, purity, normalized mutual information, NMI, and the adjusted RAND index, ARI, can be used to compare the obtained clusters to known class labels. However, in many real-world unsupervised learning scenarios, such external information is not available. Visualization techniques play a crucial role in evaluating and interpreting the results of unsupervised learning. Techniques like TSNE and PCA can be used to visualize high-dimensional data in 2 or 3 dimensions, allowing us to see how the data points are clustered or separated. Visual inspection of the clusters or the reduced dimensional representation can provide valuable insights into the structure of the data and the performance of the algorithm. Interpreting the results of unsupervised learning often requires domain knowledge and qualitative analysis. For example, after clustering customers based on their purchasing behavior, a marketing expert might examine the characteristics of each cluster to determine if they represent meaningful customer segments. Similarly, after applying dimensionality reduction, a researcher might examine the principal components to understand which features contribute most to the variance in the data. It is a more subjective process than evaluating supervised learning. Preprocessing and feature engineering for unsupervised learning. While unsupervised learning algorithms do not rely on labeled data, the quality of the input data and the way it is represented can still significantly impact the performance of these algorithms. In this section, we will discuss the importance of data preprocessing and feature engineering for unsupervised learning and explore some common techniques. Data scaling is often a crucial preprocessing step for unsupervised learning, particularly for distance-based algorithms like k-means clustering and PCA. Features with larger values or ranges can disproportionately influence the distance calculations, leading to biased results. Scaling techniques, such as standardization, subtracting the mean and dividing by the standard deviation, or min-max scaling, scaling the data to a specific range, usually 0 to 1, can ensure that all features contribute equally to the distance calculations. Feature extraction techniques can also be beneficial for unsupervised learning. For example, in text data, techniques like TF-IDF, term frequency inverse document frequency, can be used to create numerical representations of text documents that capture the importance of each word in the document. In image data, techniques like SIFT, scale invariant feature transform, or HOG, histogram of oriented gradients, can be used to extract features that are invariant to scale, rotation, and illumination changes. Handling categorical variables appropriately is important for unsupervised learning, just as it is for supervised learning. Techniques like one-hot encoding or label encoding can be used to convert categorical variables into numerical representations that can be used by unsupervised learning algorithms. However, care must be taken when applying these techniques, as they can sometimes introduce unintended relationships or biases into the data. For example, label encoding might imply an ordinal relationship between categories that does not actually exist. Dealing with high-dimensional data is a common challenge in unsupervised learning. As the number of features increases, the data becomes sparser, and the distance between data points becomes less meaningful. This is known as the curse of dimensionality. Dimensionality reduction techniques, such as PCA and TSNE, can be used to reduce the number of features while preserving the essential structure of the data. Feature selection techniques, which aim to select a subset of the most relevant features, can also be applied. Domain knowledge plays a crucial role in feature engineering for unsupervised learning. Understanding the underlying domain and the meaning of the features can help in selecting appropriate preprocessing techniques, extracting meaningful features, and interpreting the results of unsupervised learning algorithms. For example, in a medical application, knowledge about the typical ranges and relationships between different physiological measurements can guide the feature engineering process and help in identifying anomalies. Advanced clustering techniques. While basic clustering algorithms like k-means and hierarchical clustering are widely used, there are many advanced clustering techniques that can be more suitable for certain types of data or specific applications. In this section, we will explore some of these advanced techniques, including fuzzy clustering, spectral clustering, model-based clustering, subspace clustering, and semi-supervised clustering. Fuzzy clustering, also known as soft clustering, is an extension of k-means where data points can belong to multiple clusters with varying degrees of membership. Instead of assigning each data point to a single cluster, fuzzy clustering assigns a probability or membership score to each data point for each cluster. This can be useful when the boundaries between clusters are not well defined or when data points exhibit characteristics of multiple clusters. The most popular fuzzy clustering algorithm is fuzzy C-means, FCM. Spectral clustering is a technique that uses the spectrum, eigenvalues, of the similarity matrix of the data to perform dimensionality reduction before clustering in fewer dimensions. It can identify complex cluster shapes and is particularly effective when dealing with non-convex clusters. Spectral clustering is based on graph theory concepts and involves constructing a graph representing the data and then partitioning the graph into clusters. Model-based clustering, also known as distribution-based clustering, assumes that the data is generated from a mixture of underlying probability distributions, typically Gaussian distributions. The most common model-based clustering algorithm is the expectation maximization (EM) algorithm applied to a Gaussian mixture model (GMM). Model-based clustering can identify clusters of different shapes and sizes and provides a probabilistic framework for clustering. Subspace clustering is a technique that aims to find clusters that exist in different subspaces of a high-dimensional dataset. In many high-dimensional datasets, clusters may only be meaningful in specific subsets of features, subspaces. Subspace clustering algorithms attempt to identify these subspaces and find the corresponding clusters. This is particularly useful in domains such as gene expression data analysis, where different genes may be relevant for different biological processes. Semi-supervised clustering combines elements of both supervised and unsupervised learning. It leverages a small amount of labeled data or pairwise constraints, e.g., must-link or cannot-link constraints, to guide the clustering process. This can improve the accuracy and relevance of the clusters, especially when the unlabeled data is abundant but labeled data is scarce or expensive to obtain. Semi-supervised clustering can be particularly useful in domains where some prior knowledge is available but not enough to perform fully supervised learning. Real-world applications and case studies in unsupervised learning. Unsupervised learning has a wide range of real-world applications across various domains. In this section, we will explore some specific examples and case studies that demonstrate the power and versatility of unsupervised learning in solving real-world problems. These examples will showcase how unsupervised learning is used to extract insights, discover patterns, and enable data-driven decision-making. Customer segmentation is a common application of unsupervised learning, particularly in marketing and e-commerce. By applying clustering algorithms to customer data, such as purchase history, browsing behavior, and demographics, companies can identify distinct groups of customers with similar characteristics and preferences. These segments can then be used for targeted marketing campaigns, personalized recommendations, and tailored product development. In image and video analysis, unsupervised learning techniques are used for tasks such as object recognition, image segmentation, and video summarization. For example, clustering can be used to group similar images together, while dimensionality reduction techniques can be used to extract features from images that can then be used for object recognition. Generative models, such as GANs and VAEs, can be used to generate new images or enhance existing ones. Topic modeling is a powerful application of unsupervised learning in text analysis. By applying techniques like latent Dirichlet allocation, LDA, to a large corpus of text documents, it is possible to discover the underlying topics or themes that are present in the documents. This can be used for document organization, information retrieval, and content recommendation. Topic modeling has been widely applied in areas such as news analysis, social media analysis, and scientific literature analysis. Network intrusion detection is another important application of unsupervised learning, particularly anomaly detection. By analyzing network traffic data, unsupervised learning algorithms can identify unusual patterns or behaviors that might indicate a cyber attack or a network intrusion. This can help organizations detect and respond to security threats in real time. Anomaly detection techniques are also used for fraud detection in financial transactions and for detecting faults in industrial systems. In the field of medical data analysis, unsupervised learning can be used to identify patterns in patient data that might be indicative of a particular disease or condition. For example, clustering can be used to group patients with similar symptoms or medical histories, potentially revealing new subtypes of a disease. Anomaly detection can be used to identify unusual patient cases that might require further investigation or to detect errors in medical data. These are just a few examples of the many real-world applications of unsupervised learning. As data continues to grow in size and complexity, unsupervised learning techniques will play an increasingly important role in extracting insights, discovering patterns, and enabling data-driven decision-making across various domains. The ability to learn from unlabeled data makes unsupervised learning a powerful tool for exploring and understanding the complex world around us. This lesson has provided a comprehensive overview of unsupervised learning, covering its fundamental principles, key techniques, and diverse applications. We have explored various clustering algorithms, dimensionality reduction techniques, anomaly detection methods, and association rule learning. We have also discussed the challenges of evaluating unsupervised learning and the importance of data preprocessing and feature engineering. Unsupervised learning is a powerful paradigm for extracting insights and discovering hidden structures in unlabeled data. It enables us to explore complex datasets, identify patterns, and generate hypotheses in the absence of explicit guidance or labeled examples. As the volume and complexity of data continue to grow, unsupervised learning will play an increasingly crucial role in data analysis, knowledge discovery, and decision-making across various domains. In the following lessons, we will continue to build upon these foundations, exploring other important areas of machine learning, including reinforcement learning, deep learning, and more. Remember that mastering machine learning requires not only theoretical understanding but also hands-on practice. I encourage you to experiment with the techniques discussed in this lesson on real-world datasets and to continue exploring the vast and exciting field of machine learning. Lesson 4, Reinforcement Learning, Learning by Doing. In this lesson, we will explore the fascinating world of reinforcement learning, RL, a powerful paradigm within machine learning that focuses on training agents to make sequential decisions in an environment to maximize cumulative rewards. Unlike supervised and unsupervised learning, which primarily deal with analyzing existing data, reinforcement learning involves an agent actively interacting with its environment and learning through trial and error. Reinforcement learning is inspired by behavioral psychology, particularly the concept of operant conditioning, where learning occurs through reinforcement in the form of rewards or punishments. In RL, an agent interacts with an environment by taking actions. The environment responds by transitioning to a new state and providing a scalar reward signal to the agent. The agent's goal is to learn an optimal policy, which is a mapping from states to actions that maximizes the expected cumulative reward over time. The reinforcement learning process can be summarized as follows. The agent observes the current state of the environment, selects an action based on its policy, and receives a reward and the next state from the environment. This process repeats iteratively, with the agent continually updating its policy based on the feedback it receives. The agent learns through trial and error, gradually improving its policy by associating actions with their long-term consequences. Reinforcement learning differs significantly from supervised and unsupervised learning. In supervised learning, the algorithm learns from labeled examples, where the correct output is provided for each input. In unsupervised learning, the algorithm learns from unlabeled data, seeking to discover hidden patterns or structures. In reinforcement learning, the agent learns from sequential feedback in the form of rewards, which are often sparse and delayed. There is no supervisor providing the correct action, the agent must discover it on its own. Reinforcement learning has a wide range of applications, including game playing, robotics, control systems, resource management, and personalized recommendations. It is particularly well suited for problems that involve sequential decision-making, where the current action can affect future outcomes. Some of the most impressive achievements in AI in recent years, such as AlphaGo's victory over the world champion in Go, have been driven by advances in reinforcement learning. Despite its power and versatility, reinforcement learning also presents several challenges. The exploration-exploitation dilemma requires the agent to balance between exploring new actions to discover potentially better strategies and exploiting the knowledge it has already gained to maximize its current reward. Designing an appropriate reward function that accurately reflects the desired behavior can be difficult. Furthermore, reinforcement learning algorithms can be sample inefficient, requiring a large amount of interaction with the environment to learn an effective policy. Markov decision processes, MDPs, Markov decision processes, MDPs, provide a formal mathematical framework for modeling sequential decision-making problems in reinforcement learning. They capture the essential elements of the reinforcement learning problem, including states, actions, transitions, and rewards. Understanding MDPs is crucial for understanding and developing reinforcement learning algorithms. An MDP is defined by a tuple, S, A, P, R, gamma, where S is a set of states, A is a set of actions, P is a state transition probability function, R is a reward function, and gamma is a discount factor. The state represents the current situation or configuration of the environment. The action is the choice made by the agent at each step. The state transition probability function P, SS, A, specifies the probability of transitioning to state S from state S after taking action A. The reward function R, S, A, S, provides the immediate reward received by the agent after taking action A in state S and transitioning to state S. The discount factor gamma, 0 less than or equal to gamma less than or equal to 1, determines the present value of future rewards, with lower values emphasizing immediate rewards over long-term rewards. A key assumption in MDPs is the Markov property, which states that the future is independent of the past given the present. In other words, the next state and reward depend only on the current state and action, and not on the history of previous states and actions. This property simplifies the analysis and allows for the development of efficient algorithms. The agent's behavior in an MDP is defined by a policy pi, AS, which specifies the probability of taking action A in state S. The goal of reinforcement learning is to find an optimal policy pi asterisk that maximizes the expected cumulative discounted reward, also known as the return. The value function v pi, s, represents the expected return starting from state S and following policy pi. The action value function q pi, s, a, represents the expected return starting from state S, taking action A, and then following policy pi. The Bellman equations are a set of recursive equations that relate the value of a state, or state-action pair, to the values of its successor states, or state-action pairs. They provide a way to compute the value function for a given policy and are fundamental to many reinforcement learning algorithms. The Bellman optimality equations define the optimal value function and optimal policy, which are the solutions that maximize the expected return. Model-free reinforcement learning, Q-learning model-free reinforcement learning methods are a class of algorithms that learn directly from the agent's interactions with the environment, without explicitly learning a model of the environment's dynamics. Q-learning is one of the most popular and influential model-free reinforcement learning algorithms. In this section, we will introduce model-free methods, discuss the Q-learning algorithm in detail, and explore the exploration-exploitation trade-off. Model-free methods are based on the idea of learning an action value function, also known as a Q function, which estimates the expected cumulative reward for taking a particular action in a given state and following a specific policy thereafter. Unlike model-based methods, model-free methods do not attempt to learn the transition probabilities or the reward function of the environment. Instead, they directly estimate the value of state-action pairs based on the observed rewards and state transitions. The Q-learning algorithm is an off-policy, model-free reinforcement learning algorithm that learns an optimal Q function, denoted as Q** S, A. The algorithm iteratively updates the Q values based on the observed rewards and the estimated values of the next state action pairs, using the Bellman equation as an update rule. The Q-learning update rule is given by Q, S, A, Q, S, A, plus alpha, R, S, A, S, plus gamma asterisk max, Q, S, A, where alpha is the learning rate, gamma is the discount factor, and max, Q, S, is the maximum Q value for the next state S over all possible actions A. The exploration-exploitation trade-off is a fundamental challenge in reinforcement learning. The agent needs to balance between exploring new actions and states to discover potentially better strategies, exploration, and exploiting the knowledge it has already gained to maximize its current reward, exploitation. A common strategy for balancing exploration and exploitation is the epsilon-greedy strategy. With probability epsilon, the agent chooses a random action, and with probability 1, epsilon, it chooses the action with the highest estimated Q value. SIRSA, State Action Reward State Action, is another model-free reinforcement learning algorithm that is closely related to Q-learning. Unlike Q-learning, which is an off-policy algorithm, SIRSA is an on-policy algorithm. This means that SIRSA learns the value of the policy that is being used to make decisions, rather than learning the value of the optimal policy directly. The SIRSA update rule is given by Q, S, A, plus alpha, R, S, A, S, plus gamma asterisk Q, S, A, where A is the action taken in the next state S according to the current policy. Model-free methods, such as Q-learning and SIRSA, are widely used in reinforcement learning due to their simplicity and flexibility. They do not require a model of the environment and can be applied to a wide range of problems. However, they can also be sample inefficient, requiring a large number of interactions with the environment to learn an effective policy. They may also struggle with large or continuous state and action spaces, where function approximation techniques may be needed. Model-based reinforcement learning methods take a different approach compared to model-free methods. Instead of directly learning a value function or policy, model-based methods learn a model of the environment's dynamics, including the transition probabilities and the reward function. This learned model is then used for planning and decision-making. The key idea behind model-based reinforcement learning is to learn a model of the environment, denoted as M equals P, R, where P represents the state transition probability function P, SS, A, and R represents the reward function R, S, A, S. The agent interacts with the environment, observes the state transitions and rewards, and updates its model based on these observations. The learned model can then be used to simulate the environment and predict the outcomes of different actions. Once a model of the environment has been learned, the agent can use it for planning. Planning involves using the model to simulate different action sequences and evaluate their potential outcomes without actually interacting with the real environment. This can be done using techniques such as value iteration or policy iteration, which are dynamic programming methods that can be applied to the learned model to compute the optimal value function or policy. The DynaQ algorithm combines model-based and model-free methods. It learns a model of the environment and uses it to generate simulated experiences, which are then used to update the Q function, in addition to the updates from real experiences. This allows the agent to learn more efficiently by leveraging both real and simulated experiences. DynaQ integrates learning, planning, and acting into a single algorithm. Monte Carlo tree search, MCTS, is another powerful model-based method that has achieved remarkable success in complex sequential decision-making problems, such as the game of Go. MCTS builds a search tree by selectively sampling trajectories through the state space, guided by a tree policy that balances exploration and exploitation. It uses Monte Carlo simulations to estimate the value of each node in the tree and gradually expands the tree by adding new nodes. MCTS has the advantage of being able to focus the search on the most promising areas of the state space. Model-based methods offer several advantages over model-free methods. They can be more sample efficient, as they can learn from simulated experiences generated from the learned model. They can also enable better generalization, as the learned model can capture the underlying structure of the environment. However, model-based methods also have some disadvantages. They rely on the accuracy of the learned model, and if the model is inaccurate or incomplete, the resulting policy may be suboptimal. Learning an accurate model can also be challenging, especially in complex environments with high-dimensional state and action spaces. Deep reinforcement learning, DRL, combines the power of deep neural networks with reinforcement learning algorithms to tackle complex decision-making problems. By using deep neural networks as function approximators, DRL can handle high-dimensional state and action spaces and learn intricate, nonlinear relationships between states, actions, and rewards. This section will introduce the key ideas behind DRL, discuss popular DRL algorithms, and highlight their applications. The core idea behind DRL is to use deep neural networks to approximate the value function, the policy, or both. Deep neural networks, with their ability to learn hierarchical representations and capture complex patterns in data, are well suited for approximating the complex functions that often arise in reinforcement learning. This enables DRL agents to learn directly from raw sensory inputs, such as images or text, without the need for handcrafted features. Deep Q networks, DQN, is a seminal DRL algorithm that combines Q-learning with deep neural networks. In DQN, a deep neural network is used to approximate the Q function, taking the state as input and outputting the Q values for each action. DQN uses several techniques to stabilize the learning process, including experience replay, which stores past experiences in a replay buffer and samples from it to update the network, and a separate target network, which is used to compute the target Q values and is periodically updated. Policy gradient methods are another important class of DRL algorithms that directly learn a parameterized policy, often represented by a deep neural network. Unlike value-based methods like DQN, which learn a value function and then derive a policy from it, policy gradient methods directly optimize the policy to maximize the expected cumulative reward. Policy gradient methods use gradient ascent to update the policy parameters in the direction that increases the expected return. Actor-critic methods combine the advantages of both value-based and policy-based methods. They learn both a value function, the critic, and a policy, the actor. The critic provides feedback to the actor on the quality of its actions, and the actor uses this feedback to improve its policy. Actor-critic methods can be more stable and sample-efficient than either value-based or policy-based methods alone. Examples include advantage actor-critic, A2C, and asynchronous advantage actor-critic, A3C. DRL has achieved remarkable success in various complex environments, including playing Atari games from raw pixel inputs, mastering the game of Go, and controlling robots in simulated and real-world environments. DRL algorithms have demonstrated the ability to learn complex behaviors and strategies directly from raw sensory inputs, surpassing human performance in some cases. However, DRL also faces challenges, such as high sample complexity, instability during training, and difficulty in exploring efficiently in large state and action spaces. Advanced topics in reinforcement learning. In this section, we will explore some advanced topics in reinforcement learning that extend beyond the basic algorithms and concepts discussed earlier. These topics address more complex scenarios and challenges that arise in real-world applications of reinforcement learning. Partially observable Markov decision processes, POMPs, are an extension of MDPs that deal with situations where the agent cannot fully observe the current state of the environment. In a POMDP, the agent receives observations that are probabilistically related to the underlying state. The agent must maintain a belief state, which is a probability distribution over possible states, and make decisions based on this belief state. Solving POMPs is generally more challenging than solving fully observable MDPs. Inverse reinforcement learning, IRL, is a problem where the goal is to infer the reward function of an agent, given its observed behavior or demonstrations. In many real-world scenarios, it is difficult to specify an appropriate reward function that accurately captures the desired behavior. IRL aims to overcome this challenge by learning the reward function from expert demonstrations. This can be useful in situations where it is easier for an expert to demonstrate the desired behavior than to explicitly specify a reward function. Hierarchical reinforcement learning, HRL, addresses the challenge of learning complex behaviors by decomposing them into a hierarchy of subbehaviors or subtasks. HRL methods learn at multiple levels of abstraction, allowing the agent to reason and plan at different time scales. This can improve the efficiency of learning and enable the agent to solve more complex problems that would be intractable for traditional, flat reinforcement learning methods. The options framework is a popular approach to HRL. Multi-agent reinforcement learning, MARL, deals with scenarios where multiple agents interact with each other and the environment. In MARL, each agent must learn a policy that takes into account the actions of other agents. This can lead to complex dynamics, as the optimal policy for one agent may depend on the policies of the other agents. MARL algorithms must address challenges such as non-stationarity, scalability, and the exploration-exploitation trade-off in a multi-agent setting. Transfer learning in reinforcement learning aims to leverage knowledge gained from one task or environment to improve learning performance on a different but related task or environment. Transfer learning can significantly reduce the amount of data and training time required to learn a new task by transferring relevant knowledge from a source task to a target task. This can be particularly useful in real-world applications where data is scarce or expensive to obtain. Evaluating reinforcement learning agents. Evaluating the performance of reinforcement learning agents is crucial for understanding their capabilities, comparing different algorithms, and identifying areas for improvement. In this section, we will discuss various metrics and techniques for evaluating reinforcement learning agents. The primary metric for evaluating reinforcement learning agents is the average return or average reward per episode. This measures the agent's ability to achieve its goal of maximizing the cumulative reward. Learning curves, which plot the average return over time, e.g., over training episodes, are commonly used to visualize the learning progress of an agent. Benchmarking against baselines is important for assessing the performance of reinforcement learning agents. Common baselines include random agents, which take random actions, and human expert performance, if available. Comparing the agent's performance to these baselines provides a measure of the agent's skill level and the difficulty of the task. Generalization is a key aspect of evaluating reinforcement learning agents. A good agent should not only perform well in the training environment but also generalize to new, unseen environments or variations of the task. Evaluating the agent's performance in different environments or under different conditions can provide insights into its ability to generalize. Several challenges arise when evaluating reinforcement learning agents. The performance of an agent can be highly variable due to the stochasticity of the environment and the agent's exploration strategy. Multiple runs with different random seeds are often necessary to obtain statistically significant results. The choice of evaluation metrics can also significantly impact the assessment of an agent's performance. Different metrics may capture different aspects of the agent's behavior, and it is important to choose metrics that are appropriate for the specific task and goals. Exploration strategies in reinforcement learning. Exploration is a critical aspect of reinforcement learning, as it enables the agent to discover new states, actions, and potentially better strategies. In this section, we will discuss various exploration strategies used in reinforcement learning. Epsilon-greedy exploration is one of the simplest and most widely used exploration strategies. The agent chooses the action with the highest estimated value, exploitation, with probability 1 epsilon and chooses a random action, exploration, with probability epsilon. The value of epsilon is typically decreased over time, starting with a high value to encourage exploration early on and gradually shifting towards exploitation as the agent learns more about the environment. Upper confidence bound, UCB, is a more sophisticated exploration strategy that selects actions based on their potential to yield high rewards. UCB assigns an exploration bonus to actions that have not been tried often or have high uncertainty in their value estimates. The UCB action selection rule chooses the action that maximizes the sum of the estimated value and the exploration bonus. Thompson sampling naturally balances exploration and exploitation, as actions with higher uncertainty are more likely to have high sampled values and thus be selected for exploration. Entropy-based exploration methods encourage exploration by adding an entropy term to the reward function. The entropy of a probability distribution measures its randomness or uncertainty. By maximizing both the reward and the entropy of the policy, the agent is encouraged to explore actions with uncertain outcomes. Entropy regularization can be incorporated into both value-based and policy-based methods. Curiosity-driven exploration is a more recent approach that motivates the agent to explore states that are novel or surprising. The agent is intrinsically rewarded for visiting states that are different from what it has experienced before or for which its predictions are inaccurate. This can be implemented by maintaining an internal model of the environment and rewarding the agent for prediction errors or for visiting states that lead to significant updates to the internal model. Advanced exploration techniques often combine multiple exploration strategies or adapt the exploration strategy based on the agent's learning progress. For example, the agent might start with a high degree of exploration early in training and gradually reduce it as it gains more knowledge about the environment. Exploration strategies can also be tailored to specific domains or tasks, taking into account prior knowledge or structure in the environment. Function approximation in reinforcement learning. In many real-world reinforcement learning problems, the state and action spaces are too large to be represented exactly using tabular methods like Q-learning or SURSA. Function approximation techniques are used to generalize from sampled experience to unseen states and actions, enabling reinforcement learning agents to handle large or continuous state and action spaces. Linear function approximation is a simple and widely used approach where the value function or action value function is approximated as a linear combination of features. The features can be hand-engineered or learned automatically. Linear function approximation can be effective when the features are well chosen and the underlying value function is approximately linear in the features. However, it may struggle to capture complex, nonlinear relationships. Neural network function approximation has become increasingly popular in recent years, particularly with the rise of deep reinforcement learning. Deep neural networks can learn hierarchical representations of the state and action spaces, allowing them to capture complex, nonlinear relationships between states, actions, and values. Deep Q networks, DQN, use deep neural networks to approximate the Q function, while policy gradient methods and actor-critic methods use neural networks to represent the policy and/or value function. Deep reinforcement learning with function approximation has achieved remarkable success in various domains, including playing Atari games from raw pixel inputs, mastering the game of Go, and controlling robots in simulated and real-world environments. However, combining function approximation with reinforcement learning can also introduce challenges. One challenge is the deadly triad, which refers to the combination of function approximation, bootstrapping, using estimated values to update value estimates, and off-policy learning, learning about a policy different from the one being used to generate behavior. When these three elements are combined, it can lead to instability and divergence during training. Another challenge is the non-stationarity of the target values in reinforcement learning. Unlike supervised learning, where the targets are fixed, in reinforcement learning, the target values depend on the agent's current policy or value function, which are constantly changing during training. This can make it difficult for function approximators to converge to a stable solution. Despite these challenges, function approximation is a crucial tool for scaling reinforcement learning to complex, real-world problems. Ongoing research aims to develop more stable and efficient algorithms for deep reinforcement learning with function approximation, as well as to better understand the theoretical properties of these methods. Real-world applications and case studies in reinforcement learning has shown great promise in solving a wide range of real-world problems, and its applications continue to expand. In this section, we will explore some notable examples and case studies of reinforcement learning in various domains. Game playing has been a major application area and testbed for reinforcement learning algorithms. Reinforcement learning agents have achieved superhuman performance in various games, including classic Atari games, board games like chess and Go, and modern video games like Dota 2 and StarCraft 2. AlphaGo, developed by DeepMind, was a landmark achievement, demonstrating that deep reinforcement learning can master the complex game of Go, surpassing the best human players. In robotics, reinforcement learning is used to train robots to perform complex tasks, such as grasping objects, locomotion, and navigation. Reinforcement learning allows robots to learn directly from interaction with the environment, without the need for explicit programming or hand-engineered control policies. This is particularly useful in unstructured or dynamic environments where it is difficult to specify a precise control strategy in advance. Control systems are another important application area for reinforcement learning. Reinforcement learning can be used to optimize the performance of various control systems, such as traffic light control, HVAC, heating, ventilation, and air conditioning systems, and industrial processes. By learning from data and feedback, reinforcement learning agents can adapt to changing conditions and improve the efficiency and robustness of control systems. Resource management problems, such as inventory management, supply chain optimization, and energy management, can also be addressed using reinforcement learning. For example, reinforcement learning agents can learn to optimize inventory levels to minimize costs while ensuring product availability, or to schedule energy consumption to reduce costs and carbon emissions. These applications often involve complex, dynamic environments with multiple interacting components. Personalized recommendations and advertising are areas where reinforcement learning is beginning to have an impact. By framing the recommendation problem as a sequential decision-making task, where the agent, recommender system, interacts with the user over time and receives feedback in the form of clicks, ratings, or purchases, reinforcement learning can be used to learn personalized recommendation policies that maximize user engagement and satisfaction. These are just a few examples of the many real-world applications of reinforcement learning. As algorithms continue to improve and as more domains are successfully addressed with reinforcement learning, we can expect to see even more widespread adoption of these techniques in the years to come. Reinforcement learning has the potential to revolutionize many aspects of our lives, from transportation and healthcare to entertainment and education. This concludes our exploration of reinforcement learning in Lesson 4. We have covered the fundamental concepts of reinforcement learning, including agents, environments, states, actions, and rewards. We have discussed different types of reinforcement learning algorithms, including model-free methods like Q-learning and SURSA, and model-based methods like DynaQ and Monte Carlo tree search. We have also delved into deep reinforcement learning, which combines the power of deep neural networks with reinforcement learning principles to tackle complex, high-dimensional problems. Advanced topics like inverse reinforcement learning, hierarchical reinforcement learning, multi-agent reinforcement learning, transfer learning, and meta-learning were also discussed. We also examined important considerations in reinforcement learning, such as the exploration-exploitation trade-off, various exploration strategies, and the challenges of using function approximation. Finally, we highlighted the diverse and impactful real-world applications of reinforcement learning, showcasing its potential to revolutionize fields such as game playing, robotics, control systems, resource management, and personalized recommendations. Reinforcement learning is a dynamic and rapidly evolving field that offers exciting opportunities for creating intelligent agents that can learn to make optimal decisions in complex environments. As you continue your machine learning journey, keep in mind that the principles and techniques discussed in this lesson form a strong foundation for understanding and applying reinforcement learning to a wide range of problems. In subsequent lessons, we will continue to build upon this foundation, exploring other fascinating areas of machine learning. Remember, continuous learning is key. Lesson 5, Deep Learning, Neural Networks and Beyond. In this lesson, we embark on a journey into the fascinating world of deep learning, a powerful subfield of machine learning that has revolutionized artificial intelligence in recent years. Deep learning algorithms, inspired by the structure and function of the human brain, have achieved remarkable success in a wide range of applications, from image and speech recognition to natural language processing and game playing. Deep learning is a class of machine learning techniques that uses artificial neural networks with multiple layers, hence deep, to model and understand complex patterns in data. Deep learning is a subset of machine learning, which itself is a subset of artificial intelligence, AI. AI is the broad concept of creating machines that can perform tasks that typically require human intelligence. Machine learning provides a set of tools for achieving AI, and deep learning is a particularly powerful set of techniques within machine learning. The history of deep learning can be traced back to the 1940s with the development of the first artificial neuron model by McCulloch and Pitts. However, it wasn't until the 2010s that deep learning truly took off, thanks to the availability of large datasets, increased computational power, especially GPUs, and algorithmic innovations. Deep learning's resurgence has been driven by its ability to automatically learn hierarchical representations of data, eliminating the need for manual feature engineering in many cases. Key concepts in deep learning include artificial neural networks, layers, neurons, or units, activation functions, weights, biases, backpropagation, and gradient descent. Deep learning models typically consist of many layers of interconnected neurons, organized in a hierarchical structure. Each neuron receives input from neurons in the previous layer, applies a nonlinear activation function, and passes the output to neurons in the next layer. The network learns by adjusting the weights and biases to minimize a loss function, using techniques like backpropagation and gradient descent. Deep learning has a wide range of applications across various domains. In computer vision, deep learning models are used for image classification, object detection, image segmentation, and facial recognition. In natural language processing, they are used for machine translation, text summarization, sentiment analysis, and question answering. In speech recognition, deep learning has dramatically improved the accuracy of automatic speech recognition systems. Other applications include drug discovery, medical image analysis, recommender systems, fraud detection, and autonomous driving. Artificial neural networks, the building blocks of deep learning. Artificial neural networks, ANNs, are the fundamental building blocks of deep learning. They are computational models inspired by the biological neural networks that constitute animal brains. Understanding the structure and function of ANNs is essential for grasping the principles of deep learning. The concept of artificial neural networks draws inspiration from the biological neurons in the brain. A biological neuron receives signals from other neurons through its dendrites, processes these signals in its cell body, and transmits an output signal through its axon to other neurons. Similarly, an artificial neuron receives inputs, applies a weighted sum and a nonlinear transformation, activation function, and produces an output. The perceptron, developed in the late 1950s, was one of the earliest artificial neural network models. It consisted of a single layer of artificial neurons that could learn to classify linearly separable data. However, the perceptron had limitations, as it could not learn nonlinear relationships. The exclusive or XOR problem highlighted this limitation, as a single-layer perceptron is unable to solve it. Multilayer perceptrons, MLPs, also known as feed-forward neural networks, overcome the limitations of the perceptron by introducing multiple layers of neurons, including one or more hidden layers between the input and output layers. Each neuron in a layer is connected to all neurons in the previous and subsequent layers. This layered architecture allows MLPs to learn complex, nonlinear relationships between inputs and outputs by learning hierarchical representations of the data. Activation functions introduce nonlinearity into neural networks, enabling them to learn complex patterns. Common activation functions include the sigmoid function, the hyperbolic tangent, tan, function, and the rectified linear unit, ReLU. The choice of activation function can impact the network's learning dynamics and its ability to model different types of data. Backpropagation is a key algorithm for training MLPs. It is a method for efficiently computing the gradients of the loss function with respect to the weights and biases in the network. Backpropagation uses the chain rule of calculus to propagate the error signal from the output layer back through the network, layer by layer. These gradients are then used by an optimization algorithm, such as gradient descent, to update the weights and biases and improve the network's performance. Training deep neural networks presents several challenges due to their depth and complexity. These challenges include vanishing and exploding gradients, the need for careful weight initialization, and the risk of overfitting. This section will explore these challenges and discuss techniques for effectively training deep networks. The vanishing gradient problem occurs when the gradients during backpropagation become extremely small as they are propagated back through many layers. This can make it difficult to train the earlier layers of the network effectively. The exploding gradient problem is the opposite, where the gradients become extremely large, leading to unstable training. These problems are particularly pronounced in deep networks with many layers and can hinder convergence. Weight initialization plays a crucial role in training deep networks. Proper initialization can help to prevent vanishing and exploding gradients and can speed up convergence. Techniques like Xavier/Glorot initialization and He initialization are commonly used to initialize the weights in a way that takes into account the number of input and output connections of a neuron. These methods help to ensure that the activations and gradients have appropriate scales during training. Batch normalization is a technique that normalizes the activations of each layer during training. It helps to stabilize and accelerate training by reducing the internal covariate shift, which is the change in the distribution of network activations due to the changing parameters during training. Batch normalization has been shown to improve the performance of deep networks and make them less sensitive to the choice of hyperparameters. Regularization techniques are essential for preventing overfitting in deep learning. Overfitting occurs when the network learns the training data too well, including the noise and outliers, and fails to generalize to new, unseen data. Dropout is a widely used regularization technique that randomly drops out, sets to zero, a fraction of the neurons in each layer during training. This forces the network to learn more robust features and prevents it from relying too heavily on any single neuron. Other regularization techniques include L1 and L2 regularization, which add a penalty term to the loss function based on the magnitude of the network's weights. Early stopping is another common technique, which involves monitoring the network's performance on a validation set during training and stopping the training process when the performance starts to degrade, indicating overfitting. Convolutional neural networks, CNNs, convolutional neural networks, CNNs, are a specialized type of deep neural network that has revolutionized the field of computer vision. CNNs are particularly well suited for processing grid-like data, such as images, and have achieved state-of-the-art performance in tasks like image classification, object detection, and image segmentation. CNNs are characterized by the use of convolutional layers, which apply a set of learnable filters to the input data. Each filter detects a specific pattern or feature in the input, such as edges, corners, or textures. The output of a convolutional layer is a set of feature maps, where each feature map represents the presence and location of a particular feature in the input. Convolutional layers exploit the spatial structure of images by using local receptive fields and shared weights, which significantly reduces the number of parameters compared to fully connected layers. Pooling layers are another key component of CNNs. Pooling layers reduce the spatial dimensions of the feature maps, decreasing the computational complexity and providing a degree of translation invariance. The most common type of pooling is max pooling, which takes the maximum value within a local region of the feature map. Other types of pooling include average pooling and L2 norm pooling. Over the years, several influential CNN architectures have been developed. Lenet 5, one of the earliest CNNs, was designed for handwritten digit recognition. AlexNet significantly improved upon Lenet 5 and achieved a breakthrough in the ImageNet large-scale visual recognition challenge in 2012, popularizing deep learning for computer vision. ResNet, residual network, introduced the concept of residual connections, which allow for the training of much deeper networks by mitigating the vanishing gradient problem. CNNs have found widespread applications in image recognition and computer vision. They are used for tasks such as image classification, object detection, object tracking, image segmentation, and facial recognition. CNNs have achieved remarkable accuracy in these tasks, often surpassing human performance. They are used in self-driving cars, medical image analysis, surveillance systems, and many other applications. Transfer learning is a powerful technique that leverages pre-trained CNNs for new tasks. Instead of training a CNN from scratch, which can require a large amount of data and computational resources, transfer learning involves using a CNN that has been pre-trained on a large dataset, e.g., ImageNet, and fine-tuning it for a specific task with a smaller dataset. This allows for faster training and often leads to better performance, especially when the available data for the new task is limited. Recurrent neural networks, RNNs, are a type of deep neural network designed to process sequential data, where the order of the data points matters. Unlike feed-forward neural networks, RNNs have internal memory that allows them to maintain information about previous inputs in the sequence. This makes them well suited for tasks involving natural language processing, time series analysis, and other domains where the data has a temporal or sequential structure. The key feature of RNNs is the presence of recurrent layers, which contain feedback connections that allow information to persist across time steps. At each time step, the recurrent layer receives an input and updates its hidden state based on the current input and the previous hidden state. The hidden state acts as a memory that summarizes the information seen so far in the sequence. The output of the recurrent layer can be used for prediction or passed to other layers in the network. One of the challenges in training RNNs is the vanishing gradient problem, which can make it difficult to learn long-range dependencies in the data. Long short-term memory, LSTM, networks are a special type of RNN designed to address this problem. LSTMs have a more complex internal structure than standard RNNs, with specialized memory cells and gating mechanisms that allow them to selectively store and retrieve information over long sequences. The gates control the flow of information into and out of the memory cells, enabling LSTMs to learn long-range dependencies more effectively. Gated recurrent units, GRUs, are another type of RNN that, like LSTMs, use gating mechanisms to control the flow of information. GRUs have a simpler architecture than LSTMs, with fewer parameters, which can make them faster to train. They have been shown to perform similarly to LSTMs on many tasks, although there is no clear consensus on which architecture is universally superior. RNNs, including LSTMs and GRUs, have found widespread applications in natural language processing, NLP, and time series analysis. In NLP, they are used for tasks such as machine translation, text summarization, sentiment analysis, and speech recognition. RNNs can model the sequential structure of language, allowing them to capture dependencies between words and generate coherent text. In time series analysis, RNNs can be used to model and forecast time-dependent data, such as stock prices, weather patterns, and sensor readings. Autoencoders and dimensionality reduction autoencoders are a type of neural network used for unsupervised learning, particularly for dimensionality reduction and feature learning. They are trained to reconstruct their input data, and in doing so, they learn a compressed representation of the data in a lower dimensional space, known as the latent space or bottleneck. An autoencoder consists of two main parts, an encoder and a decoder. The encoder maps the input data to a lower dimensional representation in the latent space, while the decoder maps the latent representation back to the original input space. The network is trained to minimize the reconstruction error, which is the difference between the input data and the reconstructed output. Undercomplete autoencoders have a latent space with a lower dimensionality than the input space. This forces the network to learn a compressed representation of the data, capturing the most important features and discarding redundant or irrelevant information. Undercomplete autoencoders can be used for dimensionality reduction, similar to principal component analysis, PCA, but with the ability to learn nonlinear relationships. Sparse autoencoders impose a sparsity constraint on the latent representation, meaning that only a small number of neurons in the latent space are active for any given input. This encourages the network to learn features that are only relevant for specific subsets of the data, leading to a more efficient and interpretable representation. Sparsity can be enforced by adding a penalty term to the loss function that encourages small activation values. Denoising autoencoders are trained to reconstruct the input data from a corrupted or noisy version of the input. This forces the network to learn robust features that are not affected by noise and to capture the underlying structure of the data. Denoising autoencoders can be used for data denoising, as well as for feature learning. Variational autoencoders, VAEs, are a type of generative model that combines autoencoders with variational inference. VAEs learn a probabilistic mapping from the input data to a latent space, where the latent variables are assumed to follow a specific distribution, typically a Gaussian distribution. This allows VAEs to generate new samples by sampling from the latent distribution and then decoding them. VAEs are often used for tasks such as image generation, data imputation, and anomaly detection. Autoencoders and their variants have numerous applications, including dimensionality reduction, feature learning, data compression, data denoising, and generative modeling. They can be used as a pre-processing step to reduce the dimensionality of the data before applying other machine learning algorithms, or they can be used to learn meaningful representations of the data that can be used for downstream tasks. Generative adversarial networks, GANs, generative adversarial networks, GANs, are a powerful class of neural networks that have revolutionized the field of generative modeling. Introduced by Ian Goodfellow and his colleagues in 2014, GANs have shown remarkable capabilities in generating realistic and diverse samples of data, including images, text, and audio. GANs consist of two neural networks, a generator and a discriminator, that are trained simultaneously in a competitive, adversarial game. The generator's goal is to produce synthetic data samples that are indistinguishable from real data, while the discriminator's goal is to correctly distinguish between real data samples and fake samples produced by the generator. The two networks are trained in an alternating fashion, with each network trying to outperform the other. The training process of GANs can be formulated as a minimax game, where the generator tries to minimize the discriminator's ability to distinguish between real and fake samples, while the discriminator tries to maximize its ability to correctly classify the samples. This adversarial training process drives both networks to improve over time, with the generator learning to produce increasingly realistic samples and the discriminator becoming more discerning. Since their introduction, various types of GANs have been proposed, each with its own strengths and weaknesses. Deep convolutional GANs, use convolutional layers in both the generator and discriminator, making them particularly well suited for image generation tasks. Cycle GANs can learn to translate images from one domain to another without paired training examples, enabling tasks like style transfer and image-to-image translation. GANs have found numerous applications, particularly in image generation and manipulation. They have been used to generate realistic images of faces, objects, and scenes, often with impressive quality and diversity. GANs have also been used for image editing tasks, such as image and painting, filling in missing parts of an image, super-resolution, increasing the resolution of an image, and style transfer, applying the style of one image to another. Despite their impressive capabilities, GANs are notoriously difficult to train. They can suffer from issues such as mode collapse, where the generator produces only a limited variety of samples, and non-convergence, where the training process fails to reach a stable equilibrium. Researchers are actively working on developing more stable and efficient training methods for GANs, as well as exploring new architectures and applications. Deep Reinforcement Learning, DRL, Deep Reinforcement Learning, DRL, is a powerful combination of deep learning and reinforcement learning that has led to significant breakthroughs in artificial intelligence. By using deep neural networks as function approximators, DRL can handle complex, high-dimensional environments and learn sophisticated policies and value functions. In DRL, deep neural networks are used to approximate the value function, the policy, or both. This allows DRL agents to learn directly from raw sensory inputs, such as images or text, without the need for handcrafted features. The deep neural networks learn hierarchical representations of the state and action spaces, enabling them to capture complex, nonlinear relationships between states, actions, and rewards. Deep Q networks, DQN, introduced by DeepMind in 2015, was one of the first successful DRL algorithms. DQN combines Q-learning with deep convolutional neural networks to learn to play Atari games directly from pixel inputs. The network is trained to approximate the Q function, taking the game screen as input and outputting the Q values for each possible action. DQN uses techniques like experience replay and a target network to stabilize the learning process. Policy gradient methods have also been combined with deep neural networks in DRL. Instead of learning a value function, policy gradient methods directly learn a parameterized policy, often represented by a deep neural network. The network takes the state as input and outputs a probability distribution over actions. Policy gradient methods use gradient ascent to update the policy parameters in the direction that increases the expected cumulative reward. Actor-critic methods combine the advantages of both value-based and policy-based methods. In actor-critic methods, a deep neural network is used to represent both the policy, the actor, and the value function, the critic. The critic provides feedback to the actor on the quality of its actions, and the actor uses this feedback to improve its policy. Actor-critic methods can be more stable and sample-efficient than either value-based or policy-based methods alone. DRL has achieved remarkable success in various complex environments, including playing Atari games from raw pixel inputs, mastering board games like Go and chess, and controlling robots in simulated and real-world environments. DRL algorithms have demonstrated the ability to learn complex behaviors and strategies directly from interactions with the environment, surpassing human performance in some cases. However, DRL also faces challenges, such as high sample complexity, instability during training, and difficulty in exploring efficiently in large state and action spaces. In this section, we will explore some advanced topics in deep learning that are pushing the boundaries of what's possible with neural networks. These topics represent active areas of research and have the potential to significantly impact the capabilities and applications of deep learning. Attention mechanisms have emerged as a powerful technique for improving the performance of deep learning models, particularly in natural language processing and computer vision. Attention allows the model to focus on the most relevant parts of the input when making a prediction or generating an output. In sequence-to-sequence tasks like machine translation, attention mechanisms enable the model to selectively attend to different parts of the input sequence when generating each word in the output sequence. This has led to significant improvements in translation quality compared to traditional RNN-based models. Transformers are a relatively new type of deep learning architecture that relies entirely on attention mechanisms, dispensing with recurrence and convolutions. Introduced in the paper, Attention is All You Need, by Vaswani et al., 2017, transformers have achieved state-of-the-art results in many NLP tasks, including machine translation, text summarization, and question answering. The transformer architecture is highly parallelizable, making it more efficient to train than RNNs. Its ability to capture long-range dependencies through attention has made it a powerful tool for modeling sequential data. Graph neural networks, GNNs, are a class of deep learning models designed to operate on graph-structured data. GNNs can learn representations of nodes and edges in a graph, taking into account the graph structure and the features of nodes and edges. They have applications in social network analysis, recommendation systems, drug discovery, and other domains where data can be naturally represented as a graph. GNNs generalize convolutional networks to graph data by defining convolution operations on graphs. Deep learning for 3D data is a growing area of research that aims to extend the success of deep learning to 3D data, such as point clouds, meshes, and volumetric grids. This has applications in computer-aided design, robotics, autonomous driving, and medical imaging. One challenge in this area is developing representations and architectures that can effectively handle the sparsity and irregularity of 3D data. PointNet and PointNet++ are examples of deep learning architectures designed for processing point cloud data. Unsupervised and self-supervised deep learning are approaches that aim to learn useful representations from unlabeled data. Unsupervised deep learning methods, such as autoencoders and GANs, learn to model the data distribution without explicit labels. Self-supervised learning is a form of unsupervised learning where the data itself provides the supervision. For example, a model might be trained to predict a masked portion of an image or a missing word in a sentence. These approaches have shown promise in reducing the reliance on large labeled datasets and improving the generalization ability of deep learning models. Real-world applications and case studies in deep learning has demonstrated remarkable success across a wide range of real-world applications, transforming industries and creating new possibilities. In this section, we will examine some notable examples and case studies that highlight the impact of deep learning in various domains. Image and video recognition is one of the areas where deep learning has had the most significant impact. Deep convolutional neural networks, CNNs, have achieved superhuman performance on benchmark image classification tasks like ImageNet. They are also used in object detection, image segmentation, and facial recognition. These capabilities have applications in autonomous driving, medical image analysis, surveillance systems, and robotics. In natural language processing, NLP, deep learning models, particularly recurrent neural networks, RNNs, and transformers, have dramatically improved the performance of machine translation, text summarization, sentiment analysis, and question answering systems. Deep learning-based language models like BERT and GPT have achieved state-of-the-art results on many NLP benchmarks, demonstrating a remarkable ability to understand and generate human language. Speech recognition and synthesis have also benefited significantly from deep learning. Deep neural networks have replaced traditional acoustic models in many speech recognition systems, leading to substantial improvements in accuracy. Deep learning is also used in speech synthesis, text-to-speech, enabling the creation of more natural-sounding and expressive synthetic voices. These technologies have applications in virtual assistants, voice search, and accessibility tools. In healthcare, deep learning is being used for drug discovery, medical imaging, and personalized medicine. Deep learning models can analyze large datasets of molecular structures to identify promising drug candidates, accelerating the drug development process. In medical imaging, deep learning is used to detect and diagnose diseases like cancer, often with accuracy comparable to or surpassing that of human experts. Deep learning can also analyze patient data to predict disease risk and tailor treatment plans. Autonomous driving is another area that has been significantly impacted by deep learning. Deep neural networks are used to process data from various sensors, such as cameras, LiDAR, and radar, enabling self-driving cars to perceive their environment, make driving decisions, and navigate complex scenarios. Companies like Tesla, Waymo, and others are heavily investing in deep learning research and development to make autonomous driving a reality. These are just a few examples of the many real-world applications of deep learning. As research continues to advance and as deep learning becomes more integrated with other technologies, we can expect even more transformative applications to emerge in the coming years. Deep learning has the potential to revolutionize many aspects of our lives, from the way we work and communicate to the way we diagnose and treat diseases. This concludes our exploration of deep learning in Lesson 5. We have covered the fundamental building blocks of deep learning, artificial neural networks, and explored various architectures such as convolutional neural networks, CNNs, recurrent neural networks, RNNs, autoencoders, and generative adversarial networks, GANs. We have also delved into advanced topics like attention mechanisms, transformers, graph neural networks, and discussed the growing importance of unsupervised and self-supervised learning. Deep learning has emerged as a powerful set of techniques for solving complex problems in various domains, as evidenced by the numerous real-world applications and case studies we have examined. From computer vision and natural language processing to healthcare and autonomous driving, deep learning is transforming industries and creating new possibilities. As you continue your journey in machine learning, remember that deep learning is a rapidly evolving field with ongoing research and development. Staying up to date with the latest advancements and continuing to deepen your understanding of the underlying principles will be crucial for harnessing the full potential of deep learning. In the following lessons, we will continue to build upon these foundations, exploring other important aspects of machine learning. Lesson 6, Model Evaluation and Selection. Introduction to Model Evaluation. Welcome to Lesson 6. In this lesson, we will dive into the crucial topic of model evaluation and selection. Building and training a machine learning model is only part of the process. Equally important is the ability to rigorously evaluate a model's performance, understand its strengths and weaknesses, and choose the best model for a given task. This lesson will cover the key concepts, techniques, and metrics used to assess and compare machine learning models. The importance of evaluating model performance cannot be overstated. A machine learning model that performs well on training data but poorly on unseen data is of little practical use. Therefore, we need robust methods to estimate how well a model will generalize to new data. Proper model evaluation allows us to identify and address issues such as overfitting and underfitting, to compare different models, and to tune hyperparameters effectively. The train-test split is a fundamental technique in model evaluation. The available data is divided into two sets, a training set used to train the model, and a test set used to evaluate its performance. The test set serves as a proxy for unseen data, providing an estimate of the model's generalization ability. Cross-validation is a more sophisticated technique that involves partitioning the data into multiple folds and iteratively training and testing the model on different combinations of folds. This provides a more robust estimate of performance. The bias-variance trade-off is a central concept in model evaluation. Bias refers to the error introduced by approximating a real-world problem with a simplified model. Variance refers to the model's sensitivity to fluctuations in the training data. A high-bias model underfits the data, while a high-variance model overfits the data. The goal is to find a model with an optimal balance of bias and variance that minimizes the overall error on unseen data. Overfitting occurs when a model learns the training data too well, including the noise and outliers, resulting in poor generalization to new data. Underfitting occurs when a model is too simple to capture the underlying patterns in the data, leading to poor performance on both training and test data. Understanding and addressing these issues is crucial for building effective machine learning models. Generalization performance refers to a model's ability to perform well on unseen data. This is the ultimate goal of model evaluation. A model that generalizes well has learned the underlying patterns in the data and can make accurate predictions on new data points that were not part of the training set. The techniques and metrics discussed in this lesson are all aimed at assessing and improving a model's generalization performance. Performance metrics for classification tasks, where the goal is to assign data points to specific categories, require specialized evaluation metrics. In this section, we will discuss the most common and important metrics used to evaluate the performance of classification models. Accuracy is perhaps the most intuitive metric, representing the percentage of correctly classified instances out of the total number of instances. While simple to understand, accuracy can be misleading when dealing with imbalanced datasets, where one class has significantly more instances than others. Precision and recall are two crucial metrics that provide a more nuanced view of a classifier's performance, especially in cases of class imbalance. Precision measures the proportion of true positive predictions out of all positive predictions made by the model, i.e., how many of the instances classified as positive are actually positive. Recall, also known as sensitivity, measures the proportion of true positive predictions out of all actual positive instances, i.e., how many of the actual positive instances were correctly classified. The F1 score is the harmonic mean of precision and recall, providing a single metric that balances both. It is particularly useful when there is an uneven class distribution. A high F1 score indicates that the model has both high precision and high recall. A confusion matrix is a table that provides a detailed breakdown of a classifier's predictions, showing the counts of true positives, true negatives, false positives, and false negatives for each class. It helps visualize the performance of a classification model and identify the types of errors it is making. For example, it can reveal whether the model is confusing certain classes or has a bias towards a specific class. ROC, Receiver Operating Characteristic, curves and AUC, area under the ROC curve, are widely used for evaluating binary classifiers. The ROC curve plots the true positive rate, recall, against the false positive rate at various classification thresholds. The AUC provides a single scalar value summarizing the overall performance of the classifier across all thresholds. A higher AUC indicates better performance. Precision recall curves are another useful tool, particularly when dealing with imbalanced datasets. They plot precision against recall for different thresholds. Analyzing the precision recall curve can help in choosing an appropriate threshold that balances precision and recall based on the specific needs of the application. Choosing the right metric for classification depends on the specific problem and the relative importance of different types of errors. For example, in medical diagnosis, a false negative, failing to detect a disease, might be more costly than a false positive, incorrectly diagnosing a disease. In such cases, recall might be prioritized over precision. Performance metrics for regression tasks, where the goal is to predict a continuous output variable, require different evaluation metrics than classification tasks. In this section, we will discuss the most common and important metrics used to evaluate the performance of regression models. Mean absolute error (MAE) is a straightforward metric that measures the average absolute difference between the predicted values and the actual values. It is easy to interpret and less sensitive to outliers than some other metrics. However, it treats all errors equally, regardless of their magnitude. Mean squared error (MSE) is another widely used metric that measures the average squared difference between the predicted values and the actual values. Squaring the errors gives more weight to larger errors, making MSE more sensitive to outliers than MAE. Root mean squared error, RMSE, is simply the square root of the MSE. It has the same units as the target variable, making it easier to interpret than MSE. RMSE is also sensitive to outliers and penalizes large errors more heavily than small errors. R-squared, coefficient of determination, is a statistical measure that represents the proportion of the variance in the target variable that is explained by the model. R-squared ranges from 0 to 1, with higher values indicating a better fit. An R-squared of 1 indicates that the model perfectly predicts the target variable, while an R-squared of 0 indicates that the model does no better than simply predicting the mean of the target variable. Choosing the right metric for regression depends on the specific problem and the desired properties of the model. MAE is a good choice when all errors should be treated equally and interpretability is important. MSE or RMSE are preferred when large errors are particularly undesirable. R-squared provides a measure of the overall goodness of fit of the model. It's often useful to consider multiple metrics when evaluating a regression model. Cross-validation techniques. Cross-validation is a powerful set of techniques for evaluating the performance of machine learning models and estimating their generalization ability. It provides a more robust estimate of performance than a single train test split by using multiple train test splits and averaging the results. K-fold cross-validation is the most common type of cross-validation. The data is divided into k-equal-sized folds. The model is trained on k-1 folds and evaluated on the remaining fold. This process is repeated k times, with each fold serving as the evaluation set once. The performance scores from each fold are then averaged to obtain an overall estimate of the model's performance. Stratified k-fold cross-validation is a variation of k-fold cross-validation that is particularly useful for classification tasks with imbalanced datasets. It ensures that each fold has approximately the same proportion of instances from each class as the original dataset. This helps to prevent folds from having too few instances of a particular class, which can lead to unreliable performance estimates. Leave one out cross-validation, LOOKV, is a special case of k-fold cross-validation where k is equal to the number of data points. Each data point is used as the evaluation set once, and the model is trained on the remaining data. LOOKV can be computationally expensive for large datasets but provides a nearly unbiased estimate of the model's performance. Time series cross-validation is a specialized technique for time series data, where the temporal order of the data must be respected. In this approach, the model is trained on a portion of the data up to a certain point in time and evaluated on a subsequent portion. The training set is then expanded to include more data, and the process is repeated. This ensures that the model is always evaluated on data that comes after the data it was trained on, mimicking a real-world forecasting scenario. Choosing the right cross-validation strategy depends on the specific problem, the size and nature of the dataset, and the computational resources available. K-fold cross-validation is a good general-purpose choice, while stratified k-fold is preferred for imbalanced classification problems. Time series cross-validation is essential for time-dependent data. Hyperparameter tuning. Hyperparameters are parameters of a machine learning model that are not learned from the data during training but are set prior to the learning process. Tuning these hyperparameters is crucial for achieving optimal model performance. This section will discuss various techniques for hyperparameter tuning. Grid search is a common and straightforward approach to hyperparameter tuning. It involves defining a set of possible values, a grid, for each hyperparameter to be tuned. The model is then trained and evaluated for each possible combination of hyperparameter values using cross-validation. The combination that yields the best cross-validation performance is selected as the optimal set of hyperparameters. Grid search is exhaustive but can be computationally expensive, especially when dealing with many hyperparameters and a large range of values. Randomized search is a more efficient alternative to grid search, particularly when dealing with a large number of hyperparameters. Instead of evaluating all possible combinations, randomized search samples a fixed number of hyperparameter combinations from specified probability distributions. This allows for a broader exploration of the hyperparameter space within a given computational budget. Randomized search is often more efficient than grid search and can sometimes find better hyperparameter combinations. Bayesian optimization is a more advanced technique that uses a probabilistic model to guide the search for optimal hyperparameters. It builds a surrogate model of the objective function, e.g., the model's cross-validation performance as a function of the hyperparameters, and uses it to select the next set of hyperparameters to evaluate. Bayesian optimization can be more efficient than grid search or randomized search, particularly when the objective function is expensive to evaluate, as it intelligently explores the hyperparameter space. Early stopping is a technique used during the training process to prevent overfitting and implicitly tune the number of training iterations. It involves monitoring the model's performance on a validation set during training and stopping the training process when the performance stops improving or starts to degrade. Early stopping can be seen as a form of regularization and can help to find a good balance between model complexity and generalization performance. Automated hyperparameter tuning tools are becoming increasingly popular. These tools, often integrated into machine learning libraries or platforms, automate the process of hyperparameter tuning using various techniques like grid search, randomized search, and Bayesian optimization. They can significantly reduce the manual effort involved in hyperparameter tuning and help to find better hyperparameter settings more efficiently. Examples include HyperOpt, Optuna, and the tuning capabilities within libraries like scikit-learn. Model selection strategies. Model selection is the process of choosing the best machine learning model for a particular task and dataset. This often involves comparing different algorithms, different feature sets, and different hyperparameter settings. This section will discuss strategies for effective model selection. One common approach to model selection is to compare different algorithms that are suitable for the problem at hand. For example, for a classification task, one might compare logistic regression, support vector machines, decision trees, and random forests. For a regression task, one might compare linear regression, support vector regression, and tree-based models. The choice of algorithm depends on factors such as the nature of the data, the size of the dataset, the desired interpretability of the model, and the computational resources available. Another important aspect of model selection is comparing different feature sets. Different subsets of features may be more or less informative for the task, and selecting the right features can significantly impact model performance. Feature selection techniques, as discussed in Lesson 7, can be used in conjunction with model selection to find the best combination of features and model. Comparing different hyperparameter settings is also a crucial part of model selection. As discussed in the previous section, hyperparameter tuning can have a significant impact on model performance. It is important to thoroughly explore the hyperparameter space for each candidate model to ensure that the best possible configuration is identified. Nested cross-validation is a technique used to perform both hyperparameter tuning and model selection while providing an unbiased estimate of the model's generalization performance. It involves using an outer loop of cross-validation for model selection and an inner loop of cross-validation for hyperparameter tuning within each outer fold. This ensures that the hyperparameter tuning is performed on a separate dataset from the final evaluation, preventing information leakage. Statistical significance testing can be used to determine whether the observed differences in performance between models are statistically significant or due to random chance. Techniques like the t-test or ANOVA can be used to compare the cross-validation scores of different models. However, it's important to be mindful of the limitations of statistical significance testing and to consider the practical significance of the performance differences as well. Addressing class imbalance, where one or more classes have significantly fewer instances than other classes, is a common problem in machine learning, particularly in classification tasks. This section will discuss techniques for addressing class imbalance and improving model performance on minority classes. Oversampling techniques aim to balance the class distribution by increasing the number of instances in the minority class. One popular oversampling technique is SMOTE, synthetic minority oversampling technique, which creates synthetic samples by interpolating between existing minority class instances. This helps to increase the representation of the minority class in the training data and can improve the model's ability to learn patterns from that class. Undersampling techniques, on the other hand, aim to balance the class distribution by decreasing the number of instances in the majority class. Random undersampling randomly removes instances from the majority class, while more sophisticated techniques try to remove redundant or less informative instances. Undersampling can reduce the computational cost of training and can sometimes improve performance, but it also risks discarding potentially useful information. Cost-sensitive learning is another approach to dealing with class imbalance. It involves assigning different misclassification costs to different classes during training. For example, in a medical diagnosis task, the cost of misclassifying a patient with a disease as healthy, false negative, might be higher than the cost of misclassifying a healthy patient as having the disease, false positive. Cost-sensitive learning can be incorporated into various algorithms by modifying the loss function or the decision threshold. Anomaly detection techniques can also be used to address class imbalance, particularly when the minority class represents anomalies or outliers. By treating the minority class as anomalies, anomaly detection algorithms can be used to identify these instances. This approach can be particularly useful when the minority class is very small or when the classes are highly overlapping. Choosing the right approach for addressing class imbalance depends on the specific problem, the dataset, and the algorithm being used. It is often useful to experiment with different techniques and compare their performance using appropriate evaluation metrics, such as precision, recall, F1 score, or AUC, which are more informative than accuracy when dealing with imbalanced data. Evaluating unsupervised learning models. Evaluating the performance of unsupervised learning models presents unique challenges compared to supervised learning. Since there are no ground truth labels to compare against, it is more difficult to assess the quality of the results in an objective manner. This section will discuss the challenges in evaluating unsupervised learning and introduce various evaluation metrics and techniques. The main challenge in evaluating unsupervised learning is the lack of a clear objective metric. In supervised learning, we can measure the accuracy or error of the model's predictions by comparing them to the true labels. In unsupervised learning, however, the goal is often to discover hidden patterns or structures in the data, and the correctness of these patterns is subjective and depends on the specific application. Internal evaluation metrics for clustering, such as the silhouette score, the Kolinsky-Harabas index, and the Davies-Bolden index, assess the quality of the clusters based on the distances between data points within and between clusters. These metrics can provide a quantitative measure of how well the clusters are separated and how compact they are. However, they do not necessarily reflect the usefulness or meaningfulness of the clusters for a particular task. External evaluation metrics can be used when some external information about the true labels or categories of the data is available, even if it was not used during training. For example, purity, normalized mutual information, NMI, and the adjusted RAND index, ARI, can be used to compare the obtained clusters to known class labels. However, in many real-world unsupervised learning scenarios, such external information is not available or may not be reliable. Visualization techniques play a crucial role in evaluating and interpreting the results of unsupervised learning. Techniques like TSNE and PCA can be used to visualize high-dimensional data in 2 or 3 dimensions, allowing us to see how the data points are clustered or separated. Visual inspection of the clusters or the reduced dimensional representation can provide valuable insights into the structure of the data and the performance of the algorithm. Interpreting the results of unsupervised learning often requires domain knowledge and qualitative analysis. For example, after clustering customers based on their purchasing behavior, a marketing expert might examine the characteristics of each cluster to determine if they represent meaningful customer segments. Similarly, after applying dimensionality reduction, a researcher might examine the principal components to understand which features contribute most to the variance in the data. Evaluating reinforcement learning agents. Evaluating the performance of reinforcement learning agents involves assessing their ability to learn effective policies for maximizing cumulative rewards in an environment. This section will discuss various metrics and techniques for evaluating reinforcement learning agents. Reinforcement learning tasks can be broadly classified as episodic or continuing. Episodic tasks have a natural endpoint, such as a game ending or a robot reaching a goal state. Continuing tasks, on the other hand, do not have a terminal state and continue indefinitely. The choice of evaluation metric may depend on the type of task. The primary metric for evaluating reinforcement learning agents is the average return or average reward per episode, for episodic tasks, or average reward per step, for continuing tasks. This measures the agent's ability to achieve its goal of maximizing cumulative reward. Learning curves, which plot the average return over time, e.g., over training episodes or steps, are commonly used to visualize the learning progress of an agent. Benchmarking against baselines is important for assessing the performance of reinforcement learning agents. Common baselines include a random agent that takes random actions and human expert performance, if available. Comparing the agent's performance to these baselines provides a measure of the agent's skill level and the difficulty of the task. For example, achieving superhuman performance on a task is a significant milestone for a reinforcement learning agent. Generalization is a key aspect of evaluating reinforcement learning agents. A good agent should not only perform well in the training environment but also generalize to new, unseen environments or variations of the task. Evaluating the agent's performance in different environments or under different conditions can provide insights into its ability to generalize. For example, an agent trained to play a racing game should ideally be able to perform well on different tracks or with different car models. Several challenges arise when evaluating reinforcement learning agents. The performance of an agent can be highly variable due to the stochasticity of the environment, the agent's exploration strategy, and the inherent randomness in the learning process. Multiple runs with different random seeds are often necessary to obtain statistically significant results. The choice of evaluation metrics can also significantly impact the assessment of an agent's performance. Different metrics may capture different aspects of the agent's behavior, and it is important to choose metrics that are appropriate for the specific task and goals. Model interpretability and explainability. As machine learning models become increasingly complex and are deployed in high-stakes applications, the need for interpretability and explainability has grown significantly. Model interpretability refers to the ability to understand how a model works and why it makes certain predictions. Explainability is the ability to explain a model's decisions in a human understandable way. The importance of model interpretability stems from several factors. First, interpretability can help to build trust in machine learning systems, particularly in domains where decisions have significant consequences, such as healthcare and finance. Second, interpretability can aid in debugging and improving models, as it allows developers to understand the model's strengths and weaknesses. Third, interpretability can provide insights into the underlying data and the problem being solved, potentially leading to new discoveries. Feature importance is a common technique for interpreting machine learning models. It involves determining the relative importance of each input feature in the model's predictions. For example, in a linear model, the magnitude of the coefficients can be used as a measure of feature importance. In tree-based models, feature importance can be calculated based on how often a feature is used for splitting and how much it reduces impurity. Partial dependence plots are another useful tool for model interpretation. They show the marginal effect of one or two features on the predicted outcome of a machine learning model. Partial dependence plots can help to visualize the relationship between a feature and the target variable, holding other features constant. They can reveal whether the relationship is linear, monotonic, or more complex. SHAP, Shapley additive explanations, values are a more recent and powerful technique for explaining individual predictions of complex models. Based on game theory, SHAP values provide a unified measure of feature importance that is both consistent and locally accurate. They decompose a prediction into the contributions of each feature, showing how much each feature contributed to the prediction compared to the average prediction. LIME, Local Interpretable Model Agnostic Explanations, is another popular technique for explaining individual predictions. LIME works by approximating the complex model locally with an interpretable model, e.g., a linear model or decision tree, and then using this interpretable model to explain the prediction. LIME can provide local explanations for any type of machine learning model, regardless of its complexity. This concludes our in-depth exploration of model evaluation and selection in Lesson 6. We have covered a wide range of topics, including performance metrics for classification and regression, cross-validation techniques, hyperparameter tuning, model selection strategies, addressing class imbalance, evaluating unsupervised learning models and reinforcement learning agents, and the importance of model interpretability and explainability. Mastering these concepts and techniques is crucial for building effective and reliable machine learning models. Proper model evaluation allows us to estimate how well a model will generalize to new data, compare different models, tune hyperparameters, and identify areas for improvement. As machine learning becomes increasingly integrated into various applications, the ability to rigorously evaluate and select models will only grow in importance. In the following lessons, we will continue to build upon this foundation, exploring other key aspects of machine learning, such as feature engineering, ensemble methods, and advanced techniques. Remember that model evaluation is an iterative process and often requires experimentation and domain knowledge. Keep practicing and refining your skills in this area, and you'll be well on your way to becoming a proficient machine learning practitioner. Lesson 7, Feature Engineering and Data Preprocessing. Introduction to Feature Engineering. In this lesson, we will delve into the crucial topic of feature engineering in data preprocessing. While machine learning models often take center stage, the quality of the data and the way it is represented can have an even greater impact on the performance of these models. Feature engineering and data preprocessing are the processes of transforming raw data into a format that is more suitable for machine learning algorithms, and they are essential steps in any machine learning pipeline. Feature engineering is the process of creating new features from existing ones, typically by applying transformations or combining features in meaningful ways. It is often said that better features lead to better models, and feature engineering is where domain knowledge and creativity play a significant role. The goal of feature engineering is to create features that capture the most important information in the data and make it easier for the model to learn the underlying patterns. Data preprocessing, on the other hand, involves cleaning, transforming, and preparing the raw data for use in machine learning models. This can include handling missing values, dealing with outliers, scaling or normalizing features, and encoding categorical variables. The goal of data preprocessing is to ensure that the data is in a format that is compatible with the chosen machine learning algorithm and to improve the quality and consistency of the data. Feature engineering and data preprocessing are closely related and often iterative processes. Decisions made during preprocessing can affect the types of features that can be engineered, and new features may require additional preprocessing steps. Both processes require a good understanding of the data, the problem being solved, and the machine learning algorithms being used. The importance of feature engineering and data preprocessing cannot be overstated. High-quality, well-engineered features can significantly improve the performance of machine learning models, often more so than simply choosing a more complex algorithm. Conversely, poor-quality data or poorly engineered features can lead to suboptimal or even misleading results. In many real-world applications, feature engineering and data pre-processing can consume a significant portion of the time and effort in a machine learning project. The feature engineering pipeline typically involves several steps, including brainstorming potential features, creating them, selecting the most relevant ones, and evaluating their impact on model performance. This process is often iterative, with new features being created and evaluated until satisfactory performance is achieved. It requires a combination of domain knowledge, creativity, and experimentation. It's important to keep in mind that there is no one-size-fits-all approach to feature engineering and that the best features will depend on the specific problem and dataset. Data cleaning and preprocessing. Data cleaning and preprocessing are essential steps in preparing data for machine learning. Real-world data is often messy, incomplete, and inconsistent, and these issues need to be addressed before training a model. This section will discuss common data cleaning and preprocessing techniques. Handling missing values is a common challenge in data preprocessing. Missing values can occur for various reasons, such as data entry errors, sensor failures, or non-response in surveys. One approach is to simply remove instances with missing values, but this can lead to loss of valuable information. Another approach is imputation, where missing values are replaced with estimated values. Common imputation techniques include mean imputation, median imputation, mode imputation, and regression imputation. Outlier detection and treatment is another important aspect of data cleaning. Outliers are data points that deviate significantly from the rest of the data. They can be caused by errors in data collection or measurement, or they can represent genuinely unusual but valid data points. Outliers can have a disproportionate impact on some machine learning models, so it's important to identify and handle them appropriately. Outliers can be detected using statistical methods, e.g., based on standard deviations from the mean, or visualization techniques, e.g., box plots. They can be removed, transformed, or capped, depending on the specific situation. Data normalization and standardization are techniques used to scale features to a similar range. Normalization typically involves scaling features to a range between 0 and 1, while standardization involves transforming features to have a mean of 0 and a standard deviation of 1. Scaling is important for algorithms that are sensitive to the scale of the input features, such as distance-based algorithms, e.g., k-nearest neighbors, k-means clustering, and algorithms that use gradient descent, e.g., linear regression, neural networks. Data transformation involves applying a mathematical function to a feature to change its distribution or relationship with other features. Common transformations include the logarithmic transformation, square root transformation, and Box-Cox transformation. These transformations can help to make the data more normally distributed, stabilize the variance, or linearize relationships between variables, which can improve the performance of some machine learning models. Encoding categorical variables is necessary when dealing with features that represent categories or labels rather than numerical values. One-hot encoding is a common technique that creates binary features for each category, where a value of 1 indicates the presence of the category and 0 indicates its absence. Label encoding assigns a unique numerical value to each category. The choice of encoding technique depends on the nature of the categorical variable and the specific machine learning algorithm being used. Feature extraction techniques. Feature extraction is the process of transforming raw data into a set of features that can be used by a machine learning model. This often involves reducing the dimensionality of the data while preserving the most important information. This section will discuss several common feature extraction techniques. Principal component analysis, PCA, is a widely used technique for dimensionality reduction and feature extraction. PCA transforms the original features into a new set of uncorrelated features called principal components. These principal components are linear combinations of the original features and are ordered by the amount of variance they explain in the data. By selecting a subset of the principal components, we can reduce the dimensionality of the data while retaining most of the variance. Linear discriminant analysis, LDA, is another dimensionality reduction technique that is similar to PCA but takes into account class labels. LDA aims to find a linear combination of features that maximizes the separation between different classes while minimizing the variance within each class. LDA is often used as a pre-processing step for classification tasks. Feature extraction from text data is a crucial step in natural language processing. One common technique is the bag of words, BAW, model, which represents a text document as a collection of individual words, disregarding grammar and word order but keeping track of word frequency. TF-IDF, term frequency inverse document frequency, is a refinement of the BAW model that weights words based on their importance in the document and across the corpus. Feature extraction from images is a key aspect of computer vision. Handcrafted features, such as HOG, histogram of oriented gradients, and SIFT, scale invariant feature transform, were traditionally used to extract relevant information from images. However, deep learning has revolutionized feature extraction from images, with convolutional neural networks, CNNs, automatically learning hierarchical features directly from the raw pixel data. Feature extraction from time series data often involves computing statistical measures over time windows, such as the mean, standard deviation, minimum, maximum, and percentiles. Other techniques include extracting frequency domain features using Fourier transforms or wavelet transforms. The choice of features depends on the specific characteristics of the time series and the problem being addressed. Feature selection techniques. Feature selection is the process of selecting a subset of the most relevant features for training a machine learning model. It can improve model performance, reduce overfitting, enhance interpretability, and decrease training time. This section will discuss various feature selection techniques. Filter methods are a class of feature selection techniques that assess the relevance of features based on their statistical properties, independent of any specific machine learning model. Common filter methods include correlation-based feature selection, which selects features that are highly correlated with the target variable but have low correlation with each other, and mutual information, which measures the amount of information that one variable provides about another. Filter methods are computationally efficient but may not select the best features for a specific model. Wrapper methods evaluate different subsets of features by training and testing a specific machine learning model. They use the model's performance as the evaluation criterion to search for the best subset of features. Recursive feature elimination, RFE, is a popular wrapper method that recursively removes features and builds a model on the remaining features, using the model's performance to identify the least important features. Wrapper methods are tailored to a specific model but can be computationally expensive. Embedded methods incorporate feature selection as part of the model training process. For example, lasso, least absolute shrinkage and selection operator, is a linear regression technique that uses L1 regularization to shrink the coefficients of less important features to zero, effectively performing feature selection. Decision trees and tree-based ensemble methods like random forests can also be used for feature selection, as they provide a measure of feature importance based on how often a feature is used for splitting and how much it reduces impurity. Choosing the right feature selection technique depends on various factors, including the size and dimensionality of the dataset, the type of machine learning model being used, and the computational resources available. It is often beneficial to experiment with different techniques and compare their performance using cross-validation. Feature selection is an important step in the machine learning pipeline that can lead to simpler, faster, and more accurate models. Feature scaling and normalization. Feature scaling and normalization are important pre-processing techniques that can significantly impact the performance of many machine learning algorithms. They involve transforming the features to a similar scale or range, which can help to prevent features with larger values from dominating those with smaller values and can improve the convergence of optimization algorithms. Min-max scaling is a normalization technique that scales features to a specific range, usually between 0 and 1. It is calculated as x_scaled equals x min x / max x min x, where x is the original feature value, min x is the minimum value of the feature, and max x is the maximum value of the feature. Min-max scaling preserves the relationships among the original data values but can be sensitive to outliers. Standardization, also known as z-score normalization, transforms features to have a mean of 0 and a standard deviation of 1. It is calculated as x_standardized equals x mean x / std x, where mean x is the mean of the feature and std x is the standard deviation of the feature. Standardization is less affected by outliers than min-max scaling and is often preferred for algorithms that assume normally distributed features. Robust scaling is a technique that is less sensitive to outliers than min-max scaling or standardization. It uses the median and interquartile range, IQR, to scale the features. The formula for robust scaling is x_robust equals x median x / IQR x. Robust scaling can be a good choice when the data contains outliers or when the distribution of the features is not known. Unit vector scaling involves scaling the components of a feature vector so that the vector has a length of 1. This is often used in text analysis and information retrieval, where the magnitude of the feature vector is less important than its direction. Unit vector scaling can be combined with other scaling techniques. The choice of whether and how to scale features depends on the specific machine learning algorithm being used. Distance-based algorithms, such as k-nearest neighbors and k-means clustering, and algorithms that use gradient descent, such as linear regression and neural networks, are particularly sensitive to feature scaling. Tree-based algorithms, such as decision trees and random forests, are generally invariant to feature scaling. It is often a good practice to experiment with different scaling techniques and compare their impact on model performance using cross-validation. Handling categorical data, which represents categories or labels rather than numerical values, is common in many real-world datasets. However, most machine learning algorithms require numerical inputs. Therefore, it is necessary to encode categorical features into numerical representations before using them in a model. One-hot encoding is a widely used technique for handling categorical features. It creates a binary feature for each category, where a value of 1 indicates the presence of the category and 0 indicates its absence. For example, if a categorical feature, color, has 3 categories, red, green, blue, one-hot encoding would create 3 binary features, color_red, color_green, and color_blue. One-hot encoding is particularly suitable for nominal categorical variables, where there is no inherent order among the categories. Label encoding is another technique that assigns a unique integer to each category. For example, red might be encoded as 0, green as 1, and blue as 2. Label encoding is more compact than one-hot encoding, as it only creates one new feature. However, it can introduce an artificial ordinal relationship between the categories, which may not be appropriate for nominal variables. Ordinal encoding is used when the categorical variable has an inherent order or ranking. For example, a feature representing education level, high school, bachelor's, master's, PhD, has a natural order. Ordinal encoding assigns integers to the categories based on their order. It is important to ensure that the assigned numerical values reflect the true order of the categories. Target encoding, also known as mean encoding, is a technique that replaces each category with the average value of the target variable for that category. For example, if we are predicting customer churn, we might replace each category in a state feature with the average churn rate for customers from that state. Target encoding can be effective but must be used with caution, as it can lead to overfitting if not done carefully, such as by using cross-validation to estimate the target values. Embedding categorical features is a more advanced technique that involves learning a low-dimensional vector representation for each category. This is often done using neural networks, where an embedding layer maps each category to a dense vector. Embeddings can capture semantic relationships between categories and can be learned as part of the overall model training process. They are particularly useful when dealing with high cardinality categorical features, where the number of unique categories is very large. Dealing with time and date features are common in many datasets and often contain valuable information for machine learning models. However, they require special handling to extract meaningful features and represent them in a way that can be effectively used by algorithms. Extracting date components is a common first step in working with time and date features. This involves breaking down a date or timestamp into its constituent parts, such as year, month, day, hour, minute, and second. These components can then be used as separate features in a model. For example, the day of the week or the hour of the day might be relevant for predicting customer traffic or energy consumption. Creating time-based features can capture important temporal patterns in the data. Examples include day of week, hour of day, weekend versus weekday, holiday indicators, and time since a specific event. These features can be particularly useful in applications such as demand forecasting, fraud detection, and predictive maintenance, where the timing of events is crucial. Handling time zones is important when dealing with data collected from different geographical locations. Timestamps should be converted to a common time zone, such as Coordinated Universal Time, UTC, to ensure consistency and avoid ambiguity. It may also be necessary to consider local time zones when creating features, such as the hour of the day, as patterns may vary across different locations. Creating lag features involves using past values of a variable as features to predict future values. For example, in time series forecasting, the value of the target variable at previous time steps, e.g., T1, T2, T3, can be used as features to predict the value at the current time step, T. Lag features can capture autocorrelation and trends in the data. Rolling window features involve computing statistics over a sliding window of past values. Common examples include rolling mean, rolling standard deviation, and rolling maximum/minimum. These features can capture recent trends and patterns in the data and can be particularly useful in time series analysis and forecasting. For example, a 7-day rolling average of sales can capture the weekly trend. Feature engineering for text data, also known as unstructured data, requires specialized techniques for feature engineering to convert it into a numerical format that can be used by machine learning algorithms. This section will discuss common feature engineering techniques for text data. Tokenization is the process of splitting a text document into individual words or tokens. Stemming and lemmatization are techniques for reducing words to their root form. Stemming is a more basic approach that simply removes suffixes, while lemmatization uses a dictionary to map words to their base form, lemma. For example, stemming might reduce running, runs, and ran to run, while lemmatization would map them to run, verb, or ran, past tense of run. The bag of words, BAO, model is a simple but effective way to represent text documents as numerical vectors. In the BAO model, each document is represented as a vector where each element corresponds to the count or frequency of a specific word in the document's vocabulary. The order of words is disregarded. BAO is easy to implement but does not capture the semantic meaning of words or the relationships between them. TF-IDF, term frequency inverse document frequency, is a refinement of the BAO model that takes into account the importance of a word in a document relative to the entire corpus. TF-IDF assigns a weight to each word in a document based on its frequency in the document, term frequency, and its inverse frequency across all documents in the corpus, inverse document frequency. Words that are frequent in a document but rare in the corpus are given higher weights. N-grams are sequences of n consecutive words in a text. Using n-grams as features, instead of individual words, can help to capture some of the local context and word order information. For example, bigrams, n equals 2, capture pairs of adjacent words, while trigrams, n equals 3, capture sequences of 3 adjacent words. N-grams can be combined with BOW or TF-IDF to create more informative text representations. Word embeddings are a powerful technique for representing words as dense vectors in a continuous vector space, where semantically similar words are mapped to nearby vectors. Popular word embedding methods include word2vec, glove, and fast text. Word embeddings can capture semantic relationships between words, such as synonymy and analogy, and can be used as features in various natural language processing tasks. They have been shown to improve the performance of many NLP models compared to using traditional methods like one-hot encoding. Feature engineering for image data, like text data, requires specialized feature engineering techniques to extract meaningful information that can be used by machine learning algorithms. This section will discuss several common approaches for feature engineering with image data. Image augmentation is a technique for artificially increasing the size of an image dataset by creating modified versions of existing images. Common augmentation techniques include rotation, scaling, flipping, shifting, and adding noise. Image augmentation can help to improve the generalization ability of image recognition models and make them more robust to variations in the input data. Extracting features from pre-trained convolutional neural networks, CNNs, is a powerful technique that leverages the knowledge learned by deep learning models trained on large-scale image datasets like ImageNet. The idea is to use a pre-trained CNN as a fixed feature extractor by removing the final classification layer and using the output of the penultimate layer as features for a new task. This approach can be very effective, especially when the available data for the new task is limited. Color histograms are a simple but useful way to represent the distribution of colors in an image. They are computed by dividing the color space into bins and counting the number of pixels that fall into each bin. Color histograms can be used as features for image classification or retrieval, particularly when color is a distinguishing characteristic of the objects of interest. Texture features capture the spatial arrangement of pixel intensities in an image. They can be used to describe the roughness, smoothness, or regularity of an image region. Various techniques can be used to extract texture features, such as Gabor filters, Haralick features, and local binary patterns, LBPs. Texture features can be particularly useful for tasks like material classification and medical image analysis. Edge detection is a fundamental technique in image processing that aims to identify the boundaries between different regions in an image. Edges often correspond to object boundaries or significant changes in intensity. Common edge detection algorithms include the Sobel operator, the Canny edge detector, and the Laplacian of Gaussian, log. Edge information can be used as features for object recognition, image segmentation, and other computer vision tasks. Automated feature engineering is an emerging area that aims to automate the process of creating and selecting features for machine learning models. This can save time and effort compared to manual feature engineering and can potentially discover novel features that might be overlooked by human experts. Feature Tools is a popular Python library for automated feature engineering, particularly for relational datasets. It uses the concept of deep feature synthesis to automatically generate a large number of candidate features by applying mathematical functions across relationships in the data. Feature Tools can handle multiple tables and different types of relationships, making it suitable for a wide range of applications. TS-Fresh is another Python library that specializes in automated feature extraction from time series data. It can automatically generate a large number of features based on various statistical and time series specific characteristics, such as the mean, standard deviation, skewness, kurtosis, and various time domain and frequency domain features. TS-Fresh can be used to extract features for classification, regression, and forecasting tasks involving time series data. Baruta is a feature selection algorithm that uses random forests to iteratively identify all relevant features in a dataset. It works by comparing the importance of the original features to the importance of randomly shuffled, shadow features. Features that are significantly more important than the shadow features are considered relevant. Baruta can be used as a feature selection method on its own or in combination with other feature engineering techniques. Other automated feature engineering libraries and tools include FeatureWiz, categorical encoding, and AutoFeat. Each of these tools has its own strengths and weaknesses, and the choice of which tool to use depends on the specific dataset, problem, and computational resources available. While automated feature engineering can be a powerful tool, it also has limitations. It may not always be able to capture the domain-specific knowledge that is often crucial for effective feature engineering. It can also generate a large number of features, many of which may be irrelevant or redundant, leading to increased computational cost and potential overfitting. Therefore, it is important to use automated feature engineering judiciously and to combine it with careful evaluation and validation. This concludes our exploration of feature engineering in data preprocessing in Lesson 7. We have covered a wide range of techniques, including data cleaning, handling missing values, outlier treatment, feature scaling, encoding categorical variables, and specialized feature engineering methods for text and image data. We have also discussed the emerging field of automated feature engineering. Feature engineering and data preprocessing are crucial steps in the machine learning pipeline that can significantly impact the performance of models. By carefully cleaning, transforming, and engineering features, we can improve the quality of the data, reduce noise, highlight important patterns, and make it easier for algorithms to learn effectively. As you continue your machine learning journey, remember that feature engineering is often an iterative process that requires experimentation, domain knowledge, and creativity. Don't be afraid to try out different techniques, evaluate their impact on model performance, and refine your approach. In the following lessons, we will build upon these foundations and explore more advanced machine learning concepts and techniques. Keep practicing and experimenting with different approaches. Lesson 8. Ensemble Methods and Advanced Techniques. Introduction to Ensemble Learning. In this lesson, we will explore the powerful world of ensemble methods and other advanced techniques in machine learning. Ensemble methods combine the predictions of multiple models to improve overall performance, often achieving higher accuracy and robustness than any single model. We will also discuss advanced techniques such as handling imbalanced datasets, regularization, transfer learning, active learning, and semi-supervised learning, which can significantly enhance the capabilities of machine learning systems. The core idea behind ensemble learning is the wisdom of the crowd concept. Just as a group of diverse individuals can often make better decisions than a single expert, an ensemble of diverse models can often make better predictions than any single model. By combining the strengths of different models and mitigating their individual weaknesses, ensembles can achieve superior performance. Ensemble methods offer several benefits over single models. They can improve predictive accuracy, reduce overfitting, increase robustness to noise and outliers, and handle complex, nonlinear relationships in the data more effectively. Ensembles are often among the top-performing models in machine learning competitions and real-world applications. The bias-variance trade-off, which we discussed in earlier lessons, is also relevant to ensemble methods. Ensemble methods can help to reduce both bias and variance. For example, bagging can reduce variance by averaging out the errors of individual models, while boosting can reduce bias by sequentially focusing on the errors made by previous models. Stacking can improve both bias and variance by learning an optimal combination of the base models. There are several types of ensemble methods, but the most common ones are bagging, boosting, and stacking. Bagging, bootstrap aggregating, involves training multiple models on different subsets of the training data, often using bootstrap sampling. Boosting involves training models sequentially, where each model focuses on correcting the errors made by the previous models. Stacking involves training a meta-model to combine the predictions of multiple base models. Creating diverse ensembles is crucial for achieving good performance. Diversity can be achieved by using different algorithms, different subsets of features, different hyperparameter settings, or different training sets. If the base models are too similar, they will make similar errors, and the ensemble will not offer much improvement over the individual models. Ideally, the base models should be both accurate and diverse, making different kinds of errors that can be compensated for by the ensemble. Bagging, bootstrap aggregating, bagging, which stands for bootstrap aggregating, is an ensemble technique that involves training multiple instances of the same learning algorithm on different subsets of the training data. These subsets are created using a technique called bootstrap sampling. This section will discuss the mechanics of bagging and its most famous implementation. Random forest's bootstrap sampling is a resampling technique that involves randomly sampling the training data with replacement. This means that each subset of the data, called a bootstrap sample, is created by randomly drawing instances from the original training set, and each instance can be selected multiple times. On average, a bootstrap sample will contain about 63.2% of the unique instances from the original training set, with some instances appearing multiple times and others not appearing at all. In bagging, each model in the ensemble is trained on a different bootstrap sample of the training data. This introduces diversity into the ensemble, as each model sees a slightly different version of the training data. The models are trained independently and in parallel. Once the models are trained, their predictions are aggregated to make the final prediction. For regression tasks, the predictions are typically averaged. For classification tasks, the predictions are typically combined using majority voting, where each model's prediction is considered a vote, and the class with the most votes is chosen as the final prediction. Random forests are a highly successful and widely used implementation of bagging that uses decision trees as the base models. In addition to training each tree on a different bootstrap sample, random forests also introduce randomness into the tree building process by randomly selecting a subset of features to consider at each split. This further increases the diversity of the trees and reduces the correlation between their predictions. Out-of-bag error estimation is a technique for estimating the generalization error of a bagged ensemble without the need for a separate validation set. Since each bootstrap sample only contains about 63.2% of the unique instances, the remaining instances, about 36.8%, can be used as a validation set for the model trained on that bootstrap sample. These instances are called out-of-bag instances. The out-of-bag error is the average error on the out-of-bag instances across all models in the ensemble. Boosting is another powerful ensemble technique that, unlike bagging, trains models sequentially rather than in parallel. Each model in the ensemble is trained to correct the errors made by the previous models. This section will discuss some of the most popular boosting algorithms, including AdaBoost, gradient boosting machines, XGBoost, LightGBM, and CatBoost. AdaBoost, adaptive boosting, was one of the first successful boosting algorithms. It works by assigning weights to each training instance and iteratively training a sequence of weak learners, models that are only slightly better than random guessing, on different weighted versions of the training data. After each iteration, the weights of misclassified instances are increased, forcing the next weak learner to focus more on these difficult instances. The final prediction is a weighted combination of the predictions of all the weak learners. Gradient boosting machines, GBM, are a generalization of AdaBoost that can be applied to a wider range of loss functions. Instead of adjusting instance weights, GBM trains each new model to predict the residual errors, the difference between the true target and the prediction of the ensemble so far, of the previous models. This is done by fitting the new model to the negative gradient of the loss function with respect to the ensemble's predictions. GBM can be used with various types of base learners, but decision trees are the most common choice. XGBoost, extreme gradient boosting, is an optimized implementation of gradient boosting that has become extremely popular in machine learning competitions and real-world applications. XGBoost includes several enhancements over the standard GBM algorithm, such as regularization to prevent overfitting, handling of missing values, and efficient computation using parallel and distributed computing. It also uses a more regularized model formalization to control overfitting, which gives it better performance. LightGBM is another gradient boosting framework that uses tree-based learning algorithms. It is designed to be distributed and efficient, with a focus on faster training speed and higher efficiency. LightGBM uses a novel technique called gradient-based one-side sampling, GOS, to reduce the number of data instances and a technique called exclusive feature bundling, EFB, to reduce the number of features. These techniques help to speed up training without sacrificing accuracy. CatBoost is a more recent gradient boosting algorithm that is designed to handle categorical features effectively. It uses a technique called ordered boosting, which is a permutation-driven alternative to the classic boosting algorithm, and an innovative algorithm for processing categorical features. CatBoost has been shown to achieve state-of-the-art results on various tasks and is particularly effective when dealing with datasets that have a large number of categorical features. Stacking, stack generalization, stacking, also known as stack generalization, is an ensemble method that combines the predictions of multiple base models by training a metamodel on these predictions. Unlike bagging and boosting, which typically use the same type of base model, stacking often involves using different types of base models. The basic idea behind stacking is to train several diverse base models on the training data and then use their predictions as input features for a higher-level model, called the metamodel or blender. The base models can be any type of machine learning algorithm, such as decision trees, support vector machines, or neural networks. The metamodel is typically a simpler model, such as linear regression or logistic regression, that learns to combine the predictions of the base models in an optimal way. The training process in stacking usually involves two stages. In the first stage, the base models are trained on the training data, often using cross-validation to generate out-of-fold predictions. These out-of-fold predictions are then used as the input features for training the metamodel in the second stage. Using out-of-fold predictions helps to prevent overfitting and provides a more realistic estimate of the base model's performance on unseen data. Stacking can be extended to multi-level stacking, where multiple layers of models are stacked on top of each other. For example, a two-level stacking model might have several base models in the first level, a second level of models that combine the predictions of the base models, and a final metamodel that combines the predictions of the second-level models. Multi-level stacking can potentially capture more complex relationships in the data but also increases the risk of overfitting and the computational cost. Stacking offers several advantages. It can improve predictive accuracy by leveraging the strengths of different models and learning an optimal way to combine their predictions. It can also reduce the variance and improve the stability of the ensemble. However, stacking also has some disadvantages. It can be computationally expensive, particularly when using complex base models or multi-level stacking. It also requires careful tuning to avoid overfitting, and the choice of base models and metamodel can significantly impact performance. Some best practices for stacking include using a diverse set of base models that make different kinds of errors, using cross-validation to generate the input features for the metamodel, and using a simple, regularized metamodel to prevent overfitting. It's also important to ensure that the base models are well tuned before using them in the stacking ensemble. Ensemble methods for unsupervised learning. While ensemble methods are most commonly used in supervised learning, they can also be applied to unsupervised learning tasks, such as clustering and anomaly detection. This section will discuss how ensemble techniques can be adapted for unsupervised learning. Ensemble clustering is an approach that combines the results of multiple clustering algorithms or multiple runs of the same algorithm with different initializations or parameters. The goal is to obtain a more robust and stable clustering solution than can be achieved by any single clustering algorithm. Ensemble clustering methods can be based on various techniques, such as voting, co-occurrence matrix, or graph-based methods. Consensus clustering is a specific type of ensemble clustering where the goal is to find a single consensus partition that best summarizes the clusterings produced by the individual ensemble members. This can be formulated as an optimization problem, where the objective is to find a partition that maximizes the agreement with the individual clusterings, subject to certain constraints. Various algorithms have been proposed for consensus clustering, including methods based on median partitions, consensus trees, and graph partitioning. Feature-weighted ensembles are another approach to ensemble clustering. In this approach, different clustering algorithms are applied to different subsets of features or different representations of the data. This can be particularly useful when dealing with high-dimensional data, where different features or subsets of features may reveal different aspects of the underlying structure. The results of the individual clusterings are then combined, often using a consensus clustering method. Ensemble methods can also be applied to anomaly detection. For example, one can train multiple anomaly detection models on different subsets of the data or using different algorithms and then combine their predictions using techniques like averaging or voting. This can improve the robustness and accuracy of anomaly detection, particularly when dealing with complex, high-dimensional data. Ensemble methods can also be used to combine the results of different anomaly detection algorithms, each of which may be sensitive to different types of anomalies. Combining different clustering algorithms or different anomaly detection algorithms in an ensemble can offer several benefits. It can improve the robustness and stability of the results, reduce the sensitivity to the choice of algorithm or parameters, and potentially uncover structures that might be missed by any single algorithm. However, ensemble methods for unsupervised learning also face challenges, such as the difficulty of evaluating the quality of the results and the computational cost of running multiple algorithms. Handling imbalanced datasets, where one or more classes have significantly fewer instances than other classes, are a common challenge in machine learning. This section will discuss techniques for addressing class imbalance and improving model performance on minority classes. Oversampling techniques aim to balance the class distribution by increasing the number of instances in the minority class. One popular oversampling technique is SMOTE, synthetic minority oversampling technique. SMOTE creates synthetic samples for the minority class by interpolating between existing minority class instances. Specifically, for each minority instance, it finds its k-nearest neighbors in the minority class, randomly selects one of them, and creates a new synthetic instance along the line segment joining the minority instance and its selected neighbor. Undersampling techniques, on the other hand, aim to balance the class distribution by decreasing the number of instances in the majority class. Random undersampling randomly removes instances from the majority class until a desired class distribution is achieved. More sophisticated undersampling techniques try to remove redundant or less informative instances from the majority class, such as Tomek links or near-miss. Cost-sensitive learning is another approach to dealing with class imbalance. It involves assigning different misclassification costs to different classes during training. For example, in a medical diagnosis task, the cost of misclassifying a patient with a disease as healthy, false negative, might be higher than the cost of misclassifying a healthy patient as having the disease, false positive. Cost-sensitive learning can be incorporated into various algorithms by modifying the loss function or the decision threshold. Ensemble methods can also be effective for imbalanced data. For example, easy ensemble and balance cascade are methods that train an ensemble of classifiers on different balanced subsets of the data, obtained by undersampling the majority class. The final prediction is made by combining the predictions of all the classifiers in the ensemble. These methods can improve the performance on the minority class without sacrificing the performance on the majority class. Choosing the right approach for addressing class imbalance depends on the specific problem, the dataset, and the algorithm being used. It is often useful to experiment with different techniques and compare their performance using appropriate evaluation metrics, such as precision, recall, F1 score, or AUC, which are more informative than accuracy when dealing with imbalanced data. It's also important to consider the interpretability of the results and the potential consequences of different types of errors. Advanced regularization techniques. Regularization is a crucial technique for preventing overfitting and improving the generalization ability of machine learning models. While we have already discussed basic regularization techniques like L1 and L2 regularization, this section will explore more advanced regularization techniques, including dropout, drop connect, and early stopping. Dropout is a powerful regularization technique that was originally proposed for neural networks but can also be applied to other types of models. During training, dropout randomly sets a fraction of the neurons in a layer to 0 at each update. This prevents the network from relying too heavily on any single neuron and forces it to learn more robust features. Dropout can be seen as a form of model averaging, where an ensemble of different networks, with different subsets of neurons dropped out, is trained simultaneously. Drop connect is a generalization of dropout where, instead of dropping out entire neurons, individual weights, connections, are randomly set to 0 during training. This can be seen as a more fine-grained form of regularization, as it introduces noise at the level of individual connections rather than entire neurons. Drop connect can be applied to any type of neural network layer, including fully connected layers and convolutional layers. Early stopping is a simple but effective technique for preventing overfitting, particularly when training models using iterative optimization algorithms like gradient descent. Early stopping involves monitoring the model's performance on a validation set during training and stopping the training process when the performance stops improving or starts to degrade. This prevents the model from overfitting to the training data and helps to find a good balance between bias and variance. L1 and L2 regularization, which we discussed in earlier lessons, can also be considered advanced regularization techniques. L1 regularization, lasso, adds a penalty term to the loss function that is proportional to the sum of the absolute values of the model's weights. This encourages sparsity in the model, effectively performing feature selection by driving some weights to 0. L2 regularization, ridge, adds a penalty term that is proportional to the sum of the squares of the model's weights. This encourages small weights and can improve the model's generalization ability. Elastic net is a regularization technique that combines both L1 and L2 regularization. It adds a penalty term that is a linear combination of the L1 and L2 penalties. Elastic net can provide a good balance between the feature selection properties of L1 regularization and the stability of L2 regularization. It has two hyperparameters that control the strength of the L1 and L2 penalties, which can be tuned using cross-validation. Transfer learning is a powerful technique that leverages knowledge gained from one task or domain to improve learning performance on a different but related task or domain. Instead of training a model from scratch, transfer learning uses a pre-trained model as a starting point. This section will discuss the concepts, benefits, and limitations of transfer learning. Using pre-trained models is the most common approach to transfer learning. A model that has been trained on a large dataset for a specific task, such as image classification or natural language processing, can be used as a starting point for a new, related task. The pre-trained model has already learned useful features from the large dataset, which can be transferred to the new task. This can significantly reduce the amount of data and training time required to achieve good performance on the new task. Fine-tuning pre-trained models is a common way to adapt a pre-trained model to a new task. The idea is to replace the final layers of the pre-trained model with new layers that are appropriate for the new task and then train the entire model on the new dataset, typically with a smaller learning rate. This allows the model to adapt the pre-trained features to the new task while preserving the knowledge gained from the original task. Domain adaptation is a specific type of transfer learning where the goal is to adapt a model trained on a source domain to perform well on a different but related target domain. This can be useful when there is a large amount of labeled data available for the source domain but limited or no labeled data for the target domain. Domain adaptation techniques aim to reduce the discrepancy between the source and target domains, allowing the model to generalize better to the target domain. Transfer learning has found numerous applications, particularly in computer vision and natural language processing. In computer vision, models pre-trained on large image datasets like ImageNet can be fine-tuned for various tasks, such as object detection, image segmentation, and medical image analysis. In natural language processing, pre-trained language models like BERT and GPT can be fine-tuned for tasks like text classification, question answering, and machine translation. Transfer learning offers several benefits. It can significantly reduce the amount of data and training time required to achieve good performance on a new task. It can also improve the generalization ability of models, especially when the new task has limited labeled data. Furthermore, transfer learning can help to mitigate the problem of overfitting, as the pre-trained model has already learned robust features from a large dataset. However, transfer learning also has some limitations. The effectiveness of transfer learning depends on the similarity between the source task and the target task. If the tasks are too different, the pre-trained model may not provide much benefit or could even hurt performance. Fine-tuning can also be challenging, as it requires careful selection of the learning rate and other hyperparameters. There is also a risk of negative transfer, where the knowledge from the source task interferes with learning the target task. Active learning is a special case of semi-supervised machine learning in which a learning algorithm is able to interactively query the user, or some other information source, to obtain the desired outputs at new data points. This section will discuss the principles of active learning and its applications. The core idea behind active learning is that a machine learning algorithm can achieve greater accuracy with fewer training labels if it is allowed to choose the data from which it learns. An active learner may pose queries, usually in the form of unlabeled data instances to be labeled by an oracle, e.g., a human annotator. Active learning is well motivated in many modern machine learning problems, where unlabeled data may be abundant or easily obtained, but labels are difficult, time-consuming, or expensive to obtain. There are several different strategies for how an active learner can choose which instances to query. Uncertainty sampling is one of the simplest and most commonly used query strategies. In this approach, an active learner queries the instances about which it is least certain how to label. Query by committee is another approach, which involves maintaining a committee of models trained on the current labeled set, and querying the instances where the committee members disagree the most. Expected model change is a more general active learning framework. The idea is to query the instance that would lead to the greatest change in the current model if we knew its label. This approach can be computationally expensive, as it requires retraining the model for each potential query. However, approximations and heuristics can be used to make it more practical. Active learning has numerous applications, particularly in situations where labeled data is scarce or expensive to obtain. In data labeling and annotation, active learning can be used to select the most informative instances to be labeled by human annotators, reducing the overall labeling effort. In scientific research, active learning can guide experiments by suggesting the most informative data points to collect next. It can also be used in medical diagnosis, fraud detection, and other domains where obtaining labels is costly or time-consuming. Semi-supervised learning is a class of machine learning techniques that makes use of both labeled and unlabeled data for training, typically a small amount of labeled data with a large amount of unlabeled data. This section will discuss the principles of semi-supervised learning and explore some common approaches. Semi-supervised learning falls between unsupervised learning, with no labeled training data, and supervised learning, with completely labeled training data. Many real-world machine learning problems fall into this category because it can be expensive or time-consuming to obtain labeled data, while unlabeled data is often abundant and cheap. The goal of semi-supervised learning is to leverage the large amount of unlabeled data to improve the performance of a model trained primarily on a small amount of labeled data. Self-training is one of the simplest semi-supervised learning methods. It starts by training a model on the small amount of labeled data. This model is then used to make predictions on the unlabeled data. The most confident predictions are added to the labeled set, and the model is retrained. This process is repeated iteratively. Self-training can be effective but is sensitive to errors made by the initial model. Co-training is another semi-supervised learning method that assumes that the features can be split into two sufficient and redundant sets. Two separate models are trained on each set of features, and then each model's confident predictions on unlabeled data are used to augment the other model's training set. Co-training can be effective when the two feature sets provide complementary information about the data. Multi-view learning is a generalization of co-training where more than two feature sets or views of the data are available. Multiple models are trained on different views, and their predictions are combined or used to augment each other's training sets. Multi-view learning can be particularly useful when the different views provide independent and complementary information about the data. Graph-based methods are a class of semi-supervised learning algorithms that represent the data as a graph, where nodes represent data instances, both labeled and unlabeled, and edges represent similarities between instances. These methods propagate labels from labeled nodes to unlabeled nodes through the graph structure. Graph-based methods can be effective when the data has an underlying graph structure or when similarity relationships between data points can be reliably estimated. Semi-supervised learning can be a powerful approach when labeled data is scarce and unlabeled data is abundant. However, it also comes with challenges. The unlabeled data may not always be representative of the same distribution as the labeled data, and errors made early in the learning process can propagate and be amplified. Despite these challenges, semi-supervised learning remains an active area of research and has shown promise in various applications, including natural language processing, computer vision, and bioinformatics. This concludes our exploration of ensemble methods and advanced techniques in Lesson 8. We have covered a wide range of topics, including bagging, boosting, and stacking for ensemble learning, techniques for handling imbalanced datasets, advanced regularization methods, and approaches for leveraging unlabeled data through transfer learning, active learning, and semi-supervised learning. These techniques represent powerful tools in the machine learning practitioner's toolkit, enabling the development of more accurate, robust, and efficient models. By understanding and applying these methods, you are well equipped to tackle complex real-world machine learning problems and further advance your expertise in the field. Keep experimenting with these techniques. Lesson 9: The Ethical and Societal Implications of Machine Learning. Introduction to ethical considerations in machine learning. As machine learning becomes increasingly integrated into various aspects of our lives, it is crucial to consider the ethical and societal implications of this powerful technology. This lesson will explore the ethical challenges associated with machine learning, discuss the potential harms and risks, and examine frameworks and guidelines for responsible development and deployment of machine learning systems. The importance of ethical considerations in machine learning stems from the profound impact that these systems can have on individuals and society. Machine learning algorithms are being used to make decisions that affect people's lives, such as loan applications, hiring processes, and even criminal justice. It is therefore essential to ensure that these systems are developed and used in a responsible and ethical manner. Failing to do so can lead to unfair or discriminatory outcomes, privacy violations, and other harms. The potential harms of machine learning are numerous and varied. Biased algorithms can perpetuate and amplify existing societal biases, leading to discriminatory outcomes. Lack of transparency and interpretability can make it difficult to understand why a model made a particular decision, hindering accountability. Privacy breaches can expose sensitive personal information. The automation of tasks can lead to job displacement and exacerbate economic inequality. Furthermore, malicious actors can exploit vulnerabilities in machine learning systems to cause harm. Various ethical frameworks and guidelines have been proposed to guide the development and deployment of machine learning systems. These frameworks often emphasize principles such as fairness, transparency, accountability, privacy, and human oversight. For example, the European Union's General Data Protection Regulation, GDPR, includes provisions related to automated decision-making and profiling, aiming to protect individuals' rights and freedoms in the context of machine learning. The stakeholders in machine learning ethics are diverse and include researchers, developers, policymakers, regulators, businesses, civil society organizations, and the general public. Each stakeholder group has a role to play in ensuring that machine learning is developed and used ethically. Machine learning practitioners, in particular, have a responsibility to be aware of the ethical implications of their work and to strive to build systems that are fair, transparent, and beneficial to society. They have a large amount of influence. Bias and fairness in machine learning. Bias in machine learning refers to situations where a model systematically makes errors or predictions that are skewed in a particular direction, often reflecting underlying biases in the data or the development process. Fairness, on the other hand, is a broader concept that relates to the equitable treatment of different individuals or groups by a machine learning system. Sources of bias in machine learning are varied and can be introduced at different stages of the machine learning pipeline. Historical bias occurs when the training data reflects existing societal biases, such as gender or racial discrimination. Representation bias arises when the training data does not adequately represent the diversity of the population to which the model will be applied. Measurement bias occurs when the way data is collected or measured is systematically different for different groups. Types of bias that can manifest in machine learning systems include, but are not limited to, gender bias, racial bias, age bias, and socioeconomic bias. For example, a facial recognition system that is primarily trained on images of white faces may perform poorly on individuals with darker skin tones, leading to biased outcomes. Similarly, a hiring algorithm trained on historical data that reflects past hiring discrimination may perpetuate those biases in its recommendations. Fairness definitions and metrics have been developed to quantify and assess fairness in machine learning. These include concepts such as demographic parity, equal outcomes across groups, equal opportunity, equal true positive rates across groups, and equalized odds, equal true positive and false positive rates across groups. However, different fairness definitions can conflict with each other, and choosing the appropriate definition depends on the specific context and application. There are often trade-offs. Techniques for mitigating bias in machine learning include careful data collection and pre-processing, using fairness-aware algorithms, and post-processing model outputs to adjust for bias. It is also important to ensure diversity and inclusion in the teams developing and deploying machine learning systems. However, mitigating bias is an ongoing challenge that requires continuous monitoring and evaluation. Trade-offs between fairness and accuracy often arise in machine learning. In some cases, improving fairness may come at the cost of reduced accuracy, and vice versa. For example, enforcing strict demographic parity might lead to lower overall accuracy if the underlying distributions of the target variable differ across groups. Navigating these trade-offs requires careful consideration of the specific context, the potential harms of bias, and the values and priorities of the stakeholders involved. Transparency, interpretability, and explainability. As machine learning models become increasingly complex, particularly with the rise of deep learning, the need for transparency, interpretability, and explainability has grown. This section will discuss the importance of these concepts and explore techniques for making machine learning models more understandable. The black box problem refers to the difficulty in understanding the inner workings of complex machine learning models, such as deep neural networks. These models often have millions or even billions of parameters, and their decision-making processes can be opaque and difficult to interpret. This lack of transparency can make it challenging to identify and correct errors or biases, and it can also erode trust in the system, especially in high-stakes applications. The importance of transparency and interpretability stems from several factors. First, interpretability can help to build trust in machine learning systems, particularly in domains where decisions have significant consequences, such as healthcare and finance. Second, interpretability can aid in debugging and improving models by allowing developers to understand the model's strengths and weaknesses. Third, interpretability can provide insights into the underlying data and the problem being solved, potentially leading to new discoveries. Techniques for interpreting models include methods for assessing feature importance, visualizing decision boundaries, and generating explanations for individual predictions. Feature importance measures the relative contribution of each input feature to the model's predictions. Partial dependence plots visualize the relationship between a feature and the target variable, holding other features constant. These techniques can help to understand which features are most influential in the model's decision-making process. Explainable AI, XAI, is a rapidly growing field that aims to develop methods for explaining the decisions of complex machine learning models in a human-understandable way. LIME, Local Interpretable Model Agnostic Explanations, is a popular XAI technique that explains individual predictions by approximating the complex model locally with an interpretable model, such as a linear model or decision tree. SHAP, Shapley Additive Explanations, is another powerful XAI method based on game theory that provides a unified and consistent way to attribute the contribution of each feature to a specific prediction. Trade-offs between interpretability and performance often exist in machine learning. Simpler models, such as linear models and decision trees, are generally more interpretable but may have lower predictive accuracy compared to more complex models, such as deep neural networks. Choosing the right balance between interpretability and performance depends on the specific application and the importance of understanding the model's decision-making process. Accountability and responsibility in machine learning. As machine learning systems are increasingly used to make decisions that impact people's lives, it is crucial to establish clear lines of accountability and responsibility. This section will discuss the challenges in assigning accountability for algorithmic decisions and explore the role of regulation, oversight, and responsible AI practices. Establishing accountability for algorithmic decisions can be challenging due to the complexity of machine learning systems and the distributed nature of their development and deployment. It can be difficult to pinpoint the exact cause of an error or a harmful outcome, especially when multiple actors are involved, such as data providers, model developers, and end users. Furthermore, the autonomous nature of some machine learning systems can blur the lines of responsibility. The question of liability for harms caused by machine learning systems is a complex and evolving area. Existing legal frameworks may not be well equipped to deal with the unique challenges posed by AI and machine learning. Determining who is at fault when a self-driving car causes an accident or when an algorithm makes a discriminatory decision is a non-trivial task. New legal and regulatory approaches may be needed to address these challenges. The role of regulation and oversight in ensuring the responsible development and use of machine learning is a topic of ongoing debate. Some argue that government regulation is necessary to prevent harms, protect individual rights, and ensure that machine learning systems are used for the benefit of society. Others caution against overly restrictive regulations that could stifle innovation. Finding the right balance between promoting innovation and protecting the public interest is a key challenge for policymakers. Auditing machine learning systems is an important mechanism for ensuring accountability and identifying potential problems. This can involve both internal audits conducted by the developers or deployers of the system and external audits conducted by independent third parties. Audits can assess various aspects of a system, including its accuracy, fairness, transparency, and robustness to errors or adversarial attacks. They can also examine the data used to train the system and the processes used for development and deployment. Building responsible AI systems requires a multifaceted approach that goes beyond technical solutions. It involves considering ethical principles throughout the entire lifecycle of a machine learning system, from problem definition and data collection to model development, deployment, and monitoring. It also requires engaging with stakeholders and affected communities, fostering interdisciplinary collaboration, and promoting a culture of responsibility among machine learning practitioners. Privacy and security in machine learning systems often rely on vast amounts of data, which may include sensitive personal information. This raises significant concerns about privacy and security. This section will discuss the privacy risks associated with machine learning, explore techniques for protecting privacy, and examine security threats to machine learning models. Privacy risks associated with machine learning include the potential for re-identification of individuals from anonymized data, the inference of sensitive attributes from seemingly innocuous data, and the possibility of membership inference attacks, where an adversary tries to determine whether a specific individual's data was used to train a model. These risks are particularly acute in domains such as healthcare, finance, and social media, where the data used to train machine learning models can be highly sensitive. Data anonymization and de-identification techniques aim to remove or obscure personally identifiable information, PI, from datasets. However, it has been shown that anonymized data can often be re-identified by linking it with other publicly available data sources. Therefore, anonymization alone may not be sufficient to guarantee privacy, especially when dealing with high-dimensional data. Differential privacy is a rigorous mathematical framework for quantifying and limiting the privacy risks associated with statistical and machine learning analyses. It provides a formal guarantee that the output of an analysis will not reveal too much information about any individual data point in the input. Differential privacy is typically achieved by adding carefully calibrated noise to the data or the model's outputs. Federated learning is a privacy-preserving machine learning technique that allows multiple parties to collaboratively train a model without sharing their raw data. Instead of centralizing the data in one location, the data remains distributed across the participating parties' devices or servers. The model is trained iteratively by sending model updates between the central server and the local devices, without the raw data ever leaving the devices. This approach can help to mitigate privacy risks while still enabling the training of accurate models on large, decentralized datasets. Security threats to machine learning models include adversarial attacks, where malicious actors intentionally manipulate inputs to cause the model to make incorrect predictions. Adversarial examples can be crafted by adding small, carefully designed perturbations to inputs that are imperceptible to humans but cause the model to misclassify them. Protecting against such attacks is an active area of research and requires developing more robust and secure machine learning models. The impact of machine learning on employment and the workforce. The increasing automation capabilities of machine learning have raised concerns about its potential impact on employment and the workforce. While machine learning can create new job opportunities and enhance productivity, it may also lead to job displacement in certain sectors. This section will discuss the complex relationship between machine learning and employment. Automation and job displacement are significant concerns associated with the rise of machine learning and AI. Tasks that are routine, repetitive, and require limited cognitive skills are particularly susceptible to automation. This includes jobs in manufacturing, transportation, logistics, and some white-collar jobs like data entry and basic customer service. The displacement of workers in these sectors could have significant economic and social consequences. The changing nature of work is another important consideration. As machine learning systems take over routine tasks, the demand for workers with skills that complement these systems is likely to increase. This includes skills such as critical thinking, creativity, problem-solving, emotional intelligence, and complex communication. Jobs that require uniquely human skills, such as those involving social interaction, empathy, and adaptability, are less likely to be fully automated in the near future. The rise of machine learning is also creating opportunities for new job creation. This includes jobs directly related to the development, deployment, and maintenance of machine learning systems, such as machine learning engineers, data scientists, and AI ethicists. It also includes new roles that involve working alongside AI systems, leveraging their capabilities to enhance human productivity and decision-making. Entirely new industries and business models may emerge as a result of advances in machine learning. The need for reskilling and upskilling the workforce is becoming increasingly apparent. As the demand for certain skills declines and the demand for others grows, workers will need to adapt to the changing job market. This requires investing in education and training programs that equip workers with the skills needed to thrive in an AI-powered economy. Lifelong learning will become increasingly important as the pace of technological change continues to accelerate. Policy responses to workforce transitions are crucial for ensuring a smooth and equitable transition to an economy increasingly influenced by machine learning. These responses may include investing in education and training, providing social safety nets for displaced workers, promoting job creation in new sectors, and exploring new models of work and income distribution, such as universal basic income. Addressing the societal impact of automation requires a multifaceted approach involving governments, businesses, and individuals. Machine learning and social justice. Machine learning systems can have a profound impact on social justice issues, both positive and negative. This section will explore how machine learning can exacerbate existing inequalities, as well as its potential to promote social good. Algorithmic discrimination is a major concern in the context of social justice. Machine learning models trained on biased data can perpetuate and even amplify existing societal biases, leading to discriminatory outcomes in areas such as hiring, lending, and criminal justice. For example, a recidivism prediction algorithm trained on historical data that reflects racial biases in the criminal justice system may unfairly predict higher recidivism rates for certain racial groups. Machine learning can reinforce existing inequalities by automating and scaling up biased decision-making processes. If not carefully designed and monitored, machine learning systems can exacerbate disparities in access to opportunities, resources, and services. For example, an algorithm used to allocate educational resources might inadvertently disadvantage students from low-income backgrounds if it relies on features that are correlated with socioeconomic status. However, machine learning also has the potential to be a powerful tool for promoting social good. It can be used to identify and address societal challenges, improve the efficiency and fairness of public services, and empower marginalized communities. For example, machine learning can be used to analyze satellite imagery to identify areas at risk of natural disasters, to optimize the allocation of resources in public health, or to detect and combat online hate speech. Several case studies highlight the ethical challenges that can arise in real-world applications of machine learning. For instance, the use of facial recognition technology by law enforcement has raised concerns about racial bias and the potential for mass surveillance. The use of predictive policing algorithms has been criticized for perpetuating discriminatory practices by targeting certain neighborhoods or demographic groups. These examples underscore the need for careful consideration of the social justice implications of machine learning. Addressing power imbalances in machine learning is crucial for ensuring that the technology is used for the benefit of all. This involves promoting diversity and inclusion in the development and deployment of machine learning systems, engaging with affected communities, and ensuring that the benefits and risks of machine learning are distributed equitably. It also requires addressing the concentration of power in the hands of a few large technology companies that control much of the data and infrastructure for machine learning. Ethical considerations in specific domains. The ethical implications of machine learning can vary significantly depending on the specific domain of application. This section will explore some of the unique ethical challenges that arise in specific domains, including healthcare, criminal justice, finance, education, and autonomous vehicles. In healthcare, machine learning has the potential to revolutionize diagnosis, treatment, and patient care. However, it also raises ethical concerns related to patient data privacy, the potential for algorithmic bias in diagnosis and treatment recommendations, and the need for transparency and explainability in medical decision-making. Ensuring that machine learning systems are used responsibly in healthcare requires careful consideration of these ethical challenges, as well as robust regulatory frameworks. In the criminal justice system, machine learning is increasingly being used for tasks such as predictive policing, risk assessment, and sentencing decisions. However, the use of algorithms in this domain raises significant concerns about fairness, due process, and the potential for exacerbating existing biases in the criminal justice system. For example, risk assessment tools have been criticized for disproportionately predicting higher recidivism rates for certain racial groups, potentially leading to harsher sentences. In finance, machine learning is used for tasks such as credit scoring, algorithmic trading, and fraud detection. Ethical concerns in this domain include the potential for algorithmic bias in lending decisions, which could perpetuate discriminatory practices, as well as the need for transparency and accountability in algorithmic trading. The use of machine learning in finance also raises questions about the stability and fairness of financial markets. In education, machine learning is being used to develop personalized learning systems, automate grading, and monitor student performance. Ethical considerations in this domain include concerns about student privacy, the potential for algorithmic bias to affect educational opportunities, and the impact of automation on the role of teachers. It is crucial to ensure that machine learning systems are used to enhance, rather than replace, human judgment and interaction in education. Autonomous vehicles represent a particularly challenging domain for ethical considerations in machine learning. Self-driving cars must be programmed to make decisions in complex and unpredictable situations, including accident scenarios where harm may be unavoidable. This raises difficult ethical dilemmas, such as how to program a vehicle to choose between different potential harms, the trolley problem. Ensuring the safety and ethical behavior of autonomous vehicles requires addressing these dilemmas and developing robust ethical guidelines for their design and deployment. Developing and deploying ethical machine learning systems. Building ethical machine learning systems requires a proactive and holistic approach that goes beyond technical solutions. This section will discuss principles and practices for developing and deploying machine learning systems in a responsible and ethical manner. Ethical principles for machine learning provide a foundation for guiding the development and deployment of these systems. While specific principles may vary, common themes include fairness, transparency, accountability, privacy, and human oversight. Fairness requires that machine learning systems treat all individuals and groups equitably, avoiding discriminatory outcomes. Transparency involves making the decision-making process of algorithms understandable and explainable. Accountability entails establishing clear lines of responsibility for the actions of machine learning systems. Privacy involves protecting individuals' personal information and ensuring that data is used responsibly. Human oversight emphasizes the importance of maintaining human control and judgment in the development and use of machine learning systems. Building interdisciplinary teams is crucial for addressing the complex ethical challenges of machine learning. Teams should include not only machine learning experts but also ethicists, social scientists, legal experts, and domain experts. This diversity of perspectives can help to identify potential ethical issues early on, develop more robust solutions, and ensure that the system aligns with societal values and expectations. Interdisciplinary collaboration can also foster a more holistic understanding of the potential impacts of machine learning systems. Engaging with stakeholders and affected communities is essential for developing and deploying ethical machine learning systems. This involves actively seeking input from those who will be affected by the system, understanding their concerns and needs, and incorporating their feedback into the design and development process. Engaging with stakeholders can help to build trust, identify potential risks and harms, and ensure that the system is aligned with societal values. It can also help to create a sense of ownership and shared responsibility for the ethical implications of the technology. Continuous monitoring and evaluation are necessary to ensure that machine learning systems remain ethical and effective over time. This involves regularly assessing the system's performance, identifying any unintended consequences or biases that may emerge, and making adjustments as needed. Monitoring should include not only technical metrics but also social and ethical considerations. It should involve ongoing dialogue with stakeholders and a commitment to continuous improvement. The role of professional codes of conduct is becoming increasingly important in the field of machine learning. Several organizations have developed ethical guidelines and codes of conduct for AI and machine learning practitioners. These codes can provide guidance on issues such as fairness, transparency, privacy, and accountability. They can also help to establish professional norms and promote a culture of ethical responsibility among machine learning practitioners. Adherence to such codes can help to build public trust in the technology. The future of machine learning ethics. The field of machine learning ethics is rapidly evolving as the technology advances and its applications become more widespread. This section will explore some of the emerging ethical challenges and discuss the need for ongoing research, dialogue, and education. Emerging ethical challenges include the development of increasingly autonomous systems, such as self-driving cars and autonomous weapons systems, which raise questions about decision-making authority, responsibility, and control. The use of deepfakes and other synthetic media technologies poses new challenges for trust, authenticity, and the spread of misinformation. The increasing use of machine learning in areas such as predictive policing, surveillance, and social control raises concerns about civil liberties, privacy, and the potential for abuse of power. The need for ongoing research and dialogue is crucial for addressing the complex ethical challenges of machine learning. This includes research on technical solutions, such as methods for mitigating bias and improving transparency, as well as research on the social, legal, and policy implications of machine learning. It also requires ongoing dialogue among researchers, developers, policymakers, ethicists, and the public to ensure that machine learning is developed and used in a way that aligns with societal values and promotes human well-being. The role of education and public awareness is becoming increasingly important as machine learning becomes more integrated into our lives. Educating both machine learning practitioners and the general public about the ethical implications of the technology is essential for fostering responsible innovation and informed public discourse. This includes promoting ethical literacy among machine learning developers, as well as raising public awareness about the capabilities and limitations of machine learning systems. International cooperation and governance will be necessary to address the global implications of machine learning. This includes developing international standards and norms for the ethical development and use of machine learning, as well as mechanisms for cross-border collaboration and enforcement. Given the rapid pace of technological change, developing effective governance frameworks for machine learning is a significant challenge that requires ongoing attention and adaptation. Building a more ethical and equitable future with machine learning requires a collective effort from all stakeholders. By prioritizing ethical considerations throughout the entire lifecycle of machine learning systems, from design and development to deployment and monitoring, we can harness the transformative potential of this technology while mitigating its risks. By fostering a culture of responsibility, transparency, and inclusivity, we can work towards a future where machine learning benefits all of humanity. This concludes our exploration of the ethical and societal implications of machine learning in Lesson 9. We have examined a wide range of ethical challenges, including bias and fairness, transparency and interpretability, accountability and responsibility, privacy and security, and the impact of machine learning on employment, social justice, and specific domains such as healthcare, criminal justice, finance, education, and autonomous vehicles. It is clear that the development and deployment of machine learning systems raise complex ethical questions that require careful consideration. By embracing ethical principles, engaging with stakeholders, and fostering interdisciplinary collaboration, we can work towards building machine learning systems that are not only technically sophisticated but also socially responsible and beneficial. As you continue your machine learning journey, I encourage you to keep these ethical considerations in mind and to actively contribute to the development of a more ethical and equitable future with machine learning. The choices we make today will shape the impact of this powerful technology for generations to come. Let's strive to make those choices wisely and responsibly. Lesson 10: Building and Deploying Machine Learning Models. Introduction to the Machine Learning Project Lifecycle. In this lesson, we will explore the practical aspects of building and deploying machine learning models. While previous lessons have focused on the theoretical foundations and algorithmic details, this lesson will guide you through the end-to-end process of a typical machine learning project, from defining the problem to deploying and monitoring the model. The machine learning project lifecycle is an iterative process that encompasses several key stages. It typically begins with defining the problem and setting clear objectives. This involves understanding the business or research question that needs to be addressed and translating it into a well-defined machine learning task. The next stage is data collection and preparation, where relevant data is gathered, cleaned, and transformed into a suitable format for modeling. Model selection and training is the stage where an appropriate machine learning algorithm is chosen based on the problem and data characteristics. The model is then trained using the prepared data, and its hyperparameters are tuned to optimize performance. Model evaluation and tuning involve assessing the model's performance using appropriate metrics and techniques like cross-validation. This stage often involves iterating on the previous stages, such as revisiting feature engineering or trying different algorithms. Once a satisfactory model is developed, it enters the deployment stage. Deployment involves making the model available for use in a real-world setting, such as integrating it into an application or deploying it as a web service. Finally, monitoring and maintenance are crucial for ensuring that the deployed model continues to perform well over time and adapting to changes in the data or the environment. It is important to remember that the machine learning project lifecycle is not strictly linear but rather an iterative process. Insights gained at one stage may necessitate revisiting and revising previous stages. For example, model evaluation might reveal the need for additional feature engineering or a different model selection. Flexibility and the willingness to iterate are key to successful machine learning projects. Data collection and preparation. The quality and relevance of the data are paramount to the success of any machine learning project. This section will discuss the crucial steps of data collection and preparation. Identifying data sources is the first step in the data collection process. Data can come from various sources, including internal databases, APIs, web scraping, sensor data, and publicly available datasets. The choice of data sources depends on the specific problem being addressed and the availability and accessibility of relevant data. It's important to consider the ethical implications of data collection and to ensure compliance with privacy regulations. Data quality assessment is essential for ensuring that the data is reliable and suitable for the intended purpose. This involves checking for missing values, inconsistencies, errors, and outliers. Understanding the data distribution, identifying potential biases, and assessing the representativeness of the data are also crucial steps. Data quality issues can significantly impact the performance and reliability of machine learning models. Data cleaning and preprocessing are necessary steps to address data quality issues and to transform the raw data into a format that is suitable for modeling. This may involve handling missing values through imputation or removal, dealing with outliers, and transforming variables. Data cleaning also involves ensuring consistency in data formats, units, and scales. Feature engineering and selection, as discussed in Lesson 7, are critical components of data preparation. Feature engineering involves creating new features from existing ones to improve model performance. Feature selection involves choosing a subset of the most relevant features to reduce dimensionality, improve model interpretability, and prevent overfitting. Effective feature engineering and selection can often have a greater impact on model performance than the choice of algorithm itself. Data splitting is the process of dividing the available data into different sets for training, validation, and testing. The training set is used to train the model, the validation set is used for hyperparameter tuning and model selection, and the test set is used for a final, unbiased evaluation of the model's performance. Proper data splitting is crucial for obtaining reliable estimates of a model's generalization ability. Model selection and training. Once the data is prepared, the next step is to select an appropriate machine learning algorithm and train a model. This section will discuss the process of model selection and training, including hyperparameter settings, cross-validation, and avoiding overfitting and underfitting. Choosing the right algorithm depends on several factors, including the type of problem, classification, regression, clustering, etc. The nature of the data, e.g., size, dimensionality, linearity, the desired interpretability of the model, and the computational resources available. It is often beneficial to start with simpler models and gradually increase complexity if needed. Experimenting with different algorithms and comparing their performance using cross-validation is a common practice. Setting hyperparameters is an important part of the model training process. Hyperparameters are parameters that are not learned from the data but are set prior to training. They control the behavior of the learning algorithm and can significantly impact model performance. Examples of hyperparameters include the learning rate in gradient descent, the number of trees in a random forest, and the regularization strength in linear models. Training the model on the training data involves feeding the prepared data to the chosen algorithm and allowing it to learn the underlying patterns and relationships. The specific training process depends on the algorithm being used. For example, in linear regression, training involves finding the coefficients that minimize the sum of squared errors. In decision trees, training involves recursively partitioning the data based on feature values to create a tree structure. Cross-validation, as discussed in Lesson 6, is a crucial technique for model selection and hyperparameter tuning. It provides a more robust estimate of a model's generalization performance than a single train test split by using multiple train test splits and averaging the results. K-fold cross-validation is commonly used to compare different models or different hyperparameter settings and to select the best-performing model. Avoiding overfitting and underfitting is a key consideration during model training. Overfitting occurs when a model learns the training data too well, including noise and outliers, and performs poorly on unseen data. Underfitting occurs when a model is too simple to capture the underlying patterns in the data and performs poorly on both training and unseen data. Techniques such as regularization, early stopping, and using simpler models can help to mitigate overfitting, while using more complex models or engineering better features can help to address underfitting. Model evaluation and tuning. After training a model, it is crucial to evaluate its performance and fine-tune it to achieve optimal results. This section will discuss the process of model evaluation and tuning, including the use of appropriate evaluation metrics and hyperparameter optimization techniques. Evaluating model performance on the validation set is the first step in the tuning process. The validation set, which is separate from the training and test sets, is used to assess the model's performance during hyperparameter tuning and model selection. It provides an estimate of how well the model will generalize to unseen data and helps to prevent overfitting to the training data. Hyperparameter tuning techniques are used to find the optimal settings for the model's hyperparameters. Grid search involves evaluating all possible combinations of hyperparameter values within a specified range. Randomized search samples a fixed number of hyperparameter combinations from specified distributions. Bayesian optimization uses a probabilistic model to guide the search for optimal hyperparameters, often leading to faster convergence than grid search or randomized search. Using appropriate evaluation metrics is essential for accurately assessing model performance. The choice of metric depends on the specific problem and the type of model being used. For classification tasks, metrics such as accuracy, precision, recall, F1, score, and AUC are commonly used. For regression tasks, metrics such as MAE, MSE, RMSE, and R² are appropriate. It is important to choose metrics that are aligned with the goals of the project and the relative costs of different types of errors. Iterating on model selection and tuning is often necessary to achieve optimal performance. This may involve trying different algorithms, different feature sets, and different hyperparameter settings. It is an iterative process that requires experimentation, careful evaluation, and a good understanding of the problem being solved. The insights gained from evaluating one model can inform the development of subsequent models. Final evaluation on the test set is the last step in the model evaluation process. The test set, which has not been used during training, hyperparameter tuning, or model selection, provides a final, unbiased estimate of the model's generalization performance. It is crucial to only use the test set once, at the very end, to avoid any potential bias in the evaluation. The performance on the test set is the most reliable indicator of how well the model will perform in real-world scenarios. Model deployment. Once a satisfactory model has been developed and evaluated, the next step is to deploy it for use in a real-world setting. Model deployment involves making the model available to make predictions on new data, often as part of an application or system. Deploying models as APIs or web services is a common approach for making them accessible to other applications. The model is typically packaged into a web service that can receive requests containing input data, make predictions using the model, and return the predictions as a response. This allows other applications to easily integrate the model's functionality. REST APIs are often used for this purpose. Batch versus real-time prediction is an important consideration in model deployment. Batch prediction involves making predictions on a large set of inputs at once, typically on a scheduled basis. This is suitable for applications where immediate predictions are not required. Real-time prediction, on the other hand, involves making predictions on individual inputs as they arrive, requiring low latency. This is necessary for applications such as fraud detection or online recommendations. Containerization technologies like Docker have become increasingly popular for deploying machine learning models. Containers provide a lightweight and portable way to package a model and its dependencies into a self-contained unit that can be easily deployed and run consistently across different environments. Docker containers can be deployed on various platforms, including cloud services and on-premise servers. Cloud deployment platforms such as Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform, GCP, offer a range of services for deploying and managing machine learning models. These platforms provide infrastructure, tools, and services for deploying models as APIs, managing model versions, scaling deployments, and monitoring performance. They often offer specialized services for machine learning, such as AWS SageMaker, Azure Machine Learning, and Google Cloud AI Platform. Model serving frameworks like TensorFlow Serving and TorchServe provide tools and infrastructure for deploying and serving machine learning models. They handle tasks such as model loading, versioning, request routing, and scaling, allowing developers to focus on building and training models rather than on the complexities of deployment. These frameworks often support various model formats and provide APIs for making predictions. Model monitoring and maintenance. Deploying a machine learning model is not the end of the process. Models need to be continuously monitored and maintained to ensure they continue to perform well over time. This section will discuss the importance of model monitoring and maintenance and explore techniques for detecting and addressing issues that may arise after deployment. Monitoring model performance over time is crucial for detecting any degradation in performance. This can involve tracking key performance metrics, such as accuracy, precision, recall, or RMSE, and setting up alerts for when these metrics fall below acceptable thresholds. Monitoring can help to identify issues early on and trigger interventions, such as retraining or updating the model. Detecting data drift and concept drift is an important aspect of model monitoring. Data drift refers to changes in the distribution of the input data over time. Concept drift refers to changes in the relationship between the input features and the target variable. Both types of drift can cause a model's performance to degrade. Monitoring techniques can include tracking the distribution of input features, comparing the model's predictions to actual outcomes, and using statistical tests to detect significant changes. Retraining and updating models is necessary to address performance degradation due to data drift, concept drift, or other factors. Models can be retrained periodically using new data or when performance falls below a certain threshold. The frequency of retraining depends on the specific application and how quickly the underlying data or relationships are changing. In some cases, online learning techniques can be used to continuously update the model as new data arrives. Model versioning and rollback are important for managing different versions of a model and for ensuring that it is possible to revert to a previous version if necessary. Version control systems, such as Git, can be used to track changes to the model code and training data. Model registries or repositories can be used to store and manage different versions of trained models. This allows for easy rollback to a previous version in case of issues with a new model. A/B testing can be used to evaluate the performance of model updates before fully deploying them. This involves deploying both the old and new versions of the model and randomly routing a portion of the requests to each version. By comparing the performance of the two versions on key metrics, it is possible to determine whether the new model is actually an improvement before deploying it to all users. Scalability and efficiency in machine learning. As datasets grow larger and models become more complex, scalability and efficiency become increasingly important considerations in machine learning. This section will discuss techniques for scaling data processing, training, and inference, as well as hardware considerations. Scaling data processing is crucial for handling large datasets that do not fit in the memory of a single machine. Tools like Apache Spark provide distributed data processing frameworks that can handle massive datasets by partitioning the data and processing it in parallel across a cluster of machines. Spark provides APIs for data manipulation, feature engineering, and machine learning that can be used to build scalable data pipelines. Distributed training of machine learning models is another important technique for scaling up. This involves partitioning the training data and/or the model across multiple machines and training them in parallel. Frameworks like TensorFlow and PyTorch provide support for distributed training using various strategies, such as data parallelism and model parallelism. Distributed training can significantly reduce the time required to train large models on massive datasets. Optimizing models for inference speed is important for real-time applications where low latency is crucial. Techniques like model pruning, quantization, and knowledge distillation can be used to reduce the size and computational complexity of models without significantly sacrificing accuracy. These techniques can make models faster and more memory efficient, enabling them to be deployed on resource-constrained devices. Hardware considerations play an important role in the scalability and efficiency of machine learning. Graphics processing units, GPUs, have become widely used for training deep learning models due to their ability to perform parallel computations much faster than CPUs. Tensor processing units, TPUs, are specialized hardware accelerators designed by Google specifically for machine learning workloads, offering even higher performance than GPUs for certain types of models. Model compression and quantization are techniques for reducing the size and computational cost of machine learning models, particularly deep neural networks. Pruning involves removing unnecessary connections or neurons from the network. Quantization involves reducing the precision of the model's weights and activations, for example, from 32-bit floating point to 8-bit integers. These techniques can significantly reduce the memory footprint and inference time of models, making them more suitable for deployment on mobile and embedded devices. Building machine learning pipelines. A machine learning pipeline is a sequence of steps that automates the machine learning workflow, from data ingestion and preprocessing to model training, evaluation, and deployment. Building well-structured and automated pipelines is essential for creating reproducible, scalable, and maintainable machine learning systems. Automating the machine learning workflow offers several benefits. It reduces manual effort, minimizes the risk of errors, and ensures consistency across different stages of the project. Automation also makes it easier to experiment with different models, features, and hyperparameters, and to track and reproduce results. Furthermore, it enables the deployment and maintenance of machine learning models in production environments. Orchestration tools like Apache Airflow and Kubeflow provide frameworks for defining, scheduling, and monitoring complex machine learning pipelines. These tools allow users to define pipelines as directed acyclic graphs, DAGs, where each node represents a step in the workflow, such as data preprocessing, feature engineering, model training, or evaluation. The orchestration tool manages the execution of the pipeline, handling dependencies between steps and retrying failed steps if necessary. The components of a machine learning pipeline typically include data ingestion, data validation, data preprocessing, feature engineering, model training, model evaluation, model deployment, and model monitoring. Each component can be implemented as a separate module or script, making the pipeline modular and easier to maintain. The pipeline can be triggered manually or automatically, for example, when new data arrives or on a schedule. Reproducibility and version control are crucial aspects of building machine learning pipelines. It should be possible to reproduce the results of a pipeline by rerunning it with the same data and code. Version control systems like Git should be used to track changes to the code, data, and model artifacts. This ensures that the pipeline can be easily reproduced and that previous versions can be restored if needed. CI/CD, continuous integration/continuous deployment, is a set of practices that can be applied to machine learning pipelines to automate the testing, building, and deployment of models. Continuous integration, CI, involves automatically building and testing the pipeline whenever changes are made to the code or data. Continuous deployment, CD, involves automatically deploying updated models to production after they have passed all tests. CI/CD for machine learning, sometimes referred to as MLOps, helps to ensure the quality and reliability of machine learning systems. Best practices for building machine learning systems. Building robust and reliable machine learning systems requires careful planning, attention to detail, and adherence to best practices. This section will provide some guidelines for building high-quality machine learning systems. Writing clean and maintainable code is essential for any software project, and machine learning projects are no exception. Following coding standards, using meaningful variable and function names, and writing modular code can improve readability and maintainability. It is also important to document the code thoroughly, explaining the purpose of different modules, functions, and parameters. Version control is crucial for tracking changes to the code, data, and models throughout the project lifecycle. Using a version control system like Git allows you to track changes, collaborate with others, and revert to previous versions if needed. It is a good practice to commit changes frequently with clear and descriptive commit messages. Git can also be used to manage different branches of development, such as for experimenting with new features or models. Testing is an essential part of building reliable machine learning systems. Unit tests can be used to verify the correctness of individual components of the system, such as data preprocessing functions, feature engineering steps, or model training code. Integration tests can be used to check that different components of the system work together correctly. It is also important to test the entire pipeline end-to-end to ensure that it produces the expected results. Collaboration and teamwork are crucial for the success of machine learning projects. Machine learning projects often involve individuals with different skill sets, such as data scientists, engineers, and domain experts. Effective communication, clear roles and responsibilities, and shared tools and platforms are essential for successful collaboration. Using collaborative platforms like GitHub, GitLab, or Bitbucket can facilitate teamwork and code sharing. Documenting the entire machine learning project is essential for reproducibility, maintainability, and knowledge transfer. Documentation should include not only the code but also the data, the experimental setup, the results, and the rationale behind key decisions. This documentation can take various forms, such as README files, Jupyter notebooks, comments in the code, and technical reports. Good documentation practices can save time and effort in the long run and make it easier for others to understand and build upon your work. Real-world case studies and project examples. In this final section of Lesson 10, we will examine some real-world case studies and project examples to illustrate the concepts and techniques discussed throughout the lesson. These examples will showcase how machine learning is applied in different domains and provide practical insights into building and deploying machine learning systems. Building an end-to-end machine learning project involves all the stages of the machine learning project lifecycle, from problem definition to model deployment and monitoring. A good project example should demonstrate a clear understanding of the problem, careful data preparation and feature engineering, appropriate model selection and training, rigorous evaluation and tuning, and a plan for deployment and maintenance. It should also document the entire process and provide insights into the decisions made along the way. Case study: churn prediction is a common application of machine learning in many industries, such as telecommunications, banking, and e-commerce. The goal is to predict which customers are likely to churn, i.e., cancel their subscription or stop using a service, so that proactive measures can be taken to retain them. A churn prediction project might involve collecting data on customer demographics, usage patterns, and interactions with customer service, engineering features that capture relevant aspects of customer behavior, training a classification model to predict churn probability, and deploying the model to identify at-risk customers in real time. Case study: image classification is a core task in computer vision with numerous applications. For example, a project might involve building a model to classify images of different types of products for an e-commerce company, or classifying medical images to assist in diagnosis. This could involve collecting and labeling a large dataset of images, using data augmentation techniques to increase the dataset size, training a convolutional neural network, CNN, on the data, and fine-tuning a pre-trained model using transfer learning. The model could then be deployed as a web service to classify new images. Case study: fraud detection is another important application of machine learning, particularly in the financial industry. Fraud detection models aim to identify fraudulent transactions or activities in real time, preventing financial losses and protecting customers. A fraud detection project might involve collecting data on past transactions, engineering features that capture suspicious patterns, training a classification model, e.g., a random forest or a gradient boosting machine, to distinguish between fraudulent and legitimate transactions, and deploying the model to score new transactions in real time. Anomaly detection techniques can also be used for fraud detection. Case study: recommendation system is a classic application of machine learning that aims to predict the preferences or ratings that a user would give to an item. Recommendation systems are widely used in e-commerce, entertainment, and other domains to provide personalized recommendations to users. A recommendation system project might involve collecting data on user item interactions, e.g., ratings, purchases, views, using collaborative filtering or content-based filtering techniques to build a model, and evaluating the model's performance using metrics like precision at K, recall at K, or NDCG. The model could then be deployed as a service to provide real-time recommendations. These are just a few examples of the many real-world applications of machine learning. By studying these case studies and working on your own projects, you can gain valuable experience and develop a deeper understanding of the challenges and best practices involved in building and deploying machine learning systems. This concludes Lesson 10 and our exploration of building and deploying machine learning models. We have covered the entire machine learning project lifecycle, from defining the problem and preparing the data to selecting, training, evaluating, and tuning models. We also discussed deploying models, monitoring their performance, and ensuring their scalability and efficiency. Additionally, we touched upon the importance of building machine learning pipelines, adhering to best practices, and learning from real-world case studies. Remember that building and deploying machine learning models is an iterative process that requires careful planning, experimentation, and continuous improvement. By mastering the concepts and techniques presented in this lesson, you are well equipped to develop and deploy your own machine learning solutions. As we move forward in this course, we will continue to build upon these foundations, exploring more advanced topics and techniques in machine learning. Keep practicing, experimenting, and applying what you've learned to real-world problems. The journey to becoming a proficient machine learning practitioner is ongoing, and each project you undertake will further enhance your skills and knowledge. Lesson 11, Introduction to Natural Language Processing, NLP, Fundamentals of NLP. In this lesson, we will dive into the fascinating field of natural language processing, NLP, a branch of artificial intelligence that focuses on enabling computers to understand, interpret, and generate human language. NLP plays a crucial role in bridging the gap between human communication and computer understanding, with applications ranging from chatbots and virtual assistants to sentiment analysis and machine translation. Natural language processing, NLP, is an interdisciplinary field that combines techniques from computer science, linguistics, and artificial intelligence to enable computers to process, analyze, and generate human language. The scope of NLP is vast, encompassing tasks such as text classification, sentiment analysis, machine translation, question answering, information extraction, and text summarization. The ultimate goal of NLP is to enable computers to understand and respond to natural language in a way that is similar to how humans do. NLP is closely related to both machine learning and artificial intelligence. Many NLP tasks are now addressed using machine learning techniques, particularly deep learning. Machine learning algorithms, such as deep neural networks, can learn complex patterns in language data and make accurate predictions or generate text. NLP can be seen as a subfield of AI that focuses on the specific challenges of understanding and generating human language. Understanding natural language poses significant challenges for computers due to its inherent ambiguity, variability, and complexity. Human language is full of nuances, idioms, sarcasm, and context-dependent meanings that are difficult for machines to grasp. The same sentence can have different meanings depending on the context, and different sentences can express the same meaning. Furthermore, language is constantly evolving, with new words and expressions emerging all the time. The history and evolution of NLP date back to the early days of artificial intelligence. Early approaches to NLP were primarily rule-based, relying on handcrafted rules and grammars. In the 1990s, statistical methods and machine learning techniques started to gain prominence, leading to more robust and data-driven approaches. The advent of deep learning in the 2010s has revolutionized the field, enabling the development of powerful models that can learn directly from raw text data. Key concepts and terminology in NLP include tokens, sentences, documents, corpus, a collection of documents, part-of-speech tags, named entities, and parse trees. Understanding these basic concepts is essential for working with NLP tasks and algorithms. Other important concepts include n-grams, language models, word embeddings, and attention mechanisms, which we will explore in later sections. Text preprocessing and cleaning. Before applying machine learning algorithms to text data, it is crucial to preprocess and clean the text to remove noise, inconsistencies, and irrelevant information. This section will discuss common text preprocessing and cleaning techniques used in NLP. Tokenization is the process of splitting a text document into individual words or tokens. Stemming and lemmatization are techniques for reducing words to their root form. Stemming is a more basic approach that simply removes suffixes, while lemmatization uses a dictionary to map words to their base form, lemma. For example, stemming might reduce running, runs, and ran to run, while lemmatization would map them to run, verb, or ran, past tense of run. Handling stop words, punctuation, and capitalization is important for many NLP tasks. Stop words are common words like the, a, and is that often do not carry much meaning and can be removed. Punctuation marks can also be removed or handled separately, depending on the task. Capitalization can be handled by converting all text to lowercase, although this may not be appropriate for all tasks, e.g., named entity recognition. Noise removal and text normalization involve identifying and correcting errors, inconsistencies, and variations in the text data. This can include correcting spelling errors, handling abbreviations and acronyms, and standardizing formatting. Noise removal can improve the performance of NLP models by reducing the variability and ambiguity in the data. Encoding text data is necessary because most machine learning algorithms require numerical inputs. Text data needs to be converted into a numerical representation that can be processed by these algorithms. Common encoding techniques include one-hot encoding, where each word is represented by a binary vector, and techniques based on word embeddings, which we will discuss in more detail later. Data cleaning techniques for text can vary depending on the source and nature of the data. For example, data scraped from the web may contain HTML tags, special characters, or other irrelevant content that needs to be removed. Social media data may contain emoticons, hashtags, and user mentions that require special handling. Text data from scanned documents may contain optical character recognition, OCR, errors that need to be corrected. Basic NLP tasks. This section will introduce some fundamental NLP tasks that serve as building blocks for more complex applications. These tasks often form part of the pre-processing pipeline for larger NLP projects. Part of speech, POS, tagging is the process of assigning grammatical tags to each word in a sentence, such as noun, verb, adjective, adverb, etc. POS tagging provides valuable information about the syntactic structure of a sentence and can be used as input for other NLP tasks, such as parsing and named entity recognition. Named entity recognition, NR, is the task of identifying and classifying named entities in text, such as persons, organizations, locations, dates, and times. NER is a crucial component of information extraction systems and is used in various applications, including question answering, text summarization, and knowledge base construction. Parsing involves analyzing the grammatical structure of a sentence and representing it as a parse tree. Syntactic analysis aims to understand the relationships between words in a sentence and how they are combined to form phrases and clauses. Parsing can be used to extract information about the meaning of a sentence and is a key component of many NLP applications, such as machine translation and question answering. N-grams are sequences of n consecutive words in a text. For example, bigrams, n equals 2, are pairs of adjacent words, while trigrams, n equals 3, are sequences of 3 adjacent words. N-grams can be used to capture local context and word order information. Language modeling is the task of predicting the next word in a sequence given the previous words. N-gram models are a simple but effective approach to language modeling and can be used in various applications, including speech recognition and text generation. Text classification is the task of assigning a text document to one or more predefined categories or classes. This is a supervised learning problem where the model is trained on labeled examples of text documents and their corresponding categories. Text classification has numerous applications, including spam filtering, sentiment analysis, topic categorization, and intent detection in chatbots. Representing text as vectors. To apply machine learning algorithms to text data, we need to convert text into numerical representations that can be processed by these algorithms. This section will discuss various techniques for representing text as vectors, including the bag of words model, TF-IDF, and word embeddings. The bag of words, BAW, model is a simple and widely used approach for representing text as numerical vectors. In the BAW model, each document is represented as a vector where each element corresponds to the count or frequency of a specific word in the document's vocabulary. The order of words is disregarded, hence the name bag of words. BAW is easy to implement and can be effective for tasks like document classification, but it does not capture the semantic meaning of words or the relationships between them. TF-IDF, term frequency inverse document frequency, is a refinement of the BAW model that takes into account the importance of a word in a document relative to the entire corpus. TF-IDF assigns a weight to each word in a document based on its frequency in the document, term frequency, and its inverse frequency across all documents in the corpus, inverse document frequency. Words that are frequent in a document but rare in the corpus are given higher weights, as they are considered more informative for characterizing the document. Word embeddings are a powerful technique for representing words as dense vectors in a continuous vector space, where semantically similar words are mapped to nearby vectors. Popular word embedding methods include Word2Vec, glove, and fast text. These methods learn word embeddings from large text corpora by exploiting the distributional hypothesis, which states that words that appear in similar contexts tend to have similar meanings. Word embeddings can capture semantic relationships between words, such as synonymy, antonymy, and analogy. Contextualized word embeddings are a more recent development that takes into account the context in which a word appears when generating its vector representation. Models like Elmo and BERT learn contextualized word embeddings by training deep neural networks on large text corpora using language modeling objectives. These embeddings have been shown to improve the performance of many NLP tasks, as they can capture the nuances of word meaning that depend on context. Document embeddings are techniques for representing entire documents as vectors. One simple approach is to average the word embeddings of all the words in the document. More sophisticated methods, such as doc2vec, learn document embeddings directly by extending the word2vec algorithm. Document embeddings can be used for various tasks, such as document classification, clustering, and information retrieval. Sentiment analysis, also known as opinion mining, is the task of automatically determining the sentiment or opinion expressed in a piece of text. This section will introduce the concept of sentiment analysis, discuss its applications, and explore different approaches for performing sentiment analysis. Sentiment analysis aims to identify the polarity, positive, negative, or neutral, and the intensity of the sentiment expressed in a text. It can also involve detecting more fine-grained emotions, such as joy, sadness, anger, and fear. Sentiment analysis has numerous applications, including analyzing customer feedback, monitoring social media for brand perception, understanding public opinion, and detecting hate speech or cyberbullying. Lexicon-based approaches to sentiment analysis rely on sentiment lexicons, which are dictionaries that contain words or phrases annotated with their sentiment polarity and strength. These approaches typically involve counting the number of positive and negative words in a text and using these counts to determine the overall sentiment. While simple and intuitive, lexicon-based approaches may struggle with complex linguistic phenomena like negation, sarcasm, and context-dependent sentiment. Machine learning approaches to sentiment analysis treat it as a text classification problem. A model is trained on a labeled dataset of text documents, where each document is annotated with its sentiment polarity, e.g., positive, negative, or neutral. The model learns to identify patterns and features in the text that are indicative of different sentiment polarities. Various machine learning algorithms can be used for sentiment classification, including naive Bayes, support vector machines, and deep learning models like recurrent neural networks and transformers. Sentiment analysis faces several challenges. Sarcasm and irony can be difficult for algorithms to detect, as they often involve expressing a sentiment that is the opposite of the literal meaning of the words used. Negation can also be challenging, as it can reverse the polarity of a sentiment-bearing word or phrase. Context-dependent sentiment, where the sentiment of a word or phrase depends on the surrounding text, requires more sophisticated models that can capture long-range dependencies. Evaluation metrics for sentiment analysis are similar to those used for other classification tasks. Accuracy, precision, recall, and F1 score are commonly used to assess the performance of sentiment analysis models. However, it is important to consider the specific challenges of sentiment analysis when interpreting these metrics. For example, a model that simply predicts the majority class might achieve high accuracy on an imbalanced dataset but fail to capture the nuances of sentiment. Topic modeling is an unsupervised machine learning technique used to discover latent topics in a collection of text documents. This section will introduce the concept of topic modeling, discuss popular algorithms like latent Dirichlet allocation, LDA, and non-negative matrix factorization, NMF, and explore the applications and evaluation of topic models. Topic modeling algorithms assume that each document in a corpus is a mixture of topics, and each topic is a distribution over words. The goal is to learn these topics and the topic proportions for each document from the observed data. Topic modeling can be used to summarize large text collections, discover underlying themes, and organize documents for browsing and retrieval. Latent Dirichlet allocation, LDA, is a widely used probabilistic topic model. LDA assumes that each document is generated by first choosing a distribution over topics, and then, for each word in the document, choosing a topic from this distribution and a word from the corresponding topic's distribution over words. LDA uses Bayesian inference techniques to estimate the topic word distributions and the document topic distributions. Non-negative matrix factorization, NMF, is another popular technique for topic modeling. NMF factorizes the document term matrix into two non-negative matrices, a document topic matrix and a topic term matrix. The factorization is constrained to be non-negative, which often leads to more interpretable topics compared to other matrix factorization techniques like singular value decomposition, SVD. NMF can be solved using iterative optimization algorithms. Evaluating topic models can be challenging, as there is no single ground truth for the correct topics. Common approaches include using held-out perplexity, which measures how well the model predicts unseen documents, and topic coherence, which measures the semantic similarity between the top words in each topic. Human evaluation, where domain experts assess the interpretability and relevance of the topics, is also often used. Applications of topic modeling are numerous and varied. Topic modeling can be used to analyze news articles, social media posts, scientific publications, customer reviews, and other types of text data. It can help to identify trends, discover hidden themes, and summarize large text collections. Topic modeling can also be used as a feature extraction technique for other machine learning tasks, such as document classification and clustering. Visualizing topic models can aid in their interpretation and evaluation. Common visualization techniques include word clouds, where the size of each word corresponds to its importance in a topic, and topic document graphs, which show the relationships between topics and documents. Interactive visualizations can allow users to explore the topics and their relationships in more detail. Text summarization. Text summarization is the task of automatically generating a concise and coherent summary of a longer text document while preserving its key information and overall meaning. This section will introduce the main approaches to text summarization, discuss evaluation metrics, and explore the challenges and applications of this task. There are two main approaches to automatic text summarization: extractive summarization and abstractive summarization. Extractive summarization involves selecting and concatenating the most important sentences or phrases from the original text to create a summary. Abstractive summarization, on the other hand, involves generating new sentences that capture the essence of the original text, potentially using words or phrases that were not present in the original. Extractive summarization methods often rely on scoring sentences based on various features, such as their length, position in the document, presence of key words, and similarity to the document title. These scores are then used to select the most important sentences to include in the summary. Graph-based methods, such as TextRank, can also be used for extractive summarization, where sentences are represented as nodes in a graph, and edges represent similarity relationships between sentences. Abstractive summarization is a more challenging task that requires a deeper understanding of the text and the ability to generate novel sentences. Recent advances in deep learning, particularly sequence-to-sequence models and transformers, have led to significant progress in abstractive summarization. These models are typically trained on large datasets of document summary pairs and learn to generate summaries by attending to the most relevant parts of the input document. Evaluation metrics for summarization are crucial for assessing the quality of automatically generated summaries. ROUGE, Recall-Oriented Understudy for Gisting Evaluation, is a widely used set of metrics that compare the n-grams in the generated summary to those in one or more reference summaries. Other metrics, such as BLEU and Meteor, which were originally developed for machine translation, are also sometimes used for summarization. Human evaluation, where people judge the quality of summaries based on criteria like informativeness, coherence, and fluency, is also important. Challenges in text summarization include identifying the most important information in a document, ensuring the coherence and fluency of the generated summary, and handling long documents or documents with complex structures. Abstractive summarization, in particular, faces challenges related to factuality, ensuring that the generated summary is factually consistent with the original text, and avoiding repetition or nonsensical output. Applications of text summarization include generating news headlines, summarizing email threads, creating abstracts for scientific papers, and generating summaries of legal documents. Text summarization can help users to quickly grasp the main points of a document without having to read the entire text, saving time and improving information access. Machine translation. Machine translation is the task of automatically translating text from one language to another. This section will introduce the main approaches to machine translation, discuss the role of sequence-to-sequence models and attention mechanisms, and explore evaluation metrics for machine translation. Historically, statistical machine translation, SMT, was the dominant approach to machine translation. SMT models learn statistical relationships between words and phrases in the source and target languages from large parallel corpora, collections of texts in two or more languages, where each text is a translation of the others. SMT systems typically involve several components, including a translation model, a language model, and a decoder. Neural machine translation, NMT, has emerged as the state-of-the-art approach to machine translation in recent years. NMT models use deep neural networks, typically sequence-to-sequence models, to learn a direct mapping from the source language to the target language. Unlike SMT, NMT does not rely on explicit phrase tables or word alignments but instead learns to encode the source sentence into a continuous vector representation and then decode it into the target sentence. Sequence-to-sequence models, often based on recurrent neural networks, RNNs, or transformers, are commonly used in NMT. These models consist of an encoder network that processes the source sentence and a decoder network that generates the target sentence. The encoder learns to create a fixed-length vector representation that captures the meaning of the source sentence, and the decoder uses this representation to generate the target sentence word by word. Attention mechanisms have become a standard component of state-of-the-art NMT models, including transformer-based models which rely entirely on attention and dispense with recurrence and convolutions. Evaluation metrics for machine translation are crucial for assessing the quality of translations and comparing different models. BLEU, Bilingual Evaluation Understudy, is a widely used metric that measures the n-gram overlap between the machine-generated translation and one or more human reference translations. Other metrics, such as METEOR and TR, are also used. Human evaluation, where bilingual speakers judge the quality of translations, is considered the gold standard for evaluation. Machine translation has numerous applications, including translating websites, documents, and communication in real time. It can facilitate cross-lingual communication, improve access to information, and enable businesses to operate in global markets. Despite significant advances in recent years, machine translation remains a challenging task, particularly for low-resource languages and for translating complex or nuanced text. Question answering systems. Question answering, QA, systems aim to automatically answer questions posed in natural language. This section will discuss different types of QA systems, explore knowledge-based and text-based approaches, and introduce reading comprehension models. Question-answering systems can be broadly classified into two categories, open domain and closed domain. Open domain QA systems are designed to answer questions on any topic, typically by searching and analyzing a large corpus of text, such as the web. Closed domain QA systems, on the other hand, are designed to answer questions within a specific domain, such as customer support for a particular product. Knowledge-based question-answering systems rely on structured knowledge bases, such as ontologies or knowledge graphs, to answer questions. These systems typically involve parsing the question into a formal query, mapping the query to entities and relations in the knowledge base, and retrieving or reasoning over the relevant facts to produce an answer. Knowledge-based QA systems can provide precise answers to factual questions but require a comprehensive and up-to-date knowledge base. Text-based question-answering systems, also known as reading comprehension systems, aim to answer questions based on a given text passage or a collection of documents. These systems typically involve two main components: a document retriever that selects relevant documents or passages from a large corpus, and a reader that extracts the answer from the retrieved text. Recent advances in deep learning have led to significant progress in text-based QA. Reading comprehension models are a type of text-based QA system that focuses on answering questions based on a single document or passage. These models are often based on deep neural networks, such as recurrent neural networks, RNNs, or transformers, that learn to encode the question and the passage into continuous vector representations and then predict the answer span within the passage. Models like BERT and its variants have achieved state-of-the-art results on several reading comprehension benchmarks. Evaluating question answering systems typically involves metrics such as exact match, EM, and F1 score, which measure the overlap between the predicted answer and the ground truth answer. For open domain QA, metrics like top K accuracy are often used, where a system is considered correct if the true answer is among the top K answers returned by the system. Human evaluation, where people judge the correctness and relevance of the answers, is also important. Question answering has numerous applications, including virtual assistants, search engines, and customer support. QA systems can provide users with direct answers to their questions, rather than just a list of potentially relevant documents. Despite significant progress, question answering remains a challenging task, particularly for questions that require complex reasoning, common sense knowledge, or understanding of context and nuance. Real-world applications and case studies in NLP. In this final section of Lesson 11, we will explore some real-world applications and case studies of natural language processing, NLP, to illustrate the impact and versatility of this field. Chatbots and conversational AI are one of the most prominent applications of NLP. Chatbots are computer programs designed to simulate conversation with human users, often through text or voice interfaces. They are used in various applications, such as customer service, virtual assistants, and online education. Advances in deep learning, particularly in sequence-to-sequence models and transformers, have enabled the development of more sophisticated and human-like chatbots. Information retrieval and search engines are another area where NLP plays a crucial role. Search engines use NLP techniques to understand the meaning of search queries and to retrieve relevant documents from a large corpus. Techniques like stemming, lemmatization, and query expansion are used to improve the accuracy of search results. More advanced NLP techniques, such as semantic search and question answering, are being incorporated into search engines to provide more direct and relevant answers to user queries. Text classification is used in various real-world applications, such as spam filtering and content moderation. Spam filters use NLP techniques to classify emails as spam or not spam based on their content. Content moderation systems use similar techniques to automatically detect and filter out inappropriate or harmful content on social media platforms, online forums, and other websites. These applications often involve training machine learning models on large labeled datasets of text. Sentiment analysis is widely used in social media monitoring and brand management. Companies use sentiment analysis to track public opinion about their products or services, to identify potential issues or crises, and to understand customer feedback. Sentiment analysis can also be used to analyze customer reviews, survey responses, and other forms of text data to gain insights into customer preferences and satisfaction. Machine translation is used to facilitate cross-lingual communication in various contexts. It enables people who speak different languages to communicate with each other, and it can be used to translate websites, documents, and other types of content. Machine translation is used by businesses to operate in global markets, by governments to communicate with citizens who speak different languages, and by individuals to access information and connect with people around the world. These are just a few examples of the many real-world applications of NLP. As NLP techniques continue to advance, we can expect to see even more innovative and impactful applications in the years to come. NLP has the potential to transform many aspects of our lives, from the way we communicate and access information to the way we do business and interact with technology. This concludes our introduction to natural language processing, NLP. We have covered the fundamentals of NLP, including its definition, scope, and relationship to machine learning and AI. We explored various text pre-processing and cleaning techniques, basic NLP tasks such as POS tagging and NAR, and different methods for representing text as vectors, including word embeddings. We also discussed several important NLP applications, including sentiment analysis, topic modeling, text summarization, machine translation, and question answering systems. NLP is a rapidly evolving field that is transforming the way we interact with computers and with each other. By enabling computers to understand, interpret, and generate human language, NLP is opening up new possibilities for human-computer interaction, information access, and knowledge discovery. As you continue your journey in machine learning, keep in mind that NLP is a rich and rewarding area to explore, with many opportunities for innovation and impact. The techniques and concepts you have learned in this lesson will provide a solid foundation for further exploration of this exciting field. Lesson 12, Computer Vision. Introduction to Computer Vision. In this lesson, we will embark on an exciting journey into the field of computer vision, a branch of artificial intelligence that aims to enable computers to see and interpret the visual world in a way that is similar to humans. Computer vision has witnessed remarkable progress in recent years, driven by advances in deep learning and the availability of large-scale image and video datasets. Computer vision is the science and technology of machines that see. It is concerned with the theory and technology for building artificial systems that obtain information from images or multidimensional data. The scope of computer vision is broad, encompassing tasks such as image classification, object detection, image segmentation, image generation, and video analysis. The ultimate goal is to enable computers to understand and interpret visual information in a way that is useful for various applications. Computer vision is closely related to machine learning and artificial intelligence. Many computer vision tasks are now addressed using machine learning techniques, particularly deep learning. Machine learning algorithms, such as deep neural networks, can learn complex patterns in visual data and make accurate predictions or decisions. Computer vision can be seen as a subfield of AI that focuses on the specific challenges of processing and understanding visual information. Challenges in computer vision include dealing with variations in lighting, viewpoint, scale, and object appearance. Objects can be occluded or appear in cluttered scenes, making them difficult to detect and recognize. Images can be noisy or low resolution, and the same object can appear very different depending on the context. Furthermore, understanding the semantics and context of an image often requires high-level reasoning and common-sense knowledge. The history and evolution of computer vision date back to the 1960s, with early work focusing on edge detection, image segmentation, and object recognition using simple geometric models. In the 1980s and 1990s, more sophisticated methods based on handcrafted features and statistical models were developed. The advent of deep learning in the 2010s has revolutionized the field, enabling the development of powerful models that can learn directly from raw pixel data and achieve state-of-the-art performance on many tasks. Key concepts and terminology in computer vision include pixels, resolution, color spaces, image features, filters, convolutions, and neural networks. Understanding these basic concepts is essential for working with computer vision tasks and algorithms. Other important concepts include object detection, image segmentation, and optical flow, which we will explore in later sections. Image fundamentals. Before diving into more advanced computer vision techniques, it's important to understand the basics of how images are represented and processed in computers. This section will cover fundamental concepts related to digital images. Image representation in computers typically involves representing an image as a grid of pixels, where each pixel stores a numerical value representing the intensity or color at that location. The resolution of an image refers to the number of pixels in the grid, e.g., 1920 by 1080. Color spaces define how colors are represented numerically. The most common color space is RGB, red, green, blue, where each pixel is represented by three values corresponding to the intensity of red, green, and blue light. Other color spaces include HSV, hue, saturation, value, and CMYK, cyan, magenta, yellow, key/black. Common image file formats include JPEG, PNG, GIF, and BMP. JPEG is a lossy compressed format that is widely used for photographs. PNG is a lossless compressed format that is often used for images with sharp lines and text. GIF is an older format that supports animation but is limited to 256 colors. BMP is an uncompressed format that is rarely used for web images due to its large file size. Basic image operations include resizing, cropping, and rotating images. Resizing changes the resolution of an image, while cropping removes parts of the image. Rotation changes the orientation of the image. These operations are often used for data preprocessing and augmentation in computer vision tasks. Image filtering and enhancement techniques are used to modify or improve the appearance of an image. Common filters include blurring filters, e.g., Gaussian blur, sharpening filters, and edge detection filters. Image enhancement techniques include contrast adjustment, brightness adjustment, and histogram equalization. These techniques can be used to reduce noise, enhance details, or improve the visual quality of an image. Histograms are a graphical representation of the distribution of pixel intensities in an image. They can be used to analyze the overall brightness and contrast of an image and to identify potential issues, such as underexposure or overexposure. Image statistics, such as the mean, standard deviation, minimum, and maximum pixel values, can also provide useful information about an image. Feature detection and extraction. Feature detection and extraction are crucial steps in many computer vision applications. They involve identifying and describing interesting or informative regions in an image that can be used for tasks like object recognition, image matching, and tracking. Edge detection is a fundamental technique in image processing that aims to identify the boundaries between different regions in an image. Edges often correspond to object boundaries or significant changes in intensity. Common edge detection algorithms include the Sobel operator, which computes the gradient of the image intensity, and the Canny edge detector, which uses a multi-stage process to detect a wide range of edges while reducing noise. Corner detection aims to identify points in an image where two edges meet at a significant angle. Corners are often stable and distinctive features that can be used for image matching and object recognition. Common corner detection algorithms include the Harris corner detector and the Chertomasi corner detector, both of which are based on analyzing the local structure of the image gradient. Blob detection aims to identify regions in an image that differ in properties, such as brightness or color, compared to surrounding regions. Blobs can represent objects or parts of objects. Common blob detection methods include Laplacian of Gaussian, log, and difference of Gaussians, dog, which detect blobs at different scales. Scale invariant feature transform, SIFT, is a powerful algorithm for detecting and describing local features in images that are invariant to scale, rotation, and changes in illumination. SIFT features are widely used for object recognition, image stitching, and 3D reconstruction. The SIFT algorithm involves detecting keypoints at different scales, assigning an orientation to each keypoint, and computing a descriptor that is invariant to scale and rotation. Histogram of oriented gradients, HOG, is a feature descriptor used for object detection, particularly for detecting pedestrians. HOG features are computed by dividing an image into small cells, computing a histogram of gradient orientations within each cell, and then normalizing the histograms across larger blocks of cells. HOG features capture information about the local shape and appearance of objects and are relatively robust to changes in illumination and small variations in pose. Image classification. Image classification is the task of assigning a label or category to an entire image. It is one of the most fundamental and widely studied problems in computer vision, with numerous applications in various domains. Traditional approaches to image classification often involved handcrafted features, such as color histograms, texture descriptors, or SIFT/HOG features, combined with a classifier like a support vector machine, SVM, or a random forest. These approaches required significant domain expertise and feature engineering effort and often did not generalize well to new datasets or tasks. Convolutional neural networks, CNNs, have revolutionized image classification and are now the dominant approach. CNNs can learn hierarchical features directly from raw pixel data, eliminating the need for manual feature engineering. CNNs have achieved state-of-the-art results on many image classification benchmarks, often surpassing human performance. Popular CNN architectures include AlexNet, VGG, ResNet, and Inception. Transfer learning and fine-tuning pre-trained models have become common practices in image classification. Instead of training a CNN from scratch, which can require a large amount of data and computational resources, it is often more efficient to start with a model that has been pre-trained on a large dataset like ImageNet. The pre-trained model can then be fine-tuned on a smaller dataset for a specific task, typically by replacing the final classification layer and retraining the network with a smaller learning rate. Data augmentation is a crucial technique for improving the performance of image classification models, particularly when the training dataset is limited. Data augmentation involves applying random transformations to the training images, such as rotations, flips, crops, and color adjustments, to create new training examples. This helps to increase the effective size of the training set and makes the model more robust to variations in the input data. Evaluating image classification models typically involves metrics such as accuracy, precision, recall, F1 score, and the confusion matrix. For multi-class classification, metrics like top 1 and top 5 accuracy are often reported. It is also important to analyze the types of errors the model makes and to visualize the model's predictions to gain insights into its strengths and weaknesses. Object detection is a computer vision task that involves not only classifying objects in an image but also localizing them by identifying their spatial extent, typically with bounding boxes. This section will discuss various approaches to object detection and their applications. The sliding window approach is a simple but computationally expensive method for object detection. It involves running a classifier at multiple locations and scales across the image, using a sliding window. Each window is classified as either containing the object of interest or not. This approach can detect objects at different locations and scales but requires a large number of classifications, making it slow and inefficient. Region proposal methods aim to reduce the number of candidate regions that need to be classified by identifying regions that are likely to contain objects. Selective search is a popular region proposal method that uses a hierarchical grouping algorithm to generate a set of candidate regions. RCNN, regions with CNN features, was an early deep learning-based object detection method that combined region proposals with CNN-based classification. Faster RCNN is an improvement upon RCNN that integrates region proposal generation into the network using a region proposal network, RPN. The RPN shares convolutional features with the object detection network, making region proposal generation nearly cost-free. Faster RCNN significantly improves the speed and accuracy of object detection compared to RCNN. YOLO, you only look once, and SSD, single-shot multi-box detector, are single-stage object detection methods that perform object localization and classification in a single pass through the network. They divide the image into a grid and predict bounding boxes and class probabilities for each grid cell. YOLO and SSD are much faster than two-stage methods like faster RCNN, making them suitable for real-time applications. Evaluating object detection models typically involves metrics like mean average precision, MAP. Average precision, AP, is computed for each class by averaging the precision values at different recall levels. MAP is then computed by averaging the AP values across all classes. Intersection over union, IOU, is a common metric used to evaluate the accuracy of bounding box predictions. Applications of object detection are numerous and include autonomous driving, surveillance, robotics, and medical image analysis. Object detection can be used to detect pedestrians, vehicles, and other objects in self-driving cars, to identify suspicious behavior in surveillance footage, to enable robots to interact with objects in their environment, and to detect and localize tumors in medical images. Image segmentation. Image segmentation is the task of partitioning an image into multiple segments or regions, typically corresponding to different objects or parts of objects. This section will discuss different types of image segmentation and popular algorithms. Semantic segmentation aims to assign a class label to each pixel in an image. For example, in an image of a street scene, each pixel might be labeled as road, car, pedestrian, or building. Semantic segmentation provides a pixel-level understanding of the image content but does not distinguish between different instances of the same class. Instance segmentation goes a step further by not only assigning a class label to each pixel but also distinguishing between different instances of the same class. For example, in an image with multiple cars, instance segmentation would assign a unique identifier to each car instance in addition to labeling the pixels as car. Fully convolutional networks, FCNs, were one of the first deep learning-based approaches to semantic segmentation. FCNs adapt classification networks like VGG or ResNet to perform pixel-level prediction by replacing fully connected layers with convolutional layers. They can process images of arbitrary size and produce segmentation maps of the same size. UNet is a popular architecture for semantic segmentation that was originally developed for biomedical image segmentation. It consists of a contracting path that captures context and an expanding path that enables precise localization. The contracting path is similar to a typical CNN, while the expanding path uses upsampling operations and concatenations with high-resolution features from the contracting path to generate a segmentation map. Mask RCNN is a state-of-the-art method for instance segmentation that extends faster RCNN by adding a branch for predicting an object mask in parallel with the existing branch for bounding box recognition. Mask RCNN can accurately segment individual object instances and has achieved impressive results on benchmark datasets. It is widely used in applications such as autonomous driving, robotics, and image editing. Evaluating segmentation models typically involves metrics like pixel accuracy, mean intersection over union, MEO, and frequency-weighted intersection over union, FWAU. Pixel accuracy measures the percentage of correctly classified pixels. MEO computes the IOU for each class and then averages over all classes. FWAU weights the IOU of each class by its frequency. Image generation and manipulation. This section will discuss techniques for generating and manipulating images using deep learning, focusing on generative adversarial networks, GANs, and their applications. Generative adversarial networks, GANs, have shown remarkable capabilities in generating realistic images. GANs consist of two networks, a generator and a discriminator, that are trained simultaneously in an adversarial game. The generator tries to create realistic images, while the discriminator tries to distinguish between real images from the training data and fake images generated by the generator. Through this adversarial training process, the generator learns to produce increasingly realistic images. Style transfer is an application of deep learning that involves transferring the style of one image to another image while preserving the content of the second image. For example, one might transfer the style of a famous painting to a photograph. This can be achieved using CNNs by optimizing the content and style representations of the generated image to match those of the content and style images, respectively. Image in painting is the task of filling in missing or damaged parts of an image. Deep learning models, particularly GANs, have been used for image in painting with impressive results. These models learn to generate plausible content for the missing regions based on the surrounding context. Image in painting has applications in photo restoration, editing, and object removal. Super-resolution aims to increase the resolution of an image, generating a high-resolution image from a low-resolution input. Deep learning models, such as super-resolution convolutional neural networks, SRCNNs, and enhanced deep residual networks for super-resolution, EDSR, have achieved state-of-the-art results in super-resolution. These models learn a mapping from low-resolution to high-resolution images and can generate details that are not present in the input. Deepfakes are synthetic media in which a person in an existing image or video is replaced with someone else's likeness. While the term is commonly associated with malicious uses, deep learning techniques for generating and manipulating images and videos also have legitimate applications, such as in entertainment and filmmaking. However, the potential for misuse of these technologies raises significant ethical considerations, particularly regarding consent, misinformation, and privacy. Video analysis is a challenging area of computer vision that deals with processing and understanding video data. This section will discuss various video analysis tasks and their applications. Object tracking in videos is the task of following one or more objects over time in a video sequence. This typically involves detecting the object in each frame and associating the detections across frames to maintain the object's identity. Object tracking has applications in surveillance, autonomous driving, and sports analysis. Challenges include dealing with occlusions, changes in appearance, and fast motion. Action recognition aims to identify and classify human actions in videos. This can involve recognizing simple actions, such as walking or running, or more complex activities, such as playing a sport or cooking a meal. Action recognition has applications in video surveillance, human-computer interaction, and content-based video retrieval. Deep learning models, such as 3D CNNs and two-stream networks, have achieved state-of-the-art results in action recognition. Video summarization is the task of creating a short summary of a longer video while preserving the most important or informative content. This can involve selecting key frames or generating a short clip that represents the main events or actions in the video. Video summarization has applications in video browsing, surveillance, and content-based video retrieval. Deep learning-based approaches to video summarization have shown promising results. Challenges in video analysis include the large amount of data, the temporal dimension, and the need to model motion and temporal relationships between frames. Videos are also often affected by variations in lighting, viewpoint, and scale, as well as occlusions and cluttered backgrounds. Dealing with these challenges requires specialized techniques and architectures that can effectively process and model video data. Applications of video analysis are numerous and span across various domains. In surveillance, video analysis can be used for real-time monitoring, anomaly detection, and person re-identification. In sports, it can be used for performance analysis, automatically generating highlights, and tracking players. In healthcare, video analysis can be used for patient monitoring, analyzing surgical procedures, and studying behavior. 3D computer vision is a subfield of computer vision that deals with analyzing and understanding 3D data, such as point clouds, meshes, and depth images. This section will introduce some key tasks and applications in 3D computer vision. Stereo vision is a technique for estimating depth information from two or more images taken from slightly different viewpoints. By finding corresponding points in the images and using triangulation, it is possible to estimate the 3D location of points in the scene. Depth estimation is a related task that aims to estimate the distance from the camera to each point in the scene. Depth information can be represented as a depth map or a point cloud. Structure from motion, SFM, is a technique for reconstructing the 3D structure of a scene from a set of 2D images taken from different viewpoints. SFM involves finding corresponding points across multiple images, estimating the camera poses, position and orientation, for each image, and then triangulating the 3D positions of the points. SFM is widely used in applications such as 3D modeling, augmented reality, and visual effects. Point clouds are a common representation for 3D data. A point cloud is a set of 3D points, typically represented by their x, y, z coordinates, and may also include additional information such as color or intensity. Point clouds can be obtained from various sensors, such as LiDAR or depth cameras, or generated from multiple images using techniques like SFM. 3D reconstruction aims to create a 3D model of an object or scene from a set of point clouds or images. 3D computer vision has numerous applications. In robotics, 3D vision enables robots to perceive and interact with their environment in 3D, allowing for tasks such as object manipulation, navigation, and mapping. In autonomous driving, 3D vision is used to perceive the 3D structure of the road and surrounding environment, detect obstacles, and plan paths. In augmented reality, 3D vision is used to track the user's viewpoint and overlay virtual objects onto the real world. Challenges in 3D computer vision include dealing with the large size and complexity of 3D data, the need for accurate calibration and registration of sensors, and the computational cost of processing 3D data. Other challenges include handling occlusions, dealing with variations in lighting and texture, and reconstructing accurate and complete 3D models from incomplete or noisy data. Deep learning techniques, such as PointNet and 3D CNNs, are increasingly being applied to 3D computer vision tasks. Real-world applications and case studies in computer vision. In this final section of Lesson 12, we will explore some real-world applications and case studies of computer vision to illustrate the impact and versatility of this field across various domains. Medical image analysis is a significant application area for computer vision. Computer vision techniques are used to analyze medical images, such as X-rays, CT scans, MRI scans, and ultrasound images, to assist in the diagnosis and treatment of diseases. For example, deep learning models have been developed to detect and classify tumors in medical images, often with accuracy comparable to or surpassing that of human experts. Computer vision is also used for tasks such as cell segmentation, organ detection, and image-guided surgery. Autonomous driving is another area that heavily relies on computer vision. Self-driving cars use computer vision algorithms to process data from cameras and other sensors to perceive their environment, detect objects such as pedestrians, vehicles, and traffic signs, and make driving decisions. Computer vision is used for tasks such as lane detection, object tracking, depth estimation, and scene understanding. The development of reliable and robust computer vision systems is crucial for the safety and success of autonomous driving technology. Surveillance and security applications often employ computer vision techniques for tasks such as facial recognition, object detection, and anomaly detection. Facial recognition systems are used for identifying individuals in images or videos, with applications ranging from unlocking smartphones to law enforcement. Object detection and tracking can be used to monitor public spaces for suspicious activities or objects. Anomaly detection can help identify unusual events or behaviors that may require attention. In retail, computer vision is used for tasks such as product recognition, shelf monitoring, and customer behavior analysis. Computer vision systems can automatically identify products on shelves, track inventory levels, and detect misplaced or out-of-stock items. They can also analyze customer behavior in stores, such as foot traffic patterns and dwell time, to optimize store layout and product placement. Some retailers are experimenting with cashierless checkout systems that use computer vision to automatically track items that customers pick up and charge them accordingly. Agriculture is another domain where computer vision is making an impact. Computer vision systems are used for tasks such as crop monitoring, yield estimation, and weed detection. Drones equipped with cameras and computer vision algorithms can fly over fields and capture images that are then analyzed to assess crop health, detect stress or disease, and estimate yield. Computer vision can also be used to guide autonomous agricultural robots for tasks such as planting, spraying, and harvesting. These are just a few examples of the many real-world applications of computer vision. As computer vision techniques continue to advance, driven by progress in deep learning and the availability of large-scale visual datasets, we can expect to see even more transformative applications emerge in the coming years. Computer vision has the potential to revolutionize many aspects of our lives, from healthcare and transportation to manufacturing and entertainment. This concludes our exploration of computer vision in Lesson 12. We have covered the fundamentals of computer vision, including image representation, basic image operations, and feature detection and extraction. We delved into key computer vision tasks such as image classification, object detection, image segmentation, image generation and manipulation, and video analysis. We also touched upon the emerging field of 3D computer vision. Throughout the lesson, we discussed various techniques and algorithms, with a particular emphasis on deep learning-based approaches, which have driven much of the recent progress in the field. Finally, we examined a range of real-world applications and case studies that demonstrate the transformative impact of computer vision across diverse domains. Computer vision is a rapidly evolving field with immense potential to address real-world challenges and create new opportunities. As you continue your journey in machine learning, keep in mind that the principles and techniques you have learned in this lesson form a strong foundation for further exploration and innovation in this exciting area. The field is constantly evolving, so it's important to stay updated. Lesson 13, Time Series Analysis and Forecasting. Introduction to Time Series Data. In this lesson, we will explore the fascinating world of time series analysis and forecasting. Time series data is ubiquitous, appearing in domains such as finance, economics, retail, meteorology, and many others. Understanding and modeling time series data is crucial for making informed decisions and predictions in these areas. Time series data is a sequence of data points collected or recorded over time, typically at regular intervals. Examples include stock prices, daily temperatures, monthly sales figures, and annual GDP. The defining characteristic of time series data is that the observations are ordered chronologically, and there may be dependencies between observations at different time points. Time series data is different from cross-sectional data, which consists of observations on multiple entities at a single point in time. In cross-sectional data, the ordering of observations is typically not important. In contrast, the temporal ordering of observations is crucial in time series data, as it often contains valuable information about trends, patterns, and dependencies. Time series data can often be decomposed into several components: trend, seasonality, cycles, and noise. The trend component represents the long-term direction of the data, e.g., increasing or decreasing. The seasonality component represents regular, repeating patterns within a fixed period, e.g., daily, weekly, or yearly. Cycles are longer-term patterns that are not of a fixed period. The noise component represents random fluctuations that cannot be explained by the other components. Stationarity is an important concept in time series analysis. A time series is said to be stationary if its statistical properties, such as the mean, variance, and autocorrelation, do not change over time. Many time series models assume stationarity, and non-stationary data often needs to be transformed before modeling. Non-stationarity can manifest as trends, seasonality, or changing variance over time. Time series analysis has numerous applications, including financial forecasting, e.g., stock prices, exchange rates, demand forecasting in retail and supply chain management, energy consumption forecasting, weather forecasting, and predictive maintenance in manufacturing. It is a powerful tool for understanding past behavior, identifying patterns, and making predictions about the future. Time series decomposition. Time series decomposition is a technique for separating a time series into its constituent components: trend, seasonality, cycles, and noise. This can help in understanding the underlying patterns in the data and can also be useful for pre-processing the data before applying forecasting models. Additive and multiplicative decomposition are two common approaches to time series decomposition. In additive decomposition, the time series is assumed to be the sum of its components, y, t, equals trend, t, plus seasonality, t, plus cycles, t, plus noise, t. In multiplicative decomposition, the time series is assumed to be the product of its components, y, t, equals trend, t, asterisk seasonality, t, asterisk cycles, t, asterisk noise, t. The choice between additive and multiplicative decomposition depends on the nature of the time series and whether the magnitude of the seasonal fluctuations changes with the level of the trend. Moving averages are often used to estimate the trend component of a time series. A moving average smooths out short-term fluctuations and highlights longer-term trends. A simple moving average of order k is calculated by taking the average of k consecutive observations. A centered moving average centers the average at the middle of the window. Seasonal decomposition using STL, seasonal and trend decomposition using LUS, is a powerful and versatile method for decomposing time series data. STL uses LUS, locally estimated scatterplot smoothing, to decompose the time series into trend, seasonal, and remainder components. It can handle any type of seasonality and allows the seasonal component to change over time. It is also robust to outliers. Identifying and handling outliers in time series is an important step in data preprocessing. Outliers can distort the results of time series analysis and forecasting. They can be identified using statistical methods, such as calculating z-scores or using the interquartile range, or by visual inspection of the time series plot. Outliers can be removed, replaced with imputed values, or treated using robust methods that are less sensitive to outliers. Visualizing time series data is crucial for understanding its patterns and characteristics. Time series plots, which show the data values plotted against time, are the most basic and important visualization tool. Other useful visualizations include autocorrelation plots, partial autocorrelation plots, and seasonal subseries plots. Visualization can help to identify trends, seasonality, cycles, outliers, and other patterns in the data. Basic time series models. This section will introduce some fundamental time series models that are widely used for analyzing and forecasting time series data. These models capture different aspects of the temporal dependencies in the data. Autoregressive, AR, models are a class of linear models that assume the current value of a time series is a linear combination of its past values, plus a random error term. An AR, P, model uses the P previous values to predict the current value. The order P can be determined using techniques like the partial autocorrelation function, PACF. Moving average, MA, models are another class of linear models that assume the current value of a time series is a linear combination of past error terms. An MA, Q, model uses the Q previous error terms to predict the current value. The order Q can be determined using techniques like the autocorrelation function, ACF. Autoregressive moving average, ARMA, models combine AR and MA models to capture both autoregressive and moving average components in the data. An ARMA, P, Q, model includes P autoregressive terms and Q moving average terms. ARMA models are more flexible than AR or MA models alone but require careful identification of the appropriate orders P and Q. Autoregressive integrated moving average, ARIMA, models are an extension of ARMA models that can handle non-stationary time series. The I in ARIMA stands for integrated, which refers to differencing the time series to make it stationary. An ARIMA, P, D, Q, model includes P autoregressive terms, D differencing operations, and Q moving average terms. ARIMA models are widely used for forecasting non-stationary time series data. Model identification and selection are crucial steps in time series modeling. The autocorrelation function, ACF, and partial autocorrelation function, PACF, are commonly used to identify the appropriate orders of AR, MA, and ARIMA models. The ACF measures the correlation between a time series and its lagged values, while the PACF measures the correlation between a time series and its lagged values after removing the effects of the intervening lags. Model selection criteria, such as the Akaika Information Criterion, AIC, and the Bayesian Information Criterion, BIC, can also be used to choose the best model. Time series forecasting. Time series forecasting is the process of using a model to predict future values of a time series based on its past values and, potentially, other relevant information. This section will discuss various techniques for time series forecasting and how to evaluate forecast accuracy. Evaluating forecast accuracy is crucial for assessing the performance of forecasting models and for comparing different models. Common metrics for evaluating forecast accuracy include mean absolute error (MAE), mean squared error (MSE), root mean squared error (RMSE), and mean absolute percentage error (MAPE). These metrics measure the difference between the forecasted values and the actual values. The choice of metric depends on the specific application and the desired properties of the forecast error measure. Naive forecasting methods are simple baseline methods that can be used to benchmark the performance of more complex models. The simplest naive method is to use the last observed value as the forecast for all future values. Another naive method is the seasonal naive method, which uses the value from the same period in the previous season as the forecast. These methods can be surprisingly effective for some types of time series data. Exponential smoothing methods are a family of forecasting methods that use weighted averages of past observations to make forecasts, with the weights decaying exponentially as the observations get older. Simple exponential smoothing is suitable for data with no trend or seasonality. Holt's method extends simple exponential smoothing to handle data with a trend. Holt-Winters method further extends Holt's method to handle data with both trend and seasonality. Forecasting with ARIMA models involves several steps. First, the time series is checked for stationarity, and differencing is applied if necessary to make it stationary. Second, the orders of the AR and MA components, P and Q, are identified using the ACF and PACF. Third, the model parameters are estimated using maximum likelihood estimation. Finally, the model is used to generate forecasts for future time periods. ARIMA models can be extended to include seasonality, SARIMA models, and exogenous variables, Aramax models. Handling seasonality in forecasts is important for many types of time series data. Seasonality can be incorporated into forecasting models in several ways. In exponential smoothing, Holt-Winters method explicitly models seasonality. In ARIMA models, seasonal differencing and seasonal AR and MA terms can be used. Machine learning models can handle seasonality by including appropriate features, such as time-based features or lagged values. Properly accounting for seasonality can significantly improve forecast accuracy. Feature engineering for time series. Feature engineering plays a crucial role in time series analysis and forecasting, particularly when using machine learning models. This section will discuss various techniques for creating features from time series data. Lag features are one of the most common and important types of features for time series. A lag feature is simply the value of the time series at a previous time point. For example, the value of the time series at time t1, t2, etc., can be used as features to predict the value at time t. Lag features can capture the autocorrelation and temporal dependencies in the time series. Rolling window features involve computing statistics over a sliding window of past values. Common examples include the rolling mean, rolling standard deviation, rolling minimum, and rolling maximum. These features can capture recent trends and patterns in the data and can be particularly useful when the statistical properties of the time series are changing over time. The window size is an important parameter that needs to be chosen carefully. Time-based features can be created from the timestamp of each observation. Examples include the hour of the day, day of the week, day of the month, month of the year, and year. These features can capture cyclical patterns and seasonality in the data. For example, energy consumption might be higher during certain hours of the day or certain months of the year. Holiday indicators can also be useful time-based features. Extracting features from date and time components can be particularly important when dealing with data that has multiple seasonal patterns. For example, a time series might have daily, weekly, and yearly seasonality. By extracting features such as the hour of the day, day of the week, and month of the year, we can capture these different seasonal patterns and improve the accuracy of our models. Handling missing data in time series is an important aspect of data preprocessing. Missing data can arise due to various reasons, such as sensor failures, data entry errors, or irregular sampling. Techniques for handling missing data include imputation methods, such as forward fill, backward fill, or interpolation, and model-based approaches that can handle missing data directly. The choice of method depends on the nature of the missing data and the specific application. Machine learning for time series forecasting. While traditional time series models like ARIMA and exponential smoothing are powerful and widely used, machine learning techniques have also been successfully applied to time series forecasting. This section will discuss how machine learning models can be used for forecasting and the challenges involved. Using regression models for forecasting is a common approach in machine learning. The idea is to formulate the forecasting problem as a regression problem, where the input features are lagged values of the time series, rolling window statistics, and time-based features, and the target variable is the future value of the time series that we want to predict. Any regression algorithm, such as linear regression, support vector regression, or tree-based models, can be used for this purpose. Feature engineering for machine learning models is crucial for achieving good forecasting performance. As discussed in the previous section, lag features, rolling window features, and time-based features can capture important temporal patterns and dependencies in the data. Feature selection techniques can be used to identify the most relevant features for forecasting. Domain knowledge can also play an important role in guiding the feature engineering process. Tree-based models such as random forests and gradient boosting machines have been successfully applied to time series forecasting. These models can capture nonlinear relationships and interactions between features and can handle a large number of features. They are also relatively robust to outliers and missing data. Tree-based models have been shown to achieve state-of-the-art performance on various forecasting benchmarks. Support vector regression, SVR, is another machine learning technique that has been used for time series forecasting. SVR is an extension of support vector machines, SVMs, to regression problems. It aims to find a function that approximates the relationship between the input features and the target variable while minimizing the error and, at the same time, staying within a certain margin of tolerance. SVR can handle nonlinear relationships by using a kernel trick. Challenges in using machine learning for forecasting include the need for careful feature engineering, the risk of overfitting, and the difficulty of capturing complex temporal dependencies. Unlike traditional time series models, many machine learning algorithms do not explicitly model the temporal structure of the data. Therefore, it is crucial to engineer features that capture this structure. Cross-validation techniques that respect the temporal order of the data, such as time series cross-validation, should be used for model evaluation and selection. Deep learning for time series forecasting. Deep learning models, particularly recurrent neural networks, RNNs, and convolutional neural networks, CNNs, have shown great promise for time series forecasting. This section will discuss how these models can be applied to time series data and their advantages and limitations. Recurrent neural networks, RNNs, are a natural choice for modeling sequential data like time series. RNNs have internal memory that allows them to maintain information about previous inputs in the sequence, making them well-suited for capturing temporal dependencies. Long short-term memory, LSTM, networks are a popular type of RNN that use gating mechanisms to control the flow of information through the network, enabling them to learn long-range dependencies more effectively. Convolutional neural networks, CNNs, which are typically used for image data, can also be applied to time series forecasting. 1D convolutions can be used to extract features from the time series by sliding a filter along the temporal dimension. CNNs can be particularly effective when there are local patterns or motifs in the time series that are important for forecasting. They can also be computationally more efficient than RNNs for long sequences. Sequence-to-sequence models are a type of neural network architecture that is often used for tasks like machine translation, where the input and output are both sequences. These models can also be applied to time series forecasting, where the input is a sequence of past values, and the output is a sequence of future values. Sequence-to-sequence models typically consist of an encoder network that processes the input sequence and a decoder network that generates the output sequence. Hybrid models that combine different types of neural networks have also been proposed for time series forecasting. For example, A CNN-LSTM model might use convolutional layers to extract local features from the time series and recurrent layers to capture temporal dependencies. Hybrid models can potentially leverage the strengths of different architectures and capture complex patterns in the data. Deep learning models offer several advantages for time series forecasting. They can automatically learn hierarchical representations of the data, reducing the need for manual feature engineering. They can also capture complex nonlinear relationships and interactions between variables. However, deep learning models also have limitations. They typically require large amounts of data to train effectively, can be computationally expensive, and can be difficult to interpret. Advanced time series models. In addition to the basic time series models and machine learning techniques discussed earlier, there are several advanced models that can be used for analyzing and forecasting time series data. This section will provide an overview of some of these advanced models. Vector autoregression, VR, models are used for modeling and forecasting multivariate time series, where multiple time series are analyzed together. VR models are an extension of autoregressive, AR, models to the multivariate case. They capture the linear interdependencies among multiple time series by modeling each variable as a linear function of the past values of all variables in the system. State space models are a general framework for modeling time series data that can represent a wide range of models, including ARIMA models and exponential smoothing models. State space models consist of two equations: a measurement equation that relates the observed data to a hidden state vector, and a state equation that describes the evolution of the hidden state over time. The Kalman filter is a common algorithm for estimating the hidden state in state space models. Dynamic linear models are a type of state space model where the state vector is assumed to evolve linearly over time, and the measurement equation is also linear. Dynamic linear models can be used to model trends, seasonality, and other patterns in time series data. They are particularly useful when the underlying structure of the time series is believed to change over time. Hidden Markov models, HMMs, are used for modeling time series data where the underlying system is assumed to be a Markov process with hidden states. HMMs have been applied to various domains, including speech recognition, bioinformatics, and finance. In an HMM, the observed data is assumed to be generated by a hidden state that follows a Markov process. The model parameters can be estimated using the Baum-Welch algorithm, and the Viterbi algorithm can be used to find the most likely sequence of hidden states. Gaussian processes are a powerful nonparametric approach to modeling time series data. A Gaussian process defines a probability distribution over functions, where any finite set of function values is assumed to follow a multivariate Gaussian distribution. Gaussian processes can be used for regression, classification, and forecasting tasks. They are particularly useful when dealing with small datasets or when uncertainty quantification is important. However, they can be computationally expensive for large datasets. Time series anomaly detection. Time series anomaly detection is the task of identifying unusual patterns or outliers in time series data that do not conform to the expected behavior. This section will discuss various approaches to anomaly detection in time series data. Statistical approaches to anomaly detection often involve modeling the distribution of the data and identifying data points that have a low probability of being generated by that distribution. For example, one might assume that the data follows a Gaussian distribution and flag data points that are more than a certain number of standard deviations away from the mean as anomalies. Time series decomposition techniques can also be used for anomaly detection by identifying points that deviate significantly from the expected trend or seasonal pattern. Machine learning approaches to anomaly detection in time series data often involve training a model on normal data and then using the model to identify deviations from the learned patterns. One-class SVMs and isolation forests, which we discussed in the context of unsupervised learning, can be applied to time series anomaly detection. Clustering techniques can also be used to identify anomalies as points that do not belong to any cluster or form their own small clusters. Using clustering for anomaly detection can be effective when anomalies form distinct clusters that are separate from the normal data points. Algorithms like DISCAN, which can identify noise points that do not belong to any cluster, are particularly useful for this purpose. Clustering can also be used in combination with other techniques, such as using the distance to the cluster centroid as a feature for anomaly detection. Deep learning approaches for anomaly detection have gained popularity in recent years, particularly for complex, high-dimensional time series data. Autoencoders, which learn to reconstruct normal data, can be used to detect anomalies by identifying points with high reconstruction error. Recurrent neural networks, RNNs, such as LSTMs, can be trained to predict the next value in a time series, and deviations from the predicted values can be used to identify anomalies. Generative adversarial networks, GANs, have also been applied to anomaly detection by learning the distribution of normal data and identifying points that are unlikely to be generated by the learned distribution. Applications in fraud detection, system monitoring, and predictive maintenance are numerous. In fraud detection, time series anomaly detection can be used to identify unusual patterns in financial transactions, such as credit card purchases or bank transfers, that might indicate fraudulent activity. In system monitoring, it can be used to detect abnormal behavior in server metrics, network traffic, or sensor readings, which might indicate a system failure or a security breach. In predictive maintenance, anomaly detection can be used to identify early signs of equipment failure by analyzing time series data from sensors monitoring the equipment's condition. Real-world applications and case studies in time series analysis. In this final section of Lesson 13, we will explore some real-world applications and case studies of time series analysis and forecasting to illustrate the practical impact and versatility of these techniques across various domains. Financial forecasting is a prominent application area for time series analysis. Predicting stock prices, exchange rates, and other financial instruments is a challenging but potentially lucrative task. Time series models like ARIMA, GRCH, generalized autoregressive conditional heteroskedasticity, and machine learning models like LSTM networks are used to model and forecast financial time series. Feature engineering often plays a crucial role in financial forecasting, with features such as technical indicators, sentiment scores from news articles, and macroeconomic variables being used to improve forecasting accuracy. Demand forecasting in retail and supply chain management is another important application. Retailers and manufacturers use time series forecasting to predict future demand for their products, which helps them to optimize inventory levels, production schedules, and pricing strategies. Accurate demand forecasting can lead to significant cost savings, improved customer satisfaction, and increased revenue. Machine learning models, such as tree-based models and deep learning models, are increasingly being used for demand forecasting due to their ability to handle large datasets and complex, nonlinear relationships. Energy consumption forecasting is crucial for energy providers, grid operators, and policymakers. Time series models are used to predict future energy demand at various levels of aggregation, from individual households to entire countries. Accurate energy forecasts are essential for ensuring grid stability, optimizing energy production and distribution, and planning for future energy needs. Features such as weather data, time-based features, and calendar information, e.g., holidays, are often used in energy forecasting models. Weather forecasting is a classic application of time series analysis that has a significant impact on many aspects of our lives. Numerical weather prediction, NWP, models, which are based on physical models of the atmosphere, are the primary tool for weather forecasting. However, statistical and machine learning models are increasingly being used to improve the accuracy of NWP models, to forecast specific weather variables, and to generate probabilistic forecasts. Deep learning models, in particular, have shown promise in improving the accuracy of short-term forecasts and in capturing complex, nonlinear relationships in weather data. Predictive maintenance in manufacturing is an emerging application of time series analysis that aims to predict equipment failures before they occur. By analyzing time series data from sensors monitoring the condition of equipment, such as vibration, temperature, and pressure, machine learning models can identify patterns that indicate an impending failure. This allows maintenance to be scheduled proactively, reducing downtime, preventing costly repairs, and improving overall efficiency. Anomaly detection techniques are often used in predictive maintenance to identify unusual patterns that may signal a developing fault. These are just a few examples of the many real-world applications of time series analysis and forecasting. As the amount of time-dependent data continues to grow across various domains, the importance of these techniques will only increase. By mastering the concepts and methods covered in this lesson, you will be well equipped to tackle a wide range of time series problems and contribute to the growing field of time series analysis. This concludes our exploration of time series analysis and forecasting in Lesson 13. We have covered the fundamentals of time series data, including its unique characteristics and components. We delved into various techniques for time series decomposition, basic time series models like AR, MA, ARMA, and ARIMA, and methods for evaluating forecast accuracy. We also discussed the importance of feature engineering for time series and how machine learning and deep learning models can be applied to forecasting tasks. Furthermore, we explored advanced time series models and techniques for anomaly detection. Finally, we examined real-world applications and case studies to illustrate the practical impact of time series analysis across diverse domains such as finance, retail, energy, meteorology, and manufacturing. The ability to analyze and forecast time series data is a valuable skill in today's data-driven world, with applications that span across many industries and research areas. As you continue your machine learning journey, remember that time series analysis is a rich and evolving field with ongoing research and development. Keep exploring new techniques, experimenting with different models, and applying what you've learned to real-world problems. The knowledge and skills you've gained in this lesson will serve as a strong foundation for your future endeavors in time series analysis and forecasting. Lesson 14, Recommender Systems. Introduction to Recommender Systems. In this lesson, we will delve into the fascinating world of recommender systems, a specialized class of machine learning systems that aim to predict the preferences or ratings that a user would give to an item. Recommender systems have become ubiquitous in today's digital landscape, playing a crucial role in e-commerce, entertainment, social media, and many other domains. Recommender systems are information filtering systems that seek to predict the rating or preference a user would give to an item. They help users discover items they might like, based on their past behavior, the behavior of similar users, or the characteristics of the items themselves. The purpose of recommender systems is to provide personalized suggestions that enhance user experience, increase engagement, and drive sales or other desired outcomes. There are several types of recommender systems, broadly classified as collaborative filtering, content-based, and hybrid approaches. Collaborative filtering methods make recommendations based on the past behavior of users and items, such as ratings, purchases, or clicks. Content-based methods use information about the items themselves, such as their description, category, or features, to make recommendations. Hybrid approaches combine both collaborative and content-based techniques to leverage their complementary strengths. Building effective recommender systems presents several challenges. These include the cold start problem, how to make recommendations for new users or new items with little or no data, data sparsity. Most users interact with only a small fraction of items, scalability, handling large datasets of users and items, and the diversity-accuracy trade-off, balancing the accuracy of recommendations with their diversity and novelty. Evaluation metrics for recommender systems differ from those used in traditional classification or regression tasks. Common metrics include precision at K, recall at K, mean average precision, MAP, normalized discounted cumulative gain, NDCG, and root mean squared error, RMSE. These metrics focus on the ranking quality of recommendations and the ability to recommend relevant items in the top positions. Recommender systems have become an integral part of many online services. In e-commerce, they are used to recommend products to users, such as Amazon's "customers who bought this item also bought" feature. In entertainment, they are used to suggest movies, music, or books, such as Netflix's movie recommendations and Spotify's music discovery features. Recommender systems are also used in news and article recommendation, social network recommendations, e.g., friend suggestions, and personalized advertising. Collaborative filtering is a widely used approach in recommender systems that leverages the collective behavior of users to make recommendations. It is based on the assumption that users who have agreed in the past will agree in the future, and that users will like similar items to those they have liked before. User-based collaborative filtering is a type of collaborative filtering that makes recommendations based on the preferences of similar users. The process involves finding users who have similar tastes to the target user, e.g., have rated similar items highly, and then recommending items that these similar users have liked but the target user has not yet seen. The similarity between users is typically measured using metrics like Pearson correlation or cosine similarity. Item-based collaborative filtering is another type of collaborative filtering that makes recommendations based on the similarity between items. It recommends items that are similar to the items the user has liked in the past. Item similarity is typically computed based on the ratings given to the items by users. For example, if many users who liked item A also liked item B, then items A and B are considered similar. Amazon's "customers who bought this item also bought" feature is an example of item-based collaborative filtering. Matrix factorization techniques are a powerful class of collaborative filtering methods that decompose the user-item interaction matrix, e.g., ratings matrix, into lower-dimensional matrices that capture the latent factors underlying user preferences and item characteristics. Singular value decomposition, SVD, and alternating least squares, ALS, are commonly used matrix factorization techniques. These methods can handle sparse data and often provide more accurate recommendations than neighborhood-based methods. Neighborhood-based methods, also known as memory-based methods, are a class of collaborative filtering techniques that make recommendations based on the ratings or preferences of a user's neighbors, either similar users or similar items. These methods are relatively simple to implement and interpret but can suffer from scalability issues and may not be as accurate as model-based methods like matrix factorization. The cold start problem is a significant challenge in collaborative filtering. It refers to the difficulty of making recommendations for new users or new items that have little or no interaction data. For new users, there is no history of their preferences, making it difficult to find similar users or recommend relevant items. For new items, there are no ratings or interactions to compare them to other items. Various techniques have been proposed to address the cold start problem, including content-based filtering for new items and demographic filtering for new users. Content-based filtering is another major approach to building recommender systems. Unlike collaborative filtering, which relies on user-item interactions, content-based filtering uses information about the items themselves and the user's preferences for those items to make recommendations. Representing items using content features is a crucial aspect of content-based filtering. Items are described by a set of features that capture their characteristics. For example, in a movie recommender system, features might include the genre, director, actors, plot keywords, and average rating. In a news recommender system, features might include the article's topic, keywords, source, and author. The choice of features depends on the specific domain and the type of items being recommended. Building user profiles based on content preferences is another key component of content-based filtering. A user profile represents the user's preferences and interests in terms of the item features. For example, a user profile might indicate that a user likes action movies directed by Christopher Nolan and starring Leonardo DiCaprio. User profiles can be created explicitly, by asking users to rate or provide feedback on features, or implicitly, by inferring preferences from user behavior, e.g., items purchased, viewed, or rated highly. TF-IDF, term frequency inverse document frequency, is a technique often used in content-based filtering for text-based items, such as articles or product descriptions. TF-IDF weights each term based on its frequency in an item, term frequency, and its inverse frequency across all items, inverse document frequency. This gives higher weight to terms that are frequent in a specific item but rare across the entire collection, making them more discriminative for that item. Content-based filtering has both advantages and disadvantages. One advantage is that it can recommend new items that have not yet been rated or viewed by any user, addressing the item cold start problem. It can also provide explanations for recommendations based on the content features. However, content-based filtering is limited by the quality and availability of content features. It may also suffer from overspecialization, recommending items that are too similar to what the user has already seen, and may fail to capture complex user preferences that are not reflected in the content features. Combining content-based and collaborative filtering is a common approach to leverage the strengths of both methods. This can be done in various ways, such as using content-based filtering to generate features for collaborative filtering, using collaborative filtering to refine content-based recommendations, or building hybrid models that incorporate both content and interaction data. Hybrid approaches can often outperform either method alone and can help to mitigate the limitations of each approach. Hybrid recommender systems combine multiple recommendation techniques, typically collaborative filtering and content-based filtering, to leverage their complementary strengths and overcome their individual limitations. This section will discuss different approaches to building hybrid recommender systems. The most straightforward way to build a hybrid system is to combine the predictions of separate collaborative filtering and content-based models. This can be done by taking a weighted average of the predictions or by using a switching mechanism that selects the most appropriate model based on the specific user or item. The weights or switching rules can be learned from data or set based on domain knowledge. Weighted hybrid methods assign a weight to each recommendation technique and combine their predictions accordingly. For example, a hybrid movie recommender system might assign a weight of 0.7 to collaborative filtering and 0.3 to content-based filtering. The weights can be fixed or adapted based on the user, item, or context. Determining the optimal weights is a key challenge in building weighted hybrid systems. Switching hybrid methods use a criterion to decide which recommendation technique to use for a given user or item. For example, the system might use content-based filtering for new items with little or no interaction data and switch to collaborative filtering once enough interaction data becomes available. The switching criterion can be based on factors such as the amount of data available, the confidence of the predictions, or the user's context. Cascade hybrid methods involve using one recommendation technique to refine the results of another. For example, a content-based filtering method might be used to generate an initial set of candidate items, which are then re-ranked by a collaborative filtering method. This approach can leverage the strengths of each technique while mitigating their weaknesses. For instance, content-based filtering can help to address the cold start problem, while collaborative filtering can improve the accuracy and personalization of recommendations. The benefits of hybrid approaches are numerous. They can improve the overall accuracy and robustness of recommendations by combining the strengths of different techniques. They can also address the limitations of individual methods, such as the cold start problem and data sparsity. Hybrid methods can provide more diverse and novel recommendations by incorporating both collaborative and content information. However, building and tuning hybrid systems can be more complex than using a single approach. Matrix factorization for recommendation. Matrix factorization is a powerful class of collaborative filtering techniques that has achieved state-of-the-art performance in many recommendation tasks. This section will discuss various matrix factorization methods and their application to recommender systems. The basic idea behind matrix factorization is to decompose the user-item interaction matrix, e.g., ratings matrix, into the product of two lower-dimensional matrices, a user feature matrix and an item feature matrix. These matrices capture the latent factors that underlie user preferences and item characteristics. For example, in a movie recommendation setting, the latent factors might correspond to genres like action, comedy, or drama. Singular value decomposition, SVD, is a classic matrix factorization technique that decomposes a matrix into three matrices, U, sigma, and V to the power of T, where U and V are orthogonal matrices and sigma is a diagonal matrix containing the singular values. SVD can be used for dimensionality reduction and to identify latent factors in the data. However, applying SVD directly to the user item matrix can be challenging due to missing values. Not all users have rated all items. Alternating least squares, ALS, is an iterative optimization algorithm that is commonly used for matrix factorization in recommender systems. ALS alternates between fixing the user feature matrix and updating the item feature matrix, and vice versa. Each step involves solving a least squares problem, which can be done efficiently. ALS can handle missing values and is more scalable than traditional SVD. Non-negative matrix factorization, NMF, is a matrix factorization technique that imposes non-negativity constraints on the factor matrices. This can lead to more interpretable factors and can be particularly useful when dealing with non-negative data, such as counts or ratings. NMF can be solved using iterative algorithms, such as multiplicative update rules. Probabilistic matrix factorization, PMF, is a Bayesian approach to matrix factorization that models the user-item interactions using probability distributions. PMF assumes that the observed ratings are drawn from a Gaussian distribution, with the mean being the dot product of the corresponding user and item latent vectors. PMF can incorporate prior knowledge and provide uncertainty estimates for the learned factors. Handling implicit feedback data is an important consideration in many recommender systems. Implicit feedback data consists of user interactions that are not explicit ratings but can be used as indicators of preference, such as purchases, clicks, views, or listens. Matrix factorization techniques can be adapted to handle implicit feedback data by treating the data as binary, e.g., 1 if the user interacted with the item, 0 otherwise, or by using confidence weights that reflect the strength of the observed interactions. Deep learning for recommender systems. Deep learning has emerged as a powerful approach for building recommender systems, offering the ability to learn complex, nonlinear relationships between users and items. This section will explore various deep learning architectures and techniques used in recommendation. Using neural networks for collaborative filtering is a natural extension of matrix factorization. Instead of learning linear factors, neural networks can learn nonlinear representations of users and items. A simple neural collaborative filtering model might consist of an embedding layer for users and items, followed by one or more fully connected layers that combine the embeddings to predict the interaction. Autoencoders have been successfully applied to recommendation tasks. An autoencoder can be trained to reconstruct the user-item interaction matrix, learning a compressed representation of users and items in the process. These models can leverage the strengths of different architectures and potentially achieve better performance than single architecture models. Evaluating recommender systems. Evaluating the performance of recommender systems is crucial for comparing different models, tuning hyperparameters, and ensuring that the system meets the desired objectives. This section will discuss various evaluation metrics and methodologies for recommender systems. Offline evaluation metrics are used to evaluate recommender systems using historical data. Common metrics include precision at K, recall at K, mean average precision, MAP, and normalized discounted cumulative gain, NDCG. Precision at K measures the proportion of recommended items in the top K that are actually relevant. Recall at K measures the proportion of relevant items that are in the top K recommended items. MAP and NDCG take into account the ranking of the recommended items, giving more weight to relevant items that are ranked higher. Online evaluation involves deploying the recommender system in a live environment and measuring its performance based on real user interactions. A/B testing is a common technique for online evaluation, where different versions of the system, e.g., with different recommendation algorithms, are presented to different groups of users, and their behavior is compared. Metrics such as click-through rate, conversion rate, and user engagement can be used to assess the effectiveness of the recommender system in a live setting. User studies and qualitative evaluation can provide valuable insights into the user experience and perceived usefulness of a recommender system. Surveys, interviews, and focus groups can be used to gather feedback from users about their satisfaction with the recommendations, their understanding of the system, and their suggestions for improvement. Qualitative evaluation can complement quantitative metrics and help to identify aspects of the system that may not be captured by offline or online metrics. Challenges in evaluating recommender systems include the difficulty of obtaining ground truth data, the sparsity of user-item interactions, and the dynamic nature of user preferences. Offline evaluation may not always accurately reflect online performance due to differences between the training data and the live environment. Furthermore, evaluation metrics that focus solely on accuracy may not capture other important aspects of recommender systems, such as diversity, novelty, and serendipity. Beyond accuracy, it is important to consider other dimensions of recommender system performance, such as diversity, novelty, and serendipity. Diversity refers to the variety of items recommended to a user. Novelty refers to the degree to which the recommended items are unknown or unexpected to the user. Serendipity refers to the ability of the system to recommend items that the user finds surprisingly interesting or relevant. These aspects can significantly impact user satisfaction and engagement but are not always captured by traditional accuracy metrics. Addressing the cold start problem. The cold start problem is a significant challenge in recommender systems, referring to the difficulty of making recommendations for new users or new items that have little or no interaction data. This section will discuss various approaches for addressing the cold start problem. The cold start problem arises because many recommender systems, particularly those based on collaborative filtering, rely on historical user-item interactions to make recommendations. When a new user joins the system, there is no information about their preferences, making it difficult to provide personalized recommendations. Similarly, when a new item is added, there are no ratings or interactions to compare it to other items. Content-based filtering can be used to address the cold start problem for new items. Since content-based methods rely on item features rather than interaction data, they can generate recommendations for new items as long as their content features are available. For example, a new movie can be recommended based on its genre, director, or cast, even if no user has rated it yet. Demographic filtering can be used to address the cold start problem for new users. This approach involves collecting demographic information about users, such as age, gender, location, or occupation, and using this information to make initial recommendations. For example, new users might be shown popular items among users with similar demographics until more interaction data is collected. Hybrid approaches that combine collaborative filtering and content-based filtering can help to mitigate the cold start problem. For example, a hybrid system might use content-based filtering for new items and switch to collaborative filtering once enough interaction data is collected. Similarly, a hybrid system might use demographic information to make initial recommendations for new users and then transition to collaborative filtering as the user interacts with the system. Exploiting social connections and other side information can also help to address the cold start problem. For example, if a new user has friends or connections in the system, their preferences might be used to inform the initial recommendations for the new user. Other types of side information, such as user reviews, item descriptions, or knowledge graphs, can also be incorporated into the recommendation process to alleviate the cold start problem. Scalability and efficiency in recommender systems. As the number of users and items grows, recommender systems face significant challenges in terms of scalability and efficiency. This section will discuss these challenges and explore approaches for handling large-scale data and providing real-time recommendations. Challenges in scaling recommender systems include the need to process and store massive amounts of data, to compute recommendations quickly, and to handle a large number of concurrent users. As the user-item interaction matrix grows, the computational cost of many recommendation algorithms, particularly those based on matrix factorization or neighborhood methods, can become prohibitive. Furthermore, users expect fast and responsive recommendations, particularly in interactive settings. Approaches for handling large-scale data include using distributed computing frameworks like Apache Spark, which can partition the data and computations across a cluster of machines. Dimensionality reduction techniques, such as matrix factorization, can also help to reduce the size of the data and improve computational efficiency. Sampling techniques can be used to reduce the amount of data used for training or making recommendations, although care must be taken to ensure that the sample is representative. Efficient algorithms for matrix factorization have been developed to address the scalability challenges. Alternating least squares, ALS, is an iterative algorithm that can be parallelized and distributed, making it suitable for large-scale matrix factorization. Stochastic gradient descent, SGD, is another optimization algorithm that can be used for matrix factorization and can be applied in an online or mini-batch fashion, allowing it to handle streaming data or data that does not fit in memory. Real-time recommendations are crucial in many applications, such as e-commerce, news recommendation, and online advertising. Providing recommendations in real time requires efficient algorithms and infrastructure that can quickly process new user interactions and update recommendations accordingly. Approaches for real-time recommendation include using pre-computed recommendations, caching popular items, and using approximate nearest neighbor search techniques. Caching and indexing techniques can significantly improve the efficiency of recommender systems. Caching involves storing frequently accessed data, such as user profiles or item features, in a fast-access memory to reduce computation time. Indexing techniques, such as inverted indexes or locality-sensitive hashing, can be used to quickly retrieve relevant items or users based on their features or interactions. These techniques can help to reduce latency and improve the responsiveness of recommender systems. Real-world applications and case studies in recommender systems. In this final section of Lesson 14, we will explore some real-world applications and case studies of recommender systems to illustrate their impact and versatility across various domains. E-commerce is one of the most prominent application areas for recommender systems. Amazon, for example, uses recommender systems extensively to suggest products to users based on their browsing and purchase history, as well as the behavior of similar users. Amazon's customers who bought this item also bought and frequently bought together features are classic examples of item-based collaborative filtering. Recommender systems are also used in e-commerce for personalized search results, targeted advertising, and email marketing. Entertainment is another domain where recommender systems play a crucial role. Netflix uses recommender systems to suggest movies and TV shows to users based on their viewing history, ratings, and the preferences of similar users. Spotify uses similar techniques to recommend music tracks and create personalized playlists. These recommender systems enhance user engagement and satisfaction by helping users discover content they are likely to enjoy. News and article recommendations are important for helping users navigate the vast amount of online content and find articles that are relevant to their interests. News websites and aggregators often use a combination of collaborative filtering and content-based filtering to recommend articles. They may also incorporate factors such as the user's location, the time of day, and trending topics to provide timely and relevant recommendations. Social network recommendations are used to suggest friends, groups, or pages that users might be interested in. Facebook, for example, uses a variety of signals, including mutual friends, shared interests, and group memberships, to recommend potential connections. LinkedIn uses similar techniques to suggest jobs and professional connections. Recommender systems can also be used in social networks to recommend content, such as posts, articles, or videos, that users might find interesting. Personalized advertising is another important application of recommender systems. By analyzing user data, such as browsing history, demographics, and past purchases, advertisers can use recommender systems to target ads to users who are most likely to be interested in them. This can improve the effectiveness of advertising campaigns and provide a more relevant and engaging experience for users. Personalized advertising, however, also raises ethical concerns about privacy and the potential for manipulation. These are just a few examples of the many real-world applications of recommender systems. As data collection and analysis techniques continue to advance, and as machine learning algorithms become more sophisticated, we can expect to see even more innovative and impactful applications of recommender systems in the years to come. Recommender systems have the potential to transform many aspects of our lives, from the way we shop and consume entertainment to the way we connect with others and discover new information. This concludes our exploration of recommender systems in Lesson 14. We have covered the fundamental concepts of recommender systems, including the different types of recommendation approaches such as collaborative filtering, content-based filtering, and hybrid methods. We delved into matrix factorization techniques and discussed the use of deep learning in modern recommender systems. We also examined methods for evaluating recommender systems and addressed the cold start problem. Additionally, we explored the challenges of scalability and efficiency in large-scale recommender systems. Finally, we highlighted the diverse real-world applications of recommender systems in domains such as e-commerce, entertainment, news, social networking, and advertising. Recommender systems have become an indispensable part of many online services, enhancing user experience and driving engagement. As you continue your machine learning journey, remember that recommender systems are a dynamic and evolving field, with ongoing research and development pushing the boundaries of what's possible. By understanding the principles and techniques covered in this lesson, you are well equipped to further explore this exciting area and to develop innovative recommendation solutions of your own. Keep experimenting and learning. Lesson 15, Anomaly Detection. Introduction to Anomaly Detection. In this lesson, we will explore the fascinating and important field of anomaly detection, also known as outlier detection. Anomaly detection is the task of identifying patterns or instances in data that do not conform to expected behavior. These unusual patterns are often referred to as anomalies, outliers, exceptions, or deviants. Anomaly detection aims to identify data points or patterns that are significantly different from the majority of the data. Anomalies can be broadly classified into three categories: point anomalies, contextual anomalies, and collective anomalies. Point anomalies are individual data points that are anomalous with respect to the rest of the data. Contextual anomalies are data points that are anomalous in a specific context but not otherwise. Collective anomalies are collections of data points that are anomalous as a group, even though the individual data points may not be anomalous on their own. Challenges in anomaly detection include the difficulty of defining what constitutes normal behavior, the often high dimensionality of the data, the lack of labeled data for training, and the presence of noise. Anomalies are, by definition, rare events, which can make them difficult to detect and model. Furthermore, what is considered anomalous can change over time, requiring adaptive and dynamic anomaly detection techniques. Anomaly detection is different from classification in several key ways. First, anomaly detection is typically an unsupervised learning task, as labeled data on anomalies is often scarce or unavailable. Second, anomaly detection deals with highly imbalanced data, where the number of anomalies is much smaller than the number of normal instances. Third, the goal of anomaly detection is to identify any unusual pattern, not to classify instances into predefined categories. Applications of anomaly detection are numerous and span across various domains. In fraud detection, anomaly detection is used to identify unusual patterns in financial transactions that might indicate fraudulent activity. In intrusion detection, it is used to detect malicious activity in computer networks. In manufacturing, it is used to identify defects in products or equipment. In healthcare, it can be used to detect abnormal patient conditions or errors in medical data. Evaluation metrics for anomaly detection are similar to those used in classification but with some important differences. Since anomaly detection often deals with highly imbalanced data, accuracy is not a suitable metric. Instead, metrics like precision, recall, F1 score, and the area under the ROC curve, AUC, are commonly used. It is also important to consider the specific costs associated with false positives and false negatives in a given application. Statistical approaches to anomaly detection. Statistical approaches to anomaly detection typically involve modeling the distribution of the normal data and then identifying data points that have a low probability of being generated by that distribution. These methods are often based on the assumption that anomalies are rare and significantly different from the normal data. One simple statistical approach is to use statistical measures such as the mean and standard deviation to identify outliers. For example, one might assume that the data follows a Gaussian distribution and flag data points that are more than a certain number of standard deviations away from the mean as anomalies. This approach is easy to implement but may not be effective for complex, high-dimensional data. Gaussian models can be used for anomaly detection by fitting a probability distribution, such as a multivariate Gaussian, to the normal data. The probability density of each data point can then be computed, and points with low probability density can be flagged as anomalies. This approach assumes that the normal data can be well modeled by a Gaussian distribution, which may not always be the case. Density-based methods are a class of statistical techniques that estimate the density of the data and identify anomalies as points that lie in low-density regions. Local outlier factor, LOF, is a popular density-based method that compares the local density of a point to the local densities of its neighbors. Points that have a substantially lower density than their neighbors are considered outliers. Time series anomaly detection using statistical methods often involves modeling the temporal dependencies in the data. Techniques such as time series decomposition can be used to separate the trend, seasonal, and residual components of the time series. Anomalies can then be identified as points that deviate significantly from the expected trend or seasonal pattern, or that have large residuals. ARIMA models can also be used for time series anomaly detection by identifying points that are poorly predicted by the model. Limitations of statistical approaches include the difficulty of modeling complex, high-dimensional data, the sensitivity to the choice of parameters, and the need for assumptions about the data distribution. Statistical methods may also struggle to detect subtle or complex anomalies that do not significantly deviate from the overall distribution of the data. They are often more effective when combined with domain knowledge and when tailored to the specific characteristics of the data. Machine learning approaches to anomaly detection. Machine learning approaches to anomaly detection leverage the power of learning algorithms to automatically learn patterns from data and identify deviations from those patterns. This section will discuss various machine learning techniques for anomaly detection. One-class support vector machines, SVMs, are a popular machine learning method for anomaly detection. They learn a boundary around the normal data points in the training set and classify any data point outside this boundary as an anomaly. One-class SVMs are particularly effective when the normal data can be well separated from the rest of the feature space but do not assume any specific distribution for the data. Isolation forest is another powerful technique for anomaly detection that is based on the idea of isolating anomalies instead of profiling normal points. The algorithm recursively partitions the data space using randomly selected features and split points until each data point is isolated. Anomalies are expected to require fewer splits to be isolated than normal points. Isolation forest is efficient and effective for high-dimensional data. Autoencoders, which we discussed in the context of deep learning, can also be used for anomaly detection. An autoencoder is trained to reconstruct normal data points, and the reconstruction error is used as an anomaly score. The assumption is that anomalies will have a higher reconstruction error than normal points, as the autoencoder has not learned to reconstruct them effectively. Autoencoders can capture complex, nonlinear patterns in the data. Clustering-based anomaly detection methods use clustering algorithms, such as k-means or DISCAN, to group similar data points together. Anomalies are then identified as points that do not belong to any cluster or form their own small clusters. Clustering-based methods can be effective when anomalies form distinct clusters that are separate from the normal data points. Ensemble methods can also be used for anomaly detection. By combining the results of multiple anomaly detection models, ensemble methods can improve the robustness and accuracy of anomaly detection. For example, one might train multiple one-class SVMs on different subsets of the data or using different features and then combine their predictions using averaging or voting. Deep learning for anomaly detection. Deep learning techniques have shown great promise for anomaly detection, particularly for complex, high-dimensional data such as images, text, and time series. This section will explore the use of deep learning models for anomaly detection. Deep autoencoders are a natural extension of autoencoders for anomaly detection. They use deep neural networks with multiple hidden layers for both the encoder and decoder. This allows them to learn more complex and hierarchical representations of the data, potentially capturing subtle patterns that might be missed by shallower models. Deep autoencoders are trained on normal data, and the reconstruction error is used as an anomaly score. Variational autoencoders, VAEs, which we discussed in the context of generative models, can also be used for anomaly detection. VAEs learn a probabilistic mapping from the input data to a latent space, where the latent variables are assumed to follow a specific distribution, typically a Gaussian distribution. Anomalies can be identified as data points that have a low probability under the learned distribution. The reconstruction error can also be used as an anomaly score. Generative adversarial networks, GANs, another type of generative model, have been adapted for anomaly detection. The idea is to train a GAN on normal data and then use the discriminator network to identify anomalies. Data points that the discriminator classifies as fake, i.e., not belonging to the distribution of normal data, are considered anomalies. GAN-based anomaly detection methods have shown promising results in image and video data. Recurrent neural networks, RNNs, particularly long short-term memory, LSTM, networks, are well suited for anomaly detection in time series data. RNNs can learn temporal dependencies in sequential data and can be trained to predict the next value in a time series. Anomalies can then be identified as points where the prediction error is large. RNNs can also be used to learn representations of time series data that capture normal behavior, and deviations from these representations can be used to detect anomalies. Advantages of deep learning approaches for anomaly detection include their ability to automatically learn complex patterns and representations from high-dimensional data, their flexibility in handling different types of data, and their potential to achieve high accuracy. Disadvantages include the need for large amounts of training data, the computational cost of training deep models, and the difficulty of interpreting the results. Deep learning models are often considered black boxes, and understanding why a particular data point is flagged as an anomaly can be challenging. Unsupervised anomaly detection. Unsupervised anomaly detection is a particularly challenging setting where no labeled data is available, not even for normal instances. The algorithms must learn the characteristics of normal data solely from the unlabeled data itself. The challenges of unsupervised anomaly detection stem from the lack of labeled data and the difficulty of defining normality without any examples. The algorithms must be able to identify any data point that deviates significantly from the learned patterns, without any prior knowledge of what constitutes an anomaly. This often requires making assumptions about the structure of the data and the distribution of anomalies. Clustering-based methods are commonly used for unsupervised anomaly detection. Algorithms like k-means and discan can be used to group similar data points together. Anomalies are then identified as points that do not belong to any cluster or form their own small, isolated clusters. The effectiveness of these methods depends on the choice of the number of clusters, for k-means, and the density parameters, for discan. Density-based methods, such as local outlier factor, LOF, and connectivity-based outlier factor, COF, estimate the local density around each data point and compare it to the local densities of its neighbors. Points that have a substantially lower density than their neighbors are considered anomalies. These methods can be effective in detecting local anomalies but may struggle with datasets where the density of normal points varies significantly. Reconstruction-based methods, such as principal component analysis, PCA, and autoencoders, are another powerful approach to unsupervised anomaly detection. These methods learn a low-dimensional representation of the data that captures the main patterns in the normal data. Anomalies are then identified as points that have a large reconstruction error, i.e., they cannot be accurately reconstructed from their low-dimensional representation. PCA uses a linear transformation to project the data onto a lower-dimensional subspace, while autoencoders can learn nonlinear mappings. Ensemble methods can also be applied to unsupervised anomaly detection. By combining the results of multiple anomaly detection algorithms or multiple runs of the same algorithm with different parameters, ensemble methods can improve the robustness and accuracy of anomaly detection. Different algorithms may be sensitive to different types of anomalies, and combining them can provide a more comprehensive detection of outliers. Voting, averaging, and stacking are common techniques for combining anomaly scores. Semi-supervised and supervised anomaly detection. While unsupervised anomaly detection is the most common setting, there are situations where some labeled data is available either for normal instances or for both normal and anomalous instances. This section will discuss semi-supervised and supervised approaches to anomaly detection. Semi-supervised anomaly detection leverages a small amount of labeled data, typically consisting of only normal instances, to improve the performance of anomaly detection. The labeled data can be used to guide the learning process and to help define the boundary between normal and anomalous data. This can be particularly useful when anomalies are rare or difficult to define precisely. Semi-supervised methods often combine elements of unsupervised learning with supervised learning. Semi-supervised anomaly detection algorithms include methods that incorporate labeled data into the training of unsupervised models. For example, one-class SVMs can be trained primarily on unlabeled data but with some labeled normal instances to help define the decision boundary. By assigning different misclassification costs to different classes, the learning algorithm can be made more sensitive to the minority class, anomalies. The costs can be incorporated into the loss function or used to adjust the decision threshold of the classifier. Anomaly detection in time series data. Time series data, where observations are collected sequentially over time, presents unique challenges and opportunities for anomaly detection. This section will discuss the specific considerations and techniques for detecting anomalies in time series data. The challenges of anomaly detection in time series include the temporal dependencies between observations, the presence of trends and seasonality, and the potential for concept drift, where the underlying data generating process changes over time. Anomalies in time series data can be point anomalies, individual data points that are anomalous, contextual anomalies, data points that are anomalous in their specific time context, or collective anomalies, sequences of data points that are anomalous as a group. Time series decomposition can be used for anomaly detection by separating the time series into its trend, seasonal, and residual components. Anomalies can then be identified as points that deviate significantly from the expected trend or seasonal pattern, or that have large residuals. This approach can be particularly useful when anomalies are characterized by sudden changes in the level or seasonality of the time series. Using ARIMA models for anomaly detection involves fitting an ARIMA model to the normal time series data and then using the model to predict future values. Anomalies are identified as points where the prediction error is large, i.e., where the actual value deviates significantly from the predicted value. This approach assumes that the normal data can be well modeled by an ARIMA process. Recurrent neural networks, RNNs, particularly long short-term memory, LSTM, networks, have been successfully applied to anomaly detection in time series data. RNNs can learn complex temporal dependencies in the data and can be trained to predict the next value in a time series. Anomalies can be detected based on the prediction error or by using the learned representations of the RNN to identify unusual patterns. Dynamic time warping, DTW, is a technique for measuring the similarity between two time series that may vary in speed or length. DTW can be used for anomaly detection by comparing a new time series to a set of known normal time series. Anomalies are identified as time series that have a large DTW distance to all the normal time series. DTW can be particularly useful when anomalies are characterized by shape distortions or phase shifts. Anomaly detection in high-dimensional data, where the number of features or variables is large, poses specific challenges for anomaly detection. This section will discuss these challenges and explore techniques for detecting anomalies in high-dimensional settings. The curse of dimensionality refers to various phenomena that arise when analyzing and organizing data in high-dimensional spaces. In the context of anomaly detection, the curse of dimensionality can manifest as increased data sparsity, where data points become more distant from each other, and the notion of density becomes less meaningful. Many anomaly detection algorithms that rely on distance or density calculations can become less effective in high-dimensional spaces. Feature selection and dimensionality reduction are important pre-processing steps for anomaly detection in high-dimensional data. Feature selection aims to identify the most relevant features for detecting anomalies, while dimensionality reduction aims to project the data onto a lower dimensional space while preserving its essential structure. Techniques like principal component analysis, PCA, and autoencoders can be used for dimensionality reduction. Feature selection can be based on domain knowledge or on statistical measures of feature importance. Subspace and correlation-based methods are specifically designed for anomaly detection in high-dimensional data. These methods exploit the observation that anomalies may be detectable only in specific subspaces or projections of the data. Subspace methods search for anomalies in different subspaces spanned by subsets of features. Correlation-based methods look for deviations from expected correlations between features. Angle-based outlier detection, ABOD, is a technique that considers the angles between data points in high-dimensional space. The idea is that outliers tend to lie in the outskirts of the data distribution, and the variance of angles to an outlier from other points is smaller compared to the variance of angles to normal points. ABOD computes an anomaly score based on the variance of angles between a data point and all pairs of other points in the dataset. The challenges of high-dimensional anomaly detection include the increased computational cost, the difficulty of visualizing and interpreting the data, and the potential for false positives due to the sparsity of data in high-dimensional space. It is often necessary to use specialized algorithms and techniques that are designed to handle the unique characteristics of high-dimensional data. Careful feature selection and dimensionality reduction can play a crucial role in improving the effectiveness of anomaly detection in these settings. Evaluating anomaly detection models. Evaluating the performance of anomaly detection models is crucial for selecting the best model, tuning hyperparameters, and understanding the strengths and weaknesses of different approaches. This section will discuss the challenges and metrics for evaluating anomaly detection performance. The challenges in evaluating anomaly detection performance stem from the unsupervised nature of the task and the rarity of anomalies. Unlike supervised learning, there is typically no ground truth available for what constitutes an anomaly. Furthermore, the class imbalance between normal and anomalous instances can make standard classification metrics like accuracy misleading. Evaluation often relies on indirect measures or the use of datasets with labeled anomalies for benchmarking. Precision, recall, and F1 score can be used to evaluate anomaly detection models if labeled data is available. In this context, precision measures the proportion of true anomalies among the instances flagged as anomalies, while recall measures the proportion of true anomalies that were correctly identified by the model. The F1 score is the harmonic mean of precision and recall. These metrics are commonly used in information retrieval and can be adapted for anomaly detection. ROC curves and AUC, area under the ROC curve, can also be used to evaluate anomaly detection models. The ROC curve plots the true positive rate, recall, against the false positive rate at various thresholds for the anomaly score. The AUC provides a single scalar value that summarizes the overall performance of the model. A higher AUC indicates better 1 performance, with a perfect detector having an AUC of 1.0. Precision recall curves are often more informative than ROC curves when dealing with imbalanced datasets, which are common in anomaly detection. Precision recall curves plot precision against recall for different thresholds. They are particularly useful when the cost of false positives and false negatives is different. The area under the precision recall curve, AUPRC, can also be used as a summary metric. Using domain knowledge to evaluate anomaly detection results is often crucial. In many applications, the ultimate assessment of an anomaly detection system depends on whether it detects anomalies that are meaningful and actionable in the specific context. This may involve consulting with domain experts to assess the detected anomalies and determine their relevance. Visualization techniques can also play an important role in understanding and interpreting the results of anomaly detection. Real-world applications and case studies in anomaly detection. In this final section of Lesson 15, we will explore some real-world applications and case studies of anomaly detection to illustrate the practical impact and versatility of these techniques across various domains. Fraud detection in financial transactions is a major application area for anomaly detection. Credit card fraud, insurance fraud, and money laundering are examples of fraudulent activities that can be detected by identifying unusual patterns in transaction data. Anomaly detection models can be trained on historical transaction data to learn patterns of normal behavior and then used to flag transactions that deviate significantly from these patterns. Features such as transaction amount, location, time, and merchant can be used to detect anomalies. Intrusion detection in computer networks is another important application. Anomaly detection techniques can be used to identify malicious activity in network traffic data, such as hacking attempts, malware infections, and data breaches. By analyzing network traffic patterns, anomaly detection models can detect deviations from normal behavior that might indicate an intrusion. Features such as packet size, protocol, source and destination IP addresses, and traffic volume can be used for intrusion detection. Fault detection in industrial processes is crucial for ensuring the safety and efficiency of manufacturing and other industrial operations. Anomaly detection can be used to identify unusual patterns in sensor data from machinery and equipment that might indicate a fault or malfunction. Early detection of faults can help prevent costly downtime, improve product quality, and reduce safety risks. Time series anomaly detection techniques are often used in this context. Medical anomaly detection has numerous applications, including identifying abnormal heart rhythms in ECG data, detecting tumors in medical images, and identifying unusual patterns in patient records that might indicate a rare disease or an adverse drug reaction. Anomaly detection can be used as a screening tool to flag cases that require further investigation by medical professionals. Deep learning techniques, such as autoencoders and GANs, have shown promise in medical anomaly detection. Anomaly detection in sensor networks is important for various applications, such as environmental monitoring, infrastructure monitoring, and surveillance. Sensor networks can generate large amounts of data, and anomaly detection techniques can be used to identify unusual events or readings that might indicate a problem, such as a pollution event, a structural failure, or an intrusion. Challenges in this domain include dealing with noisy and missing data, as well as the need for real-time or near real-time detection. These are just a few examples of the many real-world applications of anomaly detection. As data collection and analysis capabilities continue to advance, and as machine learning algorithms become more sophisticated, we can expect to see even more widespread use of anomaly detection techniques across various domains. The ability to automatically identify unusual patterns and events is becoming increasingly important in our complex, data-driven world. This concludes our exploration of anomaly detection in Lesson 15. We have covered the fundamental concepts of anomaly detection, including the definition of anomalies, the challenges in detecting them, and the differences between anomaly detection and classification. We discussed various statistical and machine learning approaches to anomaly detection, including one-class SVMs, isolation forests, autoencoders, and clustering-based methods. We also examined the use of deep learning for anomaly detection, particularly in the context of time series data. Furthermore, we explored the challenges of unsupervised anomaly detection, as well as semi-supervised and supervised approaches. We discussed the specific considerations for anomaly detection in time series and high-dimensional data. We also addressed the important topic of evaluating anomaly detection models, highlighting the limitations of standard metrics like accuracy and the importance of using precision, recall, F1, score, ROC curves, and precision recall curves. Finally, we examined real-world applications and case studies to illustrate the practical impact of anomaly detection in domains such as fraud detection, intrusion detection, fault detection, medical anomaly detection, and sensor networks. Anomaly detection is a crucial task in many domains, and the techniques we have discussed in this lesson provide a powerful toolkit for identifying unusual patterns and events in data. As you continue your machine learning journey, keep in mind that anomaly detection is a vibrant and evolving field, with ongoing research and development leading to new and improved techniques. By understanding the principles and methods covered in this lesson, you are well equipped to further explore this exciting area and apply anomaly detection techniques to real-world problems. Lesson 16, Introduction to Reinforcement Learning. Fundamentals of Reinforcement Learning. In this lesson, we will embark on a journey into the fascinating world of reinforcement learning, RL, a powerful branch of machine learning that focuses on training agents to make sequential decisions in an environment to maximize cumulative rewards. Unlike supervised and unsupervised learning, which primarily deal with analyzing existing data, reinforcement learning involves an agent actively interacting with its environment and learning through trial and error. Reinforcement learning, RL, is a type of machine learning where an agent learns to behave in an environment by performing certain actions and observing the results. The agent's goal is to learn an optimal policy, which is a mapping from states of the environment to actions, that maximizes the cumulative reward received over time. Key concepts in reinforcement learning include the agent, which is the learner and decision maker, the environment, which is the external system that the agent interacts with, the state, which represents the current situation of the agent in the environment, the action, which is what the agent does in a particular state, and the reward, which is the feedback signal that the agent receives from the environment after taking an action. The goal of reinforcement learning is for the agent to learn an optimal or near-optimal policy that maximizes the expected cumulative reward over time. The policy can be deterministic, mapping each state to a single action, or stochastic, defining a probability distribution over actions for each state. The optimal policy is one that, if followed, will lead to the highest possible long-term reward. Reinforcement learning differs significantly from supervised and unsupervised learning. In supervised learning, the algorithm learns from labeled examples, where the correct output is provided for each input. In unsupervised learning, the algorithm learns from unlabeled data, seeking to discover hidden patterns or structures. In reinforcement learning, the agent learns from sequential feedback in the form of rewards, which are often sparse and delayed. There is no supervisor providing the correct action, the agent must discover it through exploration and trial and error. The exploration-exploitation dilemma is a fundamental challenge in reinforcement learning. The agent must balance between exploring new actions and states to discover potentially better strategies and exploiting the knowledge it has already gained to maximize its current reward. Too much exploration can lead to suboptimal performance, while too much exploitation can prevent the agent from discovering the optimal policy. Markov decision processes, MDPs, Markov decision processes, MDPs, provide a mathematical framework for modeling decision-making situations where outcomes are partly random and partly under the control of a decision-maker. They are a fundamental concept in reinforcement learning and provide the foundation for many RL algorithms. A Markov decision process, MDP, is formally defined by a tuple, S, A, P, R, gamma, where S is a set of states, A is a set of actions, P is a state transition probability function, R is a reward function, and gamma is a discount factor. The state represents the current situation of the agent in the environment. The action is the choice made by the agent at each step. The state transition probability function P, SS, A, specifies the probability of transitioning to state S from state S after taking action A. The reward function R, S, A, S, provides the immediate reward received by the agent after taking action A in state S and transitioning to state S. The discount factor gamma, 0 less than or equal to gamma less than or equal to 1, determines the present value of future rewards. A key assumption in MDPs is the Markov property, which states that the future is independent of the past given the present. In other words, the next state and reward depend only on the current state and action, and not on the history of previous states and actions. This property simplifies the analysis and allows for the development of efficient algorithms. Not all environments can be accurately modeled as MDPs, but many real-world problems can be approximated as such. The agent's behavior in an MDP is defined by a policy pi, AS, which specifies the probability of taking action A in state S. The goal of reinforcement learning is to find an optimal policy pi asterisk that maximizes the expected cumulative discounted reward, also known as the return. The value function v pi, S, represents the expected return starting from state S and following policy pi. The action value function q pi, S, A, represents the expected return starting from state S, taking action A, and then following policy pi. The Bellman equations are a set of recursive equations that relate the value of a state, or state-action pair, to the values of its successor states, or state-action pairs. They provide a way to compute the value function for a given policy and are fundamental to many reinforcement learning algorithms. The Bellman optimality equations define the optimal value function and optimal policy, which are the solutions that maximize the expected return. Finding a policy that satisfies the Bellman optimality equation is equivalent to finding an optimal policy. Dynamic programming, DP, is a method for solving complex problems by breaking them down into simpler subproblems, solving each subproblem only once, and storing their solutions. In the context of reinforcement learning, DP methods can be used to compute optimal policies and value functions when a perfect model of the environment, i.e., the MDP, is available. Policy evaluation is the process of computing the value function v pi, S, for a given policy pi. This can be done iteratively using the Bellman equation for v pi. Starting from an arbitrary initial value function, the algorithm repeatedly updates the value of each state based on the values of its successor states and the rewards obtained, until the value function converges. Policy evaluation provides a way to assess the performance of a given policy. Policy improvement is the process of finding a better policy given the value function of the current policy. This is typically done by acting greedily with respect to the current value function. For each state, the agent chooses the action that maximizes the expected return according to the current value function. This new policy is guaranteed to be at least as good as the original policy, and often strictly better. Policy iteration is an algorithm that alternates between policy evaluation and policy improvement steps. It starts with an arbitrary policy and iteratively evaluates the policy, improves it, and then evaluates the new policy, until convergence. Policy iteration is guaranteed to converge to an optimal policy in a finite number of iterations. However, each iteration requires a full policy evaluation, which can be computationally expensive. Value iteration is another dynamic programming algorithm that directly computes the optimal value function v** s, without explicitly iterating over policies. It starts with an arbitrary value function and iteratively updates the value of each state using the Bellman optimality equation for v**. Once the optimal value function is found, an optimal policy can be derived by acting greedily with respect to v**. Value iteration is often faster than policy iteration in practice. Generalized policy iteration, GPI, refers to the general idea of letting policy evaluation and policy improvement processes interact, independent of the granularity and other details of the two processes. Almost all reinforcement learning methods are well described as GPI. GPI captures the core idea of both policy iteration and value iteration, highlighting the interplay between learning the value function and improving the policy. Monte Carlo methods. Monte Carlo (MC) methods are a class of reinforcement learning algorithms that learn from complete episodes of experience, without requiring a model of the environment's dynamics. Unlike dynamic programming, MC methods do not need to know the transition probabilities or the reward function. They rely on averaging sample returns to estimate value functions and discover optimal policies. Monte Carlo prediction aims to estimate the value function v pi s for a given policy pi by experiencing episodes of interaction with the environment. The agent follows the policy pi, generating complete episodes from start to finish. For each state visited in an episode, the return, cumulative discounted reward, following that state is recorded. The value of a state is then estimated as the average of the returns obtained from all episodes in which that state was visited. Monte Carlo control aims to find an optimal policy by iteratively improving the policy based on the estimated value function. Similar to generalized policy iteration, MC control alternates between policy evaluation, estimating the value function for the current policy, and policy improvement, making the policy greedy with respect to the current value function. MC control methods often use an epsilon-greedy exploration strategy to balance exploration and exploitation. On-policy versus off-policy methods is an important distinction in reinforcement learning. On-policy methods, such as on-policy Monte Carlo control, evaluate and improve the same policy that is used to generate the data, episodes. Off-policy methods, such as off-policy Monte Carlo control and Q-learning, can learn about one policy while following another. This allows for greater flexibility and can potentially lead to more efficient learning. Importance sampling is a technique used in off-policy Monte Carlo methods to estimate the value function of one policy, the target policy, while following another policy, the behavior policy. Importance sampling weights the returns from each episode by the ratio of the probability of the episode occurring under the target policy to the probability of it occurring under the behavior policy. This allows off-policy methods to learn from data generated by a different policy. Incremental implementation is a practical aspect of Monte Carlo methods. Instead of storing all the returns for each state and averaging them at the end, the value estimates can be updated incrementally after each episode. This reduces memory requirements and allows for online learning. Incremental implementation involves updating the value estimate for each state visited in an episode towards the observed return, using a small step size parameter. Temporal difference learning. Temporal difference, TD, learning is a central concept in reinforcement learning that combines ideas from Monte Carlo methods and dynamic programming. TD methods can learn directly from raw experience without a model of the environment's dynamics, like Monte Carlo methods, and they can update estimates based on other learned estimates, without waiting for a final outcome, like dynamic programming. The TD0 algorithm is the simplest TD method for estimating the value function v pi s of a given policy pi. Unlike Monte Carlo methods, which update value estimates only at the end of an episode, TD0 updates the value estimate for each state after every transition. The update rule is based on the difference between the current estimate and a bootstrapped estimate that combines the immediate reward and the estimated value of the next state. This difference is known as the TD error. SURSA, State Action Reward. State Action, is an on-policy TD control algorithm that learns an action value function Q, S, A. SURSA updates the Q value for a state action pair based on the observed reward and the Q value of the next state and the action chosen by the current policy. The name SURSA comes from the sequence of events that the algorithm considers: the current state, the action taken, the reward received, the next state, and the next action. Q-learning is an off-policy TD control algorithm that is one of the most widely used reinforcement learning algorithms. Like SURSA, Q-learning learns an action value function Q, S, A. However, unlike SURSA, Q-learning updates the Q value based on the maximum Q value of the next state, regardless of the action chosen by the current policy. This allows Q-learning to learn the optimal Q function directly, even while following a suboptimal policy. Expected SURSA is a variation of SURSA that uses the expected value of the next state action pairs, weighted by their probabilities under the current policy, instead of the value of a single sampled action. Expected SURSA can have lower variance than SURSA and can sometimes lead to faster learning. It can be seen as a generalization of Q-learning that allows for on-policy learning. Double Q-learning is an extension of Q-learning that addresses the problem of maximization bias. In Q-learning, the same samples are used both to determine the maximizing action and to estimate its value, which can lead to overestimation of the Q values. Double Q-learning uses two separate Q functions, each of which is updated using the other's estimate of the maximum value. This helps to reduce the overestimation bias and can lead to more stable and accurate learning. Value function approximation. In many real-world reinforcement learning problems, the state and action spaces are too large to be represented exactly using tabular methods like Q-learning or SURSA. Value function approximation addresses this challenge by using a parameterized function to approximate the value function or action value function. Linear function approximation is a simple and widely used approach where the value function is approximated as a linear combination of features of the state or state action pair. The features can be hand-engineered or learned automatically. Linear function approximation can be effective when the features are well chosen and the underlying value function is approximately linear in the features. However, it may struggle to capture complex, nonlinear relationships. Nonlinear function approximation allows for more complex and flexible approximations of the value function. Neural networks are commonly used as nonlinear function approximators in reinforcement learning. A neural network can take the state or state action pair as input and output the estimated value. The network's weights are adjusted during training to minimize the difference between the predicted values and the target values, e.g., observed returns or TD errors. Deep Q networks, DQN, which we discussed in the context of deep reinforcement learning, are an example of using neural networks for value function approximation. DQN uses a deep neural network to approximate the Q function, taking the state as input and outputting the Q values for each action. DQN combines several techniques, such as experience replay in a target network, to stabilize the learning process and improve performance. Challenges of function approximation in reinforcement learning include the potential for instability and divergence, particularly when combining function approximation with bootstrapping and off-policy learning, the deadly triad. Other challenges include the need for careful tuning of hyperparameters, such as the learning rate and the exploration strategy, and the risk of overfitting to the training data. Despite these challenges, function approximation is a crucial tool for scaling reinforcement learning to complex, real-world problems. By using function approximation, reinforcement learning agents can generalize from sampled experience to unseen states and actions, enabling them to handle large or continuous state and action spaces. Ongoing research aims to develop more stable and efficient algorithms for reinforcement learning with function approximation. Policy gradient methods. Policy gradient methods are a class of reinforcement learning algorithms that directly learn a parameterized policy, often represented by a deep neural network. Unlike value-based methods, which learn a value function and then derive a policy from it, policy gradient methods directly optimize the policy to maximize the expected cumulative reward. The core idea behind policy gradient methods is to adjust the policy parameters in the direction that increases the expected return. This is typically done using gradient ascent, where the gradient of the expected return with respect to the policy parameters is estimated and used to update the parameters. The policy gradient theorem provides a way to compute this gradient without needing to differentiate through the environment dynamics. The reinforce algorithm is a basic policy gradient method that uses Monte Carlo sampling to estimate the return and the policy gradient. Reinforce updates the policy parameters after each complete episode, using the observed return as an estimate of the value of each state action pair. Reinforce can be applied to both episodic and continuing tasks and can handle stochastic policies. Actor-critic methods combine policy gradient methods with value function approximation. In actor-critic methods, an actor network represents the policy and is updated using policy gradient, while a critic network learns a value function or action value function to evaluate the actions taken by the actor. The critic provides feedback to the actor, helping it to learn a better policy. Actor-critic methods can be more stable and sample-efficient than pure policy gradient methods like reinforce. Advantage actor-critic, A2C, is a synchronous, deterministic version of the asynchronous advantage actor-critic, A3C, algorithm. A 2C uses an advantage function, which measures how much better an action is compared to the average action at a given state, to reduce the variance of the policy gradient updates. A 2C typically uses multiple parallel actors that interact with their own copy of the environment and update a shared model. Asynchronous advantage actor-critic, A3C, is an extension of the A2C algorithm that uses asynchronous updates. In A3C, multiple parallel actors interact with their own copy of the environment and asynchronously update a shared model. This allows A3C to scale to larger problems and achieve faster learning. A3C has been shown to be effective on a variety of tasks, including Atari games and continuous control problems. Deep reinforcement learning, DRL, combines the power of deep neural networks with reinforcement learning algorithms to tackle complex decision-making problems. By using deep neural networks as function approximators, DRL can handle high-dimensional state and action spaces and learn intricate, nonlinear relationships between states, actions, and rewards. Combining deep learning with reinforcement learning allows DRL agents to learn directly from raw sensory inputs, such as images or text, without the need for handcrafted features. Deep neural networks can automatically learn hierarchical representations of the state and action spaces, enabling them to capture complex patterns and generalize to unseen situations. This has led to significant breakthroughs in areas like game playing, robotics, and control systems. Deep Q networks, DQN, which we discussed earlier, was one of the first successful DRL algorithms. DQN combines Q-learning with deep convolutional neural networks to learn to play Atari games directly from pixel inputs. The network is trained to approximate the Q function, taking the game screen as input and outputting the Q values for each possible action. DQN uses techniques like experience replay and a target network to stabilize the learning process. Policy gradient methods with deep neural networks have also been successfully applied in DRL. Instead of learning a value function, these methods directly learn a parameterized policy represented by a deep neural network. The network takes the state as input and outputs a probability distribution over actions. Policy gradient methods, such as reinforce and actor-critic, use gradient ascent to update the policy parameters in the direction that increases the expected return. Applications of deep reinforcement learning in complex environments include playing games with high-dimensional state spaces, e.g., Atari games, Go, StarCraft, controlling robots in simulated and real-world environments, and optimizing complex systems like data center cooling and traffic control. DRL has demonstrated the ability to learn complex behaviors and strategies directly from interactions with the environment, surpassing human performance in some cases. However, DRL also faces challenges, such as high sample complexity, requiring a large number of interactions with the environment, instability during training, and difficulty in exploring efficiently in large state and action spaces. Challenges in deep reinforcement learning include the need for careful tuning of hyperparameters, the sensitivity to the choice of neural network architecture, and the difficulty of understanding and interpreting the learned policies. Furthermore, DRL algorithms can be computationally expensive to train, requiring significant computational resources and time. Despite these challenges, DRL remains an active and rapidly evolving area of research, with ongoing efforts to develop more stable, efficient, and interpretable algorithms. Exploration strategies in reinforcement learning continued. In Lesson 16, we introduced various exploration strategies, including epsilon greedy, upper confidence bound, UCB, and Thompson sampling. Here, we continue the discussion with more advanced exploration techniques. Curiosity-driven exploration is an intrinsic motivation approach that encourages the agent to explore states that are novel or surprising. The agent is rewarded for visiting states that are different from what it has experienced before or for which its predictions are inaccurate. This can be implemented by maintaining an internal model of the environment and rewarding the agent for prediction errors or for visiting states that lead to significant updates to the internal model. Curiosity-driven exploration can be particularly useful in environments with sparse or delayed rewards. Advanced exploration techniques often combine multiple exploration strategies or adapt the exploration strategy based on the agent's learning progress. For example, the agent might start with a high degree of exploration early in training and gradually reduce it as it gains more knowledge about the environment. Exploration strategies can also be tailored to specific domains or tasks, taking into account prior knowledge or structure in the environment. Some advanced techniques include: these advanced exploration methods aim to improve the efficiency and effectiveness of exploration, particularly in complex, high-dimensional environments with sparse rewards. Real-world applications of reinforcement learning. Reinforcement learning has shown great promise in solving a wide range of real-world problems, and its applications continue to expand. In this final section of Lesson 16, we will explore some notable examples and case studies of reinforcement learning in various domains. Game playing has been a major application area and testbed for reinforcement learning algorithms. Reinforcement learning agents have achieved superhuman performance in various games, including classic Atari games, board games like chess and Go, and modern video games like Dota 2 and StarCraft 2. AlphaGo, developed by DeepMind, was a landmark achievement, demonstrating that deep reinforcement learning can master the complex game of Go, surpassing the best human players. The techniques developed for game playing have also been applied to other domains. In robotics, reinforcement learning is used to train robots to perform complex tasks, such as grasping objects, locomotion, and navigation. Reinforcement learning allows robots to learn directly from interaction with the environment, without the need for explicit programming or hand-engineered control policies. This is particularly useful in unstructured or dynamic environments where it is difficult to specify a precise control strategy in advance. Applications of RL in robotics include robotic manipulation, autonomous navigation, and human-robot interaction. Control systems are another important application area for reinforcement learning. Reinforcement learning can be used to optimize the performance of various control systems, such as traffic light control, HVAC, heating, ventilation, and air conditioning systems, and industrial processes. By learning from data and feedback, reinforcement learning agents can adapt to changing conditions and improve the efficiency and robustness of control systems. For example, RL has been used to optimize data center cooling, reducing energy consumption significantly. Resource management problems, such as inventory management, supply chain optimization, and energy management, can also be addressed using reinforcement learning. For example, reinforcement learning agents can learn to optimize inventory levels to minimize costs while ensuring product availability, or to schedule energy consumption to reduce costs and carbon emissions. These applications often involve complex, dynamic environments with multiple interacting components, making them well-suited for reinforcement learning approaches. Personalized recommendations and advertising are areas where reinforcement learning is beginning to have an impact. By framing the recommendation problem as a sequential decision-making task, where the agent, recommender system, interacts with the user over time and receives feedback in the form of clicks, ratings, or purchases, reinforcement learning can be used to learn personalized recommendation policies that maximize user engagement and satisfaction. RL can also be applied to optimize bidding strategies in online advertising. These are just a few examples of the many real-world applications of reinforcement learning. As algorithms continue to improve and as more domains are successfully addressed with reinforcement learning, we can expect to see even more widespread adoption of these techniques in the years to come. Reinforcement learning has the potential to revolutionize many aspects of our lives, from transportation and healthcare to entertainment and education. This concludes our introduction to reinforcement learning in Lesson 16. We have covered the fundamental concepts of reinforcement learning, including agents, environments, states, actions, and rewards. We discussed different types of reinforcement learning algorithms, including model-free methods like Q-learning and SURSA, and model-based methods like DynaQ and Monte Carlo tree search. We also delved into deep reinforcement learning, which combines the power of deep neural networks with reinforcement learning principles to tackle complex, high-dimensional problems. We explored advanced topics such as inverse reinforcement learning, hierarchical reinforcement learning, multi-agent reinforcement learning, transfer learning, and meta-learning in the context of RL. We also discussed important considerations such as the exploration-exploitation trade-off and various exploration strategies. Finally, we highlighted the diverse and impactful real-world applications of reinforcement learning, showcasing its potential to revolutionize fields such as game playing, robotics, control systems, resource management, and personalized recommendations. Reinforcement learning is a dynamic and rapidly evolving field that offers exciting opportunities for creating intelligent agents that can learn to make optimal decisions in complex environments. As you continue your machine learning journey, keep in mind that the principles and techniques discussed in this lesson form a strong foundation for understanding and applying reinforcement learning to a wide range of problems. In the following lessons, we will continue to build upon this foundation, exploring other fascinating areas of machine learning. Lesson 17, Advanced Reinforcement Learning. In this lesson, we will delve into advanced topics in reinforcement learning, RL, building upon the foundational concepts introduced in Lesson 16. We will explore various extensions and refinements of RL techniques that address more complex scenarios and challenges. These advanced methods enable the application of RL to a wider range of real-world problems, pushing the boundaries of what's possible with intelligent agents. Inverse reinforcement learning. Inverse reinforcement learning, IRL, is a fascinating area of research that tackles the problem of inferring the reward function of an agent based on its observed behavior. Instead of learning a policy from a predefined reward function, IRL aims to learn the reward function that best explains the observed behavior, typically demonstrated by an expert. The core idea behind IRL is that it is often easier for experts to demonstrate desired behavior than to specify a reward function that would generate that behavior. For example, it might be easier for a human driver to demonstrate how to drive a car safely and efficiently than to write down a precise mathematical function that captures all the nuances of good driving. IRL seeks to extract this underlying reward function from the expert's demonstrations. Challenges in inverse reinforcement learning include the fact that the problem is inherently ill-posed, multiple reward functions can explain the same behavior, and some behaviors might be optimal under many different reward functions. Furthermore, the expert's demonstrations may be suboptimal or noisy, and the learner may not have access to the same state and action spaces as the expert. Dealing with these challenges requires making assumptions about the form of the reward function or the nature of the expert's behavior. Apprenticeship learning is a specific approach to IRL where the goal is to learn a policy that performs at least as well as the expert whose demonstrations are provided. The learner tries to find a policy that matches the expert's behavior, typically by matching feature expectations, the expected cumulative discounted feature counts under the expert's policy. Apprenticeship learning can be used in situations where the reward function is unknown or difficult to specify. Maximum entropy inverse reinforcement learning is a popular IRL algorithm that addresses the ambiguity problem by seeking the reward function that leads to the observed behavior while maximizing the entropy of the policy. This approach favors reward functions that explain the expert's behavior with the least amount of commitment, avoiding overly specific or complex reward functions. The maximum entropy principle provides a principled way to select a reward function among the many that could explain the observed behavior. IRL has found numerous applications in robotics and control, where it can be used to learn complex behaviors from expert demonstrations. For example, IRL can be used to learn control policies for robots by observing human demonstrations, to learn navigation strategies from animal behavior, or to infer the goals and preferences of humans in human-robot interaction scenarios. IRL can also be applied in other domains, such as economics and cognitive science, to model and understand the behavior of humans and other agents. Hierarchical reinforcement learning. Hierarchical reinforcement learning, HRL, is an approach to scaling up reinforcement learning to complex, long-horizon tasks by learning at multiple levels of abstraction. HRL methods decompose a complex task into a hierarchy of subtasks, enabling the agent to learn and plan at different time scales and levels of detail. The core idea behind HRL is to learn skills or sub-policies that can be reused and combined to solve more complex tasks. Instead of learning a flat policy that maps directly from states to actions, HRL methods learn a hierarchy of policies, where higher-level policies select among lower-level policies or skills, and the lowest-level policies interact directly with the environment. This hierarchical structure can significantly reduce the complexity of learning and improve the efficiency of exploration. The options framework is a popular formalism for HRL. An option can be thought of as a temporally extended action or a subroutine that consists of a policy, a termination condition, and an initiation set. The policy determines how to act while the option is executing, the termination condition specifies when the option should terminate, and the initiation set defines the states in which the option can be invoked. Options can be learned from data or defined manually. Feudal reinforcement learning is another approach to HRL where higher-level managers learn to set goals or tasks for lower-level workers. The workers learn to achieve these goals, and the managers learn to set goals that maximize the overall reward. This hierarchical structure allows for a division of labor and can facilitate learning in complex environments. Feudal RL draws inspiration from hierarchical organizational structures. HRL has found applications in complex tasks and planning problems, such as robot navigation in large environments, complex manipulation tasks, and long-horizon decision-making problems. By decomposing a complex task into simpler subtasks, HRL can make learning more tractable and enable the agent to learn more efficiently. HRL can also improve the interpretability and transferability of learned policies. Challenges in hierarchical reinforcement learning include the difficulty of learning effective and reusable skills or options, the problem of credit assignment across different levels of the hierarchy, and the need for efficient exploration strategies at multiple levels of abstraction. Furthermore, the hierarchical structure itself needs to be learned or specified, which can be a non-trivial task. Despite these challenges, HRL remains an active and promising area of research. Multi-agent reinforcement learning. Multi-agent reinforcement learning, MARL, extends the standard reinforcement learning framework to scenarios involving multiple agents that interact with each other and a shared environment. This section will discuss the unique challenges and approaches in MARL and explore its applications. In MARL, each agent seeks to learn a policy that maximizes its own cumulative reward, but the presence of other agents significantly complicates the learning problem. The environment becomes non-stationary from the perspective of each individual agent, as the other agent's policies may change over time. Furthermore, the agent's actions can affect each other, leading to complex interactions and dynamics. MARL scenarios can be broadly classified as cooperative, competitive, or mixed. In cooperative settings, agents share a common goal and work together to maximize a joint reward. In competitive settings, agents have opposing goals, and one agent's gain is another agent's loss. Mixed settings involve elements of both cooperation and competition. The appropriate learning algorithms and solution concepts depend on the nature of the multi-agent interaction. Challenges in multi-agent learning include the exponential growth of the joint action space with the number of agents, the difficulty of credit assignment when agents share rewards, the non-stationarity of the environment due to other agents learning, and the need for coordination and communication among agents. Furthermore, issues of scalability, stability, and convergence become even more pronounced in the multi-agent setting. Independent learners versus joint action learners is an important distinction in MARL. Independent learners treat other agents as part of the environment and learn their own policies independently, without explicitly modeling the other agents. Joint action learners, on the other hand, explicitly consider the joint action space of all agents and try to learn a joint policy. Independent learning is simpler and more scalable but may lead to suboptimal policies if agents' actions are highly interdependent. Joint action learning can potentially achieve better coordination but faces challenges in terms of computational complexity and scalability. Marl has found numerous applications, including robotics, e.g., multi-robot coordination, distributed control, traffic control, e.g., optimizing traffic light timings, autonomous driving in the presence of other vehicles, multi-agent systems, e.g., distributed sensor networks, smart grids, economics, e.g., modeling markets and auctions, and game theory, e.g., learning to play games with multiple players. Transfer learning and reinforcement learning. Transfer learning, which we discussed in the context of supervised learning, also plays an important role in reinforcement learning. Transfer learning in RL aims to leverage knowledge gained from one task or environment to improve learning performance on a different but related task or environment. The motivation for transfer learning in RL is similar to that in supervised learning. It can significantly reduce the amount of data and training time required to learn a new task by transferring relevant knowledge from a source task to a target task. This can be particularly useful in real-world applications where data is scarce or expensive to obtain, or where the environment is complex and training from scratch is impractical. Approaches for transfer learning in RL include policy transfer, where a policy learned in the source task is used to initialize the policy for the target task, reward shaping, where the reward function of the target task is modified based on the source task's reward function, and model transfer, where a model of the environment dynamics learned in the source task is used in the target task. Other approaches involve learning representations or features that are transferable across tasks. Challenges in transfer learning for RL include the potential for negative transfer, where the knowledge from the source task interferes with learning the target task, and the difficulty of determining which aspects of the source task are relevant to the target task. Furthermore, differences in state and action spaces between the source and target tasks can complicate the transfer process. Addressing these challenges often requires careful consideration of the relationship between the tasks and the choice of appropriate transfer mechanisms. Transfer learning has found applications in robotics, where a policy learned in simulation can be transferred to a real robot, or where a policy learned for one task can be adapted to a new task. It has also been applied in game playing, where an agent trained on one game can be adapted to play a different but related game. Domain adaptation is a specific type of transfer learning where the goal is to adapt a policy learned in a source domain to a different target domain, for example, adapting a policy learned in a simulated environment to the real world. Metalearning and reinforcement learning. Metalearning, or learning to learn, is a subfield of machine learning that aims to learn efficient learning algorithms or to learn how to adapt quickly to new tasks. In the context of reinforcement learning, metalearning can enable agents to learn new tasks more rapidly by leveraging experience from previous tasks. The core idea behind metalearning in reinforcement learning is to train an agent that can quickly adapt to new tasks or environments, given only a small amount of experience in the new task. This is often referred to as few-shot learning or fast adaptation. The agent is trained on a distribution of tasks, with the goal of learning a learning strategy or a set of prior knowledge that can be efficiently adapted to new tasks drawn from the same distribution. Model-agnostic metalearning (MAML) is a popular metalearning algorithm that can be applied to reinforcement learning. MAML aims to learn an initial set of model parameters that are well suited for fast adaptation. During meta-training, MAML samples a batch of tasks, and for each task, it computes an update to the model parameters based on a small amount of data from that task. It then updates the initial parameters to improve the model's performance after one or a few gradient steps on the new tasks. Recurrent models can also be used for metalearning in reinforcement learning. By using a recurrent neural network, RNN, as the agent's policy, the recurrent state can serve as a memory that encodes the agent's experience from previous tasks. Instead, it may receive only partial or noisy observations. Partially observable Markov decision processes, POMPs, provide a framework for modeling such situations in reinforcement learning. In a POMDP, the agent maintains a belief state, which is a probability distribution over possible states, representing the agent's uncertainty about the true state of the environment. The agent updates its belief state based on the observations it receives and the actions it takes. The belief state serves as the input to the agent's policy, which determines the action to take based on the current belief. Dealing with partial observability in reinforcement learning is challenging because the agent must reason about the unobserved state of the environment and make decisions under uncertainty. The optimal policy in a POMDP is a mapping from belief states to actions, which can be significantly more complex than a policy that maps from fully observed states to actions. Furthermore, the belief space is typically continuous and high-dimensional, making it difficult to represent and update the belief state efficiently. Solving POMDPs exactly is computationally intractable in general. However, various approximation methods have been developed. Point-based value iteration is a popular approach that involves maintaining a set of representative belief points and updating their values using dynamic programming. The policy is then defined over this set of belief points. Other approaches include Monte Carlo methods, which use sampling to approximate the belief state and the value function, and methods based on deep learning, which use neural networks to represent the belief state and the policy. POMDPs have applications in robotics, where robots often have to act based on partial and noisy sensor observations. They are also used in dialogue management, where the agent, e.g., a chatbot, must infer the user's hidden state, e.g., their intentions or preferences, from their utterances. Other applications include assistive technologies, surveillance, and medical diagnosis. Challenges in POMDPs include the computational complexity of planning and learning, the difficulty of representing and updating the belief state accurately, and the need for effective exploration strategies that can reduce the agent's uncertainty about the environment. Developing scalable and efficient algorithms for solving POMDPs remains an active area of research. Model-based reinforcement learning. Model-based reinforcement learning, MBRL, is an approach that involves learning an explicit model of the environment's dynamics and using this model for planning and decision-making. This section will discuss the key ideas behind MBRL and compare it with model-free methods. In MBRL, the agent learns a model of the environment, typically consisting of a transition model and a reward model. The transition model predicts the next state given the current state and action, while the reward model predicts the immediate reward. These models can be learned from data collected through interactions with the environment, often using supervised learning techniques. For example, the transition model can be a neural network that takes the current state and action as input and outputs a probability distribution over next states. Once a model is learned, the agent can use it for planning. Planning involves using the model to simulate different action sequences and evaluate their potential outcomes without actually interacting with the real environment. This can be done using techniques such as DynaQ, which integrates model learning with Q-learning. In DynaQ, the agent not only updates its Q values based on real experiences but also based on simulated experiences generated from the learned model. Model-based versus model-free methods have different strengths and weaknesses. Model-based methods can be more sample-efficient, as they can learn from simulated experiences generated from the model. They can also enable better generalization by capturing the underlying structure of the environment. However, model-based methods rely on the accuracy of the learned model, and if the model is inaccurate or incomplete, the resulting policy may be suboptimal. Model-free methods, on the other hand, directly learn a value function or policy without explicitly modeling the environment's dynamics. The advantages of model-based RL include sample efficiency, the ability to plan and reason about the consequences of actions, and the potential for better generalization. The disadvantages include the reliance on an accurate model, the computational cost of planning, and the complexity of learning a good model, especially in high-dimensional or partially observable environments. MBRL has found applications in robotics and control, where sample efficiency and the ability to plan are particularly important. For example, model-based RL can be used to learn complex control policies for robots from relatively small amounts of real-world interaction data. Model-based methods have also been applied to problems in autonomous driving, game playing, and other domains where simulation or planning can be beneficial. Imitation learning is a paradigm where an agent learns to perform a task by observing and mimicking expert demonstrations. Instead of learning from rewards, the agent learns from examples of good behavior provided by an expert. The core idea behind imitation learning is to learn from expert demonstrations. The expert can be a human or another agent that can perform the task well. The demonstrations typically consist of state-action pairs or trajectories, showing how the expert behaves in different situations. The goal of imitation learning is to learn a policy that closely matches the expert's policy. Behavioral cloning is a simple approach to imitation learning where the agent learns a policy by using supervised learning to map states to actions, using the expert demonstrations as training data. The policy can be represented by a neural network or any other function approximator. While straightforward, behavioral cloning can suffer from issues like compounding errors, where small mistakes made by the learned policy accumulate over time, leading to poor performance. Dataset aggregation, DAGger, is an iterative algorithm that addresses some of the limitations of behavioral cloning. In DAGger, the agent starts by learning an initial policy using behavioral cloning. It then executes this policy in the environment and collects a new dataset of state-action pairs. An expert is queried to provide the correct action for each state in this new dataset. The new dataset is then aggregated with the original demonstration dataset, and the policy is retrained. This process is repeated, gradually improving the policy. In Gale, a discriminator network is trained to distinguish between the agent state-action pairs and the expert state-action pairs, while a generator network, the agent's policy, is trained to produce state-action pairs that are indistinguishable from the experts. Gale can be seen as a form of inverse reinforcement learning, where the discriminator implicitly learns a reward function that makes the agent's behavior similar to the experts. Imitation learning has found numerous applications in robotics and autonomous driving, where it can be used to learn complex control policies from human demonstrations. For example, a self-driving car can learn to drive by observing demonstrations from a human driver. Imitation learning can also be used to learn robotic manipulation skills, such as grasping and pouring, from human demonstrations. It is often easier and safer to provide demonstrations than to hand-code a policy or define a reward function. Safety and reinforcement learning. As reinforcement learning agents are increasingly deployed in real-world applications, ensuring their safety becomes crucial. Safety in RL refers to the ability of an agent to avoid harmful or undesirable behavior while pursuing its objectives. This section will discuss the importance of safety in RL and explore various approaches for developing safe RL agents. Defining and ensuring safety in RL agents is a complex challenge. Safety can encompass various aspects, such as avoiding physical harm to the agent or its environment, preventing actions with irreversible consequences, adhering to ethical norms and social conventions, and ensuring robustness to uncertainties and adversarial attacks. Defining safety often requires careful consideration of the specific application domain and the potential risks involved. Constrained reinforcement learning is an approach to safe RL where the agent's policy is constrained to satisfy certain safety requirements. This can be formulated as a constrained Markov decision process, CMDP, where the agent aims to maximize the expected cumulative reward subject to constraints on the expected cumulative costs or risks. Various algorithms have been developed to solve CMDPs, such as constrained policy optimization, CPO. Safe exploration techniques aim to prevent the agent from taking actions during training that could lead to unsafe or undesirable states. One approach is to use a safety layer or a shield that monitors the agent's actions and overrides them if they are deemed unsafe. Another approach is to incorporate safety constraints into the exploration process itself, for example, by biasing the exploration towards actions that are considered safer based on a model or prior knowledge. Risk-averse reinforcement learning focuses on learning policies that are not only high-performing in terms of expected return but also robust to rare, high-cost events. Instead of maximizing the expected cumulative reward, risk-averse RL algorithms aim to optimize risk-sensitive criteria, such as the conditional value at risk, CVR, which measures the expected return in the worst-case scenarios. This can lead to more conservative policies that avoid actions with a high potential for negative outcomes. Safety is particularly important in safety-critical domains, such as autonomous driving, medical diagnosis and treatment, industrial automation, and power systems control. In these domains, the consequences of unsafe behavior can be severe, including damage to property, injury, or even loss of life. Developing safe and reliable RL agents is therefore of paramount importance in these applications. Rigorous testing, verification, and validation are essential before deploying RL agents in safety-critical settings. Real-world applications and case studies in advanced reinforcement learning. In this final section of Lesson 17, we will explore some real-world applications and case studies that demonstrate the power and potential of advanced reinforcement learning techniques. Autonomous driving is a particularly exciting and challenging application area for advanced RL. Reinforcement learning can be used to train self-driving cars to make complex driving decisions, such as lane changing, merging, and overtaking, based on sensory inputs. Advanced RL techniques, such as hierarchical RL and multi-agent RL, can be used to handle the complexity of driving in multi-agent traffic scenarios. Inverse reinforcement learning can be used to learn driving policies from human demonstrations, while safety constraints can be incorporated to ensure safe driving behavior. Robotics and automation are domains where advanced RL has shown great promise. Reinforcement learning can be used to train robots to perform complex manipulation tasks, such as grasping, assembly, and tool use. Inverse reinforcement learning and imitation learning can enable robots to learn from human demonstrations, while hierarchical RL can help to decompose complex tasks into simpler subtasks. Multi-agent RL can be used for coordinating multiple robots in tasks such as warehouse automation and collaborative assembly. Transfer learning can help to adapt policies learned in simulation to real-world robotic systems. Personalized healthcare is an emerging application area for reinforcement learning. RL can be used to develop personalized treatment strategies for chronic diseases, such as diabetes or HIV, by learning optimal treatment policies from patient data. Inverse reinforcement learning can be used to infer patient preferences and tailor treatment plans accordingly. Reinforcement learning can also be used to optimize the operation of medical devices, such as ventilators or insulin pumps, based on the patient's condition. In finance and algorithmic trading, reinforcement learning can be used to learn optimal trading strategies that maximize returns while managing risk. Advanced RL techniques, such as deep RL and multi-agent RL, can handle the complexity and non-stationarity of financial markets. Inverse reinforcement learning can be used to infer the preferences and risk profiles of investors from their trading behavior. However, the application of RL in finance also raises ethical concerns related to market stability and fairness. Drug discovery and molecular design are areas where reinforcement learning is beginning to have an impact. RL can be used to generate novel molecules with desired properties, such as drug candidates or materials with specific characteristics. By treating molecular design as a sequential decision-making problem, where the agent adds atoms or molecular fragments to a growing molecule, RL can learn to generate molecules that optimize a given reward function, such as binding affinity to a target protein or a desired material property. Inverse reinforcement learning can also be used to infer the design principles used by experts. These are just a few examples of the many real-world applications of advanced reinforcement learning. As research in RL continues to progress and as more sophisticated algorithms and techniques are developed, we can expect to see even more impactful applications emerge in the coming years. Reinforcement learning has the potential to revolutionize many aspects of our lives, from transportation and healthcare to manufacturing and scientific discovery. This concludes our exploration of advanced reinforcement learning in Lesson 17. We have covered a wide range of advanced topics, including inverse reinforcement learning, hierarchical reinforcement learning, multi-agent reinforcement learning, transfer learning, and meta-learning in the context of RL. We also discussed partially observable Markov decision processes, POMPs, model-based reinforcement learning, and imitation learning. Furthermore, we examined the important issue of safety in reinforcement learning. Finally, we highlighted the diverse and impactful real-world applications of advanced reinforcement learning in domains such as autonomous driving, robotics, personalized healthcare, finance, and drug discovery. These applications demonstrate the power and potential of RL to solve complex, real-world problems and to create intelligent agents that can learn from experience and adapt to new situations. As you continue your machine learning journey, keep in mind that reinforcement learning, particularly its advanced forms, is a rapidly evolving field with ongoing research and development. The techniques and concepts you have learned in this lesson provide a strong foundation for further exploration and innovation in this exciting area. By combining these advanced RL methods with other machine learning techniques and domain expertise, you can contribute to the development of intelligent systems that have a positive impact on the world. By mastering these advanced reinforcement learning techniques and understanding their applications, you are well equipped to contribute to the cutting edge of AI research and development. Remember that the journey of learning is continuous, especially in such a dynamic field. Stay curious, keep exploring new ideas, and apply your knowledge to challenging problems. The future of reinforcement learning is bright, and you are now a part of it. Lesson 18, Machine Learning in the Cloud. Introduction to Cloud Computing. For machine learning, the advent of cloud computing has significantly transformed the landscape of machine learning, offering scalable, cost-effective, and accessible resources for developing, deploying, and managing machine learning models. This lesson will explore the benefits of using cloud platforms for machine learning, introduce the key cloud providers and their services, and discuss the various aspects of leveraging the cloud for machine learning tasks. We will examine how the cloud can democratize access to powerful tools and infrastructure. Firstly, one of the primary benefits of using cloud platforms for machine learning is scalability. Cloud providers offer virtually unlimited computing resources that can be scaled up or down on demand. This allows machine learning practitioners to train complex models on massive datasets without the need to invest in and maintain expensive hardware infrastructure. Scaling in the cloud can be both vertical, adding more resources to a single machine, and horizontal, distributing the workload across multiple machines. This flexibility is crucial for handling the fluctuating demands of machine learning workloads. Secondly, cloud computing offers cost-effectiveness for machine learning. Cloud providers typically offer a pay-as-you-go pricing model, where users are charged only for the resources they consume. This eliminates the need for large upfront investments in hardware and allows organizations to pay only for what they need. Cloud providers also offer various cost optimization options, such as spot instances, which can significantly reduce the cost of training machine learning models. These options allow for significant flexibility. Thirdly, cloud platforms provide accessibility to a wide range of machine learning tools and services. Major cloud providers, such as Amazon Web Services, AWS, Google Cloud Platform, GCP, and Microsoft Azure, offer comprehensive machine learning platforms that simplify the process of building, training, and deploying machine learning models. These platforms often include pre-built algorithms, pre-trained models, and tools for data pre-processing, feature engineering, model evaluation, and deployment. This makes it far easier for organizations to get started. Fourthly, cloud computing facilitates the deployment and management of machine learning models. Cloud platforms provide services for deploying models as APIs or web services, making it easy to integrate them into applications. They also offer tools for monitoring model performance, managing model versions, and scaling deployments to handle varying levels of traffic. This simplifies the operational aspects of machine learning and allows teams to focus on model development and improvement. The cloud makes it easy to integrate models. Finally, cloud computing promotes collaboration and democratization of machine learning. Cloud-based machine learning platforms enable teams to work collaboratively on machine learning projects, sharing data, code, and models in a centralized environment. They also provide access to powerful machine learning tools and resources to individuals and organizations that may not have the resources to build their own infrastructure. This can help to lower the barrier to entry for machine learning and foster innovation. Cloud-based machine learning platforms. Several major cloud providers offer comprehensive platforms for machine learning, providing a wide range of services and tools to support the entire machine learning lifecycle. This section will introduce some of the key cloud-based machine learning platforms and their core offerings. Amazon SageMaker is a fully managed machine learning service from Amazon Web Services, AWS. It provides tools for building, training, and deploying machine learning models at scale. SageMaker includes pre-built algorithms and frameworks, as well as the ability to bring your own custom algorithms. It also offers features for automatic model tuning, model deployment as APIs, and integration with other AWS services. It is a powerful and comprehensive platform. Google Cloud AI Platform is Google Cloud's suite of machine learning services. It offers a range of tools for building, deploying, and managing machine learning models, including pre-trained models for common tasks like image and video analysis, natural language processing, and translation. Google Cloud AI Platform also provides tools for creating custom models using TensorFlow, PyTorch, scikit-learn, and other popular frameworks. It supports distributed training, hyperparameter tuning, and model deployment as APIs or for batch prediction. Microsoft Azure Machine Learning is a cloud-based service for building, training, and deploying machine learning models. It provides a visual interface for building machine learning pipelines, as well as support for popular open-source frameworks like TensorFlow, PyTorch, and scikit-learn. Azure Machine Learning also offers features for automated machine learning, AutoML, model management, and deployment to various targets, including Azure Container Instances, Azure Kubernetes Service, and IoT Edge devices. IBM Watson Studio is a cloud-based platform for data science and machine learning from IBM. It provides tools for data preparation, model building, and deployment, with a focus on collaboration and visual modeling. Watson Studio supports various open-source frameworks and offers pre-built models and APIs for tasks like natural language understanding, visual recognition, and speech-to-text. It also integrates with other IBM cloud services. In addition to these major platforms, there are many other cloud-based machine learning offerings, including Databricks, H2O, AI, and DataRobot. These platforms often focus on specific aspects of the machine learning lifecycle, such as automated machine learning or distributed training. The choice of platform depends on the specific needs of the project, the team's expertise, and the existing cloud infrastructure. Data storage and management. In the cloud, effective data storage and management are crucial for successful machine learning projects, and cloud platforms offer a variety of services for storing, processing, and managing large datasets. This section will explore cloud-based data storage and management solutions for machine learning. Cloud storage services such as Amazon S3, Google Cloud Storage, and Azure Blob Storage provide scalable, durable, and cost-effective storage for large datasets. These services can store structured, semi-structured, and unstructured data, making them suitable for a wide range of machine learning applications. They also offer various features for data management, such as versioning, access control, and lifecycle management. Cloud databases are often used to store and manage structured data for machine learning. Relational databases like Amazon RDS, Google Cloud SQL, and Azure SQL Database can be used to store tabular data, while NoSQL databases like Amazon DynamoDB, Google Cloud Spanner, and Azure Cosmos DB can handle large volumes of semi-structured or unstructured data. These databases can be integrated with machine learning platforms to provide seamless access to data for training and inference. Data lakes and data warehousing are two common approaches for managing large datasets in the cloud. A data lake is a centralized repository that stores raw data in its native format, allowing for flexible and scalable storage of large datasets. A data warehouse is a system that extracts, transforms, and loads data from various sources into a structured format optimized for querying and analysis. Both data lakes and data warehouses can be used as sources for machine learning data. Data preprocessing and transformation are often performed in the cloud using services like AWS Glue, Google Cloud Dataflow, and Azure Data Factory. These services allow users to define and execute data pipelines that can clean, transform, and prepare data for machine learning. They can handle large datasets and can be integrated with various data storage and machine learning services. They also provide visual tools for creating and managing data pipelines. Managing data pipelines in the cloud involves orchestrating the flow of data between different services and ensuring data quality and consistency. Tools like Apache Airflow, which can be used on various cloud platforms, allow users to define, schedule, and monitor complex data pipelines. These pipelines can include steps for data ingestion, preprocessing, feature engineering, model training, and evaluation, providing an end-to-end solution for managing machine learning workflows in the cloud. Training machine learning models in the cloud platforms offer powerful and scalable resources for training machine learning models, enabling practitioners to leverage vast computational power and specialized hardware. This section will discuss various aspects of training machine learning models in the cloud. Using cloud compute instances for training is a common approach. Cloud providers offer a wide range of virtual machines, e.g., Amazon EC2 instances, Google Compute Engine instances, Azure virtual machines, with different configurations of CPU, memory, and storage. These instances can be customized to meet the specific needs of a machine learning workload. For example, one might choose a compute-optimized instance for CPU-intensive tasks or a memory-optimized instance for tasks that require large amounts of RAM. Leveraging GPUs and TPUs in the cloud for accelerated training has become increasingly important, particularly for deep learning models. GPUs, graphics processing units, can significantly speed up the training of neural networks by performing parallel computations on large matrices. TPUs, tensor processing units, are specialized hardware accelerators designed by Google specifically for machine learning workloads, offering even higher performance than GPUs for certain types of models. Cloud providers offer instances with GPUs and TPUs, making them accessible to a wide range of users. Distributed training in the cloud allows for training large models on massive datasets by distributing the workload across multiple machines. Frameworks like TensorFlow and PyTorch provide support for distributed training, and cloud platforms offer services for managing distributed training jobs. For example, Amazon SageMaker and Google Cloud AI Platform can automatically distribute training jobs across multiple instances and handle the communication between them. Distributed training can significantly reduce the time required to train complex models. Hyperparameter tuning in the cloud can be performed using services offered by cloud providers. These services automate the process of searching for the best hyperparameter settings by running multiple training jobs with different hyperparameter combinations. They often use techniques like Bayesian optimization or genetic algorithms to efficiently explore the hyperparameter space. For example, Amazon SageMaker hyperparameter tuning and Google Cloud AI Platform hyperparameter tuning can automatically tune hyperparameters for a wide range of algorithms. Monitoring and logging training jobs is crucial for understanding the training process, identifying potential issues, and debugging errors. Cloud platforms provide tools for monitoring the resource utilization, loss curves, and other metrics during training. They also offer logging services that allow users to store and analyze logs generated by the training jobs. This information can be used to optimize the training process, debug errors, and improve model performance. Deploying machine learning models in the cloud. After training a machine learning model, the next step is often to deploy it to make predictions on new data. Cloud platforms offer various options for deploying models, ranging from simple API endpoints to fully managed serving infrastructure. Serving models as APIs is a common deployment pattern, particularly for real-time prediction scenarios. The trained model is packaged and deployed as a web service that can receive requests containing input data, make predictions using the model, and return the predictions as a response. REST APIs are often used for this purpose, allowing applications to easily integrate with the deployed model. Cloud platforms provide services for creating and managing these APIs. Containerization technologies like Docker are frequently used for packaging and deploying machine learning models. A Docker container packages the model, its dependencies, and the serving code into a self-contained, portable unit that can be run consistently across different environments. Kubernetes is an open-source platform for managing and orchestrating containers at scale, making it easier to deploy and manage multiple instances of a model for handling high-traffic loads. Serverless deployment is another option for deploying machine learning models in the cloud. With serverless computing, the cloud provider automatically manages the underlying infrastructure, and users are charged only for the compute resources used during prediction. AWS Lambda, Google Cloud Functions, and Azure Functions are examples of serverless platforms that can be used to deploy machine learning models. Serverless deployment can simplify the deployment process and reduce operational overhead. Batch prediction is suitable for scenarios where predictions are not needed in real time. In this case, the model can be used to make predictions on a large dataset offline, and the results can be stored for later use. Cloud platforms offer services for running batch prediction jobs, such as Amazon SageMaker Batch Transform and Google Cloud AI Platform Batch Prediction. Batch prediction can be more cost-effective than real-time prediction for some use cases. Real-time prediction is necessary for applications that require low-latency predictions, such as fraud detection, online recommendations, and real-time bidding. Cloud platforms offer various options for real-time prediction, including deploying models as APIs, using serverless functions, or integrating models with streaming data platforms like Apache Kafka. Optimizing models for inference speed and using specialized hardware like GPUs or TPUs can help to reduce latency in real-time prediction scenarios. AutoML, Automated Machine Learning in the Cloud. AutoML, or Automated Machine Learning, is a rapidly growing area that aims to automate various aspects of the machine learning pipeline, making machine learning more accessible and efficient. Cloud providers are increasingly offering AutoML services that can automatically perform tasks such as feature engineering, model selection, and hyperparameter tuning. Automating the machine learning pipeline is a key goal of AutoML. This includes automating data preprocessing, feature engineering, feature selection, model selection, hyperparameter tuning, and even model deployment. By automating these steps, AutoML can significantly reduce the time and effort required to build and deploy machine learning models. It can also enable users with less machine learning expertise to develop high-quality models. Automated feature engineering and selection is a crucial aspect of AutoML. AutoML systems can automatically generate and evaluate a large number of candidate features, often using techniques like transformation, aggregation, and interaction of existing features. They can also automatically select the most relevant features for the task at hand, using methods like filter-based, wrapper-based, or embedded feature selection. This can save a significant amount of time and effort compared to manual feature engineering. Automated model selection and hyperparameter tuning are also key components of AutoML. AutoML systems can automatically evaluate a range of different machine learning algorithms and hyperparameter settings, using techniques like grid search, random search, or Bayesian optimization. They can also use more advanced techniques like meta-learning, where a model learns to select the best algorithm and hyperparameters based on the characteristics of the dataset. Cloud AutoML services, such as Google Cloud AutoML, Azure Automated ML, and Amazon SageMaker Autopilot, provide user-friendly interfaces for building and deploying machine learning models without the need for extensive coding or machine learning expertise. These services can automatically handle many aspects of the machine learning pipeline, from data preprocessing to model selection and deployment. They often provide visualizations and explanations to help users understand the models and the results. The benefits of AutoML include increased efficiency, reduce time to market for machine learning solutions, and the ability for non-experts to build high-quality models. However, AutoML also has limitations. It may not always be able to find the best possible model or features, particularly for complex or specialized tasks. It can also be a black box approach, making it difficult to understand how the model works or why it makes certain predictions. Furthermore, AutoML may not be suitable for all types of machine learning problems, such as those requiring a high degree of customization or interpretability. Scalability and high availability in cloud machine learning. As machine learning models are increasingly deployed in production environments, ensuring their scalability and high availability becomes crucial. Cloud platforms offer various features and services to support scalable and highly available machine learning systems. Scaling machine learning workloads involves handling increasing amounts of data, traffic, or model complexity. Horizontal scaling involves distributing the workload across multiple machines, while vertical scaling involves increasing the resources of a single machine. Cloud platforms allow for both horizontal and vertical scaling of machine learning workloads, enabling systems to handle growing demands. Load balancing is a technique used to distribute incoming traffic across multiple instances of a machine learning service. This can improve the performance and availability of the service by preventing any single instance from becoming overloaded. Cloud platforms offer load balancing services that can automatically distribute traffic and handle failover in case of instance failures. Load balancing can be applied to both training and inference workloads. Autoscaling is a feature provided by cloud platforms that automatically adjusts the number of instances based on the current workload. For example, an autoscaling policy might add more instances when the CPU utilization or request rate exceeds a certain threshold and remove instances when the load decreases. Autoscaling can help to ensure that the system has enough resources to handle peak loads while minimizing costs during periods of low demand. Ensuring high availability and fault tolerance is critical for production machine learning systems. High availability means that the system is operational and accessible to users with minimal downtime. Fault tolerance means that the system can continue to operate even if some components fail. Cloud platforms offer features like multi-region deployments, automated backups, and failover mechanisms to help achieve high availability and fault tolerance. Disaster recovery is an important aspect of ensuring the resilience of machine learning systems. Cloud platforms provide services for backing up data and models, replicating data across multiple regions, and quickly restoring services in case of a major outage or disaster. Having a well-defined disaster recovery plan is essential for minimizing the impact of unexpected events on machine learning systems. Security and privacy in cloud machine learning. Security and privacy are paramount concerns when deploying machine learning models in the cloud, particularly when dealing with sensitive data. Cloud platforms offer various features and services to help secure machine learning workloads and protect data privacy. Data encryption is a fundamental security measure for protecting data both in transit and at rest. Cloud storage services typically offer encryption at rest, where data is automatically encrypted before being written to disk and decrypted when read. Encryption in transit, such as using HTTPS for API requests, ensures that data is protected as it travels over the network. It is important to use strong encryption algorithms and manage encryption keys securely. Identity and access management, IAM, is a crucial aspect of securing cloud resources, including those used for machine learning. IAM services allow administrators to control who can access which resources and perform specific actions. Cloud providers offer granular IAM controls, allowing users to define fine-grained access policies based on roles, users, and groups. It is important to follow the principle of least privilege, granting users only the permissions they need to perform their tasks. Network security is important for protecting machine learning deployments from unauthorized access and attacks. Cloud platforms offer various network security features, such as virtual private clouds, VPCs, firewalls, and intrusion detection systems. These features can be used to isolate machine learning workloads from the public internet, control inbound and outbound traffic, and monitor for suspicious activity. It is important to configure network security settings properly to prevent unauthorized access to models and data. Compliance with data privacy regulations is a key consideration when using machine learning in the cloud, particularly when dealing with personal or sensitive data. Regulations such as the General Data Protection Regulation, GDPR, in Europe and the California Consumer Privacy Act, CCPA, impose strict requirements on how personal data is collected, processed, and stored. Cloud providers offer features and services to help organizations comply with these regulations, such as data encryption, audit logging, and tools for managing data subject access requests. Protecting against adversarial attacks is an important aspect of security in machine learning. Adversarial attacks involve crafting malicious inputs that are designed to fool a machine learning model into making incorrect predictions. Cloud platforms are starting to offer services for detecting and mitigating adversarial attacks, such as AWS GuardDuty and Azure Security Center. It is also important to follow best practices for model development and deployment to minimize the risk of adversarial attacks. Cost optimization in cloud machine learning. Running machine learning workloads in the cloud can be cost-effective, but it also requires careful management and optimization to avoid unnecessary expenses. This section will discuss strategies for optimizing the cost of machine learning in the cloud. Choosing the right instance types for training and inference is a key factor in cost optimization. Cloud providers offer a wide range of instance types with different combinations of CPU, memory, storage, and GPU capabilities. Selecting an instance type that is well suited to the specific workload can significantly impact cost and performance. For example, using GPU instances for training deep learning models can be more cost-effective than using CPU-only instances, as GPUs can accelerate the training process. Leveraging spot instances can lead to significant cost savings for certain types of machine learning workloads. Spot instances are spare compute capacity that cloud providers offer at a significantly discounted price compared to on-demand instances. However, spot instances can be terminated by the cloud provider with short notice if the capacity is needed for on-demand customers. Spot instances are best suited for fault-tolerant and flexible workloads, such as batch training jobs or stateless API services that can be quickly restarted on a different instance. Monitoring and optimizing cloud resource utilization is important for controlling costs. Cloud platforms provide tools for tracking resource usage, such as CPU utilization, memory usage, and network traffic. By analyzing these metrics, it is possible to identify underutilized or over-provisioned resources and adjust the instance types or scaling policies accordingly. Setting up budget alerts and cost controls can help to prevent unexpected expenses and ensure that costs stay within predefined limits. Strategies for reducing machine learning costs in the cloud include using serverless computing for inference, which eliminates the need to manage servers and allows for automatic scaling based on demand. Another strategy is to use model compression and quantization techniques to reduce the size and computational requirements of models, making them cheaper to deploy and run. Caching frequently accessed data or model predictions can also help to reduce costs by avoiding redundant computations or data transfers. It's important to remember that cost optimization is an ongoing process that requires continuous monitoring, analysis, and adjustment. By regularly reviewing cloud bills, analyzing resource utilization, and experimenting with different cost-saving strategies, organizations can significantly reduce their cloud machine learning costs while maintaining performance and scalability. Real-world applications and case studies in cloud machine learning. In this final section of Lesson 18, we will explore some real-world applications and case studies of machine learning in the cloud to illustrate the practical impact and benefits of leveraging cloud platforms for machine learning tasks. Building and deploying a recommendation system in the cloud is a common use case that showcases the scalability and flexibility of cloud-based machine learning. For example, a company might use Amazon SageMaker to train a collaborative filtering model on a large dataset of user item interactions stored in Amazon S3. The trained model can then be deployed as an API using Amazon SageMaker endpoints, allowing the company to provide real-time personalized recommendations to its users. The cloud platform handles the infrastructure management, scaling, and deployment, allowing the company to focus on model development and improvement. Training and serving a computer vision model in the cloud is another popular application. For example, a startup might use Google Cloud AI platform to train a deep learning model for image classification on a large dataset of images stored in Google Cloud storage. They can leverage Google Cloud's TPUs to accelerate the training process and use Google Cloud's managed Kubernetes service to deploy the trained model as a scalable API. This allows them to serve the model to their application and handle a large number of image classification requests with low latency. Developing and deploying a natural language processing service in the cloud is a use case that demonstrates the power of cloud-based machine learning for NLP tasks. For example, a company might use Azure Machine Learning to train a custom text classification model on a large corpus of text data stored in Azure Blob Storage. They can then deploy the model as a web service using Azure Kubernetes Service, allowing other applications to send text data and receive classification predictions in real time. They can also leverage pre-trained models and APIs available on the cloud platform, such as Azure Cognitive Services for Language, to perform tasks like sentiment analysis, key phrase extraction, and language detection. Building a scalable machine learning pipeline for fraud detection is an example of how cloud platforms can be used to handle large-scale, real-time machine learning workloads. A financial institution might use a combination of cloud services, such as Amazon Kinesis for real-time data streaming, AWS Lambda for serverless data preprocessing, Amazon SageMaker for model training and deployment, and Amazon DynamoDB for storing predictions and metadata. This allows them to process large volumes of transaction data in real time, detect fraudulent transactions with low latency, and scale their fraud detection system to handle increasing transaction volumes. Many companies, such as Netflix, Airbnb, and Spotify, are using machine learning in the cloud to power their core products and services. Netflix uses cloud-based machine learning for its recommendation engine, content personalization, and streaming quality optimization. Airbnb uses machine learning in the cloud for search ranking, pricing optimization, and fraud detection. Spotify uses cloud-based machine learning for music recommendations, personalized playlists, and audio analysis. These case studies demonstrate the transformative impact of cloud-based machine learning on various industries. This concludes our exploration of machine learning in the cloud in Lesson 18. We have covered the benefits of using cloud platforms for machine learning, including scalability, cost-effectiveness, and accessibility. We discussed various cloud-based machine learning platforms and services offered by major cloud providers like AWS, Google Cloud, and Azure. We also examined how to store and manage data in the cloud, how to train and deploy machine learning models using cloud resources, and how to leverage AutoML capabilities. Furthermore, we discussed important considerations such as scalability, high availability, security, privacy, and cost optimization when building and deploying machine learning systems in the cloud. Finally, we explored real-world applications and case studies to illustrate the practical impact of cloud-based machine learning across different domains. As you continue your machine learning journey, keep in mind that cloud computing has become an integral part of the machine learning landscape. By mastering the concepts and techniques covered in this lesson, you are well equipped to leverage the power of the cloud for your own machine learning projects. The cloud offers unparalleled resources and flexibility for developing, deploying, and managing machine learning models at scale. Embrace the cloud, and you'll be able to unlock new levels of efficiency and innovation in your machine learning endeavors. Lesson 19, Machine Learning Project Lifecycle. Introduction to the Machine Learning Project Lifecycle. In this lesson, we will discuss the Machine Learning Project Lifecycle, a structured approach to developing and deploying machine learning models. While previous lessons have focused on specific algorithms and techniques, this lesson provides a holistic view of the entire process, from problem definition to model monitoring and maintenance. Understanding the project lifecycle is crucial for successfully applying machine learning to real-world problems. The machine learning project lifecycle is an iterative process that typically involves several key stages. It begins with defining the problem and setting objectives, which involves understanding the business or research question that needs to be addressed and translating it into a well-defined machine learning task. The next stage is data collection and preparation, where relevant data is gathered, cleaned, explored, and transformed into a suitable format for modeling. Model selection and training is the stage where an appropriate machine learning algorithm is chosen based on the problem and data characteristics. The model is then trained using the prepared data, and its hyperparameters are tuned to optimize performance. Model evaluation and tuning involve assessing the model's performance using appropriate metrics and techniques like cross-validation. This stage often involves iterating on the previous stages, such as revisiting feature engineering or trying different algorithms. Once a satisfactory model is developed, it enters the deployment stage. Deployment involves making the model available for use in a real-world setting, such as integrating it into an application or deploying it as a web service. Finally, monitoring and maintenance are crucial for ensuring that the deployed model continues to perform well over time and adapting to changes in the data or the environment. This often involves retraining the model periodically with new data. It is important to remember that the machine learning project lifecycle is not strictly linear but rather an iterative process. Insights gained at one stage may necessitate revisiting and revising previous stages. For example, model evaluation might reveal the need for additional feature engineering or a different model selection. Flexibility and the willingness to iterate are key to successful machine learning projects. The process is often cyclical. Defining the problem and setting objectives. The first step in any machine learning project is to clearly define the problem and set specific, measurable, achievable, relevant, and time-bound, SMART, objectives. This stage is crucial for ensuring that the project stays focused and delivers value. Identifying the business problem or opportunity is the starting point. This involves understanding the context, the needs of the stakeholders, and the potential impact of a machine learning solution. For example, a business problem might be to reduce customer churn, improve sales, optimize pricing, automate a manual process, or detect fraud. A research problem might involve analyzing scientific data, understanding a complex phenomenon, or developing a new theory. Translating the business problem into a machine learning problem is a critical step. This involves determining the type of machine learning task, e.g., classification, regression, clustering, anomaly detection, defining the target variable, and identifying the available data and potential features. For example, a business problem of reducing customer churn might be translated into a machine learning task of predicting the probability of churn for each customer based on their demographics, purchase history, and interactions with the company. Defining clear and measurable objectives is essential for guiding the project and evaluating its success. Objectives should be specific, quantifiable, and aligned with the business or research goals. For example, an objective might be to achieve a certain level of accuracy in predicting customer churn, to reduce the time required to process loan applications by a certain percentage, or to improve the efficiency of a manufacturing process by a certain amount. Establishing evaluation metrics is a crucial part of setting objectives. The choice of metrics depends on the specific problem and the type of machine learning task. For classification, metrics like accuracy, precision, recall, F1 score, and AUC are commonly used. For regression, metrics like MAE, MSE, RMSE, and R-squared are appropriate. It is important to choose metrics that are aligned with the project's objectives and the business or research context. Scoping the project and identifying constraints is also important at this early stage. This involves defining the boundaries of the project, identifying the available resources, e.g., data, compute, personnel, and considering any constraints, such as time, budget, or regulatory requirements. Proper scoping helps to ensure that the project is feasible and that expectations are realistic. It prevents the project from becoming overly broad. Data collection and understanding. Once the problem is defined and objectives are set, the next step is to collect and understand the data that will be used to train and evaluate the machine learning model. This stage is crucial for ensuring that the data is relevant, reliable, and suitable for the task at hand. Identifying and accessing relevant data sources is the first step in the data collection process. Data can come from various sources, including internal databases, data warehouses, APIs, web scraping, sensor data, and publicly available datasets. The choice of data sources depends on the specific problem and the availability and accessibility of relevant data. It is important to consider the ethical implications of data collection and to ensure compliance with privacy regulations. Data exploration and visualization are essential for understanding the characteristics of the data and identifying potential issues. This involves examining the data distributions, summary statistics, and relationships between variables. Visualization techniques, such as histograms, scatter plots, and box plots, can help to reveal patterns, trends, outliers, and anomalies in the data. Data exploration can also help to generate hypotheses and inform feature engineering. Assessing data quality and identifying potential issues is a crucial step in the data collection process. This involves checking for missing values, inconsistencies, errors, and outliers. Understanding the data collection process and the potential sources of bias or error is important for assessing data quality. Data quality issues can significantly impact the performance and reliability of machine learning models, so it is important to address them early on. Understanding the data distribution and characteristics is essential for making informed decisions about model selection, feature engineering, and evaluation. This involves examining the distribution of each variable, identifying skewed distributions, and understanding the relationships between variables. It is also important to consider the representativeness of the data and whether it adequately reflects the population or phenomenon of interest. Formulating hypotheses based on data understanding is an important part of the exploratory data analysis process. Insights gained from data exploration can help to refine the problem definition, suggest potential features or models, and guide the subsequent steps in the machine learning project lifecycle. Data understanding is an iterative process that often continues throughout the project, as new insights and questions emerge. Data preparation and feature engineering. Data preparation and feature engineering are critical steps that transform raw data into a format suitable for training machine learning models. This often involves cleaning, transforming, and creating new features to improve model performance. Data cleaning and pre-processing are necessary to address issues such as missing values, outliers, and inconsistencies in the data. Missing values can be handled by imputation, e.g., using the mean, median, or a predictive model, or by removing instances or features with missing values. Outliers can be detected using statistical methods or visualization and can be removed, transformed, or capped. Data cleaning also involves ensuring consistency in data formats, units, and scales. Feature scaling and normalization are important pre-processing steps for many machine learning algorithms. Min-max scaling scales features to a specific range, e.g., 0 to 1, while standardization transforms features to have zero mean and unit variance. Scaling can improve the performance of algorithms that are sensitive to the scale of the input features, such as gradient descent-based algorithms and distance-based algorithms. Feature extraction and transformation involve creating new features from existing ones or transforming features into a more suitable representation. Techniques like principal component analysis, PCA, and T-distributed stochastic neighbor embedding, TSNE, can be used for dimensionality reduction and feature extraction. Transformations like logarithmic or Box-Cox transformations can help to normalize skewed data or stabilize variance. Domain knowledge often plays a crucial role in feature engineering. Feature selection aims to identify the most relevant features for the machine learning task, reducing dimensionality, improving model interpretability, and potentially improving performance by removing irrelevant or redundant features. Feature selection methods include filter methods, e.g., correlation, mutual information, wrapper methods, e.g., recursive feature elimination, and embedded methods, e.g., lasso, tree-based feature importance. The choice of method depends on the specific problem and the algorithm being used. Creating new features based on domain knowledge is often a crucial aspect of feature engineering. This can involve combining existing features, creating interaction terms, or deriving new features based on insights into the problem. For example, in a real estate application, one might create a new feature that represents the ratio of the living area to the lot size, or in a time series application, one might create features that capture trends or seasonal patterns. Effective feature engineering often requires creativity and a deep understanding of the data and the problem. Model selection and training. After the data has been prepared and features have been engineered, the next stage in the machine learning project lifecycle is model selection and training. This involves choosing an appropriate algorithm, setting its hyperparameters, and training the model on the prepared data. Choosing the right algorithm depends on several factors, including the type of problem, classification, regression, clustering, etc., the nature of the data, e.g., size, dimensionality, linearity, the desired interpretability of the model, and the computational resources available. It's often beneficial to start with simpler models and gradually increase complexity if needed. Experimenting with different algorithms and comparing their performance using cross-validation is a common practice. Setting hyperparameters is an important part of the model training process. Hyperparameters are parameters that are not learned from the data but are set prior to training. They control the behavior of the learning algorithm and can significantly impact model performance. Examples of hyperparameters include the learning rate in gradient descent, the number of trees in a random forest, and the regularization strength in linear models. Hyperparameter tuning often involves techniques like grid search, random search, or Bayesian optimization. Training the model on the prepared training data involves feeding the data to the chosen algorithm and allowing it to learn the underlying patterns and relationships. The specific training process depends on the algorithm being used. For example, in linear regression, training involves finding the coefficients that minimize the sum of squared errors. In decision trees, training involves recursively partitioning the data based on feature values to create a tree structure. In neural networks, training involves adjusting the weights and biases using backpropagation and gradient descent. Cross-validation, as discussed in Lesson 6, is a crucial technique for model selection and hyperparameter tuning. It provides a more robust estimate of a model's generalization performance than a single train test split by using multiple train test splits and averaging the results. K-fold cross-validation is commonly used to compare different models or different hyperparameter settings and to select the best performing model. It helps to ensure that the chosen model generalizes well to unseen data. Avoiding overfitting and underfitting is a key consideration during model training. Overfitting occurs when a model learns the training data too well, including noise and outliers, and performs poorly on unseen data. Underfitting occurs when a model is too simple to capture the underlying patterns in the data and performs poorly on both training and unseen data. Techniques such as regularization, early stopping, and using simpler models can help to mitigate overfitting, while using more complex models or engineering better features can help to address underfitting. Model evaluation and tuning. Once a model has been trained, it is essential to evaluate its performance and fine-tune it to achieve optimal results. This section will discuss the process of model evaluation and tuning, including the use of appropriate evaluation metrics and hyperparameter optimization techniques. Evaluating model performance on a held-out validation set is the first step in the tuning process. The validation set, which is separate from the training and test sets, is used to assess the model's performance during hyperparameter tuning and model selection. It provides an estimate of how well the model will generalize to unseen data and helps to prevent overfitting to the training data. The validation set should be representative of the data the model will encounter in the real world. Hyperparameter tuning techniques are used to find the optimal settings for the model's hyperparameters. Grid search involves evaluating all possible combinations of hyperparameter values within a specified range, while randomized search samples a fixed number of hyperparameter combinations from specified distributions. Bayesian optimization uses a probabilistic model to guide the search for optimal hyperparameters, often leading to faster convergence than grid search or randomized search. These techniques can be computationally expensive but are often crucial for achieving the best possible performance. Using appropriate evaluation metrics is essential for accurately assessing model performance and comparing different models or hyperparameter settings. The choice of metric depends on the specific problem and the type of machine learning task. For classification, metrics like accuracy, precision, recall, F1, score, and AUC are commonly used. For regression, metrics like MAE, MSE, RMSE, and R-squared are appropriate. It is important to choose metrics that are aligned with the project's objectives and the business or research context. Iterating on model selection and tuning is often necessary to achieve optimal performance. This may involve trying different algorithms, different feature sets, and different hyperparameter settings. It is an iterative process that requires experimentation, careful evaluation, and a good understanding of the problem being solved. The insights gained from evaluating one model can inform the development of subsequent models. It's also important to keep in mind the trade-offs between model complexity, performance, and interpretability. Final evaluation on the held-out test set is the last step in the model evaluation process. The test set, which has not been used during training, hyperparameter tuning, or model selection, provides a final, unbiased estimate of the model's generalization performance. It is crucial to only use the test set once, at the very end, to avoid any potential bias in the evaluation. The performance on the test set is the most reliable indicator of how well the model will perform in real-world scenarios. Model deployment. After developing and evaluating a satisfactory machine learning model, the next step is to deploy it for use in a real-world setting. Model deployment involves making the model available to make predictions on new data, often as part of an application or system. Deploying models as APIs or web services is a common approach for making them accessible to other applications. The trained model is packaged and deployed as a web service that can receive requests containing input data, make predictions using the model, and return the predictions as a response. REST APIs are often used for this purpose, allowing applications to easily integrate with the deployed model using standard HTTP requests. This is a common pattern for deploying models. Batch versus real-time prediction is an important consideration in model deployment. Batch prediction involves making predictions on a large set of inputs at once, typically on a scheduled basis. This is suitable for applications where immediate predictions are not required, such as generating daily or weekly reports. Real-time prediction, on the other hand, involves making predictions on individual inputs as they arrive, requiring low latency. This is necessary for applications such as fraud detection, online recommendations, and autonomous driving. Containerization technologies like Docker have become increasingly popular for deploying machine learning models. A Docker container packages the model, its dependencies, and the serving code into a self-contained, portable unit that can be run consistently across different environments. Containerization simplifies the deployment process and ensures that the model behaves consistently in development, testing, and production environments. Cloud deployment platforms such as Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform, GCP, offer a range of services for deploying and managing machine learning models. These platforms provide infrastructure, tools, and services for deploying models as APIs, managing model versions, scaling deployments, and monitoring performance. They often offer specialized services for machine learning, such as AWS SageMaker, Azure Machine Learning, and Google Cloud AI Platform. Model serving frameworks like TensorFlow Serving and TorchServe provide tools and infrastructure for deploying and serving machine learning models. They handle tasks such as model loading, versioning, request routing, and scaling, allowing developers to focus on building and training models rather than on the complexities of deployment. These frameworks often support various model formats and provide APIs for making predictions. They can be used to deploy models on-premise or in the cloud. Model monitoring and maintenance. Deploying a machine learning model is not the end of the process. Models need to be continuously monitored and maintained to ensure they continue to perform well over time and adapt to changes in the data or the environment. Monitoring model performance over time is crucial for detecting any degradation in performance. This can involve tracking key performance metrics, such as accuracy, precision, recall, or RMSE, and setting up alerts for when these metrics fall below acceptable thresholds. Monitoring can help to identify issues early on and trigger interventions, such as retraining or updating the model. It's important to monitor not only overall performance but also performance on specific segments of the data. Detecting data drift and concept drift is an important aspect of model monitoring. Data drift refers to changes in the distribution of the input data over time. Concept drift refers to changes in the relationship between the input features and the target variable. Both types of drift can cause a model's performance to degrade. Monitoring techniques can include tracking the distribution of input features, comparing the model's predictions to actual outcomes, and using statistical tests to detect significant changes. Retraining and updating models is necessary to address performance degradation due to data drift, concept drift, or other factors. Models can be retrained periodically using new data or when performance falls below a certain threshold. The frequency of retraining depends on the specific application and how quickly the underlying data or relationships are changing. In some cases, online learning techniques can be used to continuously update the model as new data arrives. Model versioning and rollback are important for managing different versions of a model and for ensuring that it is possible to revert to a previous version if necessary. Version control systems, such as Git, can be used to track changes to the model code and training data. Model registries or repositories can be used to store and manage different versions of trained models. This allows for easy rollback to a previous version in case of issues with a new model, such as a significant drop in performance. A/B testing can be used to evaluate the performance of model updates before fully deploying them. This involves deploying both the old and new versions of the model and randomly routing a portion of the requests to each version. By comparing the performance of the two versions on key metrics, such as click-through rate, conversion rate, or prediction accuracy, it is possible to determine whether the new model is actually an improvement before deploying it to all users. A/B testing can help to mitigate the risks associated with deploying a new model and provide empirical evidence for the effectiveness of model updates. Scalability and efficiency in machine learning. As datasets grow larger and models become more complex, scalability and efficiency become increasingly important considerations in machine learning. This section will discuss techniques for scaling data processing, training, and inference, as well as hardware considerations. Scaling data processing is crucial for handling large datasets that do not fit in the memory of a single machine. Tools like Apache Spark provide distributed data processing frameworks that can handle massive datasets by partitioning the data and processing it in parallel across a cluster of machines. Spark provides APIs for data manipulation, feature engineering, and machine learning that can be used to build scalable data pipelines. Distributed training of machine learning models is another important technique for scaling up. This involves partitioning the training data and/or the model across multiple machines and training them in parallel. Frameworks like TensorFlow and PyTorch provide support for distributed training using various strategies, such as data parallelism and model parallelism. Distributed training can significantly reduce the time required to train large models on massive datasets. Optimizing models for inference speed is important for real-time applications where low latency is crucial. Techniques like model pruning, quantization, and knowledge distillation can be used to reduce the size and computational complexity of models without significantly sacrificing accuracy. These techniques can make models faster and more memory efficient, enabling them to be deployed on resource-constrained devices or to handle high request volumes. Hardware considerations play an important role in the scalability and efficiency of machine learning. Graphics processing units, GPUs, have become widely used for training deep learning models due to their ability to perform parallel computations much faster than CPUs. Tensor processing units, TPUs, are specialized hardware accelerators designed by Google specifically for machine learning workloads, offering even higher performance than GPUs for certain types of models. Choosing the right hardware can significantly impact training and inference speed. Model compression and quantization are techniques for reducing the size and computational cost of machine learning models, particularly deep neural networks. Pruning involves removing unnecessary connections or neurons from the network, reducing the number of parameters. Quantization involves reducing the precision of the model's weights and activations, for example, from 32-bit floating point to 8-bit integers. These techniques can significantly reduce the memory footprint and inference time of models, making them more suitable for deployment on mobile and embedded devices. Building machine learning pipelines. A machine learning pipeline is a sequence of steps that automates the machine learning workflow, from data ingestion and preprocessing to model training, evaluation, and deployment. Building well-structured and automated pipelines is essential for creating reproducible, scalable, and maintainable machine learning systems. Automating the machine learning workflow offers several benefits. It reduces manual effort, minimizes the risk of errors, and ensures consistency across different stages of the project. Automation also makes it easier to experiment with different models, features, and hyperparameters, and to track and reproduce results. Furthermore, it enables the deployment and maintenance of machine learning models in production environments. Orchestration tools like Apache Airflow and Kubeflow provide frameworks for defining, scheduling, and monitoring complex machine learning pipelines. These tools allow users to define pipelines as directed acyclic graphs, DAGs, where each node represents a step in the workflow, such as data preprocessing, feature engineering, model training, or evaluation. The orchestration tool manages the execution of the pipeline, handling dependencies between steps and retrying failed steps if necessary. The components of a machine learning pipeline typically include data ingestion, data validation, data preprocessing, feature engineering, model training, model evaluation, model deployment, and model monitoring. Each component can be implemented as a separate module or script, making the pipeline modular and easier to maintain. The pipeline can be triggered manually or automatically, for example, when new data arrives or on a schedule. Reproducibility and version control are crucial aspects of building machine learning pipelines. It should be possible to reproduce the results of a pipeline by rerunning it with the same data and code. Version control systems like Git should be used to track changes to the code, data, and model artifacts. This ensures that the pipeline can be easily reproduced and that previous versions can be restored if needed. Using containers, e.g., Docker, can also help with reproducibility by packaging the code and its dependencies into a self-contained unit. CI/CD, continuous integration/continuous deployment, is a set of practices that can be applied to machine learning pipelines to automate the testing, building, and deployment of models. Continuous integration, CI, involves automatically building and testing the pipeline whenever changes are made to the code or data. Continuous deployment, CD, involves automatically deploying updated models to production after they have passed all tests. CI/CD for machine learning, sometimes referred to as MLOps, helps to ensure the quality and reliability of machine learning systems. Best practices for building machine learning systems. Building robust and reliable machine learning systems requires careful planning, attention to detail, and adherence to best practices. This section will provide some guidelines for building high-quality machine learning systems. Writing clean and maintainable code is essential for any software project, including machine learning projects. Following coding standards, using meaningful variable and function names, and writing modular code can improve readability and maintainability. Using functions and classes to organize code into logical units can make it easier to understand, test, and reuse. It is also important to document the code thoroughly, explaining the purpose of different modules, functions, and parameters. Version control is crucial for tracking changes to the code, data, and models throughout the project lifecycle. Using a version control system like Git allows you to track changes, collaborate with others, and revert to previous versions if needed. It is a good practice to commit changes frequently with clear and descriptive commit messages. Git can also be used to manage different branches of development, such as for experimenting with new features or models. Testing is an essential part of building reliable machine learning systems. Unit tests can be used to verify the correctness of individual components of the system, such as data preprocessing functions, feature engineering steps, or model training code. Integration tests can be used to check that different components of the system work together correctly. It is also important to test the entire pipeline end-to-end to ensure that it produces the expected results. Writing tests can help to catch bugs early, improve code quality, and make it easier to refactor or modify the code later. Collaboration and teamwork are crucial for the success of machine learning projects. Machine learning projects often involve individuals with different skill sets, such as data scientists, engineers, and domain experts. Effective communication, clear roles and responsibilities, and shared tools and platforms are essential for successful collaboration. Using collaborative platforms like GitHub, GitLab, or Bitbucket can facilitate teamwork and code sharing. Regular meetings and discussions can help to ensure that everyone is on the same page and that the project is progressing smoothly. Documenting the entire machine learning project is essential for reproducibility, maintainability, and knowledge transfer. Documentation should include not only the code but also the data, the experimental setup, the results, and the rationale behind key decisions. This documentation can take various forms, such as README files, Jupyter notebooks, comments in the code, and technical reports. Good documentation practices can save time and effort in the long run and make it easier for others to understand, reproduce, and build upon your work. Real-world case studies and project examples. In this final section of Lesson 10, we will explore some real-world case studies and project examples to illustrate the concepts and techniques discussed throughout the lesson. These examples will showcase how machine learning is applied in different domains and provide practical insights into building and deploying machine learning systems. Building an end-to-end machine learning project involves all the stages of the machine learning project lifecycle, from problem definition to model deployment and monitoring. A good project example should demonstrate a clear understanding of the problem, careful data preparation and feature engineering, appropriate model selection and training, rigorous evaluation and tuning, and a plan for deployment and maintenance. It should also document the entire process and provide insights into the decisions made along the way. Case study: churn prediction is a common application of machine learning in many industries, such as telecommunications, banking, and e-commerce. The goal is to predict which customers are likely to churn, i.e., cancel their subscription or stop using a service, so that proactive measures can be taken to retain them. A churn prediction project might involve collecting data on customer demographics, usage patterns, and interactions with customer service, engineering features that capture relevant aspects of customer behavior, training a classification model to predict churn probability, and deploying the model to identify at-risk customers in real time. Case study: image classification is a core task in computer vision with numerous applications. For example, a project might involve building a model to classify images of different types of products for an e-commerce company, or classifying medical images to assist in diagnosis. This could involve collecting and labeling a large dataset of images, using data augmentation techniques to increase the dataset size, training a convolutional neural network, CNN, on the data, and fine-tuning a pre-trained model using transfer learning. The model could then be deployed as a web service to classify new images. Case study: fraud detection is another important application of machine learning, particularly in the financial industry. Fraud detection models aim to identify fraudulent transactions or activities in real time, preventing financial losses and protecting customers. A fraud detection project might involve collecting data on past transactions, engineering features that capture suspicious patterns, training a classification model, e.g., a random forest or a gradient boosting machine, to distinguish between fraudulent and legitimate transactions, and deploying the model to score new transactions in real time. Anomaly detection techniques can also be used for fraud detection. Case study: recommendation system is a classic application of machine learning that aims to predict the preferences or ratings that a user would give to an item. Recommendation systems are widely used in e-commerce, entertainment, and other domains to provide personalized recommendations to users. A recommendation system project might involve collecting data on user-item interactions, e.g., ratings, purchases, views, using collaborative filtering or content-based filtering techniques to build a model, and evaluating the model's performance using metrics like precision at K, recall at K, or NDCG. The model could then be deployed as a service to provide real-time recommendations. These are just a few examples of the many real-world applications of machine learning. By studying these case studies and working on your own projects, you can gain valuable experience and develop a deeper understanding of the challenges and best practices involved in building and deploying machine learning systems. Conclusion of Lesson 10. This concludes Lesson 10, where we have explored the practical aspects of building and deploying machine learning models. We have discussed the machine learning project lifecycle, including defining the problem, data collection and preparation, model selection and training, model evaluation and tuning, deployment, and monitoring. We also covered important topics such as scalability, efficiency, building machine learning pipelines, and best practices for developing machine learning systems. By mastering the concepts and techniques presented in this lesson, you are now well equipped to develop and deploy your own machine learning solutions. Remember that building and deploying machine learning models is an iterative process that requires careful planning, experimentation, and continuous improvement. Apply the knowledge and skills you've gained to real-world problems, and continue to learn and grow as a machine learning practitioner. The field of machine learning is constantly evolving. Lesson 20, The Future of Machine Learning. Introduction. In this lesson, we will explore the exciting future of machine learning, discussing emerging trends, new developments, and the potential impact of machine learning on various aspects of society. We will also consider the challenges and open problems that the field faces, as well as the importance of responsible development and deployment of machine learning systems. Finally, we will provide guidance on how to continue your machine learning journey after completing this course. Emerging trends in machine learning. The field of machine learning is rapidly evolving, with new techniques and applications emerging at an unprecedented pace. This section will highlight some of the key trends that are shaping the future of machine learning. Explainable AI, XAI, and interpretable machine learning are gaining increasing attention as machine learning systems are deployed in high-stakes applications. XAI aims to make complex models more transparent and understandable, enabling humans to comprehend the reasoning behind their predictions. Interpretable machine learning focuses on building models that are inherently more interpretable, such as linear models or decision trees. The growing importance of XAI reflects the need for trust, accountability, and ethical considerations in AI. Automated machine learning, AutoML, is another major trend, aiming to automate the entire machine learning pipeline, from data preprocessing to model deployment. AutoML tools can automatically perform feature engineering, model selection, hyperparameter tuning, and even generate code for deploying models. This trend is democratizing machine learning, making it accessible to a wider range of users, including those without extensive machine learning expertise. It also allows data scientists to focus on more complex and creative tasks. Federated learning is an emerging approach that enables training machine learning models on decentralized data without the need to share raw data. This addresses privacy concerns and allows for the development of models that learn from data distributed across multiple devices or institutions. Federated learning has significant potential in domains like healthcare and finance, where data privacy is paramount. It is a cutting-edge technique with a lot of potential upsides. Reinforcement learning, RL, particularly deep reinforcement learning, continues to advance rapidly. We can expect to see RL being applied to an increasing number of real-world problems, including robotics, control systems, and resource management. The development of more efficient and robust RL algorithms, along with advances in areas like transfer learning and meta-learning, will further expand the capabilities of RL agents. This is a rapidly developing area. Deep learning continues to evolve, with new architectures and techniques being developed at a rapid pace. Transformers, originally developed for natural language processing, are finding applications in other domains, including computer vision. Graph neural networks are gaining traction for problems involving structured data. Generative models, such as GANs and VAEs, are becoming increasingly powerful and are being used for a wide range of tasks beyond image generation. Explainable AI, XAI, and interpretable machine learning. As machine learning models become more complex and are deployed in high-stakes applications, the need for transparency, interpretability, and explainability has become increasingly apparent. This section will delve deeper into the growing importance of XAI and interpretable machine learning. The need for transparency and interpretability stems from several factors. First, in many applications, it is crucial to understand why a model made a particular prediction, especially when the decision has significant consequences, e.g., medical diagnosis, loan applications. Second, interpretability can help to build trust in machine learning systems, as users are more likely to trust a system if they understand how it works. Third, interpretability can aid in debugging and improving models, as it allows developers to identify potential biases or errors in the model's reasoning. Techniques for interpreting complex models have been developed to address the black box nature of many machine learning algorithms. LIME, Local Interpretable Model Agnostic Explanations, and SHAP, Shapley Additive Explanations, are two popular methods for explaining individual predictions by highlighting the features that contributed the most to the prediction. Other techniques, such as feature importance and partial dependence plots, provide insights into the overall behavior of the model. Building inherently interpretable models is another approach to achieving transparency. Linear models, decision trees, and rule-based systems are examples of models that are relatively easy to interpret due to their simple structure. However, these models may not always be as accurate as more complex models. Research is ongoing to develop models that are both accurate and interpretable. Trade-offs between interpretability and performance often exist in machine learning. More complex models, such as deep neural networks, can achieve higher accuracy on many tasks but are often more difficult to interpret. Simpler models are more interpretable but may sacrifice some accuracy. The choice of model and the desired level of interpretability depend on the specific application and the importance of understanding the model's decision-making process. The role of XAI in building trust and accountability is becoming increasingly important. By providing explanations for model predictions, XAI can help users to understand the rationale behind decisions and to identify potential biases or errors. This can increase trust in machine learning systems and promote their responsible use. XAI can also help to establish accountability by making it clearer who is responsible for the decisions made by machine learning models. Automated machine learning, AutoML. AutoML aims to automate the entire machine learning pipeline, from data preprocessing and feature engineering to model selection, hyperparameter tuning, and even deployment. This section will discuss the goals, benefits, and limitations of AutoML. Automating the machine learning pipeline can significantly reduce the time and effort required to build and deploy machine learning models. It can also enable non-experts to develop high-quality models without extensive machine learning expertise. AutoML systems typically use various techniques to automate different stages of the pipeline, such as automated feature engineering, automated model selection, and automated hyperparameter tuning. Automated feature engineering and selection is a key aspect of AutoML. AutoML systems can automatically generate and evaluate a large number of candidate features, often using techniques like transformation, aggregation, and interaction of existing features. They can also automatically select the most relevant features for the task at hand, using methods like filter-based, wrapper-based, or embedded feature selection. This can save a significant amount of time and effort compared to manual feature engineering. Automated model selection and hyperparameter tuning are also crucial components of AutoML. AutoML systems can automatically evaluate a range of different machine learning algorithms and hyperparameter settings, using techniques like grid search, random search, or Bayesian optimization. They can also use more advanced techniques like meta-learning, where a model learns to select the best algorithm and hyperparameters based on the characteristics of the dataset. The benefits of AutoML include increased efficiency, reduced time to market for machine learning solutions, and the ability for non-experts to build high-quality models. AutoML can also help to standardize the machine learning process and make it more reproducible. However, AutoML also has limitations. It may not always be able to find the best possible model or features, particularly for complex or specialized tasks. It can also be a black box approach, making it difficult to understand how the model works or why it makes certain predictions. The role of AutoML in democratizing machine learning is significant. By automating many of the technical aspects of machine learning, AutoML tools are making the technology more accessible to a wider range of users, including businesses, researchers, and individuals who may not have formal training in machine learning. This can help to unlock the potential of machine learning in various domains and accelerate innovation. Federated learning and privacy-preserving machine learning. Federated learning is a novel approach to machine learning that addresses the growing concerns about data privacy and security. It enables training machine learning models on decentralized data without the need to share raw data, thereby protecting sensitive information. The core idea behind federated learning is to train models locally on each device or server holding data and then aggregate the model updates, e.g., gradients, rather than the data itself. This allows multiple parties to collaboratively train a model without sharing their raw data with each other or with a central server. The central server coordinates the training process and aggregates the updates to create a global model. Protecting data privacy in machine learning is a major motivation for federated learning. By keeping the data localized and only sharing model updates, federated learning can significantly reduce the risk of data breaches and privacy violations. It also enables organizations to comply with data privacy regulations, such as the GDPR, which restrict the movement and sharing of personal data. Federated learning has numerous applications in healthcare, finance, and other domains where data privacy is crucial. For example, it can be used to train models on patient data distributed across multiple hospitals without the need to share sensitive medical records. In finance, it can be used to train fraud detection models on transaction data from different banks without revealing individual transactions. It can also be applied to mobile devices. Challenges of federated learning include the communication overhead of sending model updates between devices and the central server, the heterogeneity of data across different devices, and the potential for adversarial attacks on the model updates. Furthermore, ensuring the privacy and security of the model updates themselves is an important consideration. Research is ongoing to address these challenges and develop more efficient and robust federated learning algorithms. Other privacy-preserving techniques include differential privacy, which adds noise to the data or the model's outputs to provide formal privacy guarantees, and homomorphic encryption, which allows computations to be performed on encrypted data without decrypting it. These techniques can be used in conjunction with federated learning or as alternative approaches to protect data privacy in machine learning. Reinforcement learning and its growing applications. Reinforcement learning, RL, particularly deep reinforcement learning, is experiencing a surge in interest and is being applied to an increasingly diverse range of real-world problems. This section will discuss the advancements, applications, and future potential of RL. Advancements in deep reinforcement learning, such as improved algorithms, better exploration strategies, and more stable training methods, have enabled RL agents to tackle more complex and challenging tasks. Deep RL, which combines deep neural networks with reinforcement learning, has shown remarkable success in domains like game playing, robotics, and control systems. The development of new architectures, such as those incorporating attention mechanisms and transformers, is further expanding the capabilities of DRL. New applications of reinforcement learning are emerging across various industries. In robotics, RL is being used to train robots to perform complex manipulation tasks, navigate in unstructured environments, and interact with humans. In autonomous systems, RL is being applied to areas like traffic control, resource management, and energy optimization. In healthcare, RL is being used to develop personalized treatment strategies and to optimize clinical trials. In finance, RL is being explored for algorithmic trading and portfolio management. The potential of reinforcement learning to solve complex, sequential decision-making problems is immense. Unlike supervised learning, which relies on labeled examples, RL agents can learn from their own experiences and adapt to changing environments. This makes RL particularly well suited for problems where the optimal strategy is not known in advance or where the environment is too complex to be modeled explicitly. RL can also be combined with other machine learning techniques to create powerful hybrid systems. Challenges in deploying reinforcement learning in real-world settings include the need for large amounts of data or a realistic simulator, the difficulty of defining an appropriate reward function, and the potential for unsafe or unstable behavior during training. Furthermore, ensuring the robustness and reliability of RL agents in real-world environments is a critical challenge. Addressing these challenges requires careful system design, rigorous testing, and ongoing monitoring. The future of reinforcement learning research is bright, with many exciting directions being pursued. These include developing more sample-efficient and stable algorithms, improving exploration strategies, incorporating safety and ethical considerations into RL agents, and developing methods for transferring knowledge across tasks and domains. As RL research progresses and the technology matures, we can expect to see even more impactful real-world applications of reinforcement learning. Deep learning advancements and new architectures. Deep learning continues to evolve at a rapid pace, with new architectures and techniques constantly pushing the boundaries of what's possible. This section will discuss some of the recent advancements in deep learning and their impact on various applications. Transformer models, originally introduced for natural language processing, have had a profound impact on the field. Their ability to capture long-range dependencies using self-attention mechanisms has made them highly effective for a wide range of sequence-based tasks. Transformers have achieved state-of-the-art results in machine translation, text summarization, question answering, and many other NLP tasks. Their success has also led to their adaptation for other domains, such as computer vision and reinforcement learning. Graph neural networks, GNNs, are a class of deep learning models designed to operate on graph-structured data. GNNs can learn representations of nodes and edges in a graph, taking into account the graph structure and the features of nodes and edges. They have shown great promise in applications involving social networks, recommender systems, drug discovery, and other domains where data can be naturally represented as a graph. GNNs generalize convolutional networks to graph data by defining convolution operations on graphs. New developments in computer vision continue to advance the state-of-the-art. In addition to improvements in image classification, object detection, and segmentation, there is growing interest in areas such as 3D vision and video analysis. Deep learning models are being developed to process and understand 3D data, such as point clouds and meshes, with applications in robotics, autonomous driving, and virtual reality. Video analysis is also benefiting from deep learning, with models being developed for tasks like action recognition, video summarization, and object tracking in videos. Advances in generative models, such as generative adversarial networks, GANs, and variational autoencoders, VAEs, are enabling the creation of increasingly realistic and diverse synthetic data. GANs, in particular, have shown remarkable capabilities in generating high-quality images, videos, and audio. These advances have implications for various applications, including art, design, entertainment, and data augmentation. However, they also raise ethical concerns, such as the potential for creating deepfakes. The trend towards larger and more powerful models is continuing, driven by the availability of more data and computational resources. Models like GPT-3, with 175 billion parameters, have demonstrated impressive capabilities in natural language understanding and generation, but they also raise concerns about their environmental impact, potential biases, and accessibility. The development of more efficient architectures and training methods is an important area of research to address these concerns. The intersection of machine learning and other technologies. Machine learning is not an isolated field but is increasingly being integrated with other emerging technologies, creating new opportunities and synergies. This section will explore the intersection of machine learning with other technologies. Machine learning and the Internet of Things, IoT, are a powerful combination. The proliferation of connected devices and sensors generates vast amounts of data that can be leveraged by machine learning algorithms to create smarter and more responsive systems. Applications include smart homes, smart cities, industrial automation, and environmental monitoring. Machine learning can be used to analyze sensor data, detect patterns, make predictions, and optimize the performance of IoT systems. Machine learning and edge computing are also converging. Edge computing involves processing data closer to its source, rather than sending it all to the cloud. This can reduce latency, improve bandwidth efficiency, and enhance privacy. Deploying machine learning models on edge devices, such as smartphones, robots, and drones, enables real-time decision-making and intelligent behavior in these devices. This combination enables faster response times and reduced reliance on network connectivity. Machine learning and blockchain are two technologies that can complement each other. Blockchain can provide a secure and transparent ledger for recording data and model updates, which can be useful for ensuring the integrity and auditability of machine learning systems. Machine learning can be used to analyze blockchain data to detect anomalies, identify patterns, and improve the efficiency of blockchain systems. The combination of these technologies has potential applications in areas like supply chain management, digital identity, and decentralized finance. Machine learning and quantum computing represent a particularly exciting intersection. Quantum computing has the potential to dramatically accelerate certain types of computations, including some that are relevant to machine learning. While still in its early stages, quantum machine learning could potentially offer significant speedups for tasks like optimization, sampling, and solving linear systems. This could enable the development of more powerful and efficient machine learning models. The convergence of machine learning with other emerging technologies is creating new possibilities and driving innovation across various domains. As these technologies continue to mature and integrate, we can expect to see even more transformative applications that leverage the combined power of machine learning and other cutting-edge technologies. This convergence will likely reshape industries and create new opportunities for value creation. Challenges and open problems in machine learning. Despite the remarkable progress in machine learning, many challenges and open problems remain. Addressing these challenges is crucial for advancing the field and ensuring that machine learning is used responsibly and effectively. Data quality and availability remain significant bottlenecks in many machine learning applications. Training state-of-the-art models often requires large, high-quality labeled datasets, which can be expensive and time-consuming to create. Furthermore, many real-world datasets are noisy, incomplete, or biased, which can negatively impact model performance and fairness. Developing methods for learning from smaller, noisier, or unlabeled datasets is an important area of research. Model robustness and reliability are critical concerns, particularly in safety-critical applications. Machine learning models can be vulnerable to adversarial attacks, where small, carefully crafted perturbations to the input can cause the model to make incorrect predictions. They can also be sensitive to changes in the data distribution or to unexpected inputs. Developing models that are robust to such challenges and that can provide reliable uncertainty estimates is an active area of research. Computational resources and scalability remain challenges, particularly for deep learning models. Training large models can require significant computational resources and time, which can limit their accessibility and applicability. Developing more efficient algorithms, architectures, and hardware is crucial for scaling up machine learning to even larger datasets and more complex problems. This is an area of ongoing research and development. Addressing ethical concerns and biases in machine learning is of paramount importance. As discussed in Lesson 9, machine learning models can perpetuate and amplify biases present in the training data, leading to unfair or discriminatory outcomes. Developing methods for detecting and mitigating bias, ensuring fairness, and promoting transparency and accountability in machine learning systems is a crucial area of research and practice. The need for interdisciplinary research is becoming increasingly apparent in machine learning. Many of the challenges and applications of machine learning require expertise from multiple domains, including computer science, statistics, ethics, law, and the social sciences. Collaboration between researchers and practitioners from different fields is essential for developing effective and responsible machine learning systems. Interdisciplinary research can also lead to new insights and approaches that might not be apparent from within a single discipline. The role of machine learning in society. Machine learning is not just a technical field, it is increasingly shaping various aspects of our lives and society. In this section, we will reflect on the broader impact of machine learning and the need for responsible development and deployment of this technology. The impact of machine learning on various aspects of life is becoming more pronounced. In healthcare, machine learning is being used to improve diagnosis, personalize treatment, and accelerate drug discovery. In education, it is being used to create personalized learning experiences and automate administrative tasks. In transportation, it is powering the development of self-driving cars and intelligent traffic systems. In entertainment, it is used to create personalized recommendations and generate creative content. The widespread adoption of machine learning brings both potential benefits and risks. On the one hand, machine learning can improve efficiency, accuracy, and decision-making in many domains. It can automate tedious or dangerous tasks, augment human capabilities, and enable new products and services. On the other hand, it can also exacerbate existing inequalities, create new forms of discrimination, and raise concerns about privacy, security, and autonomy. It is crucial to carefully consider both the potential benefits and risks when developing and deploying machine learning systems. The need for responsible development and deployment of machine learning systems cannot be overstated. This involves considering the ethical implications of machine learning, such as fairness, transparency, accountability, and privacy, throughout the entire life cycle of a system. It also involves engaging with stakeholders, including those who will be affected by the system, and ensuring that their values and concerns are taken into account. Responsible development also requires ongoing monitoring and evaluation of deployed systems. The role of education and public awareness is crucial for shaping the future of machine learning. Educating both machine learning practitioners and the general public about the capabilities, limitations, and ethical implications of machine learning is essential for fostering informed discussions and responsible innovation. Promoting data literacy and critical thinking skills can empower individuals to better understand and engage with machine learning systems. It is important to have a broad understanding of the societal impacts. Shaping a positive future with machine learning requires a collective effort from researchers, developers, policymakers, and the public. By working together and prioritizing ethical considerations, we can harness the transformative potential of machine learning for the benefit of all. This involves developing technical solutions to address challenges like bias and fairness, creating appropriate regulatory frameworks and oversight mechanisms, and fostering a public dialogue about the values and priorities that should guide the development and use of machine learning. Continuing your machine learning journey. This concludes the final lesson of Course 1, Foundations of Machine Intelligence. We have covered a wide range of topics, from the fundamentals of machine learning to advanced techniques and emerging trends. As you conclude this course, it's important to reflect on your learning journey and consider how you will continue to develop your skills and knowledge. There are numerous resources for further learning in machine learning. Online courses, such as those offered by Coursera, edX, Udacity, and others, provide opportunities to deepen your understanding of specific topics and learn about new developments. Books on machine learning, ranging from introductory texts to advanced research monographs, offer in-depth coverage of various aspects of the field. Research papers published in conferences and journals are a valuable source of information on the latest advancements in machine learning. Staying up to date with the latest developments in the field is crucial in the rapidly evolving field of machine learning. Following research blogs, attending webinars and conferences, and reading research papers can help you stay informed about new techniques, applications, and trends. Joining online communities, such as forums, social media groups, and mailing lists, can provide opportunities to learn from and interact with other machine learning practitioners and researchers. Building a portfolio of machine learning projects is an excellent way to solidify your skills, gain practical experience, and demonstrate your expertise to potential employers or collaborators. Working on personal projects, contributing to open-source projects, or participating in machine learning competitions, e.g., on Kaggle, can help you apply what you've learned and build a strong portfolio. Sharing your projects publicly, for example on GitHub, can also help you get feedback and connect with other practitioners. Joining the machine learning community can provide valuable opportunities for learning, networking, and collaboration. Attending conferences, workshops, and meetups can help you connect with other researchers and practitioners, learn about the latest developments, and present your own work. Contributing to open-source projects, participating in online forums, and engaging in discussions on social media can also help you become an active member of the community. Career paths in machine learning are diverse and rapidly expanding. Machine learning engineers, data scientists, AI researchers, and other related roles are in high demand across various industries. Many universities now offer specialized programs in machine learning and artificial intelligence. As you continue your learning journey, consider how you can apply your skills and knowledge to real-world problems and explore the various career opportunities available in this exciting field. There are many options available. Conclusion of Course 1. Congratulations on completing Course 1, Foundations of Machine Intelligence. Throughout this course, you have embarked on a comprehensive journey through the world of machine learning, exploring its fundamental concepts, powerful algorithms, diverse applications, and profound societal implications. You have learned about different types of machine learning, including supervised learning, unsupervised learning, and reinforcement learning. You have delved into specific algorithms and techniques, such as linear regression, logistic regression, decision trees, random forests, support vector machines, 1K-means clustering, principal component analysis, Q-learning, and various deep learning architectures. You have also explored advanced topics like ensemble methods, transfer learning, active learning, semi-supervised learning, and various methods within natural language processing, computer vision, time series analysis, anomaly detection and recommender systems. Beyond the technical aspects, you have examined the crucial ethical considerations surrounding machine learning, including bias, fairness, transparency, accountability, and privacy. You have also gained an understanding of the machine learning project lifecycle and best practices for building and deploying machine learning systems. As you conclude this course, remember that your machine learning journey has just begun. The field of machine learning is constantly evolving, with new techniques, applications, and challenges emerging at a rapid pace. Continue to learn, experiment, and apply your knowledge to real-world problems. Embrace the iterative nature of machine learning projects and strive to develop systems that are not only accurate but also fair, transparent, and beneficial to society. The future of machine learning is bright and full of possibilities. Armed with the knowledge and skills you have gained in this course, you are well positioned to contribute to this exciting field and to shape the future of artificial intelligence. Thank you for joining me on this journey, and I wish you all the best in your future machine learning endeavors. Remember to always approach new challenges with curiosity and a commitment to ethical principles. Conclusion: embarking on the future of intelligent machines. As we reach the end of Course 1, Foundations of Machine Intelligence, it is fitting to reflect upon the remarkable journey we have undertaken together. We have traversed the expansive landscape of machine learning, from its fundamental principles to its cutting-edge techniques, and from its diverse applications to its profound societal implications. This course has equipped you with a solid foundation in the core concepts, algorithms, and methodologies that underpin this transformative field. In the introductory lessons, we demystified the essence of machine learning, exploring its historical roots and its relationship to the broader field of artificial intelligence. We examined the paradigm shift from traditional programming to the data-driven approach of machine learning, highlighting the power of algorithms that can learn from data, adapt to new situations, and generalize their knowledge to unseen instances. We then delved into the major branches of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Through detailed explorations of various algorithms, including linear and logistic regression, decision trees, random forests, support vector machines, k-means clustering, principal component analysis, and Q-learning, you have gained a comprehensive understanding of the tools and techniques that form the bedrock of machine learning. The journey continued with an in-depth exploration of deep learning, the driving force behind many recent breakthroughs in AI. We dissected the architecture and training of neural networks, including convolutional neural networks, CNNs, for image processing, recurrent neural networks, RNNs, for sequential data, and generative adversarial networks, GANs, for creating new content. We also touched upon advanced deep learning topics like attention mechanisms and transformers. Beyond the algorithms, we explored crucial practical aspects of machine learning, including model evaluation and selection, feature engineering and data preprocessing, and techniques for handling imbalanced datasets and overfitting. We discussed the importance of hyperparameter tuning and model selection, as well as advanced techniques like ensemble methods and transfer learning. We then ventured into specialized domains, showcasing the versatility of machine learning. We explored natural language processing, NLP, computer vision, time series analysis, anomaly detection, and recommender systems. These explorations illustrated how core machine learning principles are adapted and applied to solve a wide array of real-world problems. You also learned about model deployment strategies, including the emerging importance of cloud platforms. A significant portion of this course was dedicated to the ethical and societal implications of machine learning. We grappled with issues of bias, fairness, transparency, accountability, and privacy, emphasizing the need for responsible development and deployment of machine learning systems. We also considered the broader impact of machine learning on employment, social justice, and various domains like healthcare, finance, education, and autonomous vehicles. Finally, we peered into the future of machine learning, examining emerging trends such as explainable AI, XAI, automated machine learning, AutoML, federated learning, and the growing role of reinforcement learning. We discussed the challenges and open problems that the field faces, including data quality, model robustness, computational resources, and the need for interdisciplinary research. As you conclude this course, it is important to remember that this is just the beginning of your machine learning journey. The field is constantly evolving, with new techniques, applications, and challenges emerging at a rapid pace. To stay at the forefront of this dynamic field, continuous learning, experimentation, and engagement with the community are essential. The knowledge and skills you have acquired in this course provide a strong foundation for further exploration and specialization. Whether you choose to delve deeper into deep learning, reinforcement learning, or any other area of machine learning, the principles and techniques you have learned here will serve as a valuable guide. As you embark on your future machine learning endeavors, always remember the importance of ethical considerations. Strive to develop systems that are not only accurate and efficient but also fair, transparent, and beneficial to society. Engage in thoughtful discussions about the societal impact of machine learning and contribute to shaping a future where this powerful technology is used responsibly and for the good of all. The future of machine learning is bright, and you are now a part of it. Embrace the challenges, seize the opportunities, and never stop learning. The journey ahead is filled with exciting possibilities, and I am confident that you will make significant contributions to this transformative field. Thank you for joining me on this journey through the foundations of machine intelligence. I wish you all the best in your future machine learning endeavors.